Are you looking for a crash course for your college algebra class? Well, you've come to the right place. This video is a compilation of all 28 of my lectures that I give for my college algebra class, all of which are based on the textbook College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Lefswap Skurzipek. I am not at all affiliated with any of the authors. I'm not affiliated with the publisher Pearson. These are entirely just lectures I wanted to share. And if you're looking for individual lectures, I will put a link to a playlist of all of the individual section lectures in the description. So this video is very long because it's a compilation. So if you want specific sections, by all means, check out that playlist in the bottom, or just check out the timestamps that will also be in the bottom. So thank you so much for watching. I hope you learned something watching this, and good luck. Hi everyone, welcome to Chapter P. Chapter P is the first chapter of this college algebra class, and the name of the chapter is Basic Concepts of Algebra, and the chapter is exactly as it sounds. We're going to go over some very basic concepts of the study of algebra that we're going to use for the entire course and in future chapters. One thing I'll note is that this first section of Chapter P, section P1, is quite long. There's a lot to go over here. Real numbers and their properties is a very long section, and that's also kind of indicative of most of the chapter, where most of the chapter is very long itself. So if it's a little off-putting that this first section is over an hour long, it's okay. That's normal. Most sections will not be that long, but this is a good microcosm of how the entire chapter goes. So this video, we're going to go over P1, real numbers and their properties, and you see all the different subsections that we're going to go over. So let's get right into it. So we're going to have some classification here just to start with. We're going to deal with constants for the most part in the class. So constants are any numbers that have very concrete values, for example, 3 or 1/2 or -6, all numbers that we can put on a real number line and visualize what that means. Now, the real number line we're going to go over later on in this section, but 3, 1/2, -6, we have an idea on what those numbers are. And then the whole study of algebra is that we want to introduce these things called variables. And in general, variables are letters that can represent any number. So we want to be able to change the value of a variable. We want to be able to change the value in certain situations. And what we're going to do is use letters to represent being able to change, have a value that can be changed. So some very commonly used letters are X, Y, Z, A, B, C. And you could really use any of the 26 letters of the alphabet to be a variable. However, some letters are a little bit more commonly used for other topics. Like, for example, in Chapter 1, we're going to start defining I to be one specific value. So you could use I as a variable, but in general, I is used for other things. But again, we will use X, Y, Z, A, B, C for the most part to represent different values. 4 core operations are exactly as you'd expect them to be. Addition that we denote with a plus sign, subtraction we denote with a negative sign, A times B, multiplication. So you can use one of two notations here. You can do A times B with this little dot in the middle, and this is a pretty preferable notation here. It gets the idea across of what we're doing. Or you can also use A, B without anything in between them in the case where either both things are variables or both things, or one of the things are variables. So, for example, if we wanted to write 17x, you could write 17 times x, or you could write 17x. The only time that we don't use letters or things right next to each other is when both things are numbers. For example, if we wanted to say 17 times 19, we would have to say 17 times 19, because to write them right next to each other would be 1719, like the number 1719. So it's pretty straightforward. But the thing to get across here is that we are not going to use crosses for to denote multiplication. So, for example, when you're growing up, when you first learn multiplication, the multiplication symbol is an x. You would say AXB. But since we're going to start using x to be a variable, it can get confusing if we allow x to be used as multiplication. So in the entirety of this algebra class, and in any algebra class ever, you shouldn't use x to denote multiplication. So please don't do that. Division, exactly as we would expect. A divided by B, where we write A over B. And then one last one, it's not really an operation, but something we will talk about as time goes on, is A equals B, which just means these two things are equal. First thing we're going to talk about are sets. So sets are a collection of objects called elements. So the things inside a set is an element. We enclose elements in braces. So this is what a set would look like. This would be an empty set with nothing in it. But if we wanted to write every element in our set, we would write them in between these two braces. Some frequently used sets that we're going to talk about. One of them is the natural numbers, which we denote with a capital N. And the natural numbers are all numbers like 1, 2, 3, 4, 5, what we would typically refer to as counting numbers. The next set that goes up the ladder would be the whole numbers. And the only difference from the whole numbers to the natural numbers is that whole numbers include the element 0. So if you were to start counting from 0 and then 0, 1, 2, 3, 4, 5, and so on, those would be whole numbers. After that, we introduce the integers, and integers are the whole numbers, but where we now allow negative versions of the natural numbers. So again, we go 1, 2, 3, 4, 5, and then we introduce 0, 0, 1, 2, 3, 4, 5. But then in the integers, we start allowing those numbers to be negative, -3, -2, -1, 0, 1, 2, 3, and then forever in both directions. The empty and null set, I said the phrase empty set earlier. Empty set is just a set with nothing in it. Null set, set with nothing in it. we can use this empty set notation here, this little 0 with a line through it. There's a couple different Greek letters that kind of look like this as well, but if you write something like this gets the point across that it is an empty set. It's a set that has no elements. Or you could also use this empty set of braces where you just don't write anything between them. They mean the same thing. They both mean a set with nothing in it. The only thing I ask that you don't do is put this empty set symbol into a set of empty braces. Basically, what that would mean is a set of empty sets, and that's kind of beyond the scope of our course in terms of we don't want to broach that topic right now. So either use empty braces or use the empty set symbol. Well, you might notice that in the integers, we have numbers that are -3, -2, -1, 0, 1, 2, 3. But what happens when we want to classify a number like 2.5 or -3/4? Well, all those numbers that are in between the cracks of 1 to 2 and 2 to 3 and so on. Well, we want to introduce a set called the rational numbers. Now, rational numbers we denote with the letter Q, and rational numbers is the set of rational numbers is the set of all numbers that can be written as a ratio or as a fraction. More specifically, numbers that can be written as A over B, specifically where B does not equal 0. So very specifically, any number divided by 0 we say is undefined. So we want to make sure that all of these numbers that we can write as fractions do not allow 0 to be in the denominator. All integers are rational numbers because if we have some number A that is an integer, then we can write A as A divided by 1. Well, if we can write A as A divided by 1, this is the definition of being a rational number. So all integers are rational numbers, and you already start to see this progression. Natural numbers sat inside the whole numbers sat inside the integers are sitting inside the rational numbers. And we're going to introduce some more sets that kind of fill the other gaps, so to speak, but we'll do that in just a second. So we have a couple different ways we can denote rational numbers, and aside from writing them as fractions, they can also be terminating decimals. So for example, the number 1 over 2 is 0.5, where this is a decimal place version, but it's a terminating decimal place because it doesn't go on forever. Well, just because it goes on forever doesn't necessarily mean it's not a rational number, because we're also allowed to have non-terminating but repeating decimals. So for example, 1/3, if you were to do long division, 1/3 would be like 0.33333, but instead of writing 0.333 so on and forever, we can just write 0.3 repeating. This little bar at the top of the 3 means the number is repeating. Now, just one thing to note, we like writing 0.3 repeating because 3 is what is repeating. You wouldn't want to write 0.33 repeating because that would be redundant. So this is just supposed to be a nice shorthand way of writing everything you see right here. But again, 1/3 is a rational number, and its equivalent decimal place is a non-terminating but repeating decimal, and that's very important. For example, 26 over 99 would be 0.262626, and we would write that as 0.26 repeating. So you want to write the part that is repeating without needing to put so much under a repeating symbol. Converting fractions to decimals, this is something we're very comfortable with. We don't really need to spend a whole lot of time doing, but this is just long division. However you would have divided in elementary school when you first learned about division is exactly how we would do it here in college algebra. So we don't need to spend time changing 1/3 to 0.33333 just to change it to 0.3 repeating. We don't need to spend time doing 26 divided by 9, is 0.262626 or 0.26 repeating. It's exactly how you've done it in the past, and very rarely are we ever going to need to divide in that way. In chapter 3, we do something similar, but chapter 3 is a long way away. However, if we want to convert decimals to fractions, going backwards, we have to treat it in 2 separate ways. Notice that we only have one type of fraction. We didn't categorize the fractions themselves. We categorize the decimals. Well, if we have 2 kinds of decimals, we need 2 different ways of converting decimals back to fractions. If your decimal is terminating, all we need to do is put that decimal place over 10, 100, 1,000, whatever the however many decimal places we have over that power of 10, and just simplify. So for example, in 0.5, if we wanted to convert 0.5 back to a fraction, we would put 5 over 10. If it's 1 decimal place, we only need 1 power of 10. So you would do 5 divided by 10, and then simplify 5 over 10. If we had 0.53, well, 0.53 is 2 decimal places. You would put that over 100, so 53 over 100. Okay, but the interesting part here, the thing we should talk about is non-terminating decimals. How do we convert those to fractions if they never terminate, right? You can't infinitely put something over an infinite power of 10. That would be a lot of work. So we have a very specific method of how we do this. I'm going to cut to the whiteboard so we can do this together, and then we'll go from there. Okay, I believe we are now on the whiteboard. So let's practice putting non-terminating decimals back into fractions. So the first example we'll do is that 0.33333 repeating. Didn't mean to put that there. Ooh. Okay. X equals 0.333 and so on. And we know that 1/3 is equal to 0.3 repeating. Okay, well, how do we convert this back to a back to a fraction if this never terminates? We can't just do that. Okay, so what we're going to do is multiply this X by 10. Okay, well, when we multiply any number by 10, it moves a decimal place over 1 spot. If we were to multiply by 100, it would move the decimal place over 2 spots, and so on. Well, let's multiply this X by 10. Well, when we multiply by 10, we then get 3.333 repeating, and these 3's never stop. So even though we only had 3 3's written right here, when we move the decimal place over 1, those 3's still extend infinitely. So we don't really need to worry about running out of 3's for this. So here's what we're going to do. We have that x is 0.333 repeating, and 10x is 3.333 repeating. And what we're going to do is subtract them. So we're going to subtract 0.333 repeating, x equals 0.333 repeating from 10x. And what happens is this. Okay, well, if we have 10x minus x, we have 10 apples and you eat 1 apple. Well, now you only have 9 apples. And when we subtract the decimal places, this is why this method is so useful. Well, we have 3 minus 0, and 3 minus 0 is 3. But notice that everything to the right of the decimal place just goes away. 0.333 is the same as 0.333. Well, when you subtract the exact same thing from itself, that just goes away. So just like that, we've gotten to a point where there's no more decimal place. And that's fantastic. What we would do from here is divide both sides by 9 and divide both of those by 3 to get 1 over 3, exactly like we had before. Now we're breaking some sequence here because we haven't really talked about solving equations, but I think we're familiar enough with the process of solving something like 9x equals 3. So that's not too shabby. But okay, let's do another example like this. For example, like the 0.262626 repeating example. Well, we said 26 over 99 was 0.26 repeating. So how would you be able to do the same thing with something that repeats 2 decimal places? Well, if we multiply this by 10, we know it moves a decimal place over only 1 spot. So you would get 2.626262 forever. But notice that when we go to subtract, everything to the right of the decimal place is not the same anymore. When we subtract them, they're not identical. Of course, they share decimal places, and as you go on infinitely, they kind of go away. But as it's written, they don't perfectly go away. So this doesn't really work in this way. So what we're going to have to do is this. Well, instead of multiplying by 10, why don't we instead multiply by 100? So take x and multiply it by 100. Well, if we multiply by 100, we move the decimal place over 2 units. So then we would get 26, right? 1, 2 units. Decimal place is here now. So 26, and then everything to the right of the decimal place, oh, looks very similar. Well, we don't want to do anything else with 10x, right? That was kind of the bad sheep. We don't want to deal with that. But notice that we have 100x equals 26.262626, and we can now subtract 0.262626. All right, well, you see everything to the right of the decimal place is the same again, and that leaves us with 100x minus x, that's 99x, 26 minus 0, that's 26, and we divide both sides by 99, and we finally get back to the original. So that's how we convert non-terminating but patterned decimal places back to fractions. Now I'm going to cut back to the presentation. Okay, and I believe we're back to the presentation. So now we continue. Well, if we have a set of numbers that represents numbers that can be written as fractions, well, what about all the numbers that can't be written as fractions? What if we have a decimal place that is non-terminating, but also non-patterned, where you just continuously make up new numbers in every decimal spot? Well, we have a set for that called the irrational numbers. If rational numbers are numbers that can be written as fractions, then irrational numbers are numbers that cannot be written as fractions. For example, 2 popular ones are pi and square root of 2. So, for example, pi is roughly 3.14, but you can extend pi infinitely, 3.14159, and so on. If you look up, the never-ending digits of pi, you'll find computers that continue to find different decimal places, which is pretty interesting. Square root of 2 is roughly 1.41, I believe, but it doesn't stop at 1.41. So again, irrational numbers would be the set of all non-terminating and non-patterned decimals. And I kind of mentioned it before, rational approximation. We're going to do that quite a bit. So, you could use the pi button on your calculator to be accurate as accurate as possible. But in normal everyday talk, we sometimes just like to say pi is roughly 3.14. So in some cases, we like to just use 3.14 if our ending results wouldn't be off by that much. The rational numbers with the irrational numbers, so the set of rational numbers with the set of irrational numbers, the set of all numbers that can be written as fractions and the set of all numbers that cannot be written as fractions, they form R, which is the real numbers. Okay, so we actually have this very interesting level up when it comes to the different sets of real numbers. So I'm going to again go back to the whiteboard to show you this kind of progression. So just give me one moment. Okay, now we're back to the whiteboard. So we initially started with the natural numbers, which was roughly 1, 2, 3, 4, 5, all the counting numbers. And then we introduced 0, which then gave us the whole numbers. So the natural numbers literally sit inside the whole numbers. If a number is a natural number, then it is also a whole number. They're not exclusive. Okay, well then the next progression was to say that we have the integers and the whole numbers all set in the integers. So if it's a natural number, it's also a whole number. If it's a whole number, it's an integer. So by extension, all natural numbers are also integers. Well, we said all the integers sit in the set, the rational numbers. So again, if it's a natural number, it's a whole number. Whole number is an integer. Integer is a rational. Well, by extension, natural numbers and whole numbers are also rational numbers. But then that's where that progression stopped. And then we said we have this set on the outside that we'll denote with a capital I just for the purpose of what we're talking about. So we have this set of rational numbers. We have this set of irrational numbers that are mutually exclusive, but they together make up the real numbers. So both of them together gives us the rational numbers. Sorry, the real numbers, excuse me. The set of both of them give us the real numbers. Now, there is one more progression to this that we don't see until section 1.4, but all the real numbers sit inside an even bigger set called the complex numbers, but we're going to leave that for a little while, and we'll come back to that. But now that we have this progression of sets, we can start to classify them. So when we get back to the presentation, we're going to look at an example. Okay, and I believe we are back to the presentation. Okay, so let's do an example of classifying these numbers. So we have a set A that has the elements -6, -3.4, -9/3, -2/3, 0, 3/4, 7/9, pi, square root of 10, square root of 36, 8.8, 9, and square root of 131. Okay, so we wanted to classify these numbers into the natural numbers, into the whole numbers, into the rational numbers, and so on. But one thing we should do is see if we can simplify any of these numbers right away. Well, notice that -9/3 we can simplify to -3. Square root of 36, we haven't talked about square roots just yet, but square root of 36 would be 6. So let's make that change first. Let's simplify numbers that we do know. Okay, and now let's start to categorize these numbers into all of those sets that we've talked about. So natural numbers are all the numbers that are like counting numbers, 1, 2, 3, 4, 5, and so on. So let's go through our set A and see which of these numbers look like counting numbers. Okay, well, counting numbers are all positive, right? 1, 2, 3, 4, 5. So that immediately rules out all these negative numbers. 0 isn't a natural number. We didn't introduce 0 until the whole numbers, so 0 is also not a natural number. 3/4 and 7/9 are not counting numbers. Pi, not a counting number. Square root of 10, we couldn't simplify that, so it doesn't look like it's going to be a nice rational number for now. But 6 is a natural number. 8.8, not a counting number. It's close, but not quite. 9 is also a counting number, and square root of 131 is not. So the only natural numbers in our question are 6 and 9. Okay, well, we want to extend this to then do the whole numbers. And we can do the rest of these problems in two ways. One way we can do this is say, okay, well, natural numbers are also whole numbers. So anything that's in this set will also be in this set. And all we need to do is find the new elements that are added to the set. We can do that, or we can just rescan the entire set A to determine which is going to be in the whole numbers. So let's rescan, and you'll see that all we did was basically rewrite the natural numbers and just some added elements. So whole numbers was 0, and the counting numbers, well, that still doesn't include any negative numbers, but it does include 0. It didn't include fractions just yet. Pi still no, square root of 10 no. 6 and 9 were natural numbers, so they're also going to be whole numbers. 8.8 is still not a counting number, and square root of 131 is also still not a counting number. So the whole numbers are 0, and the two counting numbers from the previous set. So again, I want to stress, if it's a natural number, it's also a whole number. Just because it was in the natural numbers doesn't mean we exclude it in the following sets. It still belongs there. So to an extent, we're going to have sets that grow just a little bit. Okay, well, next up is the integers, and the integers would be the whole numbers, and then including any negative counting numbers, so to speak. Well, let's go through our set and see if there's any negative numbers that would also be like counting numbers, just negative. Well, -6 is a counting number, so -6 is an integer. -3.4, not quite. -3 would be an integer, but -2/3 would not. And again, if it's a whole number, it's also an integer. So we don't need to go through all this. We can just say the integers are -6, -3, and everything we've had in the previous sets. Okay, the next extension would have been the rational numbers, and the rational numbers are any numbers that can be written as fractions. And part of our simplification process is that we already picked out the things that can be written as fractions or simplified those kind of things. So let's go through. Well, -6 is an integer. It is a rational number. -3.4, terminating decimal, it is a rational number. -3 was an integer, is a rational number. -2/3, that's a fraction, rational number. 0 was an integer, also a rational number. 3/4 and 7/9, oh, both of these are fractions, the definition of rational numbers. Pi, still no. Square root of 10, still no. 6 was an integer, still a rational number. 8.8, terminating decimal, we can write that as a fraction. 9, integer, still a rational number. And square root of 131, not quite. Okay, well, we stopped the progression at rational numbers, and we said, well, we have this weird set that wants to do everything different. We have rational numbers, and then we have the set of all numbers that cannot be written as fractions. Well, we just found the set of all things that could be written as fractions. So for the first time, if it's going to be in this set, it's not going to be in irrational numbers. It can't be written as a fraction and also not be able to be written as a fraction. So we want to go through our set, pick out all the numbers that can't be written as fractions. But the easiest way to do this is, if we found it in the rational numbers, it's not going to be in the irrational numbers. So we have already left out pi, which we've already discussed being an irrational number. Square root of 10, plug it into your calculator. It's not a pretty number. It's like 3 point something, but it never terminates the decimal places. So square root of 10 is irrational. Square root of 131 is roughly 11 point something, both of which don't terminate. So again, if it was a rational number, it can't be an irrational number, and vice versa. Okay. Well, then we have the real numbers, and we haven't talked about anything that isn't a real number yet. So one way we can think about this is, if we have already talked about it, it has to be a real number. But also, just more generally, the real numbers are made up of the rational numbers and the irrational numbers combined. Put those two sets together, it happens to be the same as our original set. So we're just copying and pasting all of the numbers in the original set. Awesome. Okay, that's the entire just first subsection into the first section. So again, P1 very long, we continue. Okay, so let's talk about inequalities. And inequalities are expressions that describe the relationship between any two numbers, more specifically any two real numbers. But again, we haven't talked about anything that's not a real number so far. So of our inequalities, we have this notation that says A is less than B, which means that A is literally less than B, right? For example, 2 is less than 3. So we would use this notation to say that this number is smaller than this number, or to the left of this number, right? This inequality points to the left. A is to the left of B. Well, numbers to the left of 0, or numbers that are less than 0, we say are negative. And similarly, we have A is greater than B. All the numbers to the right of B, right? This arrow points to the right. All the numbers to the right of B, or we say A is greater than B. 3 is greater than 2. All the numbers to the right of 0, all the numbers that are A is greater than 0, we say are positive. And we also have notation that says A is less than or equal to B, and A is greater than or equal to B. So for example, 2 is strictly less than 3, but 2 is also less than or equal to 3. We know that 2 does not equal 3, but it does still fit this mold of less than or equal to 3. Now, 3 is not less than 3, but 3 is less than or equal to 3. So that's the only added thing. We allow that specific value to now be included. And same thing here. 4 is greater than or equal to 3, but 4 is also greater than or equal to 4. We also have some notation that says some number sits between A and B. We're going to use this in just a few moments as well. If we have a number that is both less than or equal to another number and greater than or equal to another number, well, the only way a number can be less than and greater than another number is if those two numbers are equal. So if this was just a strictly less than or strictly greater than symbol, this couldn't work. There's no number that is less than and greater than another number, but the only numbers that are less than or equal to or greater than or equal to are numbers that are equal to each other. If A is greater than or equal to 0, well, numbers that are greater than 0 are positive, but 0 is neither negative nor positive. And by introducing the greater than or equal to part, we're saying that this number can now be 0. Well, again, 0 isn't positive or negative, so what we can say is A is non-negative. We know it's positive if it's bigger than 0. We know it's 0 if it's equal to 0. So the way we encapsulate both of those in one word is to say A is non-negative. It's not negative. It's everything but negative. Likewise, if A is less than or equal to 0, we say A is non-positive. The trichotomy property says that all pairs of numbers must fit into one of three options. All pairs of numbers must be less than each other, equal to each other, or greater than each other. So, for example, 2 and 3, well, the only way that 2 and 3 are related is when 2 is less than 3. 5 and 25, the only way that they can be written is that 25 is bigger than 5. And the only way that 6 and 6 can be related is if 6 equals 6. So all pairs of numbers must fit into one of these three categories. Transitive property says that if we have a number that is less than B, and that B is less than C, well, then by extension, A is less than C. So if 2 is less than 3 and 3 is less than 4, then 2 has to be less than 4. So that's where that comes from. Okay, so I mentioned we'll talk about the real number line later on, and we have finally gotten to that point. So let's jump back to the whiteboard again to go over what some of these things would look like on a number line. Okay, so now we're back to the whiteboard. Let's start by just writing what the real number line looks like. Well, the real number line, believe it or not, is a line. We got arrows at both ends to say the right end goes all the way to infinity, and the left end goes all the way to negative infinity. And usually as a good placeholder, we like to put 0 right there. So all of these numbers to the right of 0 are positive. A is less than 0 if A is greater than 0 if A is to the right of 0. And all the numbers to the left of 0 are negative. So we can say B is less than 0 because B is to the left of 0. Now, to go over some of the other properties that we just talked about, we could say that A is greater than B in this case, or we can say B is less than A. They would say the same thing. If you kind of notice, if we were to reverse A is greater than B, we would get B is less than A. And we can also say that A is greater than or equal to B if we chose a B that is here, 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 anywhere to the left of B, so long as A is bigger than it. But also, A and B can be the same thing since we allow it to be equal to. And same thing for A is less than or equal to B, just everything to the right. So I'm going to erase this just very quickly just to talk about some of the other ones. Some of the other things we talked about is we said the transitive property, And one more property to talk about, we'll talk about the transitive property. Transitive property said that if A is right here, and B is right here, and C is right here, transitive property said if A is less than B, and B is less than C, if A is to the left of B, which it is, and B is to the left of C, then A has to be less than C. And that makes sense because A is to the left of C. Okay, so those are all the inequality properties, or most of the inequality properties we just talked about, but just gives you an idea how we put these things on a number line. Just to give you another very brief example as to what we might want to do. For example, if we put -3 right here, and we put 4 right here, well, then -3 is less than 4. Or we could put 2 here and say 2 is less than 4. We could put 6 here and say 6 is greater than 4, all stuff like that. Alrighty, so let's cut back to the presentation yet again. Okay, and now we're back to the presentation. I think we only need to go back to the whiteboard one more time in this section. But let's go back to talking about sets now that we've talked about some inequalities. You'll notice that when we were writing sets like we had before, that set A from like -6 to square root of 131, those numbers were quite disjoint. They weren't necessarily rhyme or reason. But what if we wanted to have a set of a lot of numbers? How could we write a lot of numbers in a very shorthanded way? So let's build our way up to that. First way we can write sets is the roster method. So the roster method just says list everything in the set. So for example, we have the set 1, 2, 3, 4, 5. That makes sense. We wrote all the numbers in the set, but we can also, just looking at another example, imagine if we wrote everybody's name in the class in a set. Well, that's why we call it a roster, right? But also, you can already imagine that it would be very tedious to write everyone in the class's name. For classes that are very large, this could take a lot of time. Well, set builder notation, what we can do is introduce a shorter way of kind of generating everything in the set. So maybe rewriting 1, 2, 3, 4, 5 over and over again isn't so bad, but the second that it's like 1 through 100, well, it would take a lot of time for us to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 100, right? I can't even say it. Like, it would take a long time for me to even just say it, let alone write it. So set builder notation would be something that looks like this. What this says is the set of x such that x is between 1 and 5, and x is a natural number, and then inset. So all the numbers between 1 and 5 such that all of those numbers are natural numbers. Well, imagine this set was from 1 to 100. What we could say is 1 is less than or equal to x, less than or equal to 100. And that would take significantly less time than writing 1 to 100 over and over and over again. If we were to extend the idea into what this class is, what you could say is a student such that the student is in Max-ematics class. Okay, so let's write the set 2, 3, 4, 5, 6, 7, 8, 9 in set builder notation. Well, let's use this as a guide. What we would write is x such that 2 is less than or equal to x, less than or equal to 9, and that x is a natural number. So yes, there's a lot more numbers that are included between 2 and 9, like for example, 2.5 or 7.33. Those numbers are also in between 2 and 9, but we're adding the restriction that x is a natural number. Okay, so let's write the set -3, -1, 1, 3, 5, 7 in set builder notation. Well, we gotta be a little careful here because we notice that all of these numbers are in between -3 and 7, but they're not all of the numbers in between -3 and 7. Well, here we had all natural numbers, but now we have negative numbers. So all of these numbers are going to be integers. That's number one. But also notice that all of these numbers are odd numbers. You don't see 2, 4, 6, -2, 0. So what we could write is x such that x is between -3 and 7, and x is odd, and x is an integer. So that's one way of writing. That's another way of writing set builder notation. We just add restrictions as we need. If we wanted to write 17, 18, 19, and so on in set builder notation, we could use another inequality that says x such that x is greater than or equal to 7, and x is a natural number. Sorry, 17. 7, not 7. 17. We can write x such that x is greater than or equal to 17, and x is a natural number. You could also technically say that x is an integer because all of these numbers are also integers, but I think it's easier that we just stick to the sets that we know. Okay. Well, now that we know some sets, we can extend this into what we call unions and intersections. Well, the union of any set is written as A union B with this little cup, this kind of U symbol here, right? U for union. That makes a lot of sense. And what A union B says, it's the set that everything sets A and B have together. So you take A, you take B, and you put them together. Okay, well, then we have intersection. So A intersection B, denoted with this, upside down cup, upside down U. This would be everything that sets A and B have in common. So that's actually kind of interesting. This isn't what they have together. It's strictly what they share. Okay. In general, when we're writing unions, intersections, or even just sets in general, we don't like repeating numbers. If we can avoid repeating numbers that are not distinct from each other, that would be ideal. For example, if 2 appears in one set and 2 appears in another set, well, 2 is not distinct from any other 2. But if we were writing like names, they would be distinct because, one person named Max has a different last name from another person named Max who has a different last name. So we would want to repeat in that case, but non-distinct things, we don't like to repeat. Numbers in a lot of cases are non-distinct. We also like to write numbers in order. So if you have the option to write numbers in order, you absolutely should. So let's say we have A is everything between 1 and 10. B is everything between 1 and 9, all the odd numbers between 1 and 19. And C is all the even numbers between 12 and 20. So let's find a couple different things. Let's first find A union B. Now, A union B says everything A and B have together. So take A, take B, and put them together. Again, restriction 1, don't repeat numbers. So we don't need to write 1 twice. We don't need to write 3 twice. We don't need to write 5 twice, and so on. And we want to write all these numbers in numerical order. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 5 repeat, but then 11, 13, 15, 17, 19. This would be the most proper way to write this union. A intersection B is everything that sets A and B have in common. So look at A, look at B, and see what numbers they both have. Okay, A intersection B, they both have a 1, they both have a 3, they both have a 5, they both have a 7, and they both have a 9. But they don't repeat anything else. So A intersection B would be 1, 3, 5, 7, 9. B union C says everything that B and C have together. So take B, take C, put them together. But again, don't repeat numbers. Thankfully, nothing repeats in this set, but write these numbers in order. So don't just write 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 12, 14, 16, 18, 20. Write those numbers in order. Last but not least, for unions and intersections, let's do B intersection C. B intersection C says everything B and C have in common, but you might notice that look at B, look at C, and they don't have anything in common. In the event that they do not have anything in common, we can say empty set. You can also use, again, a set of empty braces. Just don't use both notations at once. Use one or the other. And now we want to introduce intervals. So what you might notice that we did in set builder notation is that we had a set like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we would want to write everything or x such that x is between 1 and 10 and x is a natural number. Well, that's great and dandy, but what about including all of those things in between 1 and 10, like 9.5 or 7.2 and so on, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is a very nice set to say. They're just counting numbers. We've been using counting numbers forever, but it's not really encapsulating anything, right? We want to be able to have all the values in between where it's not just 1 and then 2 and then 3. We want to have a nice continuous set of values, and that's where intervals come in. So not only are they going to come in, but they're also going to give us a shorthanded way of even using set builder notation. So roster method can be very long. Set builder notation allows us to sort of put a cap on that, but intervals are going to be really nice for us to write it even shorter. So again, intervals are continuous sets of values, and we have two types of sets, or sorry, we have two types of intervals within that. We have bounded intervals and unbounded intervals. Well, bounded intervals come in also two different types. So we have a whole bunch of different, subtypes of these things. So bounded intervals, the first type we have is the closed interval that we denote A, B in brackets. So bracket A, comma B, bracket. And what this says is everything from A to B, not just the natural numbers, not just the integers, everything from A to B with A and B included. So when we use a bracket, it is including that endpoint. So if we're saying A to B, it's A to B in brackets, that says everything between A and B with A included and with B included. Then we also introduce the open interval, which would be A to B in parentheses. So parentheses, A, comma B, parentheses. This says everything from A to B, but not including A and B. So when we use brackets, we do include those endpoints, but when we use parentheses, we don't include those endpoints. So for example, if we had the set 2 to 3 in brackets, that says everything from 2 to 3, including 2 and including 3. But if we have the set 2 to 3 in parentheses, that says everything between 2 and 3 except 2 and 3. So that might include 2.000000001, but not 2. It might include 2.999999999, but not 3. Well, instead of writing 2.0000000 infinitely, 1 in brackets, it's a lot easier to just write 2 in parentheses. Instead of writing 2.999999999 infinitely in brackets, it's easier to just write 3 in parentheses. We also have sets that are neither open nor closed. This happens plenty of times. All it is that one side is open and one side is closed. Nothing wrong with that. It's just that we don't classify it as open or closed. One side's open, one side's closed, and this one side is closed, one side is open. So instead of giving it a name, we just say it's neither, but we're going to be more interested in actually doing things with these intervals instead of naming them. So what this one would say is everything from A to B, A not included, but B included. This would say everything from A to B with A included and B not included. Well, those are all bounded intervals. Then we also have unbounded intervals. Unbounded intervals, as they sound, are any intervals where one bound is infinity or negative infinity. And I'll say bound in quotation marks because technically we can't bound infinity or negative infinity. So for example, this would be like 2 to infinity or negative infinity to 6. This says everything bigger than 2, 2 not included. This says everything less than 6 with 6 included. The real numbers, for example, would be negative infinity to infinity, everything to the left of 0 and everything to the right of 0 and 0 included. So that's how you would write this interval. And infinity in general, we're going to talk more as your time goes on in math. You'll talk more about it in pre-calc. You'll talk more about it in Calc 1. Calc 1 is where you really start to talk about these things. But infinity in general represents a set of increasing values. It's not a value itself. It's representing this value can increase forever. So, for that reason, infinity only uses parentheses. You'll notice that we never put brackets on infinity because we can't include infinity. So if you're using infinity or negative infinity, always use parentheses for that bound, for that endpoint. Okay, well, we can draw intervals on a number line now that we don't have just 1 and 2 and 3. So let's practice writing some of these things on a number line. And I believe this is the last time we need to go to the whiteboard. So let's do it. Okay, so now we're back to the whiteboard, hopefully for the last time. I'm pretty sure it's the last time. But let's say we have our number line. 0 as a placeholder forever in both directions. And let's start by writing the interval -3 to 4. Well, -3 to 4 would be, let's put -3, let's put 4. And -3 to 4 says everything in between -3 and 4. But we need to add one more restriction. And it's the fact that on the open interval -3 to 4, parentheses mean that we're not allowed to be equal to -3, and we're not allowed to be equal to 4. We can be like 3.99999999, but not 4. Well, how we do that is we represent that with an open circle. So we would say open circle -3, everything in between -3 and 4, and open circle for 4. So technically we shouldn't have, I was afraid I was going to do that. So technically we don't want to, have that little inside, go into the open circle. So this would be a little bit more accurate as to what an open interval would look like. Okay, well, let's continue. Let's do some more examples. Okay, the next example is 2 to 6, a closed interval. So same thing, let's take 2, let's take 6, and we want everything in between positive 2 and 6. But now we need to take into account that we have brackets. And again, the brackets say that we do include those values. So if we have brackets that do include, we like to use closed circles for this. So again, open was using, parentheses was using open circles, and brackets now use closed circles. And this says everything between 2 and 6, with 2 and 6 included. So parentheses use open circles, and brackets use closed circles. Okay, so let's just continue practicing writing some of these intervals. Okay, next up, let's do -3 to 4, but this time 4 closed. So still -3, still 4, still everything in between -3 and 4. But this time, parentheses still used for -3, so we're still going to use an open circle. But this time we have a bracket at 4, so we're going to use a closed circle at 4. Okay, not so shabby. I think this makes a lot of sense. Write all the values in between them, and then just use parentheses or brackets use open circles or closed circles depending on whether or not parentheses or brackets are used. Just to do 2 more examples involving infinity. Let's say we want to do 2 to infinity. Well, 2 to infinity would be 2. We have parentheses, so we want to use an open circle. And then instead of writing like another endpoint, we just take that and extend it infinitely toward infinity. We'll use another arrow there. Don't necessarily have to, but it's good practice to say 2 and then everything to the right of 2. Similarly, if we want to do -infinity up to -7, well, let's put -7 here. -7 is using brackets, and then everything in that direction. We'll do one more example, actually. Let's say we have Let's do one more example, actually. Let's say we have -2 to infinity, and we'll put brackets. All right, well, -2, closed circle, and everything to the right. There we go, just to give you some ideas on how infinity would work. Alrighty, so let's go back to the presentation, hopefully for the rest of the time. Okay, well, now that we know how to draw intervals on a number line, let's now practice taking sets that are in set builder notation and write them as intervals. Right, we use set builder notation to sort of simplify the roster method, and now we can use intervals to simplify set builder notation. So here we have -5 less than or equal to x less than 5. This says everything between -5 and 5, with -5 included by virtue of the less than or equal to. So we are able to be equal to -5, and that's the same as using brackets. So we're going to use brackets for -5, comma, parentheses for 5. If you don't like the way I jumped to this, you could practice doing these on a number line and jump to the same conclusion that way. So -5 is included, we used a bracket for it, and 5 is not included, so we used a parentheses for it. Okay, we have x such that 0 is less than or equal to x, less than or equal to 10. So this is everything between 0 and 10. But again, 0 is included by virtue of the less than or equal to, and 10 is also included with less than or equal to. So if both of them are included, we're going to use brackets for both. Here, we have everything between 1 and 3, but 1 not included, 3 not included. So this would be 1, 3. Last but not least, we have -6 to -5. -6 not included, so we're going to use parentheses for -6, but -5 is included, so -6, -5 with brackets. Okay, last but not least, right, I think we may have a few more examples, but x such that x is bigger than 16. What this is saying everything bigger than 16. 16 is not included, so we're going to use parentheses for 16, but this will be 16 to infinity, right? Everything bigger than 16, everything to the right of 16, so 16 not included to infinity. I think this might be the last example, but now everything less than or equal to -1. Well, -1 is going to be included, so we're going to use brackets for -1, but notice that this goes forever to the left of -1, everything less than -1. Well, we don't want to write -1 to -infinity because we like writing these intervals from left to right, right? -5 to 5, 0 to 10, 1 to 3, -6 to -5, 16 to infinity. So be careful because this says -infinity up to -1. Everything less than -1, well, that's -infinity, but -infinity is to the left of -1. And again, for infinity, we always use parentheses, but here in this case, -1 is included as a value, so we use brackets. And that brings us to absolute value. Absolute value is a little different from the things we've talked about, but now that we have an idea what the number line is, we can extend our knowledge to doing these things algebraically. So absolute value in general is the distance from that number to 0. So if you're saying the absolute value of some number, it's asking how far away is this number from 0. Okay, well, if I ask you how many units away from 0 is 5, you would say it's 5 units away. But also, if I said how many units away from 0 is negative 5, you would also say 5 units. Okay, well, 5 is 5 units away from 0. Negative 5 is 5 units away from 0. So in a sense, absolute value is always going to be positive. Okay, well, the notation we're going to use for absolute value is this A and these like long vertical lines. This says absolute value of A. Again, enclosed in this in these long vertical lines. Well, distance is always positive, right? If we're talking about units away, we're usually talking about positive distance. So absolute value of A, kind of like we were just talking about, is always positive. However, don't be fooled because there are ways we can make absolute value negative. If we tack a negative sign on the outside, well, this says take the absolute value of some number and then make it negative. Okay, so we're allowed to do that. So negative absolute value of A would always be negative. Again, absolute value of A is positive, but the second we tack on a negative sign, now the whole thing is negative. So it is possible for us to get negative numbers when it comes to absolute value. Just the absolute value itself is always positive. The absolute value of any number x is defined the following way. It says that the absolute value of x is itself if x is greater than or equal to 0. So if we want the absolute value of 5, the absolute value of 5 is just 5 because 5 is bigger than 0. However, if your number is negative, then we say it's negative x. So negative x. So for example, absolute value of negative 5 would be negative 5. Negative 5 is less than 0. So if we plug in negative 5 into this says negative 5. Well, double negative cancels out. It's now positive, and that's how we get 5. Uses some properties we're going to talk about at the end of the section, but there we go. We got the idea. So some properties of absolute value. The absolute value of any number is always greater than or equal to 0. So you take any number, you make it positive, it's going to be bigger than 0. However, if you do the absolute value of 0, how far away from 0 is 0? Well, it's only 0 units away, so it can also be equal to 0. The absolute value of A is equal to the absolute value of negative A. So we just saw on the previous slide that if the negative is on the outside, it's negative, but if the negative sign is on the inside, they are then equal. And we'll see examples on the next slide as to why this is true. The absolute value of A times B can be rewritten as the absolute value of A times the absolute value of B. So we're allowed to split up multiplication with absolute values. We can also do the same thing for division so long as that the denominator is not 0. So the absolute value of A divided by B is the absolute value of A divided by the absolute value of B. The absolute value of A minus B, this is kind of interesting, is equal to the absolute value of B minus A. So here we split up multiplication, here we split up division, but we're not allowed to split up addition and subtraction. The absolute value of A minus B is equal to the absolute value of B minus A. So we can swap them in the case that it is subtraction. Here, how we get that is the following. Absolute value of A minus B, well, we can factor out a -1 from A minus B. And now this is multiplication, so we can say absolute value of -1 times absolute value of B minus A. How many units away from 0 is -1? Well, only 1 unit. And then 1 times anything is just itself. So in total, absolute value of A minus B equals absolute value of B minus A, but yeah, that's right there. Nice. So just to reiterate, we cannot split up subtraction. So absolute value of A minus B is not equal to the absolute value of A minus the absolute value of B. Can't do that. And we also can't say that the absolute value of A minus B is absolute value of A plus absolute value of B. We've been saying that, I don't know why that's highlighted. Okay, these things happen. We're also not allowed to say that this subtraction becomes an addition, right? We like the idea of absolute value making things positive, but it doesn't magically change subtraction signs into addition. So in all these cases, when you're trying to subtract things inside an absolute value, do the subtraction first and then take care of the absolute value. Likewise, absolute value of A plus B does not equal the absolute value of A plus the absolute value of B, so can't do that. Only multiplication and division can be split up, not addition or subtraction. So please do not split them up. A is always less than or equal to the absolute value of A. So same thing, every negative number, right? If you take the absolute value of it, it's now positive. Negative is less than positive version. But if that A is positive or it's 0, well, that's going to be equal to itself. Last but not least, we have the distance formula. Distance formula is denoted by D, parentheses A, comma B. So again, this is not now an open interval. This is saying distance from A to B, and we denote that as the absolute value of B minus A. However, absolute value of B minus A, we also said is the absolute value of A minus B. So two different formulas for distance, but either one is correct. And all this says is absolute value typically says how far away is this number from 0, but the distance formula says, well, how far away is this number from another number that isn't 0? It's only so exciting for me to ask you how far away from 0 is 5. It's a little bit more interesting for me to ask how far away from -3 is 5, or how far away from 13 is 5. And that's where the distance formula comes in. So let's do some examples. Oh, I have no idea why this is stuck on the screen. Hold on. Let's try closing and opening it back up. Okay, that was fixed. Alrighty, so absolute value of 25, just doing some examples. How far away from 0 is 25? Well, 25 units. And how far away from 0 is -25? Well, that's also 25 units. So there's a little bit of proof as to why the absolute value of A is equal to the absolute value of -A. Absolute value of 2 plus 5. Do not split this up. We said on the previous slide we can't split up addition and subtraction. However, What we can do is simplify the inside first. 2 plus 5 is 7, so the absolute value of 7 is 7. Okay? Absolute value of 2 minus 5, again, do not split up subtraction. We can only split up multiplication and division. So absolute value of 2 minus 5 says take care of 2 minus 5 first. 2 minus 5 is negative 3. Absolute value of negative 3 is 3. Reminder, do not split them up. Absolute value of 4 minus 6, well, 4 minus 6 is negative 2. Absolute value of negative 2 is 2. And let's do the same thing, but do absolute value of 6 minus 4 instead, just reversing those two numbers. Well, 6 minus 4 is 2, and the absolute value of 2 is 2. So there's proof. Absolute value of b minus a is the same as the absolute value of a minus b. Absolute value of negative 7 times 7, well, negative 7 times 7 is negative 49, and the absolute value of negative 49 is 49. What we could also have done is say that this is multiplication. We are allowed to split up multiplication, so we can split this up as absolute value of negative 7 times the absolute value of 7. The absolute value of negative 7 is 7. The absolute value of 7 is 7. 7 times 7 is also 49. So some proof as to why we're allowed to split up multiplication. Okay, let's do some division examples. 40 divided by the absolute value of 10. Absolute value of 10 is 10. 40 divided by 10 is 4. Okay. 40 divided by the absolute value of negative 10. Well, the absolute value of negative 10 is 10, and 40 divided by 10 is 4. Okay. 40 divided by negative absolute value of 10. So again, these are very different. That placement of the negative sign makes a very big difference. Here, this says take the absolute value of 10, which is 10, but then make it negative after doing the absolute value. Well, negative 10 is just negative 10. 40 divided by negative 10 is negative 4. So again, it's still possible to get negative answers despite the fact that we're doing a whole bunch of examples with absolute value signs. Okay, negative 40 divided by absolute value of 10. Absolute value of 10 is 10, but negative 40 divided by 10 is negative 4. Negative 40 divided by absolute value of negative 10. Do not try and cancel out these negative signs. This negative sign is stuck inside this absolute value. Well, absolute value of negative 10 is 10, and negative 40 divided by 10 is negative 4. Take care of these things in pieces. By the end of the section, we're going to talk about PEMDAS. And again, there's an order in which we do things. Start small. Don't try and answer the entire question at once. Negative 40 divided by the absolute, negative 40 divided by negative absolute value of 10. Again, negative on the outside says take the absolute value of 10, which is 10, and then make it negative. Negative 40 divided by negative 10 is positive 4. Okay. Let's do some distance examples. The distance from 1 to 6. Well, the distance formula says b minus a in absolute value, or a minus b. Let's do b minus a. So the distance from a to b is the absolute value of b minus a. 6 minus 1 is 5. Absolute value of 5 is 5. But also, we can do the same thing, but instead do a minus b. That's totally allowed. 1 minus 6 is negative 5. Absolute value of negative 5 is 5. Okay. Distance from negative 13 to negative 10. Again, absolute value of b minus a. Well, negative 10 minus negative 13. Negative is a positive. Negative 10 plus 13, you're $10 in debt, and somebody gives you $13. You now have $3. Absolute value of 3 is 3. But we can also do it backwards. Negative 13 minus negative 10. Negative creates a plus. You're $13 in debt, and somebody gives you $10. Now you're only $3 in debt, and the absolute value of negative 3 is 3. The distance from negative 15 to 15, well, absolute value of b minus a. Negative creates a plus. 15 plus 15 is 30. Absolute value of 30 is 30. The distance from 2 to 2. How far away from 2 is 2? Well, 0 units, but here's proof why. Absolute value of b minus a. 2 minus 2 is 0. Absolute value of 0 is 0. Okay. We continue. We got a little bit more to talk about. Again, I know this presentation very long. Not all of them are going to be this long, I promise. So let's talk about some exponents, some PEMDAS, and wrap up. I'll start to wrap up the section with the properties of real numbers, and then we have one more subsection after that. But the section called the real numbers and their properties, we're going to just kind of summarize all those properties there. Alrighty, exponents. In general, exponents represent multiplication of the same number multiple times. Okay, well, what we write is x times x times x times x so many times. And depending on how many times you do it, let's say that this happens n times. Well, this would be x to the n. Okay, so if we have n of these x's, we say it is x to the n. X we say is the base, and n is the exponent. If we say something is squared, what we're saying is x times x. Well, x times x, there's two x's, so that's x to the 2. And again, we like to say x squared as opposed to x to the second power. You're not wrong for saying x to the second power, but x squared rolls off a little bit better. Likewise, for cubed, this would be x times x times x, which is x to the third. And x to the third, a little bit more common than x to the second, but still, we like x cubed a lot. However, after cubed, we just say to the fourth. Well, to the fourth would be x times x times x times x, x to the literal fourth power, and so on. Everything after x cubed is to just whatever power we say it is. X to the 1, any number raised to the 1 power is itself, so x to the 1 is just x. X to the 0, a little complicated, we'll prove it in the next section, but x to the 0 is 1. Unless x equals 0, 0 to the 0 is indeterminate. That's a Calc 1 question for a long time from now. So just for now, we could take it for granted that x to the 0 is 1. Any number raised to the 0 power is 1. Negative x to the n is not the same as negative x to the n. So what you're going to see a lot in this class is that the usage of parentheses is very important. The placement of parentheses is very, very important. So here, when we have negative x in parentheses raised to the n power, this says take negative x and raise it to the n power. But this says take x, raise it to the n power, and then make it negative. So again, placement of parentheses changes entirely what the thing is asking. So negative x to the n, again, is negative x times negative x times negative x so many times. But we can also do this as negative 1 to the n times x to the n. Notice this is like negative 1 to the x times negative 1 to the, negative 1x times negative 1x times negative 1x. So we have n negative 1s multiplied together and n x's together. And we're going to use this property kind of, sort of, but we'll have a nice way of like simplifying how we think about it. Okay, but negative x to the n says take x to the n, do x to the n, and then make it negative. So please, those are very, very different. Do not screw them up. A times b times c divided by x times y times z all raised to the n would be all of these things given an n distributing n, right? We haven't really talked about distribution yet, but we know what that means. So a to the n times b to the n times c to the n divided by x to the n times y to the n times z to the n. However, this is true for multiplication and division. This is not true for addition and subtraction. So if you have things that are added or subtracted inside where we would typically distribute our exponent, we're not allowed to do that. We are allowed to distribute exponents when everything is either multiplied or divided together. We are not allowed to do this when things are added or subtracted. So please be very careful. It's a very common error. You'll probably find yourself making it at least once. So before we actually do some examples, let's just do some very quick setup. Negative 1 to the 1, any number raised to the 1 power is itself. Negative 1 squared says negative 1 times negative 1, and we know that negative times a negative is a positive. So negative 1 times negative 1 is positive 1. Well, negative 1 cubed would be negative 1 times negative 1 times negative 1. And we know that negative 1 times negative 1, if we group those two together, well, that's just 1, right? Negative 1 times negative 1, we just saw in the previous part that that's equal to 1. So first part is equal to 1, and then 1 times negative 1, any number times 1 is itself. Last but not least, negative 1 to the 4th would be negative 1 times negative 1 times negative 1 times negative 1. Let's group pairs together, and we know each of those pairs, this equals 1 from negative 1 squared, this equals 1 from 1 squared, 1 times 1 is 1. So what you actually start to see is that numbers raised to odd powers, right? This is to the power of 1, this is to the power of 3, and our final answer in each of these lines was negative 1 and negative 1. So negative numbers raised to odd powers are negative, but negative numbers raised to even powers, right? Negative 1 squared gave us positive 1, negative 1 to the 4th gave us positive 1. So negative numbers raised to odd powers are negative, negative numbers raised to even powers are positive. Okay, very important. So let's do a whole bunch of examples. 2 to the 7th. 2 to the 7th says 2 times 2 times 2 times 2 times 2 times 2 times 2, 7 times. So 2 times 2 times 2 times 2. I'm already going to forget how many times I said 2. But this, we can plug it into our calculator. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, 64 times 2 is 128. But negative 2 to the 7th is negative 2 times negative 2 times negative 2 times negative 2. And you can put all this into your calculator. But let's think about this. This is a negative number raised to an odd power. And we just said on the previous slide that negative numbers raised to odd powers are, in the end, negative. Well, we know what 2 times 2 times 2 times 2 times 2 times 2 times 2 is. I think I said that enough times. That's 128. But since we're taking a negative number, raising it to an odd power, it'll be negative 128. You can also look at it as negative 2 to the 7th is negative 1 to the 7th times 2 to the 7th. So negative 1 to the 7th would be like negative 1. 2 to the 7th is 128, negative 128. But negative 2 to the 7th, no parentheses. This says only raise 2 to the 7th power. This says raise negative 2 to the 7th power. This says just do 2 to the 7th power first. Well, 2 to the 7th power is 128, and the negative sign on the outside, make it negative. Again, placement of negative signs, usage of parentheses is very, very, very important. 2 to the 8th says 2 times 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 2. Well, 2 to the 7th was 128, so 128 times 2 is 256. Negative 2 to the 8th says negative 2 multiplied by itself 8 times. Well, negative number raised to an even power is positive, right? Negative number raised to an odd power is negative. Negative number raised to an even power is positive. So we get positive 256. Or we can also look at it as negative 1 to the 8th times 2 to the 8th, which is negative 1 to the 8th would be positive 1, 2 to the 8th would be 256. So we can get 256 that way. Negative 2 to the 8th, again, no parentheses, says just do 2 to the 8th first. We know that part's 256. Negative without parentheses says make the whole thing negative. 2 to the 0. Any number raised to the 0 power is 1. Negative 2 to the 0. Any number raised to the 0 power is 1. But negative 2 to the 0 says do 2 to the 0 power first and then make it negative. So again, very, very, very important how we write our parentheses. Just to do some more examples, 2 over 7 to the 5th. Again, division and multiplication, we are allowed to distribute those powers, those exponents. So this is 2 to the 5th over 7 to the 5th. 2 to the 5th is 32. 7 to the 5th is 16,807. Negative 2 to the 7th is negative 1 to the 5th times 2 over 7 to the 5th. Well, negative number raised to an odd power is negative. So the whole thing, negative 32 over 16,807. 2 plus 7 to the 5th is not equal to 2 to the 5th plus 7 to the 5th. 2 plus 7 to the 5th is, do the inside first. 2 plus 7 is 9. 9 to the 5th is 59,049. So please, I am begging you, do not distribute exponents across addition or subtraction, only across multiplication and division. Order of operation, PEMDAS, you've talked about this in the past. Please excuse my dear Aunt Sally. I learned it as purple elephants march down Apple Street, and I didn't realize until college that nobody actually said that, but these things happen. PEMDAS just tells us the order in which we evaluate expressions. So the P stands for parentheses, so always do parentheses first. So if you have parentheses in your expression, take care of parentheses first. Exponents, E, after you take care of parentheses, take care of your exponents. Multiplication and division, well, M and D, and this is a common misconception, even though this says P first, E second, this is not M first and then division second. Multiplication and division go in the same step. So you do parentheses and then exponents, but when you go to do multiplication, you do multiplication and division in the same step, in the same line, left to right. Don't take care of multiplication first, all the way through, and then take care of division all the way through. As you go left to right, take care of multiplication and division at the same time. And we can make the same argument for addition and subtraction. Okay, so PEMDAS. One more thing that I'll throw in there is that if you have a fraction, treat the parts of a fraction separately. You'll find a way to accidentally mix it up if you are not careful. So do the numerator first, do the denominator first, and go from there. We're very comfortable with PEMDAS, but let's do a really ugly looking example together. So we have a bunch of parentheses, we got a bunch of division. Yeah, let's do this together. So PEMDAS says do parentheses first. So we're going to take care of our expressions in parentheses. And what I'm going to do is do everything in the numerator first, then everything in the denominator second. So let's take care of just the numerator for right now. Well, we have parentheses. We got to take care of this parentheses first. And inside the parentheses, we have a multiplication and then we have a subtraction. But again, multiplication takes precedence over addition and subtraction. So we'll first do 5 times 2. 5 times 2 is 10. And then just to finish up the parentheses, 10 minus 3 is 7. Well, we have 7 plus 1 times 6. Again, multiplication takes precedent over addition. So 1 times 6 is 6. And then finishing up the numerator, 7 plus 6 is 13. Now let's do the same thing, but in the denominator. Taking care of parentheses, we have addition and we have division, but division takes precedent over addition. I say that right? Division takes precedent over addition. So we do 8 divided by 4 first, and then we can finish up the parentheses with addition. Now, we haven't mentioned it before, but if we have 7 parentheses 3, this says 7 times 3. So this says do the multiplication 7 times 3 first, and then do the division divided by 7, last but not least, plus 1. So the order in which we do these operations is given by PEMDAS. Okay, let's close out this subsection with the properties of real numbers. We've kind of been using them this whole time, and we're not going to spend a whole lot of time really proving these things. That's for a way later class, but we can talk about them. So the real numbers, the set of real numbers has all these different properties called closure, commutativity, associativity, and so on. Closure under addition says that if you take 2 real numbers and you add them, you get a real number back. So the real numbers are closed under addition because no matter which 2 real numbers you add, after you're done adding, you're still within the set of real numbers. And same thing for multiplication. You take 2 numbers that are real and you multiply them, they're still a real number. So it's closed under multiplication as well. Commutativity, the real numbers are commutative under addition because you can take any 2 numbers, add them together, but when you switch their order, it's still the same thing, right? 2 plus 3 is the same as 3 plus 2. So the real numbers are closed under addition. Likewise for multiplication, 2 times 3 is the same as 3 times 2. So the real numbers are closed under multiplication. Associativity, just the ability to move parentheses around. You've seen stuff like this before. The real numbers have identities. They have 2 types of identities. They have additive identities and multiplicative identities. So the additive identity is 0 because any number plus 0 or 0 plus any number is just itself. So if you want to add or subtract a number to any number to get the same thing back, you would add or subtract 0. So 0 is the additive identity in the real numbers. Multiplication, any number, if you want to get back to itself via multiplication or division, you would use 1. So a times 1 is the same as 1 times a, just a. So 1 is the multiplicative identity. Inverses, similar. The additive inverse to any number is the negative version of itself, or the negated version of itself, I should say. So the additive inverse of 2 would be negative 2, but the additive inverse of negative 5 would be positive 5. And what inverses do additively is that when you add them together, they get back to 0. So a little bit of a connection here between identity and inverses. Same thing for multiplication. Every number in the real numbers has a multiplicative inverse with the exception of 0. If you want to get back to 1, well, 2, you multiply 2 by 1/2, and you multiply 1/5 by 5 to get back to 1. Distributivity, all it says is we can distribute A, so we would do A times B plus A times C. And same thing if we put the c to the right. So distribution, we've kind of been using it before. You know what it means, but there you see it. Okay, some more properties, just talking about them. 0 times any number or any number times 0 is just 0. If you have two numbers or two variables multiplied together and they equal 0, then at least one of them has to be 0, right? If a and b are real numbers, there's no way that two real numbers that aren't equal to 0 multiply to 0. For example, 2 times 3 never equals 0. Negative 5 times 6 never equals 0. The only way that two numbers or two or more numbers can multiply to 0 is if at least one of them is 0, because either a is 0, 0 times b is 0, or b is 0, a times 0 is 0. A minus b, subtraction is technically just addition of negative numbers. So a minus b is the same as a plus negative b. And division, similarly, well, division is just multiplication by fractions. So when you're doing 8 divided by 4, what you're really doing is 8 times 1 over 4. Now, we know what division means, but yeah, subtraction falls into addition, and division falls into multiplication. And we know that multiplication is just repeated addition. So in some ways, I like to joke in my class saying that subtraction, multiplication, and division don't exist. It's only addition that exists. But it's just a joke. That's a very oversimplified version of explaining things. And last but not least, we say any number divided by 0 is undefined. In the case where we have 0 over 0, that's indeterminate. That's Calc 1. We're not brushing that here. So properties of opposites and fractions. We've been using some of these already. Negative 1 times a is negative a. Negative, negative cancels each other out. What other ones we got on here? Negative divided by a negative is positive, stuff like that. And these properties of fractions, you see them right here, but I think it's a little bit better if we just do some examples. So let's do that. 128 divided by 24. What we commonly want to do is simplify fractions, right? 128 divided by 24 doesn't really give us a perfect picture of how we can simplify or what it really is, right? 24 is a very big number to divide by. However, what we can do is multiply or divide both numbers by something so that it's a simpler version, right? Not as many numbers, not as big. So what we want to do is find a number that divides both 128 and 24. Well, if you don't right away see a number that divides both, just go for small numbers. For example, 128 and 24, they're both even numbers. So let's divide both by 2. Well, 128 is 2 times 64, 24 is 2 times 12. So what we're saying we can do is that since we were able to rewrite both as a multiple of 2, we can now cancel out those 2's. Okay, so maybe you don't see what 64 and 12 are both divisible by. Well, we can divide both of them by 2 again. And 32 divided by 6, same thing, we can do it one more time. So we just get 16 over 3. But doing it by 2 isn't necessarily the only way to go about doing this. If you see right away that both of them are divisible by 8, go for it. The bigger you can divide by, the better. The less steps it's going to take. So if all else fails, go for 2's, 3's, and so on. But if you see bigger ones, by all means, go for it. It saves you a lot of time. 1221 divided by 660. Well, they're both not divisible by 2. But let's just say that they're both divisible by 11. So let's rewrite both of them as multiples of 11, cancel out the 11s. Oh, well, both of these are divisible by 3, and we can do it that way. Again, if you don't see it, go up the ladder. There's no wrong or right way to do it. Fraction multiplication. When we are multiplying fractions, all we're doing is multiplying the numerators across and multiplying the denominators across. So for example, 11 over 20 times 5 over 12. If we are multiplying, all this says is multiply the numerators, divided by multiply the denominators. 11 times 5 is 55, 20 times 12 is 240, and we just saw on the previous slide how we can simplify these things. Okay, but you might notice that we could have saved ourselves a little bit of time. When we went to multiply, do you notice that 5 and 20 can be simplified? 5 over 20 would be like 1 over 4. Well, 11 times 1 is 11, 4 times 12 is 48, so this multiplication is 11 over 48. If you don't see stuff like this, that's okay. Go through all the work of dividing both of these by 5 and going the long way like we did on the previous slide. There's nothing wrong with that. All of what we, like something like this is just a tool to save you some time, to be a little bit more efficient. But just because you're inefficient doesn't mean you are wrong. So just something to keep in mind. 81 over 7 times 82 over 9. Multiply the numerators, divided by multiply the denominators. And you'll notice that 81 and 9, we can simplify to 9 over 1 and multiply that way. Could have saved us a step. Number 738 is still pretty big. It would have been even bigger if we didn't simplify it right away. Fraction addition and subtraction. So multiplication is really nice because it's just multiply across, but it's not so nice for addition and subtraction. So for fraction addition and subtraction, what we need to do is make sure the denominators are the same. If they are already the same, then you're just adding and subtracting the numerators and keeping the denominators the same. You don't do anything with the denominators in addition subtraction. But if the denominators are not the same, we have to make them the same. Now that's very eerie. Let's do this together. 3 over 5 plus 4 over 5. Well, they have the same denominator, so all we need to do is add the numerators. Add because we are adding these things. If this was subtraction, you would subtract these things. Simple as that. But notice that we kept the denominator 5 the same. Do not also add the denominators. That would be incorrect. Think about it this way. 3 over 5, 3/5 of a cookie, and 4/5 of a cookie. If you have 3/5 of a cookie and 4/5 of a cookie, in total you have a little bit more than a cookie's worth. But if you were to do 3 plus 4 over 5 plus 5, that's technically less than 1. That would be 7 over 10, and that's not a full cookie. So please, in addition, subtraction, keep the denominators the same. The only time we use both denominators is when we were doing multiplication or division. But in the case of like 3 over 2 plus 4 over 5, notice that 2 and 5 are not the same. So we can't do what we were just doing. We have to make them the same. Well, you've heard of least common denominator, least common multiple. So notice that if 2 and 5 are the same, we could add them. What multiple of 2 and 5 would make these the same? Well, let's multiply the first one by 5. 2 and 5, their least common multiple is 10. Well, how do we get from 2 to 10? By multiplying by 5. But note that we can't just multiply the denominator by 5. If we multiply the denominator by 5, we go from 3 over 2 to 3 over 10. And those numbers are not the same. We change the problem if we don't do that. So instead, what we multiply by is 5 over 5. Because 5 over 5 is just 1. And we know that if we multiply by 1, we don't change anything. Well, likewise, for 4/5, how do we get from 5 to 10? Let's multiply by 2 over 2. So now we just have a pair of fraction multiplications. And multiplication says multiply the numerators, multiply the denominators. And now, same denominator, we can add them, and we get 23 over 10. Nice. Subtraction function's just the same, but don't think that you always have to change your both denominators, right? In 2 and 5, they don't share any factors, right? 10 is the first possible multiple for both. But for 12 and 3, notice that 12 is already a multiple of 3. So you don't always need to change both. You can if you want. It would be more inefficient. You would need to simplify later. It doesn't mean it's wrong, just means a little bit more time. So in this case, we only need to change 3. We need to multiply by 4 to get to 12. So let's multiply by 4 over 4. Well, 1/3 times 4 over 4 is 4/12. 13 over 12 minus 4 over 12 is 9 over 12. And that's the same as 3 over 4 after we simplify. So there's that. Fraction division. My screen is so dark. I started recording in the light, and this section is so long that it's already dark. Okay, fraction division. Keep, change, flip to multiplication. So we don't technically fraction divide, so to speak. We only do fraction multiplication. Well, fraction multiplication, what we need to do is this keep, change, flip kind of idea. So let's say we have 7 divided by 4 divided by 1 divided by 3. Keep, change, flip says this. Keep, change, flip says keep the first fraction, change the sign to multiplication, and flip the second one. Keep, change, flip, and now it's just multiplication. So how do we do division? Keep, change, flip gets it to multiplication. 6 over 19 divided by 2 over 57. Keep, change, flip. Notice that 6 over 2 is 3 over 1. 57 over 19, 3 over 1. 3 over 1 times 3 over 1 is 9. 20 over 9 divided by 27 over 25. Well, notice 9 and 27, they have a relationship. 20 and 25, they have a relationship. But all of that canceling out, all that simplification that we do is only when we multiply. So don't try and simplify 27 over 9 and 20 over 25 until we are in multiplication. And now you'll notice 20 and 27 don't work nicely. 25 and 9 don't work nicely. So we just get a nice, non-pretty number, and that happens. And last but not least, if we want to evaluate an expression for a given x value, all we need to do is take that x value and plug it in parentheses. And let's see exactly why. So let's say we want to evaluate 2x squared plus 6x minus 1 at x equals 3, and separately at x equals -4. When x equals 3, what we do is wherever we see x, write 3 in parentheses. And here's why we need to use parentheses, because if we don't, what you might be encouraged to do would be do 2 times 3 and then square it. But that would be incorrect. Remember that this x, the only thing being raised to the second power is x. So we need to make sure that we do 3 squared first. Even with parentheses, you might be encouraged to do 2 times 3 first. But again, hopefully you see 3 in parentheses squared and you go for doing PEMDAS, right? So 3 squared, take care of that first, and then do 2 times that. If you don't use parentheses here, you're going to think you just wrote 63. That would also be incorrect. So you could write 6 times 3 in this case without parentheses, but let's stay consistent. Let's do the same thing over and over again. Okay, well, 3 squared is 9. 6 times 3 is 18. 2 times 9 is 18. 18 plus 18 minus 1, 35. So again, parentheses, very, very, very helpful. When x is -4, even more important that we use parentheses, because if you didn't use parentheses here, you might be encouraged to do 2 minus 4, and that's completely incorrect, right? We have 2 times x in the very beginning. This needs to be 2 times x here. So not 2 minus 4, 2 times -4. And again, we want to make sure that that exponent is going to -4 entirely in parentheses. If you don't use parentheses, you might be encouraged to do 4 squared and then make it negative, and that would again be incorrect. Here, you don't use parentheses, you're probably just going to subtract. So parentheses, very helpful. They're free, use them. -4 squared is +16. 6 times -4 is -24. 2 times 16 is 32. 32 minus 24 minus 1 is 7. So parentheses, very helpful. And we're going to do a lot more of this plugging in values as the class goes on. So that's finally the end of P1. It's very long. I understand it's a lot of information, but it's the longest section in the entire class. So if stuff didn't stick this time, don't worry about it. Okay, now that I'm completely shrouded in darkness, thanks so much for watching, and I will see you in P2. Hi, everyone. Welcome back to P2. We're a little more well-lit than we were at the end of P1, but that's okay. Here in P2, we continue Chapter P and the basic rules of real numbers, and what we're going to do is talk more about exponents in this section. So we talked a little bit about exponents in P1 and how they would pertain to just, evaluating certain expressions, but we're going to look at some more rules for if we are dealing with multiple exponents across multiple expressions at the same time. So what we're going to do is introduce some rules, prove those rules with some very basic examples, do a whole bunch of simplification, and then apply it to the real world using scientific notation. All right, so let's go into some rules. So from P1, we have this nice slide of rules in P1, all rules that we remember, right? If we're doing x times x times x so many times, that would be x to the n. X squared would be x to the 2. X cubed would be x to the 3rd. And everything after x cubed would be to the 4th, 5th, and so on. Any number raised to the 1 power is itself. Any number raised to the 0 power is 1, unless x equals 0, but we're not going to deal with that here. Negative things raised to exponents, we have to be careful. Don't forget that if it's a negative number raised to the nth power, we're doing that negative number n times. But if the negative's on the outside, the only thing being raised to the n power is the x. So you do x to the n first, and then you make it negative at the end. And of course, we can only distribute exponents in the case where everything is multiplied or divided on the inside, like a times b times c over x times y times z. But in the case where things are added or subtracted, we are not allowed to distribute exponents in that way. We're going to introduce one more new rule here, and that's going to be that so long as x doesn't equal 0, x to the negative n, so if we have an integer exponent, right, a negative exponent, not just a natural number, if we have x to the negative n, what we're allowed to do is say this is 1 over x to the n. So in a way, negative exponents drop down. If you have x to the negative n, then the equivalent would be 1 over x to the n. X to the negative 3 would be 1 over x cubed. And likewise, if we have a negative exponent in the denominator, we can also bring it back up. So there's this element of like, negative exponents, they can flip between the numerator and denominator, and then they become positive. Okay, so introducing some more rules, we have the product rule. So if we have two exponential terms being multiplied together, x to the a times x to the b, we can simplify this as x to the a plus b. So two things with the same base multiplied together, we can add their exponents. And here's a little proof why. X to the 5th times x cubed, well, x to the 5th would be x times x times x times x times x. X cubed would be x times x times x. So if we drop those parentheses, we have 1, 2, 3, 4, 5, 6, 7, 8 x's. So that would be x to the 8th, which we could have also done by just saying this is x to the 5 plus 3. So a little bit of proof as to why. Similarly, for quotients, x to the a divided by x to the b, when we are dividing things with the same base but raised to different exponents, we can subtract them. So multiplied together, add exponents, divided, subtract exponents. X to the 5th over x cubed, well, x to the 5th is 5x's, x cubed is 3x's. And what we saw when we were doing fractions at the very tail end of P1, we saw we can cancel out x's. So here, we can cancel out an x pair, cancel out another x pair, cancel out another x pair, and we're left with just a pair of x's in the numerator. Well, x times x would be x squared divided by 1 would be x squared. And we could have also found that by subtracting the exponents. If we have a power of a power, so we have x to some power, where the whole thing is then raised to another power, what we will do in this case is multiply those exponents. So notice that this is a little different from what we had before. X to the a times x to the b, we add those exponents, but x to the a to the b, we multiply. So please be careful to note the difference of those rules. As some proof, x cubed to the 4th, well, x cubed to the 4th says x cubed times x cubed times x cubed times x cubed 4 times. Well, each of those x cubes are sets of 3, so x cubed becomes x times x times x 4 times. We drop the parentheses, and you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 x's, x to the 12th, which is also the same as x to the 3 times 4. Power of a product, so a little bit more proof as to why we're allowed to distribute across multiplication. X to the n times y to the n times z to the n. So again, kind of the rule that we had in P1, and some proof. X times y to the 5th says x times y times x times y times x times y times x times y times x times y 5 times. Drop the parentheses. Let's regroup. Multiplication is commutative, so we're allowed to move x's and y's as freely as we want across multiplication. Let's put all the x's together, all the y's together. Let's regroup the x's and let's regroup the y's, and you see we have 5 x's and 5 y's. So x to the 5th times y to the 5th, which we could have done by just distributing that 5. So again, we had that rule in P1, but now we're proving it. And similarly for power of a quotient, same thing, we're allowed to distribute powers in such a case. But one new kind of rule would be x over y to the negative n. Well, this is going to combine that negative exponent rule we had before, along with this one. So if we have x over y to the negative n, we can first start by flipping the inside to get rid of the negative, kind of like that x to the negative n, flip it to the denominator. That's kind of what we're doing here, just taking some liberty and jumping a few algebraic steps. And now from here, this is just like the previous one, y to the n over x to the n. So 3 over 2 to the 5th, we can distribute as 3 halves times 3 halves times 3 halves times 3 halves times 3 halves. Well, fraction multiplication, 3 to the 5th over 2 to the 5th. Well, we could have gotten via distributing that exponent. 3 over 2 to the negative 5th, we can use the rule that we have up here. It says flip the inside to get rid of the negative. So we now have positive 5 as the power, but we flip the inside from 3 halves to 2/3. And now we can distribute that 5, just like we did in the previous one. Okay, we also said that x to the 0 equals 1 in P1. We can prove that here. X to the a over x to the b. Well, that's x to the a minus b. Well, this is a rule that we had. This is one of our first few rules. But if we make a and b the same power, well, x to the a over x to the a would be x to the a minus a. A minus a, any number minus itself is 0. So x to the 0. But also, any number divided by itself is 1. So x to the a over x to the a equals x to the 0, right? X to the a over x to the a equals x to the 0, but x to the a over x to the a also equals 1. So a little bit of proof as to why x to the 0 equals 1. Now, let's do some simplification questions, right? Fun part isn't going over the rules. Fun part is doing the examples. So let's get right into it. Exponential expressions are fully simplified when all of the following conditions are met. Each base only appears once. So in some cases, we might have multiple x's, multiple y's, multiple z's, multiple 2's, multiple 5's, and so on. Our expression is fully simplified when every base only appears once. We don't want to have multiple x's if we can avoid it. Each exponent is a positive number. Typically, we don't like having negative exponents, so if we can avoid doing that just by flipping negative exponents between the numerator and denominator, that would be fantastic. And also, no power over powers, or in other words, just as few parentheses as possible. So let's do 5 to the negative 4. Well, any number raised to a negative exponent is 1 over that thing raised to the positive power. So 5 to the negative 4 is the same as 1 over 5 to the 4th. Well, 5 to the 4th is 625. 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625. Okay. Negative 5 to the negative 4th. Okay. Again, anything raised to a negative exponent can be dropped down to the denominator. So let's drop negative 5 down to the denominator and make that exponent positive. And now negative 5 to the 4th, we talked about this in P1. Negative numbers raised to even powers are positive. Negative 5 to the negative 3. Okay, negative 5 to the negative 3 says, let's take negative 5, drop it to the denominator and make that exponent positive. Well, negative 5 to the 3, negative numbers raised to odd powers are negative, so we get negative 1 over 125. You can also write 1 over negative 125. That is completely correct. It's just that when either the numerator or denominator is negative, it looks a little nicer to write that negative on the outside. But if you were to write 1 over negative 125, that is perfectly correct as well. Negative 5 to the negative 3, be very careful. The only thing being raised to the negative exponent is the 5, right? Very different from here. This says negative 5 raised to the negative 3. This says 5 to the negative 3 and make it negative. So the only thing dropping down to the denominator is going to be the 5. So this becomes negative 1 over 5 to the positive 3. 5 to the 3 is 125. Okay. So again, from P1, please be very careful with negative exponents and negative stuff on the outside. So again, from P1, just be very careful when we don't have parentheses written for negative numbers. 2 to the negative 5th times 2 to the 9th. The rule that we have for two exponential terms being multiplied together is that we will add the exponents. So 2 to the negative 5th times 2 to the 9th says 2 to the negative 5 plus 9. Negative 5 plus 9 is 4. 2 to the 4th is 16. Simple as that. A little scary to begin with, not so scary when you add the exponents. 2 to the negative 5th times 2 squared. Same thing, we have two exponential terms being multiplied together, so we add the exponents. Negative 5 plus 2 is negative 3. Only difference from the previous question to now is that we have a negative exponent. That's okay, there's nothing wrong with that. All it says is we need to drop this down to the denominator, and 2 cubed is 8. Okay? 2 to the negative 5 squared. So again, note that this is a little different from what we had in the previous line. This says two exponential terms being multiplied together. This is one exponential term being raised to another power on its own. So here, multiplied together, we add here, power raised to a power, we multiply. Negative 5 times 2 is negative 10. If we have a negative exponent, drop it to the denominator and make it positive, and 2 to the 10th is 1024. Okay. 4 squared to the 3rd. Again, this is a power raised to another power. So 4 squared cubed says 4 to the 2 times 3. 2 times 3 is 6. 4 to the 6 is 4096. 6 to the 6th to the 1/3. Again, even though that this is a fraction, it doesn't change anything. If we have a power raised to another power, just like we did here, we are going to multiply. 6 times 1/3 would be 6 over 3. 6 over 3 is 2, and 6 squared is 36. 7 times 6 cubed. Again, be very careful. The placement of our parentheses tells us exactly what is being raised to the 3rd power. If we had no parentheses written, it would be the exact same. Remember that we always do exponents before multiplication. PEMDAS, P-E-M-D-A-S, exponents before multiplication division. So this says only raise 6 to the 3rd power, which is 216. And now we can multiply 1512. 3/4 to the negative 3. The rule that we have for fractions with negative exponents, technically what we can do is take the whole thing and do 1 over 3/4 to the 3rd. But to save us some work, what we can do is to get rid of the negative exponent, flip the inside first. Okay? Once we have flipped the inside, everything on the inside is multiplied or divided. So we are allowed to distribute our exponent. 4 cubed is 64. 3 cubed is 27. Again, key part here, negative exponent for fractions, flip it to begin with. It's a little bit easier to work with. 7 squared raised to the 14th, all over 7 to the 25th. Don't put this into your calculator. It is very, very big. So what we can instead do is say, well, this is a power raised to another power. In that case, we multiply. 2 times 14 is 28. Well, now we have a exponential term divided by another exponential term. So we can subtract the exponents. 28 minus 25 is 3. 7 cubed is 343. 5 to the negative 3 times 3 cubed over 5 to the negative 5 times 3 squared. Well, I haven't really mentioned it before because we haven't really needed to mention it before. But note that we can only combine and use all these rules when the bases are the same. So notice that we can't combine 5 to the negative 3 and 3 cubed because those bases aren't the same. Everything we've been doing so far has been when the bases have been the same, such as here. 7, same base, we're allowed to subtract exponents. Here, not the same base, we can't add. Here, not the same base, we can't add. But what we can do is group bases together. Notice that we have a 5 in the numerator and a 5 in the denominator. 3 in the numerator and 3 in the denominator. So why don't we group those pairs together? Okay, well, for just this first fraction, 5 to something divided by 5 to something, if terms are divided, we can subtract, and the same can be said for the 3's. So 5 to the negative 3 over 5 to the negative 5, we can subtract exponents. 3 to the 3 over 3 squared, we can again subtract the exponents. Negative 3 minus negative 5 is negative 3 plus 5. Negative 3 plus 5 is 2. 3 minus 2 is 1. 5 squared is 25. 3 to the 1 is 3. 75. So just be very careful doing these problems. You might also be wondering, why didn't we flip negative exponents? Why didn't we change this to bring 5 to the negative 5 back up and 5 to the negative 3 back down? And you are very welcome to do that. What you would get is 5 to the 5 over 5 cubed, and then you would just have 5 minus 3, which is 2, and that's where we got anyway. So what you'll notice in some of these is that there's not always one correct way to apply these rules. There's different rules you can use, right? We have a whole set of them. So just because you didn't use the rule that I did, if you got to the same answer, it's very difficult to come up with the correct answer using rules incorrectly. So if you wanted to instead change these negative exponents to positive ones by flipping each one, you're allowed to do that too. It takes a little bit more work, but just because you're being less efficient doesn't mean you're being wrong. Okay. 5 times 6 times 7 to the 10th over 5 times 6 times 7 to the 8th. Again, we have multiplication. If everything on the inside is multiplied or divided, we are allowed to distribute those exponents. But again, be very careful. The only thing being raised to the 8th power is 6 times 7. 5 does not get that 8 because 5 is on the outside of what is being raised to the 8th power. Okay, well, kind of like we did in the last question, notice that we have a pair of 5s, we have a pair of 6s, pair of 7s. So let's group those together. 5 to the 10 over 5, 5 to the 10 minus 1, 6 to the 10 over 6 to the 8, 6 to the 10 minus 8, 7 to the 10 over 7 to the 8. Again, subtract. Do those subtractions. Yeah, these are really large numbers. I don't know who came up with them. That's okay. What is this? 3,445,312,500. Naturally, you guys all could have done that in your head, right? Well, let's start doing these things with variables instead. It's very nice and concrete when we can do these with numbers, but the whole study of algebra is that we want to introduce x's into these types of things. So just because we have x as a base, it doesn't change how we do anything. All it means is we're going to leave an exponent answer in the end. So x to the negative 4 raised to the negative 15. Don't forget this is multiplication, right? Power raised to another power. We multiply. Negative 4 times negative 15 is positive 60. So instead of being able to evaluate at the very end like we were for the other problems, the last set of problems, all it is we just leave our answer as x to the 60th. And this is a lot prettier than what we started with. Okay. 2x to the 5th times 17x to the 12th, kind of like we were pairing things off earlier. What we're also going to do is pair off coefficients and pair off variables. So notice we have 2 times 17 and x to the 5th times x to the 12th. So let's group our constants together. We'll group our x's together. 2 times 17 is 34. X to the 5th times x to the 12th, that is x to the 5 plus 12, which is x to the 17. So just because we add numbers in the beginning doesn't change anything. X to the negative 3 times y cubed. Well, the only thing that has a negative exponent is this x. So what we're going to do is drop that x to the denominator. X to the negative 3 is 1 over x cubed. And now this is fraction multiplication. This is just like y cubed over 1. So 1 times y cubed over x cubed times 1, y cubed over x cubed, which now that we have established how that works, what you can also do going forward for all different problems is if you have multiple terms like this, you can just drop that x cubed down knowing that all of it is together. So don't feel like you need to show this middle step of doing 1 over x cubed times y cubed because we had multiplication in the beginning. This is all one term, so we can treat it all as one term and not need to do things in the middle. But whatever's easier for you, do it that way. X times y to the negative 1. Okay, well, everything in here is multiplied together, so we can distribute the negative 1. Well, x to the negative 1, y to the negative 1, drop those negative exponents down and make them positive. 1 over x to the 1 times 1 over y to the 1, that is fraction multiplication. 1 times 1 is 1, x to the 1 is x, y to the 1 is y, x times y is xy. But also, you can also just look at this and say, this whole thing is being raised to the negative 1. We can just drop the whole thing down. Simple as that. There's nothing wrong with that. 5 times xy squared. Again, the only thing being raised to the second power is x times y. X times y is multiplication. We are allowed to distribute the 2. And we just get 5x squared y squared. That's it. Nothing else that needs to change. But if we include that 5, well, this is now 5 times x times y. Well, all three of these things are being multiplied together. So when we distribute the 2, all three things get that 2. The only difference is x squared, y squared, we can't do anything with, but 5 squared we know is 25. 5 on the outside, xy cubed. Again, the only thing getting the cubed is going to be x and y. But if we include that 5 in there, now everything gets the cubed. 5 cubed is 125. Well, let's start making some things negative. Let's see how it changes. Here, same thing. Only thing being raised to the second power is x times y. Well, negative 5 just sits on the outside. But the second that we include negative 5 on the inside, now all three things get that squared. But don't forget, this whole thing gets the squared. So this is negative 5 squared. Negative number raised to an even power is positive. negative 5 xy cubed. All right, distribute that 3. Nothing else to do there. But the second that negative is on the inside, now we have negative 5 cubed. Negative 5 cubed is negative 125. Again, placements of negative numbers, very, very, very important. X times y squared over x to the 5th, all raised to the 5th power. Okay, everything on the inside, x times y squared divided by x to the 5th. Everything is being multiplied or divided, so we are allowed to distribute that exponent. All of these are powers to a power, so of course the x just picks up the 5, but y squared will be multiplied by 5, and x to the 5th, the exponent will be multiplied by 5. 2 times 5 is 10, 5 times 5 is 25, and notice we have 5x's up here, 25x's down here. We can cancel out 5 of them. If you also want to use the rules of division, you can do that too. You would have x to the 5th minus 25, 5 minus 25 is negative 20, and that x to the negative 20 would come down. Similarly, this is a pretty okay way of doing it, but you could have had some foresight to say, oh, look, we have multiple x's on the inside already. We have 1x here, we have 5 down here. Why don't we just cancel out that 1x to begin with? Cancel out one of the x's, we're left with 4 of them. Now we can distribute the 5 via exponential multiplication, and we can get the same answer that way. So what you're going to see is a lot in this class, a lot of different paths to get the same answer. Negative 2 times x to the negative 2, y to the negative 2 to the negative 6. The only thing being raised to the negative 6 power is x to the negative 2, y to the negative 2. So what you might want to do is say negative exponent, drop it down, and then you'll have a negative 6, and then you have to flip it again. There's no right way of doing it for every problem. Some problems you might want to do, flipping these negative exponents and then flipping it again with this negative 1. But a pretty good way of going about these problems is to just distribute that negative 6 via multiplication and then flip stuff later. But if you're comfortable flipping first and then multiplying exponents, you can do that too. Like I said, not one way of going about this. Alrighty, well, x to the negative 2 times negative 6, that's 12. So negative 2x to the 12, y to the 12. So notice we had so many negatives in the beginning, but just because we had so many negatives in the beginning doesn't mean that we will necessarily all have negatives at the end. Negative 2x over 5, all raised to the negative 4. We have a fraction with a negative exponent. Negative exponent we can get rid of by flipping the inside. 5 divided by negative 2 times x. Everything is multiplied or divided. Everything can get a 4. So we can simplify that way. So lots of rules of exponents being used. Okay, and we're going to finish up P2 with scientific notation. This is not a really long part, but many of you that are watching this might be STEM majors, you might be bio majors, chem majors, and you'll notice that you use very big numbers sometimes, or sometimes very, very small numbers. For example, this is, let's see, million, billion, trillion, quadrillion, quintillion. This is 37 sextillion, 600 quintillion. That's a lot of atoms. But is it efficient to write 37 sextillion, 600 quintillion over and over again? Or is there an easier way? And that's where scientific notation comes in. Scientific notation are numbers that are written in the form a constant times 10 to some power. So with so many decimal places, instead of writing all of those zeros over and over again, what we can do is simplify all those decimal places, or all those like hundreds, tens, hundreds, thousands, and so on. We can simplify that with 10 to the n. So c is going to be some constant, n is going to be some integer. It could be a positive integer, it could be a negative integer, it could be 0. So one restriction that we have is that this c must be between 1 and 10. So we need a way to say, okay, when do we stop moving decimal places over? When do we stop having zeros as places? Well, what we're going to do is make sure that this constant is always between 1 and 10. It'll make a little bit more sense when we do an example. If our number is very big, for example, 37 sextillion, 600 quintillion, that number is very large. In the case where your number is very large, this n, this power, should be positive. And if the number is very small, right, this should also mean that n is negative. Okay, well, think about this. If we have 10 raised to some positive power, let's say 10 to the 10th power. Well, 10 to the 10th power is really, really big, right? 10, 100, 1,000, 10,000, 100,000, million, 10 million, 100 million, billion, 10 billion. I think I got that right. Well, if we're multiplying by something times 10 to the 10th power, that's a really big number. So if n is positive, the number is large. If the number's negative, it's very small. Think about it this way. If we multiply by times 10 to the negative 10, 10 to the negative 10 is 1 over 10 to the 10. So we're, in a sense, dividing by when I say 10 billion. So if we're dividing by 10 billion, our number should be very small. So what we're going to do is take whatever our number is and move decimal places to the left or to the right to determine the magnitude of n. So last slide, let's convert some to scientific notation. So let's convert 37 sextillion, 600 quintillion into scientific notation. So what we're going to do is we know that we have an imaginary decimal place right here, and we're going to move it over so many units until we get a number that is between 1 and 10. So we move over 1 decimal place, and then we move over 2 decimal places, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And again, don't forget that we want to get to a point where the number is between 1 and 10. If the decimal place is sitting right here, well, everything to the left of the decimal place is 37,600,000. That's definitely not between 1 and 10. So we want to stop when, if we dropped our decimal place right there, it's between 1 and 10. So let's keep going. 16, 17, 18, 19, 20. If we stop the decimal place right here, everything to the left is 376. That is not between 1 and 10. Okay, let's go 21 decimal places. Well, if we drop the decimal place right here, we'd have 37.6, not between 1 and 10. But if we go one more decimal place, 22 decimal places in total, if we drop the decimal place right here, notice this would be 3.76. And 3.76 is between 1 and 10. Now, we want to write some power of 10 here. We moved over 22 decimal places, and this number is very big. If the number is big and we moved over 22 decimal places, this should be positive 22. All right, let's do a slightly smaller example. Let's do 5,001. So there's an imaginary decimal place right here, and let's move over until we get a number between 1 and 10. We move over 1, that's 500.1, not between 1 and 10. Move over here, 50.01, not between 1 and 10. Move over here, 5.001, and that's between 1 and 10. Well, so we're going to be 5.001. How many decimal places did we move? 1, 2, 3 decimal places. Okay, so since the number is big, 5,001 is big, that 3 should be positive. One more example like this. Let's stop when we get a number between 1 and 10. So let's move over 1, 2, 3, 4, 5, 6. If we drop the decimal place right here, we have 4.123. That's between 1 and 10. So 4.123 times 10 to the positive 6. We moved over 6 decimal places. This number is big. 4.123 times 10 to the 6. Okay, well, let's deal with a small number now. Let's see how this changes. Well, instead of moving decimal places to the left, let's now move decimal places to the right. Well, we don't need to worry about where that decimal place is anymore because it's sitting right there. Okay, so let's move it over until we get a number between 1 and 10. Let's move it over 1. This would be 0.996, not quite, but move over one more spot. This would be 9.96. Okay, we moved over 2 decimal places, so we know it's either going to be to the power of 2 or to the power of negative 2. 0.0996 is small, so if it's small, this will be negative 2. All right, let's do the same thing. 1, 2, 3, 4, 5. We'll stop right here, so that would be 2.6501, and we moved over 5 decimal places. Well, this number is small. If the number is small, it is going to be negative 5. Okay, we can also convert to standard notation. So if we are given scientific notation, we can go backwards. All we're going to do is move the decimal place in the correct direction. So we know we need to move 6 decimal places, but how do we know which direction we need to move? Well, this is 10 to the positive 6. So we know our number should get bigger. If we move to the left, our number is going to keep getting smaller. So we definitely don't want to move to the left. For positive, let's move to the right, which is kind of a nice way of thinking, right? Real number line, positive is to the right, negative is to the left. So in this case, positive exponent, let's move it to the right. So let's move 1, 2, 3. And you'll notice that we don't have any more places to move. So instead of trying to keep moving, if we moved 3 decimal places over, we have nowhere else to go. Well, we need to move 6. We moved 3. We need to move 6. Let's add 3 zeros at the end. And now it might be a little clearer to see if the decimal place was originally here and we move it over 6. 1, 2, 3, 4, 5, 6. So go until you can't go anymore, and then fill up the extra spots you were supposed to move with zeros. 9.872 times 10 to the negative 8. Well, negative left. Let's move the decimal place over to the left. Well, we moved over 1, and we don't have anywhere else to go. So we need to move over 7 more decimal places. Well, instead of actually moving 7 more, why don't we just tack on 7 zeros? 1, 2, 3, 4, 5, 6, 7. 5.1 times 10 to the 0. Well, 10 to the 0 is just 1. Any number raised to the 0 power is 1. 5.1 times 1 is just 5.1. Let's convert 3.99 to scientific notation. All right, well, we don't need to move the decimal place over at all. It's already between 1 and 10. So 3.99 is 3.99 times 1. And 1 is 10 to the 0. So if the number doesn't need to be changed at all, it would be times 10 to the 0 in scientific notation, but we don't typically do this. So, but still, good practice. Okay, that's the end of P2. In P3, we start to look at some polynomials. So I will see you in P3. Bye. Hi, everyone. Welcome back for P3. In P1, we talked about some real numbers and their properties and some very basic algebraic concepts. And then in P2, we extended what we talked about for exponents in P1 to an entire section in P2. And now that we have a better grasp of what exponents are and how we can add, subtract, multiply, divide those things, we can now talk about polynomials. Well, before we talk about polynomials, we should talk about monomials. So monomials are single terms with a constant and a whole number power of x. So the general monomial would be a times x to the k. So we say a is the coefficient, x would be the variable, and k is the degree. K is also an exponent, but if we're talking about the monomial itself, k is the degree of the monomial. If k is not a whole number, it's not a monomial, period. So we're only going to talk about monomials or terms that have whole number powers. So if it's like 4/3 as a power or square root of 2 as a power, we don't classify it as a monomial. If the coefficient a equals 0, well, then we have 0 times x to the k, and 0 times anything is just 0. The monomial and the eventual polynomial that is equal to 0, we say has no degree. So it's not degree 0. You're going to see on the next slide that there's a difference between degree 0 and no degree. But for when a monomial equals 0, that specifically is the only monomial that has no degree. Otherwise, we would have degree 0 in some cases. So let's do some classification. Let's say we have 2x to the 5th. Well, the coefficient would be 2, and the degree would be 5. Okay, kind of straightforward. Negative 3x squared, the coefficient would be negative 3, and the degree would be 2. 8x, well, the coefficient's easy to tell that it's 8, but the degree is 1 because x to the 1 is x. So there's an imaginary power of 1 up here. No power written. We assume it's power 1 like we've done in the past couple sections. -7, well, kind of easy to tell that the coefficient is -7, but a little less obvious what the degree is. Well, the degree in this case is going to be 0 because x to the 0 is 1. So imagine that there's an imaginary x to the 0 here that we just don't write because we never write x to the 0. Normally we would say x to the 0 is 1. So there's an imaginary x to the 0 here. So you could take it that single constants are degree 0. And again, I want to note from the previous slide, this is different from no degree. No degree is the monomial 0. Degree 0 is any constants. So -7, 3, 5/2, and so on. X to the 12th. Well, the coefficient is what's missing this time. There's an imaginary 1 out in front, right? 1 times anything is itself, so coefficient would just be 1. And the degree, 12. -x to the 4th, well, the coefficient would be -1, right? There's an imaginary 1 sitting between the negative sign and x to the 4th, and the degree would be 4. Okay? And again, just notice that all of these powers are whole numbers. We don't do anything that has a weird exponent, for example, like 4/3 or square root of 2, right? We only want whole number powers. So we can combine monomials in a couple different ways. So 2 or more monomials can be combined if they have the same degree, only when they have the same degree. For example, 2x to the 5th and 3x squared cannot be combined, but we can still write 2x to the 5th plus 3x squared or 2x to the 5th minus 3x squared. So these are things that are okay to write, and we'll talk about these things in the next slide, but in terms of combining them, we can't do that. However, -3x to the 5th and 9x to the 5th can be combined in the following ways that we call combining like terms. So we're going to use this term a lot. Anything that is a like term is anything that has the same degree. So -3x to the 5th, 9x to the 5th, they have the same degree. We can combine them. Okay, so if we wanted to add these things, well, what we're doing is just adding the coefficients. So if I have -3x to the 5ths and 9x to the 5ths and I add them, I now have 6x to the 5ths. Okay, right? -3 apples plus 9 apples, you now have 6 apples, except now those apples are just the degree term x to the 5th. Subtraction functions the same way. -3 minus 9 this time. -3 minus 9 is -12. Okay? So now those things that we couldn't combine before, 2x to the 5th plus 3x squared or 2x to the 5th minus 3x squared, they are called polynomials. Okay? So a polynomial is a sum of monomials. Now the general polynomial that we'll look at again when we get to chapter 3, but for now, just the general polynomial expression looks like this. Now, this is kind of daunting. It's okay. This says some coefficient x to some power, some coefficient times x to 1 power less, some coefficient times x to some power 2 less, and so on, all the way until we get to x squared, x to the 1, and the constant x to the 0 term. Okay, well, all of these separate things being added or subtracted together, we call them terms. The leading term is the term with the highest degree. And if you notice, well, this is n minus 1, which is going to be less than n minus 2 is less than n. So we write terms in descending power order, which means the highest power is going to be a sub n, x to the n. The highest power, n, is the degree of the polynomial. So whatever is the highest power that you see across the entire polynomial expression, that is the degree of the polynomial. And again, all of our terms must have whole number powers. And likewise, if something didn't have a whole number power, we would just say it's not a polynomial. A sub n minus 1, all the way down to a sub 0. Those are all real number coefficients. So the coefficients can be anything, but again, the powers have to be whole numbers. The leading coefficient is the coefficient of the leading term. Well, leading term's right here. Coefficient of the leading term, a sub n. And we want to make sure a sub n does not equal 0. Well, if this coefficient equals 0, then 0 times this is just 0, which would make this the new leading term. So instead of this constant, well, let's make the leading term 0, so the leading term is just the next term. That doesn't make any sense. So leading term should make sure that that coefficient does not equal 0. Standard form, I mentioned it before, it's terms being written in descending power order, right? If this is the highest power, this is 1 power less, all the way down to our constant term. If all the coefficients are 0, well, then our polynomial would be 0 times x to the n plus 0 times x to the n minus 1, and so on. And all of these things, 0 times anything is 0. And again, 0 is the only polynomial / monomial that has no degree. Not degree 0, no degree. Just to do a very brief example of classifying polynomials. So 5x squared minus 3x plus 1, the terms, each, all of the things that are being added or subtracted together. So 5x squared, negative 3x, and 1. The coefficients, well, just take the coefficients of each of the terms, 5, negative 3, and 1. And the degree is the highest power that we see in the entire polynomial. Highest power we see is 2. That's about it. Okay, well, we're very interested in doing operations on polynomials. So we're going to add, subtract, multiply, all sorts of stuff like that. So adding polynomials, if we wanted to add these two things right here, all we're going to do is combine like terms. So we have this polynomial plus this polynomial, and all we're going to do is group like terms together. So negative 4x cubed plus 6x cubed, we're going to pair those together. 5x squared and negative 2x squared, we're going to combine those together. 7x minus 8x, negative 2, and negative 5. Okay. Well, negative 4x cubed plus 6x cubed, that's going to be 2x cubed. 5x squared minus 2x squared is going to be 3x squared. 7x minus 8x will be negative x. Negative 2 minus 5, negative 7. Okay. If you can jump from this line down to this line by just combining, in your head, that's totally fine. I'm just showing you what's happening in that intermediate step. So don't feel like you have to do this. If it helps you, you should to combine and regroup, but this is the step I'm looking for. Okay, so adding, kind of straightforward. Now, when we are subtracting, subtracting is very similar, except what we're going to do is to get this back to addition and to make it look exactly like we just had on the previous slide, we're going to distribute this negative sign to each term here, right? We're doing 9x to the fourth minus 2x to the fourth minus 6x cubed minus negative 11x cubed. And you can already kind of hear that it's a little weird going on, right? So let's distribute a negative 1 to all 4 of these terms. 2x to the fourth will become negative 2x to the fourth, negative 11x cubed will be positive 11x cubed, minus 5x minus 3. And now let's group terms again. So 9x to the fourth, negative 2x to the fourth, negative 6x cubed, 11x cubed. Well, here, notice that we have a 4x squared, but we don't have an x squared term here. And that's okay. It just means there's nothing to combine with it. It's just going to stay itself. And likewise, we have a negative 5x here with no x term over here. And that's still okay. It just means negative 5x isn't going to change. Negative 1 minus 3. All right. 7x to the fourth, negative, this will be 5x cubed. 4x squared is itself, negative 5x is itself, and negative 4. Not too shabby. If we wanted to multiply polynomials, well, let's start with multiplying a monomial with a polynomial. And this is just like distribution. So we want to remember that x to the a times x to the b is adding the exponents. So let's multiply this monomial by polynomial right here. And what we're going to do is distribute 4x cubed to each term. Okay, we'll start there. Well, 4x cubed times 3x squared, this is something that we did in the previous section. 4 times 3 is 12, x to the third times x squared, x to the 3 plus 2, x to the fifth. 4 times negative 5, negative 20, x to the third times x, x to the fourth. 4 times 7, 28x cubed. That's multiplying, just using the product rule from last section. If we want to multiply a binomial with a binomial, so a binomial is a subgroup or subtype of polynomial, where a binomial is just 2 terms. So polynomial is any number of terms, a monomial is 1 term, binomial is 2 terms. Okay, well, what we're going to do is introduce this acronym FOIL. And what foiling says is take the first terms in each binomial and multiply them, F. Then take the outer terms in each binomial and multiply them. Then take the inner terms and multiply them. Then take the last term in each binomial and multiply them. So you've heard this acronym before. You probably know what FOIL means, but anyway, let's do examples of this. So here we have x plus 2 times x minus 7, and foiling says multiply the first terms, f, x times x is x squared. Then multiply the outer terms, o, x times negative 7. Notice it's like the outer terms. Okay, x times negative 7 is just negative 7x. Then multiply the inner terms, I, 2 times x, right? They're the inner. Well, if these are the outer, then 2 and x are the inner. So multiply those together, we get 2x. And then multiply the last terms in each binomial. 2 is last, 7 is last, so 2 times negative 7, negative 14. And then we just need to combine like terms, negative 5x. There we go. And what you're going to see in the next section is how we can go back from x squared minus 5x minus 14 back to x plus 2x minus 7. That's the next video. Another one, 2x plus 3 times x minus 1. First terms, 2x times x, 2x squared. 2x times negative 1, negative 2x. Inner, 3 times x, 3x. Last, 3 times negative 1, negative 3. And then just combine those inner terms. Negative 2x plus 3x is x. 3x minus 5 times 4x minus 6. 3x times 4x, 12x squared. 3x times negative 6, negative 18x. Negative 5 times 4x, negative 20x. Negative 5 times negative 6, positive 30. You are $18 in debt. You spend another 20. You are now $38 in debt. Okay, some special products that you will see over time that you could jump to if you so wanted to, but not so common. They're going to be a little bit more helpful when it comes to the next section, but still, we can introduce them here. If we have a plus b squared, so a sum being squared, well, a plus b squared is a plus b times a plus b, right? Something squared is itself multiplied by itself. Well, this is foiling. So a squared plus ab plus ba plus b squared, but ab and ba are the same thing. So a times b is the same as b times a. 2 times 3 is the same as 3 times 2. So AB plus BA is 2AB. Also 2BA, but 2AB looks a little bit nicer writing terms in alphabetical order. A minus B squared, so this is a difference squared. And same setup, except you gotta be a little bit more careful. A squared minus AB minus BA, but plus B squared, right? Negative B times negative B is positive B squared. All right, well, negative this minus itself, negative 2AB. Difference of squares, a plus b, a minus b. So difference of squares is what the final answer is going to be. Again, helpful in the next section. But in this case, a plus b, a minus b. A times a is a squared. A times negative b is negative ab. B times a is ba. B times negative b is negative b squared. And this time, notice these two things that are the same, but one is negative, one is positive, so they cancel out. So difference of squares comes from the fact that these two things squared are being subtracted. It's a difference of two things squared, difference of squares. Some more special products, a plus b cubed, a sum cubed. Looks like this bad guy. You can practice that on your own. A minus b cubed is this bad guy right here. Sum of cubes. So this is not nearly as common. You're probably not going to remember how to do this one. But yeah, this would be a cubed plus b cubed if you were to expand it. a minus b times a squared plus ab plus b squared would be a cubed minus b cubed. So again, this is a sum of cubes. This is a difference of cubes. If you want to see where these come from, these are really good polynomial practice for you guys to work on. Multiplying some bigger things, right? So we had foiling, but what we can do now is multiply anything bigger. So what you might have noticed when we were foiling is that each term in one polynomial is going to each term in the next polynomial. So, right, that first term went to both the outer and the first term in foiling went to both the first and second terms in the second polynomial. And the second term in the first binomial went to each term in the outer part. It's making more sense saying it in my head, but I think you guys understand. So long story short, what we're going to do is make sure we do 4x squared times each part here and 3x times each part here. So in a sense, 4x squared times all this plus 3x times all of this. Okay? Well, what we can do here is now just distribute 4x squared to each term. And now this is just a series of multiplying together. Okay? 4x squared times x squared, 4x to the fourth. 4x squared times 2x, 4 times 2 is 8. X squared times x, x cubed, and so on. I think you guys are okay up to there. And now just combine some like terms. 8x cubed plus 3x cubed, 11x cubed, negative 12x squared, plus x squared, negative 6x squared. So that's how we can foil, or foil on a grander scale. Just very briefly, let's talk about when we have multiple variables at play. So for terms with a constant and multiple variables, like 5x to the fourth y cubed, well, the constant is still the coefficient. So above this coefficient would still be 5. But the degree is a little different when it comes to multiple variables. Not as common, but still a little different. So the degree would be the sum of the powers of our variables. So that our degree in this term would be 4 plus 3, which is 7. We can't combine added or subtracted terms with different sets of variables, even if they have the same degree. If we want to combine them via addition or subtraction, they need to have the exact same set of variables with degrees. So for example, 5x cubed and 2y cubed, we can't simplify that because x cubed and y cubed are not the same set of variables and powers. However, 5x cubed and 2x cubed can be, 5y cubed and 2y cubed can both be simplified. But terms with the same set of variables can be combined. So 5x to the fourth y cubed plus 12, x to the fourth y cubed, right? They have the exact same set of variables, so we are able to combine. Well, 5 apples plus 12 apples is 17 apples. But again, those apples are x to the fourth y cubes. But x to the fourth y cubed, x squared y to the seventh, different set of variables, we can't combine them. So when we're multiplying terms with different variables, we just treat those variables right? Think about when we've been multiplying, 4x times 2x squared. We multiply the constants together and we multiply the x's together. And same thing here. We're just going to multiply different variables separately. So x times y is just xy. X to the 6th y to the 4th is just x to the 6th y to the 4th. X squared y cubed times x to the 7th y to the 9th. All this is multiply the x's together, multiply the y's together, and we get that. So doing one more example, if we're just expanding a multiple variable polynomial. So 2x plus 3y squared says 2x plus 3y times 2x plus 3y. Okay, 2x times 2x, 4x squared. 2x times 3y, 6xy. 3y times 2x, 6yx. 3y times 3y, 9y squared. Again, xy is the same as yx, so we get 12xy. Same set of variables, we can combine them. 6 apples plus 6 apples gives us 12 apples. Okay, and just like that, that's the end of P3. So in P4, what we're going to do is factoring polynomials. So going from expanded polynomials back to nice, pretty ones, nice, pretty factored ones. So I will see you in P4. Hi, everyone. Welcome back to P4. So in P3, we introduced polynomials and we introduced how to do some operations on polynomials, which included expanding and multiplying and adding and subtracting and all sorts of different things. And what we're going to do here in P4 is the literal opposite of expansion. So some basics. Factoring is the reverse of expanding and foiling expressions. We learned how to do x plus 3 times x minus 3. This is FOIL. So we do x times x is x squared. X times negative 3 is negative 3x. 3 times x is 3x. 3 times negative 3 is negative 9. And then we see that negative 3x and plus 3x can cancel out via combining like terms. So we can go from x plus 3x minus 3 to x squared minus 9. However, how do we go back from x squared minus 9 to x plus 3x minus 3? And that's called factoring. So when a polynomial is factored, the terms in the product are called, believe it or not, factors. So the first type of factoring we're going to do is greatest common factor, or GCF, which is the simplest form of factoring. And a GCF contains two things, at most two things. The first thing it contains is the largest integer that divides both terms' coefficients, or multiple terms' coefficients. Okay, and then it also contains the smallest exponent that appears in every term's variables. So this is very wordy. It'll make more sense in just a moment. But for the second part, kind of think of the question that's like, how many months in a year have 28 days? Well, all of them have 28 days. So that's kind of what's going on here in number 2. So let's get right into some examples. So we have 9 plus 18y. Our GCF is going to be the highest number that can divide both 9 and 18, and the least common power of y's that we see. So, well, the highest number that divides both 9 and 18 would be 9, And then what power is in common of y? Well, 9 doesn't have any y's, so we can't factor out a y. Okay, so that means 9 plus 18y. When we factor out a 9, what we're really doing is dividing everything by this GCF. So we take both terms in the original and divide them by our GCF. We see 9 divided by 9 is 1, 18y divided by 9 is 2y, and this would be considered factored, fully factored via a GCF. And if you want to prove whether or not what we have is correct, think that if we were to redistribute 9, 9 times 1 is 9, 9 times 2y is 18y. So we are taking out this factor to make everything on the inside a little bit smaller. Now, you don't necessarily have to show this middle step right here. I'm showing it here so that you understand what's actually happening in this step, but if you can jump right from 9 plus 18y to 9 times 1 plus 2y, that's totally fine as well. 2x squared plus 6x. The GCF, again, is the highest number that can divide the coefficients and the least common power that they both share. So in terms of numbers, what number divides both 2 and 6? Well, 2 divides 2 and 6, so that will be part of our GCF. And then what power do both x squared and x have in common? Well, again, kind of thinking like the months question, there are 28 days in every month. There is 1x in every term. So what do they have? What do they share? What do they have in common? Just a single x, no higher power. This one has 1x, this one has x squared. We can't take away more x's than what we have in this term, so our GCF is going to be 2x. So we take out 2x, and again, what we're doing is dividing all the original terms by 2x. So 2x squared divided by 2x, 6x divided by 2x. Well, this looks a little complicated, but 2 divided by 2 cancels out. X squared over x, one of the x's cancels out. 6x divided by 2x will be just 3. So this, considered fully factored, the fully factored version of this right here. All right, let's keep going. 5x to the fourth plus 20x squared plus 25x. Okay, well, what number divides all of 5, 20, and 25? Well, 5 is the biggest number that can divide 5, 20, and 25, nothing bigger. And how many x's do they share? Well, this one has 4 x's, this one has 2 x's, this has just a single x. Well, we can't take 2 x's out of a single x, so they only have 1 x in common. From here, we take out 5x and divide every term by 5x. 5 over 5 is just 1, x to the fourth over x is x cubed, 20 over 5 is 4, x squared over x is just a single x, 25 over 5 is 5, and those x's cancel out. So again, this factored version of the original. 7x to the fourth plus 3x cubed plus x squared. All right, well, the GCF is the highest number that divides 7, 3, and this imaginary 1 right here. Well, the only number that can divide 1 is 1, so there is no biggest number that can divide 7, 3, and 1. So we can't take out a coefficient. However, notice that we have 4 x's here, 3 x's here, and 2 x's here. They all have at least 2 x's. So we might not be able to take out a coefficient, but we can take out a pair of x's. And again, divide everything by this GCF. X to the fourth over x squared. 2 x's cancel out. We're left with 7x squared. X cubed over x squared. 2 x's cancel out. So we're left with just a single x. X squared over x squared, just 1. Okay, some more examples. 16x cubed plus 24x squared. What's the highest number that divides both 16 and 24? That would be 8. And how many x's do they share? 2 of them. So we take out 8x squared. 16 over 8 is 2. X cubed over x squared is just a single x. 24x squared over 8x squared. X squareds cancel out, and 24 divided by 8 is 3. 5x plus 3? Well, 5x plus 3 is going to be just 5x plus 3. The GCF is just 1. If we can't reduce it, right, well, there's no number that divides both 5 and 3 besides 1, and this only has an x and this doesn't have an x, so we're kind of pulling out a 1, but that's not really all that exciting. So in the event you have a polynomial or an expression that cannot be factored or cannot be reduced, it is irreducible. So a factor is irreducible if there is no GCF, or in other words, a GCF of only 1 and -1, right? You could infinitely take out 1 every single time. It doesn't change anything. You can infinitely take out -1, and all it would do is just change the sign each time. Not very exciting to us. So the factor is irreducible if there is no GCF besides 1 or -1. 5x plus 3 is irreducible since 5x and 3 don't have anything in common. However, 6x and 6x plus 3 is reducible because 3 divides both terms, right? We could still take out a 3, and even though we can't take out an x, we can still take out a 3, and 3 isn't 1 or -1. We say an expression is factored completely if the original expression is written as a product of irreducible factors. So if we can write our thing as a bunch of irreducible factors, then we know our job is done. So for example, looking at some of the original examples, there's nothing else we can factor out of here. So 8x squared is irreducible, 2x plus 3 is irreducible. We would have considered that factored completely. So for example, 3 times x plus 2 is factored completely, but 2x plus 4 times x plus 3 is not, because we can still pull a 2 out of 2x plus 4. Well, after GCF, the next simplest form of factoring is factoring by grouping. And we're going to do a lot of factoring by grouping in the next example, next type of example. So we're only going to do one example here, but let me explain what's happening. So if all of the terms in our polynomial have a collective GCF of 1, what we can do is split the terms in half and factor each pair separately, or each half of our polynomial separately. Well, if a polynomial can be factored by grouping, then what we're going to get is that the terms remaining inside our parentheses after taking out a GCF will be the same. If they're different, then that means either your polynomial can't be factored by grouping, which happens plenty of times, or then you made some kind of error. So let's see what we got. So 6x cubed minus 3x squared minus 4x plus 2. Notice they don't all have an x, so we can't take out an x. 6, 3, 4, and 2. Find me a number that divides all four. Well, the only one is 1, so that's not going to work. Okay, so what we're going to do is split these terms in two. Let's split up 6x cubed minus 3x squared and negative 4x plus 2 into each separate half. And now what we're going to do is factor each separate part using a GCF. So 6x cubed minus 3x squared, we can take out 3x squared. Negative 4x plus 2, we can take out a 2, and we're left with 3x squared times 2x minus 1 plus 2 times negative 2x plus 1. Well, I just want to stress this. We want the inside of our parentheses to be the same. In this case, they are not quite the same. So what we can do is factor out a negative 1 from negative 2x plus 1, or originally just factor out negative 2. And now the insides of our parentheses are the same. Now, how we continue from here is technically this. It is the inside of the parentheses times everything left over. So our answer is 2x minus 1 times, 2x minus 1, I think I said that right, times 3x squared minus 2, everything that was left over, 3x squared minus 2. Now, to give you a little bit of proof why, if this seems confusing, don't worry. Odds are you're never going to do this middle step, but let me just show you what's happening here. Let's just say that we have some letter c representing 2x minus 1. Well, this would be 3x squared times c plus negative 2 times c, or just negative 2c, right? 2x minus 1 is c. Well, notice these two terms have c in common, so we can factor out a c. Well, what was c? We initially replaced 2x minus 1 with c. So we can just replace 2x minus 1 back in for c. Now, again, you can see why. Our final answer once we get here is everything written in parentheses, 2x minus 1, times everything left over, 3x squared minus 2. Okay, I know it seems a little confusing because 2x minus 1 appears twice, and then it only appears once. Well, that's because we can factor out the entire term 2x minus 1 from both of these separate added terms. Okay, so those are the basics to factoring, and you think that we need more examples of factoring by grouping, except we're going to do a lot of them in this next method. So AC method is a way for us to factor quadratics, things that are ax squared plus bx plus c. Notice that I said ax squared plus bx plus c, and this method is AC. So this is how I learned to factor, and I find this way very concrete because it's going to work almost every time when it's supposed to work. However, I know I have met plenty of people that do not like this way. So if you have a different way of factoring that gets you the exact same answer, your way is completely correct. So let's do it this way. So again, like I said, it's the best way to factor in my opinion. And if a polynomial can be factored, this will always work. So for polynomials of the form ax squared plus bx plus c, these are technically quadratics, things that are to the second power. We haven't really used that term yet, but that's okay. We'll come back to it. So in the case where we have ax squared plus bx plus c, we're going to take a and we're going to take c. So not the x's, take the coefficient a, take the constant c, and multiply them together, which would literally be AC, right? A times C, AC. Okay, there are factors of A times C that when you add them, they add to B. So they multiply to AC, right? We want them to multiply to this number AC. But when you add those factors, they add to B. So we're using all of A, B, and C here. Okay, so we find this set of factors and we rewrite B as this sum. So it's going to sound a little complicated to start. When we do examples, it's going to make a lot of sense. So let's factor x squared plus 8x plus 15 using the AC method. Okay, so don't forget, this is ax squared plus bx plus c. What is A? What is C? A, as we see up here, A is the coefficient attached to the x squared term, and C is the constant term. So the coefficient attached to A would be just 1. This is like 1x squared. And C is our constant at the end, 15. So then A times C is 1 times 15, which is just 15. Now, we're going to find factors of 15 that, again, they multiply to 15. That's the point. But when we add them, they add to B, in this case, 8. So multiply to AC, but add to B, which is 8. Now, you could take a second, figure out the factors of 15 that add to 8, and you would get 3 and 5. So 3 plus 5 is 8. Okay. So what we're saying that we're going to do with 3 and 5 is this. 8 is the same as 3 plus 5. And from here, we know that we can distribute x. So we can distribute x to get 3x and x to 5x. So what we really did, I'm showing these middle steps right here. They're not my favorite steps, but what we really did was rewrite 8x as 3x plus 5x. But what we used is the thing that 8 is 3 plus 5. Well, if 8 is 3 plus 5, then 8x is 3x plus 5x. Okay, so what we can now do is factor by grouping. AC method relies on factoring by grouping. So let's group x squared plus 3x, and let's group 5x plus 15. Take out the GCF from these two. GCF from x squared plus 3x is just x. GCF from 5x plus 15 is 5. Okay, and now if we did this right, the insides of our parentheses should be the same, and they sure are. We saw in that first factoring by grouping example, our answer is whatever's in parentheses, write it once, times everything left over. So x plus 3, write it once, and then x plus 5. So again, everything in parentheses, write it once, times everything left over, x plus 5. Okay, we're going to do a lot of examples of this. Let's factor x squared minus 6x minus 16 using the AC method. All right, what is a? What is a? What is c? Well, a is the term attached to x squared. In this case, it'll be 1. And c is the constant term, negative 16. Right? Be very careful. This is supposed to be negative 16, not just 16. Okay, so then a times c, 1 times negative 16, is negative 16. We want to find factors of negative 16 that, again, they're factors, so they multiply to negative 16. But when they add them, they add to b. In this case, negative 6. Okay, take a second, find the factors of negative 16 that add to negative 6, and you would get 2 and negative 8, or negative 8 and 2. Okay, so that means that negative 6x, or negative 6, is 2 minus 8. Let's distribute x, and we specifically chose the combination 2x and negative 8x, because when we factor by grouping, we can take out an x. When we factor by grouping, we can take out a negative 8. And now we chose this group because the insides of the parentheses are now the same. So our answer is x plus 2 times everything left over, x minus 8. Okay. One thing I'll also note is that I did 2 and negative 8, but you could very well do negative 8 and 2, even though we are reversing the orders, even though we're saying negative 6x is 2x minus 8x. Negative 6x is also negative 8x plus 2x. So if you wanted to try doing this problem with x squared minus 8x plus 2x minus 16, you would get the exact same answer. Your terms would just be written in a different order. Let's keep going. 6x squared plus 17x plus 7. Oh boy. Okay. What is a? What is c? A is the term attached to the x squared term, or A is the coefficient attached to the x squared term. So A would be 6, and C is the constant 7. So A times C, 6 times 7 is 42. And now we're looking for factors of 42 that add to B, that add to 17. Okay, well, those two factors would be 3 and 14. So that means 17x is 3x plus 14x, or likewise 14x plus 3x. Let's factor by grouping. We can take out a 3x from these two. We can take out a 7 from these two. And again, if we did this correctly, the insides of our parentheses are the same, which they are, which means our final answer is everything in parentheses times everything left over. And that's how AC method works. Then we got one more example, so let's do one more. 20x squared minus 7x minus 6. Okay. What is A? What is C? A, again, attached to the x squared term. I think my camera might be covering it. That's okay. A is 20, and C is negative 6. So A times C is negative 120. Find factors of negative 120 that add to B, negative 7. All right, not obvious right away, but it is negative 15 and 8. Or again, it could be 8 and negative 15. The order doesn't exactly matter, right? If you did 8 and negative 15 instead, all you would get is a slightly different ordered answer at the very end. So that means negative 7 is negative 15 plus 8, or 8 minus 15, same thing. Well, negative 15 plus 8 times x, negative 15x plus 8x, factored by grouping. Here we could take out a 5x. Here we could take out a 2. Ooh. Here we could take out a 2. And then we have everything in parentheses is the same. So our answer is everything in parentheses times everything left over. Okay. Well, let's wrap up P4 with just some formulas. We saw toward the end of P3, toward the end of polynomial operations, is that there are some very special types of polynomials. For example, we had a rule for a plus b times a minus b. After we expanded that, we got a squared minus b squared, what we call the difference of squares. Well, if we're factoring, we can use that same rule just in reverse. So a squared minus b squared is a plus ba minus b. And let me begin to tell you, a squared minus b squared is a plus ba minus b is a infinitely important way of factoring. You're going to use a squared minus b squared equals a plus b times a minus b so often. So please, if you're going to commit any type of factoring to memory, difference of squares without fail is wildly important. Okay. We call that difference of squares. Difference of cubes, not as obvious. It's going to be this formula right here. I'll show you how to use this in just a moment. We call this difference of cubes. A cubed plus b cubed, almost identical, except instead of a minus b, it's a plus b. Instead of plus ab, it is minus ab, and we call that sum of cubes. So we have difference of squares, we have difference of cubes, we have sum of cubes. We do not have a sum of squares. We technically do. It requires some imaginary number stuff, not where we are in the course. A squared plus 2ab plus b squared. This is very difficult to pick out of a crowd, but this would be a plus b squared. Same thing but minus. This would be a minus b squared. So let's use some of those rules. X squared minus 4. Okay, well, x squared minus 4 is x squared minus 2 squared. This is a difference of two things being squared. So the formula that we have for a squared minus b squared is a plus b times a minus b. A plus b, x plus 2, times a minus b, x minus 2. Okay. 4x squared minus 25. Well, we see a 4, we see an x squared, we have a 25, so maybe these are two terms being squared. Well, 4x squared would be the whole thing, 2x squared, and 25 is 5 squared. Okay, so this is a squared minus b squared, and a squared minus b squared says a plus b and a minus b. 2x plus 5 times 2x minus 5. If you don't believe me, FOIL this out. Tell me what you get. X to the fourth minus 16. All right, well, this is kind of weird looking, but x to the fourth is like x squared squared. Ooh, using rules of exponents. And 16 is 4 squared. Okay, well, this is, again, a squared minus b squared. So a plus b, a minus b. But we're not done because x squared minus 4, oh, we had that all the way up here. So notice nothing we can do to factor x squared plus 4. You might want to do x plus 2 times x plus 2. That's not going to work. So feel free to tinker around with something like x squared plus 4. You will see you can never get it to factor. So fully factored version of x to the fourth minus 16, right there. 8x cubed plus 125. Well, 8's like a number cubed, and 125 is a number cubed, and maybe this cubed is a giveaway. Well, 8x cubed is 2x cubed, and 125 is 5 cubed. So this would be sum of cubes. Something cubed plus something cubed. Now, the formula for sum of cubes is not nearly as nice as the difference of squares formula. Sum of cubes, we can look at the previous slide, but it is a plus b times a squared minus ab plus b squared. A plus b times a squared, 2x squared, so 2x times 2x is 4x squared, minus ab, 2x times 5 is 10x, so a squared minus ab, plus b squared, 5 squared. So if it helps you to label these things out as a's and b's, you should absolutely do that. Okay, so with that said, I believe that's everything in P4, and I will see you in P5. We're going to change gears a little bit. Bye. Hi, everyone. Welcome back to P5. In P5, we're going to change gears a little bit and start talking about rational expressions. In the past, we've talked about rational numbers, so rational expressions aren't going to be super different, but different enough that we have to dedicate its own section. Okay, so if rational numbers are numbers of the form a over b, where b can't equal 0, then rational expressions are, believe it or not, expressions of the form a over b, where b does not equal 0. So in general, when we're talking about rational numbers, right, the numerator and denominator are just numbers. But in rational expressions, the numerator and denominator can technically be anything. They can have absolute values, they can have square roots, they can have all sorts of weird things. But for the purpose of what we're trying to do in this section, the numerators and denominators are going to be just polynomials for this section. But again, they can be anything. The domain for a rational expression is the set of all values where the denominator does not equal 0, right? If we want an expression to be defined, we need to make sure that the denominator does not equal 0. So for example, the domain of 2 over x minus 1 would be everywhere that x does not equal 1, because if we plug in 1, 1 minus 1 is 0, 2 over 0 is undefined. So the set that it is defined, the domain, is everywhere except 1. And we're going to spend a lot more time doing this when we get to chapter 2, but at least we're setting the stage right now. Similarly, x plus 6 over x minus 3 times x plus 4, the set of all x values for which this expression is defined, would be everywhere except 3, right? If we plug in 3, 3 minus 3 is 0, 0 times anything is 0, and also when x does not equal negative 4. Negative 4 plus 4 is 0, 0 times anything would be 0. So they are defined everywhere except those two places. But again, we'll come back to that in chapter 2. To simplify rational expressions, first what we're going to do is separately factor the numerator and denominator. Don't try and do too much at once. Factor the numerator, factor the denominator, and then divide out anything that the numerator and denominator have in common. So this is just like canceling out common factors, just like we did for numbers back in P1. So let's get right to it. X to the fourth plus 2x cubed over x plus 2. I'm going to have some of these disclaimers here, like if x doesn't equal 2, right? Because we don't want x to equal negative 2 here. But at some point I'm going to drop them, and we can just assume that we want this to be defined everywhere. So x to the fourth plus 2x cubed over x plus 2, what we're going to do is factor as much as we can and see if anything cancels out. Well, you might notice that in the numerator, they have an x cubed in common, so let's factor out x cubed. And right away, you see the numerator has an x plus 2, and the denominator has an x plus 2, so we can cancel out x plus 2. And one thing I want to note is that we can only cancel out factors. Factors are things that are being multiplied together. So this is x cubed times x plus 2. X plus 2 is a factor itself. X plus 2 in the denominator is a factor itself. So we're canceling the entire factor, right? If these were just numbers, we can't cancel things out that are being added or subtracted, but we can cancel out these multiplied and divided terms. That's very important. Okay, then x cubed over 1, just x cubed. So let me ask you, would you rather plug something into this original expression or into just x cubed? That's the goal of simplifying rational expressions. X squared minus x minus 6 over x cubed minus 3x squared. Well, we see the numerator can be factored using AC method. What two numbers multiply to negative 6 but add to negative 3? And in the denominator, we can factor out an x squared. So what two factors of negative 6 add to negative 1? Negative 3 and positive 2. And now you see x minus 3 times x plus 2 over x squared times x minus 3. X minus 3's can cancel out. And x plus 2 over x squared, perfect. And this is again where I want to stress that we can't cancel things out that are added or subtracted. Notice here you might be tempted to cancel out an x and an x squared, but we can't do that. because this x has to be added to 2 first. So do not cancel things out that are being added or subtracted. Cancel things out that are being multiplied, right? Like here, x minus 3 is being multiplied by x plus 2, and x squared is being multiplied by x minus 3. Cancel out things that are multiplied and divided, not added or subtracted. Okay, x to the 4th minus 9x squared over x to the 5th plus 6x to the 4th plus 9x cubed. Great practice from P4, but in the numerator, we can factor out an x squared. In the denominator, all of them have an x cubed, so let's factor out x squared and x cubed. Well, x squared minus 9 is a difference of squares. X squared minus 9 would be x plus 3, x minus 3, right? A squared minus b squared is a plus b, a minus b. And x squared plus 6x plus 9, what two factors of 9 add to 6? Well, 3 and 3. So again, x squared minus 9, difference of squares, a plus b, a minus b. And in the denominator, x plus 3 would be x squared plus 6x plus 9. And now let's see some of the things that we can cancel out. Well, right away, you see an x plus 3 can cancel out. There's 1 in the numerator and 2 in the denominator. We can only cancel out one of them. And then we have x squared over x cubed. We have 2 x's up here, 3 x's down here. We can cancel out 2 of them. So we're left with just a single x from that x squared over x cubed. X minus 3 stays. The other x plus 3 stays. This, very beautiful. X minus 3 over x times x plus 3. Okay, so basic simplification isn't very exciting, but just like we were able to do for polynomials and for fractions, what we want to be able to do is add, subtract, multiply, divide. But at least the benefit here is that multiplication, division, addition, subtraction, all exactly like how we did it for fractions, except the only difference now is that we're introducing x's. So multiplication and division is just like fraction multiplication and division. Multiply the numerators across and multiply the denominators across. However, I want to stress this. Oh, and before that, division is keep, change, flip, just like it was for numbers. However, before you do any operations, including addition and subtraction, right? This subsection is for multiplication and division, but for doing any operations, please factor your numerators and denominators first. We want to be able to cancel things out. But if you multiply and extend all these crazy things, what's going to happen is you're going to get some really, really crazy things that you're not going to be able to factor afterwards. So please factor before you do anything else. So x squared plus 3x plus 2 over x cubed plus 3x times 2x cubed plus 6x over x squared plus x minus 2. All right, 4 different things we need to factor. Let's get right into it. X squared plus 3x plus 2. What two factors of 2 add to 3? 2 and 1. So this will be x plus 2, x plus 1. X cubed plus 3x. They both have an x in common. Factor out an x. 2x cubed plus 6x. They both have a 2 in common, and they have a single x in common, so factor out 2x. And the denominator here, what two factors of negative 2 add to positive 1? Positive 2 and negative 1. So I'm skipping a lot of the factoring stuff. If you need to practice factoring, go back to P4. But here we go. Everything all nice and factored. Now, multiplication for rational expressions just says exactly like it did for regular fractions. Multiply the numerators across, multiply the denominators across. Okay, so x plus 2 times x plus 1 times 2x times x squared plus 3, x times x squared plus 3 times x plus 2 times x minus 1. And this is where our job is nice and pretty. If you had tried to multiply these numerators, you would be getting an x to the 5th term. A lot of different terms that you wouldn't know how to factor in the end. But since we factored to begin with, you might notice x plus 2 can cancel out, x squared plus 3 can cancel out, and a single x can cancel out. So x plus 2 went away, x went away, and x squared plus 3 went away. All we were left with is x plus 1 times 2, and this x minus 1 down here. And just to finish up, these single factors, we like to put them in front, just so it looks a little bit prettier. Do not go back and redistribute this 2. If you redistribute the 2, you went backwards, it's not fully factored, right? Our job is done when we are fully factored. Okay. 3x squared minus 24x plus 36 divided by 7x squared minus 28 divided by 9x minus 54 over 7x squared plus 63x plus 98. Oh my goodness. All right. Again, factor first. Don't do anything else besides factoring first. Okay. Up here, all of these are divisible by 3. Let's factor out a 3. Both of these are divisible by 7. Let's factor out 7. Both of these divisible by 9. Factor out 9. All of these divisible by 7. Factor out 7. Here, AC method, what two numbers of positive 12 add to negative 8, negative 6, and negative 2? X squared minus 4, difference of squares, x plus 2, x minus 2, x squared plus 9x plus 14, x plus 2, x plus 7, right? What two factors of 14 add to 9, x plus 7, and x plus 2. Okay, fully factored. Now let's go for the operation. And just like division for regular fractions, division for rational expressions is the same. Keep, change, flip. Keep the first, change the sign, flip the second. And now let's multiply across. Just combine all the numerators and denominators, and let's see what can cancel out. Well, x minus 6 can cancel out. X minus 2 can cancel out, a 7 can cancel out, and an x plus 2 can also cancel out. So that's a lot that canceled out. We're left with just a 3 and an x plus 7 in the numerator, and then we're left with just a 9 in the denominator, and then 3 over 9 is 1/3, and we can drop the 1. We don't need to say 1 times. Okay, so I know we're skipping a lot of work for factoring, right, where we assume previous section is good. So let's continue. Well, that was multiplication and division. Let's now do addition and subtraction. Well, just to very briefly reiterate the quirks and the quirks to fraction addition and subtraction. Let's do some of these. So 1/5 plus 6/5, same denominator, just add the numerators. Same denominators, subtract the numerators. -4, 7 minus 11 is -4. -4 over 12, -1/3. 1/4 plus 1/8, when they don't have the same denominator, make them the same denominator. Well, we can get 4 to look like 8 by multiplying by 2 over 2. Again, we want to multiply by 2 over 2 because 2 over 2 is just 1. If we multiply by 1, we don't change anything. And then if we multiply 4 times 2, we get 8, and we don't need to change the other one. So we get 2/8 plus 1/8, 3/8. 7 over 6 minus 5 over 18. We can change this 6 to look like an 18 by multiplying it by 3 over 3. And then subtracting 5 over 18, 21 over 18 minus 5 over 18, 16 over 18, and we can simplify that, 8 over 9. So these should be kind of familiar. We did these toward the end of P1. 1/4 plus 1/6, well, they're kind of similar, right? Here, this is a multiple of 2, and this is a multiple of 2. So their least common denominator is not just 4 times 6. We can get both of them to look like 12. All right, 3/12 plus 2/12, 5/12. 1/3 and 1/8, well, we can't say the same about 1/3 and 1/8 like we did for 1/4 and 1/6. 3 and 8 don't have any, early multiples in common like 4 and 6 do. So here, let's do 3 times 8 to get to 24. That's the first multiple that they share. 8 over 24 minus 3 over 24, 5 over 24. If we wanted to add all three of them together, well, 3, 4, and 5 don't share any factors. So if we want to get all the denominators to look the same, we got to multiply this one by 4 and 5, this one by 3 and 5, this one by 3 and 4. And we just get all sorts of ugly numbers. But the idea is here, right? If they have some similar factors, the least common denominator is not just all of the denominators together. It might be in some cases like 1/3 and 1/8, but it doesn't always have to be. So addition and subtraction, if the denominators are the same, simply add or subtract the numerators and keep the denominators the same. Okay, well, x minus 6 over x plus 1 squared minus x plus 8 over x plus 1 squared. Okay, well, we are subtracting across, but be very careful. This isn't like numbers. When this is like numbers, we just subtract those numbers. But when we're subtracting expressions, make sure you're subtracting this entire expression. Please use parentheses. They are free. Okay, so x minus 6 minus the whole of x plus 8. Let's distribute a negative sign to each term. X minus x goes away. Minus 6 minus 8, -14. Not the biggest leap that we have seen so far. Well, what we're more interested in doing is when the denominators are not the same. So we're going to make them the same. Think about when we had 1/3 and 1/8. Those factors had nothing in common. So we needed to multiply 3 by 8, and we needed to multiply 8 by 3. And that's going to be more likely of what's going to happen in a lot of these cases. Look at x plus 1 and look at x plus 3. Well, they look very similar as factors, but they're not quite the same thing, right? They both have an x. So you want to say that x is a least common denominator, but it's not. Remember that x plus 1 is a factor itself, and x plus 3 is a different factor itself. So x plus 1 and x plus 3, more likely than not, don't share anything in common. For example, if x were to equal 2, this would be 2 plus 1, which is 3. This would be 2 plus 3, which is 5. And 3 and 5 as denominators don't have anything in common. So what we're going to do is say the least common denominator between these two things is just this thing times this thing. So if we want to get our denominators to be the same, this x plus 1 denominator needs an x plus 3. And just like when we multiply numbers by 2 over 2 or 8 over 8, we need to multiply by x plus 3 over x plus 3, right? X plus 3 over x plus 3. So long as x doesn't equal -3, this is just 1. Algebra is a lot of adding 0 and multiplying by 1. Okay, likewise. So we have x plus 1 times x plus 3. That's great. That means that x plus 3 is going to need an x plus 1. Okay, so let's multiply everything across. Not everything across. Let's multiply these sets across, right? These are being added. So multiply those, not those highlighted. Hold on. Oop. Multiply those across and multiply the first two across. Okay, x times x plus 3 is just x times x plus 3. X plus 1 times x plus 3 is just x plus 1 times x plus 3. Don't expand any of these things necessarily, right? If you were to expand the denominator, it's going to change to something expanded that you could refactor. 2x minus 1 times x plus 1 over x plus 3 times x plus 1. And now these denominators are the same. They look a little different, but don't forget, a times b is the same as b times a. Okay, same denominator, we can add across. X times x plus 3 plus 2x minus 1 times x plus 1. From here, all we're going to do is expand, distribute x to each term, FOIL out these two, and from here, combine like terms. So we've been combining like terms since P3. Not going to spend too much time going over that here, but now you get the idea. Okay, we keep going. X plus 1 over x squared minus x minus 6 plus 2x minus 13 over x squared minus 9. Now, based on the previous example, what you are tempted to do is say, oh, these two things, nothing alike. Least common denominator is x squared minus x minus 6, and this one, x squared minus 9. Well, not quite, because don't forget the very first rule to doing all rational expression operations, and that is to factor. What two factors of -6 add to -1? There we go. -3 and 2. X squared minus 9. Difference of squares. Okay. Well, now let's take a deeper dive into what the least common denominator would be. Well, they both have an x minus 3. So we don't need to multiply one or both by x minus 3 because they both already have it. However, this denominator has an x plus 3, and this one doesn't have an x plus 3. So if we want to get the denominators to be the same, we need to multiply this first one by x plus 3 over x plus 3. Likewise, this first term has an x plus 2 in the denominator, and this doesn't have any x plus 2. So we need to multiply the second one by x plus 2 over x plus 2. From here, we'll multiply across in each specific term. Well, even though the denominators look very different, right? These three things, multiplication is commutative, even though they're out of order. Multiplication, order doesn't matter, so the denominators are the same. We can add the numerators, and from here, expand, FOIL, combine like terms. Okay, nice. We keep going. X plus 4 over x times x minus 1 squared times x plus 2 plus 2x plus 7 over 4x squared times x plus 2 to the third. All right, there's a lot going on here. Let's again look at each denominator and say, oh, this one has this and this one doesn't have this, and make connections. Okay, well, x minus 1 squared times x plus 2. Let's look at the other denominator and see what it has and what it doesn't have. Okay, well, there's no 4 in front, so we got to multiply this by 4. We have a single x, but this one has 2 x's, so this one needs another x. This one has a single x plus 2, but this one has 3 x plus 2's. So we need to multiply by 4 to get a 4. We need to multiply by another x to get x squared. And we need to multiply by 2 more x plus 2's to get to x plus 2 cubed. So 4x, x plus 2 squared. And now in this denominator, let's see what we're missing. Well, this has the 1 in front. Well, we have the 4 already, so we're good there. This has 1x, but we already have 2 x's. We don't need to add any more x's. This one doesn't have any x minus 1's, right? Over here, no x minus 1's, but this one has 2 of them. So we need to multiply by at least x minus 1 squared. This one has x plus 2 cubed, but we already took care of that x plus 2 cubed before. So we have now all of these denominators the same. When we rearrange our terms, even though they are, we rearrange the terms, and now we know that those denominators are the same. So we just add the numerators across. And for as ugly as it is, yeah, you're not going to get numbers this bad in almost any scenario. Even if you're not in my class or using this textbook, very rarely will you get rational expressions that are going to be this bad. So there we go. But yes, the key here is, what is this denominator missing that the other denominators have? What is this denominator missing that the other ones have? So kind of puzzle together until you get to a point where the denominators are the same. Okay, x plus 2 over x squared minus x minus 3x over 4 times x minus 1 squared. Again, step 1, make sure you factor first. Okay, what does this denominator not have that this one does? Well, this one doesn't have a 4 out in front, so we need to multiply by a 4. This one's got an x, this one doesn't, so we'll worry about that x later. But this one has a single x minus 1, and we need 2 of them. So let's multiply by 4 times x minus 1. We need the 4, and we need an extra x minus 1. Over here, well, the 4 is already there that we needed. This one already has 2 x minus 1's. Well, we don't need to add any more. But this one has a single x variable. This one does not have that outside x, so just multiply by x over x. Multiply the numerators and denominators across in each term. They now have the same denominator, so we can combine them. And now distribute and combine like terms. Okay. X minus 2 over 2x plus 1 minus x over 2x minus 1. Well, they look very similar, those denominators, don't they? 2x plus 1 and 2x minus 1. But don't forget, even though they look similar, they are not the same factors. For example, imagine that x is 2. 2 times 2 is 4. 4 plus 1 is 5. 2 times 2 is 4, but 4 minus 1 is 3. So if x is 2, this denominator is 5, and this denominator is 3. 3 and 5 don't have anything in common. So even though they look alike, 2x plus 1 is very different from 2x minus 1. So this denominator is missing 2x minus 1. This denominator is missing 2x plus 1. Combine. They have the same denominator, so we can subtract, FOIL, and distribute, and just combine like terms. If you combine like terms and you get down to this is pretty good, but we can take one more step in factoring. We're very comfortable doing that. They both have a 2 in common. We can factor out a 2. So you already see that these get kind of messy. It's just the nature of the game. Alrighty, 14x over 3x minus 1 squared minus 2x plus 7 over 9x squared minus 1. Again, let's factor fully. 9x squared minus 1, that's a difference of squares. 3x squared minus 1 squared. So we can factor 9x squared minus 1 as 3x plus 1 times 3x minus 1. Okay, this denominator has no 3x plus 1's, so the first denominator needs a 3x plus 1. However, this one already has 2 3x minus 1's, and this one only has 1 of them, so this denominator will need another 3x minus 1. Okay, combine, subtract, and FOIL, combine like terms, do whatever you need to do from there. Not necessarily the prettiest things on the planet, but that's okay. Okay, so addition, subtraction can get kind of messy. For the questions I'm going to ask you, they're not going to be nearly as messy. And I don't think almost any instructor will ask questions so messy. So yeah, but still, so long as you see like, oh, this one's missing this denominator, this one's missing this denominator, what it ends up boiling down to is just, foiling and distributing and combining like terms. Okay, now complex expressions, it's better when we are, in person talking about these things because we can make some really, really messy looking rational expressions. But for now, let's just go over one example, just so you kind of see the need to be careful aspect to it. So for complex expressions, just work as careful as possible. Simplify your simple parts first, work your way harder and harder, but start with the easy things. And then, work your way up to the bigger stuff. So let's say we have 1/2 plus 1 over x squared minus 4 over 2x. Well, in the numerator, we can combine terms here. If this was, first of all, find the least common denominator. So 2 times x, we got 2 times x over x. This one needs a 2, so 2 over 2. X squared minus 4, x plus 2 over x minus 2. Well, in the numerator, let's combine that. Okay, well, now this is a fraction divided by another fraction. Well, that's just keep, change, flip. Let's multiply across, and now you see, 2x can cancel out, and x plus 2 can cancel out. So being very careful, taking care of the numerator separately from the denominator, putting it all back, small stuff like that. But the bulk of this section is the multiplication, division, addition, subtraction, more especially the addition, subtraction. So something to keep an eye on. Okay, that's all I got for P5. So practice the addition and subtraction. But we got one more section in chapter P. So I will see you in P6. Bye-bye. Hi, everyone. Welcome back to the last section in chapter P, section P6. We're going to continue talking about rational things, but switch up a little bit about where we talk about them. Last section was all rational expressions, where the entire expression is rational, the entire expression is a fraction. But what we're going to do in this section is where the exponents are fractions. We haven't really looked at that a whole lot so far in this chapter, but we're going to really set the stage here and see the kind of things we can do with that. So for us to get to rational exponents, it's a little bit easier if we talk about radicals first, like square roots, cube roots, and so on. So we're going to start right there with square roots. So when we are squaring something, that's like taking 5 and squaring it to get to 25, right? 5 squared is 25. Now, we would then say that the square root is going from 25 back to 5. So squaring 5 to 25, square root 25 back to 5. Now, if we're saying that the square root of some number a is b, that means that b times b equals a. So using the example we have up here, 5 times 5 is 25. So we would say the square root of 25 is 5 because 5 times 5 is 25. Now, there's a couple restrictions here so that we don't get outside of the real numbers, right? We could very quickly find ourselves in a location we're not super familiar with. So we first restrict b to be positive, which in other words, we're just saying that square roots can't produce negative numbers. Kind of like absolute values. Absolute values themselves are always positive, but we could always throw a negative sign in front of it and make it positive. But we'll put that on the back burner for right now. In general, square roots cannot produce negative numbers. So that's for square roots, but we're going to break that rule in just a tad bit. So if we're saying that the square root of a equals b, just check to make sure that b squared is a, that the b you're saying is the answer. Make sure that b squared equals a and that b is 0 or positive. So some rules we got to create here. The square root of x squared is what we would like to say is just x, but we got to be very careful here. It happens to be absolute value of x for all real numbers. So it's not just x, it's absolute value of x. Now, as time goes on, we're going to become a little lenient with this rule and just assume that all of our x's are positive, so we don't need to worry about absolute value. But technically, the very specific rule is absolute value of x. For example, the square root of -9 squared is not -9 because -9 squared is 81, and the square root of 81 is 9, right? 9 times 9, 81. Square root of 81 is 9. Notice that it was not -9. So square roots can only produce positive numbers. That's why we need this absolute value here. So please just be very careful about that. Similar rule, the square root of x whole thing squared is x for all non-negative numbers. So we want to restrict to make sure that these numbers are non-negative because square root of -5 whole thing squared isn't -5. And this is because square root of -5 doesn't exist to begin with, right? If this part can't exist, then when you square it, it still doesn't exist. Now, we're going to come back around to what we can do with this in a couple of sections in 1.4. But for now, we're just going to say this is, it doesn't exist. We can't do that. Okay. However, but square root of 6 squared, well, square root of 6 squared is square root of 6 times square root of 6 using what exponents mean. Square root of 6 times square root of 6 would be square root of 6 times 6. We don't really have a rule for this just yet. We'll see it in just a moment. But 6 times 6 is then 36, and the square root of 36 is 6. So we could have jumped from square root of 6 squared is just 6 because 6 is non-negative. Product rule, speaking of that, square root of 6 times square root of 6 is square root of 6 times 6. Product rule says we are allowed to split up multiplication and only multiplication so long as those a's and b's are both positive or 0. Likewise, we can split up division, we can split up quotients so long as the numerator is 0 or positive and that b is positive. So we want to make sure there's no 0 in the denominator. There we go. So as we've seen with a couple things in this course, that we can split up multiplication, we can't split up addition or subtraction. So just to show you the inner workings of what really happens when we try to evaluate a square root. We are not going to evaluate these like this forever, but just to show you. So square root of 121, we're looking for the number that when you multiply it by itself, you get 121. Well, 121 is 11 squared. And when we're saying we have square root of something squared, that's this rule right here. Square root of something squared is the absolute value of that something, and the absolute value of 11 is 11. So the square root of 121 is 11. We don't need to do steps like this every single time, right? We kind of have an understanding of what square roots are on a surface level, so don't worry too much about that. For example, square root of 25 over 81. Well, division, we are able to split up and say square root of the top divided by square root of the bottom. Square root of 25, what number multiplied by itself gives us 25? 5. And what number multiplied by itself gives us 81? 9. So the square root of 25 over 81 is 5 over 9. Square root of 117. Well, square root of 117 itself isn't a perfect square, but what you're going to see a lot in this section is that we would like to simplify square root expressions or irrational exponent expressions. So what we can do is rewrite 117 so that at least one of its factors is a perfect square. Now, you might not know this right off the top of your head, but you could check factors of 117 to see what works. And it so happens that 117 is equal to 9 times 13. Well, now we have a product. We're allowed to split a product to say square root of 9 times square root of 13, and we know the square root of 9 is 3. So instead of square root of 117, 3 times the square root of 3 times the square root of 13 is a little bit more precise than square root of 117. There will come a time that we're okay with square root of 117 just in general, but as you know, as we're learning to manipulate and work with square roots, we like to write this instead. However, let's say that you didn't know that 117 is 9 times 13. Let's say you're just going along and checking factors of 117, right? You try dividing by 2 and dividing by 2 doesn't work. And then you try dividing by 3 and you see that 3 works. And you say that 117 is 3 times 39. Okay, well, we're not quite done yet because 39 is not a perfect square. However, we can rewrite 39 as 3 times 13, doing the same thing that we had before. Okay, well, you might notice that 3 times 3 is 9, and again, square root of 9 times square root of 13, 3 square root of 13. So even if you don't find the perfect square factor right away, that's fine. Check factors and see if you find factor pairs like this 3 and 3 to get that perfect square factor. Okay, some more examples. Square root of 6 times square root of 12. Well, this is a product. Why don't we combine it to square root of 6 times 12. 6 times 12 is 72. And what we're now looking for is a factor of 72 that is a perfect square. Well, you can think about it a little bit. What I'm thinking is that 72 is 36 times 2. Square root of 36 times 2 is the square root of 36 times the square root of 2. And we can say the square root of 36 is 6. What number multiplied by itself gives us 36? 6. Or what you could have also done is say that square root of 12, well, 12 is 6 times 12. Well, now we have square root of 6 times square root of 6 times square root of 2. Square root of 6 times square root of 6, square root of 36. And we get 6 square root of 2 that way. So a couple different options you have when it comes to simplifying. Another example, another division, square root of 36 divided by square root of 3. Well, division, we can recombine back into one square root. Square root of 36 over 3 would be square root of 12. Find a factor of 12 that is a perfect square. Well, 12 happens to be 4 times 3. Square root of 4 times square root of 3 would be 2 square root of 3, right? Square root of 4 is 2. Square root of 3 just stays square root of 3. Okay. But we're going to come back to this one. Maybe there's a different way of evaluating this one, maybe in 2 subsections. Another example, square root of 48x squared. So even though we have numbers and we have x's, that's okay. Fear not. Let's take care of the number and the variable separately. Find me a perfect square factor of 48. You can think about it. The answer would be 16 and 3. So we have square root of 16 times the square root of 3 and square root of x squared. Well, this is a rule that we have very specifically. Square root of x squared is absolute value of x. So again, square root of 16, 4, square root of 3, square root of 3, square root of x squared, it's on that very first line of examples, is absolute value of x. And just as a nice way of simplifying this or rewriting this more nicely, let's put that absolute value x in front. So in general, try not to write things to the right of the square root if it is not inside a square root. So notice here, square root of x squared became absolute value of x, not underneath a square root. If it doesn't have a square root, write it to the left so that you're not accidentally putting it over a square root. Okay. Well, we did 16 and 3, but 16 and 3 might not be your only option. What if we instead use 4 and 12? Well, if we split up 48 as 4 times 12, well, we could say that square root of 4 is 2, but square root of 12 is 4 times 3 again. Okay, so we have square root of 4 times square root of 4 times square root of 3 times square root of x squared. Well, square root of 4 is 2. Square root of 4 is 2. Square root of 3 does not change. Square root of x squared, absolute value of x. Everything that is outside of the square root, combine them. Everything that is inside a square root, combine them. 2 times 2 is 4. 4 times absolute value of x is 4 absolute value of x. And what you could have also done is tried 6 and 8. So I will let you try that on your own. If you did not see 16 and 3, if you did not see 4 and 12, point is you can get to the same answer. It might just take you more steps. As we've been saying it, just because it takes more steps, just because you're a little inefficient, does not necessarily mean you are wrong. Okay, well, what we just talked about are square roots, but square roots aren't the only type of root or radical that we can talk about. So let's talk about the general nth root. So square root says, take some number, multiply it by itself, it gets you some number. Cube root says, what if we do 3 of those numbers multiplied together? So this says the cube root of a equals b means that b times b times b is a, or that b cubed is a. Fourth root would be fourth root of a equals b means that b times b times b times b, total of 4 times, equals a, or b to the fourth equals a. Fifth root we write as fifth root of a equals b, and this would be b multiplied by itself 4 times, so b times b times b times b times b, a total of 5 times, equals a, or b to the fifth equals a. And we can go so on. So we've talked about square roots where it's just that number times itself, a total of 2 times, and then we can just do it as many times as we want. So this can continue infinitely. In general, if we write square root of x, there's an imaginary 2 here, right? It would kind of match and follow this pattern of b cubed equals a, b to the fourth equals a. But just in general, when it's a 2, we don't necessarily need to write the 2. So there's some nth root rules at play here, because square roots, we know the inside has to be positive because we can't take square root of a negative number. But maybe that kind of bends when we allow our roots to be a little different and not just 2. Okay. If the inside is positive, if the inside to your root is positive, so if a is positive, then no matter what the root is, square root, cube root, fourth root, fifth root, so on, as long as the inside's positive, the answer, the expression will also be positive. Okay, so inside's positive, whole thing's positive, nothing weird going on. But the second we allow the inside to be negative, weird things can happen. So let's say the inside is negative and the root is odd. So we're talking cube root or we're talking fifth root. Well, if the inside is negative, but the root is odd, then the nth root of a will also be negative. So for example, what we're allowed to have is the cube root of negative 125, not the square root of negative 125. Square root would be an even root. We're talking odd roots like 3 or 5. So we can evaluate cube root of negative 125. That answer is negative 5, since negative 5 times negative 5 times negative 5 is negative 125. So that satisfies the rule that the cube root of some number means this number cubed should equal the inside. So that's kind of weird, a little uncomfortable that we're allowed to have negative sometimes and not other times, but the key here is whether or not the root is even or odd. So likewise, if the inside's negative but the root is even, then that whole expression is not a real number, right? So for example, square root of negative 4. Find me a number multiplied by itself that gives you negative 4. Well, you might be really inclined to say 2, but 2 times 2 is positive 4. You might be inclined to say negative 2, but negative 2 times negative 2 is positive 4. So we don't have a square root of negative 4 just yet. Like I said, we're going to come back to it in a couple sections, but for now, square root, fourth root, sixth root, if it's an even root and a negative number, they do not exist. So please be very careful of that. It is very important to note that if the inside's negative, it doesn't necessarily mean that it does not exist. It entirely depends on the root. Okay, if your inside equals 0, then the nth root of 0 is, you guessed it, 0. If n is odd, then the nth root of n is just that answer, a. Okay, well, think back to when we had square root of x squared. I told you that's the absolute value of x. Well, now we're saying if we have nth root of a to the n for any power, it's just a. However, the stipulation here is that this root needs to be odd. Well, if that root was then even, for example, square root of x squared, then we get absolute value of that inside. So please, this is really, really important here. The difference between having an even root and an odd root are completely different questions. They share some similarities. They share a same general property, but on the whole, some things are okay in odd roots and some things are not okay in even roots. So please just be very careful when you're evaluating these things. Okay, another weird example we might have is the mth root of the nth root of a. In this very weird scenario, we just say mth root, and nth root is the m times nth root. This doesn't happen a lot, but it is still an interesting enough property. Okay, so let's do some examples. Again, if the root is odd, then nth root of a to the n is just itself. But if the root is even, then the nth root of a to the n is the absolute value of a. Okay, so cube root of 27 would be 27 is 3 cubed. So cube root of 3 cubed, this root is odd, so the answer is just itself 3. Odd root, all we do is take whatever it is, no absolute values. Likewise, cube root of negative 64. Well, negative 64 is negative 4 cubed. So odd root, odd power, or matching odd power, I should say, the answer is just negative 4, because negative 4 times negative 4 times negative 4 is negative 64. Odd roots are okay to have negative numbers, and it's okay that they produce negative numbers. Okay, but likewise, fourth root of negative 3 to the fourth, well, this is now an even root with a matching even root. That would be this rule right here. So this would be absolute value of negative 3. Well, the absolute value of negative 3, going back to P1, is positive 3. Or similarly, if you don't really like or understand why this is, don't forget that negative 3 to the fourth, negative 3 times negative 3 times negative 3 times negative 3 is positive 81. And now you see how we have to get a positive number when it comes to even roots. So what number multiplied by itself 3 times, total of 4 times, is 81? 3. So 2 ways you can do it. Even roots, you need to be careful. Odd roots, you don't need to be as careful because we are allowed to have negatives inside an odd root. Okay, some other weird examples. Cube root of 135. Well, 135 is not a perfect cube root like 64 or 8 or 27. However, we can split up 135 to have one factor that is a perfect cube root. Think about when we were doing square root of 72 earlier. We changed 72 to 36 times 2 because 36 is a perfect square root. Well, instead of perfect square root, we're just looking for a perfect cube root now. So it so happens that 135 is 27 times 5. So we can split up cube root of 27 times 5 as cube root of 27 times cube root of 5. Cube root of 27 is 3, and cube root of 5 is just cube root of 5. Nothing we can do there. Cube root of 18 divided by 64. Well, same thing. We can split up division as cube root of 18 divided by cube root of 64. Not anything we can do with 18, but cube root of 64 is 4. 4 times 4 times 4 is 64. Okay, fourth root of 162, x to the fourth. Let's start by handling the number and the variable separately. Look at this right here. Even root with a matching even power. So that's like the other rule that has absolute value. But for 162, we need to find a factor of it that is a perfect fourth root. Okay, 162 is 81 times 2. We know the fourth root of 81. What number times itself 3 times for a total of 4 times is 81? Well, 3 times 3 times 3 times 3 is 81. So we have 3 times the fourth root of 2. Nothing we can do with the fourth root of 2. And then fourth root of x to the fourth is absolute value of x. Again, even roots with matching even powers create absolute values. Odd roots with matching odd powers do not do this. Okay, and again, we like writing our absolute values are everything outside of a square root to the left of the square root. Okay, some other weird things we can do. We can also simplify expressions with differing square roots. So square root of 45 and square root of 20, they're not the same root. We can't simplify them. However, if we simplify the roots first, maybe we can simplify them after that. So 45 is 9 times 5, and 9 is special because that's a perfect square root. 20 is special because 20 is 4 times 5, and we like 4 because 4 is also a perfect square root. Square root of 9 is 3, so 3 times the square root of 5. 4, square root of 4 is 2, so 7 times 2 square root of 5. Well, 7 times 2 square root of 5 is 14 square root of 5. And now, just be very careful. Imagine that these square roots are x's. If this was 3x plus 14x, you would say it was 17x. Only difference is these are square roots. So 3 square root of 5 plus 14 square root of 5. You have 3 apples. I give you 14 apples. Now you have 17 apples. One more. Fourth root of cube root of 15. That's that one very specific, very fancy, weird looking rule that says if we have a root of a root, we just multiply those roots. 4 times 3 is 12. So 12th root of 15, nothing we can do there. I just wanted to demonstrate how that one rule would work. Okay, some warnings before we move on to the next part. Some warnings of things you're not allowed to do. We've said that we can split up multiplication and division. We cannot split up addition and subtraction. So square root of a plus or minus b is not the square root of a plus or minus b. Big no-no. We can split up multiplication. We cannot split up addition, subtraction. That is true even for nth roots. Just because this is not square root and it's an nth root, still can't split it up. Okay, even if we have nth root of a to the n plus or minus b to the n, we can't magically cancel out those roots, right? We can only split up. We can only distribute over multiplication and division. If a doesn't equal b, so these insides are not equal, even if the roots are the same, if the insides aren't the same, we can't combine them. So here, the roots are the same, right? Nth root and nth root. Since the roots are not the same, we can't combine them. Likewise, let's say the insides are the same, but the roots aren't the same. We are not allowed to combine them via addition or subtraction, even if the insides are the same. The only time we can combine via addition or subtraction is when the roots are the same. So we have n and n. Roots are the same, that's good. A and a, the insides are the same, that's good too. So if the roots aren't the same, can't combine. If the insides aren't the same, can't combine. So roots are the same, insides are the same. I have one apple and I give you another apple. Now we have 2 of those apples. So be very careful when it comes to combining these things. Okay, well, that's talking about roots, and we want to really get into what rational exponents are to cap off chapter P. One more thing to do before we get to that is rationalization. So in general, somewhere along the way, it was decided that we don't like having square roots in the denominator. It's okay sometimes, but just we consider it mathematically sound to not have radicals in the denominator. So rationalization just says multiply the numerator and denominator by something that would cancel out the square root. So in the very basic case where the denominator is just a single square root, just square root of 2, all we're going to do is multiply by that exact same square root. So square root of 2 in the denominator, let's multiply by square root of 2 over square root of 2, right? Square root of 2 over square root of 2, oh, well, that's just 1. Multiply by 1, we don't change anything. Like I said, we're going to use that tool a lot over the course of this course. So Square root of 2 over square root of 2, multiply the numerators across, multiply the denominators across, right? Just fraction multiplication. Square root of 5 times square root of 2, square root of 2 times square root of 2. Well, 5 times 2 is 10, 2 times 2 is 4, and the square root of 4 is 2. So all we did was multiply by square root of 2 over square root of 2, and what we get is something a little more sound, a little prettier to look at than square root of 5 over square root of 2. Again, we got rid of the square root in the denominator. That's typically what we like to do more. Well, we can get very complicated looking square roots, so that's not always going to be the answer. In some cases, we might have square root of something plus or minus square root of something else. So what we're going to introduce now is the phrase conjugate, and we're going to use this term a lot over the course of the entire study of college algebra, right? So the conjugate of a plus b, we say, is a minus b. So the conjugate is almost identical, except instead of a plus b, it's a minus b. Well, likewise, the conjugate of a minus b would then be a plus b. And what you're going to find a lot, and that's on purpose, is that conjugates come in pairs. So the conjugate of a plus b is a minus b in the pair, a plus b and a minus b is a conjugate pair. So the conjugate method for weird looking square roots is to multiply by the conjugate. And what our goal is to get is if we multiply a plus b times a minus b, oh, this should look really familiar because this is a squared minus b squared. Okay, right? Don't forget difference of squares. A plus b, a minus b is a squared minus b squared. I told you we were going to talk about that a lot. So please don't forget this part. Okay. So let's say our denominator is square root of x plus or minus square root of y. We want to multiply by the opposite sign, but still square root of x and square root of y. So if this is square root of x plus square root of y, multiply by square root of x minus square root of y. If this is square root of x minus square root of y, multiply by square root of x plus square root of y. Okay, and we do that because square root of x plus square root of y multiplied by its conjugate, square root of x minus square root of y. And now what you should see, a plus b times a minus b. Oh, that's right here. A plus b, a minus b, a plus b, a minus b. So what this becomes is a squared minus b squared. So we're going to take square root of x, square it, minus, take y, square root of y, square it. And we said square root of x squared is just x, square root of y squared is just y. And just like that, notice there are no more square roots. Okay. So let's just do one very brief example of that. 2 over square root of 7 minus square root of 5. So square root of 7 minus square root of 5, that's 2 square roots in the denominator. We don't like that. So let's multiply by the conjugate. Well, the square root of 7 minus square root of 5, its conjugate is square root of 7 plus square root of 5. So what we're going to do is multiply the numerator and denominator by square root of 7 plus square root of 5. Again, we can cancel this out and just make it 1. So we're not changing anything. Okay, well, let's multiply these things together. 2 times square root of 7 plus square root of 5. Square root of 7 minus square root of 5 times square root of 7 plus square root of 5. Oh, what you should notice is this is a minus b times a plus b. That is a squared minus b squared, right? Difference of squares, a minus b, a plus b. So what we can do is a squared minus b squared. Again, let me flash it on screen. We have a minus b times a plus b, same thing as what we have here. And what it simplifies to is a squared minus b squared. If you don't like what I'm doing here, that's fine. FOIL this out. Do square root of 7 times square root of 7, square root of 7 times square root of 5, square root of 5 times square root of 7, square root of 5 times square root of 5, and you'll see we get the exact same thing. Okay, well, this is really nice because square root of 7 squared is just 7. Square root of 5 squared is just 5. 7 minus 5 is 2. And we can cancel out those 2's. This step of canceling out this 2 and this 2, kind of just a nice cooked example so that, you know, that the 2 could cancel out. But even if it doesn't cancel out, as long as there are no more square roots in the denominator, that's what we prefer. So let's go back to that example I said we would come back to. Square root of 36 over square root of 3. What we did for this one before is simplify it to 36 divided by 3, 12, and then did square root of 12. But let's see what happens when we just rationalize. Square root of 36 is 6. And to rationalize, we're going to multiply by square root of 3 over square root of 3. Okay, square root of 3 times square root of 3 is square root of 9. 6 times square root of 3 is just 6 square root of 3. Square root of 9 is 3, and 6 divided by 3 is 2. And that's the same answer we got before when we looked at this example for the first time. However, I want to stress, don't try and cancel things out that are inside a square root with things that are outside the square root. Notice that this is square root of 3 and square root of 3 and 3. Just because they are both 3s does not mean we can cancel them out, right? This 3 is stuck inside a square root. This 3 is not. We can only combine things that are outside square roots with things outside of the square root, and we can only combine things inside the square root with other things that are inside the square root. And that's rationalization. So very last part of this section are rational exponents, and we have finally built up to the point that we're able to do rational exponents. They're a little weird, a little funky, but what you're going to see is that they actually end up just changing the things we've already done. So in general, the nth root of a is a to the 1 over n. So there is a connection here. We've been doing roots this entire time, but what roots really are fraction exponents. So square root of a is a to the 1/2. Cube root of a is a to the 1/3. Fourth root of a is a to the 1/4. Fifth root of a is a to the 1/5, and so on. But if we want to know what the rules are for a to the 1 over n, well, they're just the same rules that we had for nth root of a. You know, inside is positive, whole thing is going to be positive. Inside is negative, and that root is odd, well, it's going to be negative. Inside is negative, and the root is even, not a real number. And if it's 0, same thing. So all this is just another way of looking at it. And what you're going to see is the first few examples are just very easy to change, but we're going to make all of those exponents look really weird when we try and go backwards. So for example, 16 to the 1/2, well, to the 1/2 is the same as the square root. So 16 to the 1/2 is the same as square root of 16. And we know what the square root of 16 is. So square root of 16 is 4. Okay. Negative 27 to the 1/3. Well, negative 27 to the 1/3. To the 1/3 means cube root. Cube root of negative 27, negative 3. And we should be pros at that by now after doing it a whole bunch of times earlier in the section. 1 over 16 to the 1/4. Well, division, just like all the rules we've had before. 1 over 16 to the 1/4 would be fourth root of 1 over 16. We can do fourth root of 1 divided by fourth root of 16. What number multiplied by itself 3 times gives you 1? Well, that's 1. What number multiplied by itself 3 times gives you 16? Well, 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 is 16. 32 to the negative 1/5. Well, just like rules we had in previous sections, negative exponents, we drop them to the denominator. 32 to the 1/5 means fifth root of 32. What number multiplied by itself 4 times for a total of 5 times gives you 32? Well, 2 times 2 times 2 times 2 times 2 is 32. So fifth root of 32 is 2. Negative 5 to the 1/4. To the 1/4 power means fourth root of negative 5. And we can't take even roots of negative numbers. We can take odd roots of negative numbers. We cannot take even roots of negative numbers. So negative 5 to the 1/4, fourth root of negative 5 does not exist. However, all of these exponents have all been 1 in the numerator, 1 in the numerator, 1, 1, 1. Is that the only thing we can do? Of course not. So what if we want to go backwards? What if we're given an expression that has a rational exponent and we want to use roots to be able to evaluate these things without a calculator? So the rules of integer exponents can be extended to rational exponents. All the rules that we had for integer exponents, like the product rule, quotient rule, power of a power, all of those rules still true for rational exponents. So what we can do is rewrite something like a to the m over n, right? Before, all the examples we had before was like 1 over 2, 1 over 3, 1 over 4, and so on. So what if instead that numerator is anything and that denominator is anything? Well, what we can do is two things. First thing we can do is say that m over n is m times 1 over n. That's true, just going backwards from fraction multiplication. But now a to the m times 1 over n, we can again go backwards and use power of a power. Oh, right, this is what we did, I think, in P2, right? P2's exponents, I'm pretty sure. Well, if I gave you something like this back then, you would have said, oh, power raised to a power, we multiply. Oh, so we're just going backwards now. So a to the m over n is a to the m to the 1 over n. However, 1 over n power is the nth root. So a to the m over n is the nth root of a to the m. But that's not our only option. Think about multiplication. This is not the only order we could have done this. We could have also done a to the 1 over n times m, just multiplying backwards, right? 2 times 3 is the same as 3 times 2. So 1 over n times n, a to the 1 over n times m. Well, this is a to the 1 over n to the m. And this says nth root of a raised to the nth power. So we have two options for how we can split the exact same thing. And what you're going to see in all the next few examples is that there isn't really a perfect science as to when you want to use one of these decompositions versus the other. Sometimes it just comes down to how big and small your numbers are. Sometimes if you have really small numbers, maybe using one is better than the other. Or if you have really big numbers, maybe using one over the other is easier. So let's do a couple examples of this. 8 to the 2 over 3. Well, our first way says to split up 8 to the 2/3 as 2 times 1/3. Okay, well, 8 squared is 64, and 1/3 power means cube root. So 8 squared is 64, and 1/3 power means cube root. What's the cube root of 64? 4. 4 times 4 times 4 is 64. Okay, that's one option. But what if we did it the other way? 8 to the 2/3 can also be 8 to the 1/3 squared. So this says do cube root of 8 first. What's the cube root of 8? What number multiplied by itself twice gives you 8? 2 times 2 times 2 is 8, and 2 squared is 4. Same answer. The answer to the whole thing is 4, but maybe you prefer one of these two ways over the other. Sometimes one of these ways is way too difficult. Sometimes the other of these two ways is way too difficult. So whichever one happens to work, and if you happen to use one way and it's inefficient but you got the right answer, you don't need to do it the other way. Either you get the right answer or you don't. Okay, negative 16 to the 5/2. Again, we've talked time and time again about the usage of parentheses. There's no parentheses here, so this is saying just 16 to the 5/2. So again, option 1 says to do the numerator power first, 16 to the 5th, and then to the 1/2. Well, 16 to the 5th is, yeah, there you go, 1,048,576. And then 1/2 power says square root of that number. And I don't think many of you happen to know what the square root of this number is. It is, of course, 1024. But maybe not super obvious. Well, what if we went the other way instead? What if we instead did the to the 1/2 power first, and then raise it to the 5th power? Well, 16 to the 1/2 says square root of 16. Square root of 16 is 4. And 4 to the 5th is 4, 16, 64, 256, 1024. So negative 1024. Well, both of these ways dealt with really big numbers. There's no way we could get away from not having a really big number, but at least one of the ways the numbers weren't so daunting right away. So how to know which one is going to be which? It entirely depends on the question. Okay, 100 to the negative 3/2. Well, again, from P2, what do we do with negative exponents? We drop them to the denominator. Okay, first way says do 100 cubed and then do to the 1/2 power. 100 cubed is 1 million. 1 million to the 1/2 says square root of 1 million, and square root of 1 million would be 1,000. Okay, all right. Well, let's go the other way. Let's do square root first, and then raise it to the 3rd power. What's the square root of 100? What number times itself gives you 100? That would be 10. And 10 cubed. Oh, okay, that's a little bit nicer to deal with. Okay, and now that we've done a couple examples of what these rational exponents mean, let's just do one final frontier of examples to cap out chapter 6, doing all sorts of weird exponent stuff. And like I said, the rules of rational exponents are the exact same as rules of integer exponents. So for example here, 2x to the 1/3 times 5x to the 1/4. Well, if this was 2x cubed times 5x to the 4th, you would know exactly what to do with this. You would do 2 times 5 and x cubed times x to the 4th. Only difference is that we now have rational exponents. All the exact same steps. Only thing is we now need to use rules of fractions to be able to simplify x to the 1/3 times x to the 1/4. Stuff like this, you might be asking, do you need to change it back to a root with a radical? You do not. In some cases, if you get like 1/12, where 1/12 is very clearly the 12th root, you could. I will not hold that to you, but in other courses, they might hold you to it. But for example, x to the 7/12, it's not going to look any better with a radical involved. 21x to the negative 2/3 over 7x to the 1/5. Okay, well, we combine the numbers and we combine the x's. Well, 21 divided by 7 is 3. X raised to some power divided by x raised to another power. Well, when we were dividing, we subtracted. And same thing, just because those exponents are now fractions, it doesn't change anything. It just makes our combination a little bit more difficult. So speaking of things we do and don't simplify, negative exponents are one of those things that we should always simplify. X to the 3/5 to the negative 1/6. This is x raised to some power, raised to another power. What do we do in power to a power? We multiply. Well, fraction multiplication just says multiply the fractions, multiply the numerators, divided by multiply the denominators. 3/30 is 1/10. Negative exponent drops to the denominator. And this is an example of something that wouldn't be so bad to change to 10th root of x. Now you might be saying, well, this is a square root in the denominator. We should be rationalizing that. It kind of, this is not a square root, this is a 10th root. So for us to rationalize a 10th root requires a little bit more work than just plain square roots. I don't think I will ever ask you to rationalize something that is not a square root. Everything there is a square root, but you could rationalize it. It's just a little bit more work when it's not square root. 10th root, a little bit more work. 8th root of x squared. Well, 8th root says to the 1/8. Well, now we have a power raised to a power, so we multiply those powers. 2/8 is 1/4, and x to the 1/4 is 4th root of x. Oh, that's kind of weird looking. These things happen. Okay. Well, square root of cube root of x to the 8th. Well, you could use that rule we were talking about earlier with root of a root, but let's go a slightly different way to simplify. Well, on the inside, x to the 8th cube root of that says x to the 8th to the 1/3, right? Cube root of x to the 8th says x to the 8th to the 1/3. Well, power raised to a power, we multiply. And now square root of x to the 8/3 says x to the 8/3 to the 1/2. Power to a power, we multiply. Fraction multiplication, and simplifying a fraction, x to the 4/3. Who would have thought that this right here would simplify to a nice, pretty x to the 4/3? One more. I don't know if it's actually the one more example, but we'll keep going, right? 16y to the -2 over x to the -8/3 raised to the -1/4. Well, everything on the inside multiplied or divided together. Let's distribute that -1/4 power to everything. Here, fraction multiplication, fraction multiplication. Let's simplify those fractions. And also 16 to the -1/4, negative exponent drops down to the denominator. 16 to the 1/4 says 4th root of 16. 4th root of 16 is 2. Y to the 2/4, y to the 1/2, x to the 8/12, x to the 2/3. Well, I wouldn't really change x to the 2/3, but y to the 1/2 we know is square root of y. Okay, and that was the last example. So that is the end of chapter P. There's a lot of information in chapter P. I seem to think or have found that in future chapters, so if you're watching into chapter 1, chapter 1 is about solving equations. So I think some people prefer solving equations over just dealing with kind of abstract expressions, kind of just out in space, so to speak. So there's a lot of information, a lot of basic rules, stuff like that. But fear not, chapter 1, we're going to use a lot of these rules, but when we're solving equations, it seems a little bit more purposeful. So with that said, thank you so much for watching for chapter P, and I will see you in chapter 1. Bye. Hi, everyone. Welcome to chapter 1. So chapter 1 comes after chapter P. Chapter P is kind of like a chapter 0 because the name of the chapter is literally basic concepts of algebra. It's just supposed to be a review of different properties we talked about, like properties of exponents, factoring, stuff like that. Stuff that we will use for the entire course, and you'll use in almost any math course going forward. But what we're going to be more interested in doing is, instead of looking at these kind of out in space, so to speak, expressions that don't really have much of a purpose, what we can now do is solve equations and inequalities using things that look like that. Look like those expressions that we talked about in chapter P. So what we're going to do in chapter 1 is solve a whole bunch of different types of equations. And we're going to need to solve equations to answer things and answer properties of functions when we get to chapter 2 and into chapter 3. So we're going to start with talking about linear equations, where we just have equations with just a single x to the first power, nothing too crazy. And then we will extend that into quadratics in 1.3, where we now allow ourselves to have an x squared. And then we will do that in 1.5, which is in a separate file, but in 1.5 we extend it to be able to solve equations of almost any power using things that we already did in 1.1 and 1.3, and then some information in 1.2 and 1.4. What we'll do is then talk about solving inequalities, I believe in 1.6, and then in 1.7 we introduce absolute value into our equations. So lots of different types of equations. We're just going to go piece by piece. So let's get right into 1.1, linear equations in one variable. Okay, so an equation in general, an equation is just a mathematical statement saying that two expressions are equal. So we have some expression on the left-hand side, some expression on the right-hand side, and if we throw an equal sign in between them, this is now an equation, right? 7 minus 5 is just like an expression we could have talked about in chapter P. Not a whole lot we would have done with it in chapter P, but it is still just an expression. 2 is just a constant. Well, that was one of the first two things we talked about in the entire course in chapter P. So saying that these two expressions are equal is an equation. Okay, but what we're going to be interested in this section is equations in one variable. So what an equation in one variable could look like is like 7 minus 5x. So as soon as we introduce an x, which we don't, 7 minus 5 equals 2 is very concrete, but the second we introduce an x, now we don't really know what x is. We don't know what it's doing there. So what we're going to do in this section is be able to solve equations with just one variable, x to the first power. So in general, we want answers that look like x equals some constant. That's not always going to happen, but for now, for this part of the section, we will say that is what's going to happen. For us to do that, we're going to use these steps. First things first, if we have fractions, we don't like fractions. We saw how messy fractions could get in chapter P. So if given the opportunity, multiply everything by the least common denominator. In doing so, you see that all of your denominators go away, and that makes our job a lot easier. Simplify any parentheses or grouping, right? PEMDAS, stuff that we talked about, even though there isn't an E in exponents and, in linear equations still, parentheses should always come first. The fewer parentheses, the better. So taking care of parentheses when we can is definitely of interest. Then we're going to combine like terms, which we did so many times in chapter P. So we're going to combine like terms. And then our goal is to isolate the variable. So what we might have to do is if we have like 7 minus 5x, we need to get the minus 5x term by itself, minus 5 times x. So to get rid of 7 minus 5x, what we can do is subtract 7 on both sides so that the x term is all by itself on one side. Well, once that x term is by itself, what we can do is multiply or divide by the coefficient. And just like that, we will get an answer that looks like x equals some constant. As always, what I'm going to say a lot in this chapter is to check your work. So now that we have equations and things to reference, it's a lot easier to check our work, right? When we're talking about simplifying a rational expression, there isn't really a way to check your work as opposed to just doing the problem again. But now what you can do is you can take your answer, plug it in, and see if your answer holds true. So let's get right into solving equations. Let's say we have 3x plus 5 equals 14. Well, we don't have any denominators, we don't have any parentheses. So what our goal is to get x by itself. Now, think about when we do PEMDAS. PEMDAS says do multiplication and division and then do addition and subtraction. What we're going to do is go backwards because we want x by itself. We need to go backwards. So if we have 3x plus 5 equals 14, what we can do to both sides is subtract 5. If we have plus 5, we can get rid of plus 5 by subtracting 5. But like we saw a lot in chapter P, we can't just subtract 5 on one side. We need to subtract 5 on both sides. If we apply minus 5 to both sides, as long as we stay consistent, we don't change the problem at all. So whatever you do to one side, make sure you do it to the other side as well. Okay, well, plus 5 minus 5, the whole goal was to undo plus 5. Well, you have 5 apples and you take away 5 apples. Now you don't have any apples. And that was the goal. Okay, well, 14 minus 5 is 9. And now the x variable term is by itself, but it's not quite by itself. We have 3 times x. So when we had plus 5, we undid plus 5 with minus 5. Okay, and you can take a guess how we would undo 3 times x. Well, plus 5 became minus 5, 3 times x. What we're going to do is divide both sides by 3. So just like we had to subtract 5 on both sides, we also have to divide both sides by 3. We can't just do it to one side. That would really break the rules of solving equations. So we divide both sides by 3. And the reason we did that is because 3 divided by 3 is just 1. Well, we never have written 1x. So 3 divided by 3 is just 1x. X equals 9 divided by 3, 3. And we like doing this. What I found a lot in my time teaching is that we don't really like dealing with just single expressions. You know, again, this out in space thing I keep saying. But the second that we're solving equations, we like this little puzzle of, okay, I subtract 5 and then I divide 3. And we get an answer that actually means something. Now, we don't need to check our work for every problem. You should check your work for every problem. But I'm not going to do it for every problem just for the sake of time. But if we want to know if x equals 3 is correct, plug x equals 3 back into the original. So if x is 3, 3 times 3 is 9. 9 plus 5 is 14. Our equation is true when x equals 3. Okay, so let's just solve a bunch of equations just like this. 7 minus 5x equals 2. Well, step 1, we need to get minus 5x by itself. Okay, well, we have minus 5x. That's what we need to get by itself first. We have this plus 7 to the left of minus 5x. How do we get rid of positive 7? We subtract 7. 7 minus 7 will go away, but we can't just subtract 7 on one side. We need to subtract 7 on both sides. Okay, 7 minus 7 goes away. That's the whole point. 2 minus 7, you have $2 and you spend 7. You are now $5 in debt. And now be very careful because what you want to do is see minus 5 and go, oh, minus 5. Let me add 5 to both sides. That's not what we want to do. Don't forget that this is minus 5 times x. Before, we had 7 minus 5x. This 7 was not multiplied or divided. It was being added or subtracted. So we subtracted 7. But to undo negative 5 times x, we need to divide both sides by negative 5. So again, please be very careful because 7 minus 5x, 7 is being added, we have to subtract it. Negative 5 is being multiplied, we need to divide it. Well, negative 5 divided by negative 5 would just be 1. And same thing over here, negative 5 divided by negative 5 would be positive 1. Again, if we want proof if our answer is correct, plug x equals 1 back into the original. If x is 1, 5 times 1 is 5, 7 minus 5 is 2. Okay, so feel free to check these answers as we go. Of course, they're correct or I wouldn't be giving a presentation on it, but it is still good practice to do because as soon as we get to somewhere around 1.5, we're really going to need to check our answers. Okay, negative 10x minus 12 equals 0. Okay, so we need to get x by itself. We see negative 10x minus 12. How do we undo minus 12? Well, in the last few examples, we had 7 minus 5x. Positive 7, we had to subtract 7 on both sides. But negative 10x minus 12, well, if we have minus 12, the undoing of minus 12 would be adding 12. But again, adding 12 to both sides. Okay, negative 12 and 12 go away. 0 plus 12 is just 12. And same thing, we have negative 10 times x. How do we undo negative 10 times x? We divide both sides by negative 10. Okay, negative 10 divided by negative 10 is just positive 1. That's the whole point, right? We just want to get x. It doesn't make sense to divide by 5. We would be left with negative 2x. 12 divided by negative 10, simplifying fractions. We've done that before. Okay, let's keep going. 2/3 x minus 3 equals 7. Okay, well, we have 2/3 times x minus 3. Well, we need to get rid of minus 3 to get the 2/3 x by itself first. How do we undo minus 3? We undo minus 3 by adding 3 to both sides. Minus 3 plus 3 is nothing. 7 plus 3 is 10. And now we run into a slight problem because all the other ones that we've had to divide by, we would divide by like 5 or negative 10. But now we have 2/3 and we would want to divide by 2/3. But don't forget that dividing by fractions is like keep, change, flip. And we kind of saw that keep, change, flip can be a lot of work sometimes. Instead, let's jump right to a better, more efficient way of thinking about this. When we divide by 2/3, keep, change, flip would say multiply by 3/2, right? Keep whatever we're multiplying by, or keep whatever we're multiplying, change the sign to multiplication, and flip the thing that you are dividing by. Okay, well, if we're dividing by 2/3, that would be the same as multiplying 3/2, right? Keep, change, flip. So a more efficient way of thinking about this is when we have a fraction on one side, why don't we multiply both sides by the reciprocal? The reciprocal of 2/3 is 3/2. But again, can't just multiply 3/2 on one side, need to multiply it on both sides. Okay, don't forget fraction multiplication, 3/2 times 10. 10 is the same as 10/1. Don't do 3 times 10 and don't do 2 times 10. 10 is 10/1. Okay, well over here, 3/2 times 2/3, 3 times 2 is 6, 2 times 3 is 6, 3 times 10 is 30, 2 times 1 is 2. So we multiply by the reciprocal because we now get 6/6. And we know that 6/6 is just 1. The same thing happened, right? We wanted to get a 1x, and we got it by multiplying by the reciprocal. You could still divide by 2/3, but don't forget that when you divide by 2/3, that's keep, change, flip. You just got to be a little bit more careful. So multiplying by the reciprocal, just as equally correct. If anything, it's more efficient. Well, 30/2 is 15, 6/6 is 1, so our final answer is 15. Okay. I'll also take a second to note that if you can solve these problems faster than how I'm doing them here, that's totally fine. I'm teaching this with showing all the little pieces of what's really happening. I don't really expect anybody to actually show the step of multiplying by, of, adding 3 to both sides. What you're more likely to do is jump from this line down to this line, and that's totally okay. Like I said, I'm just showing what happens in those steps. Okay, let's continue. 3 times 2 minus x plus 4x equals 3x. Well, PEMDAS, take care of parentheses first. So why don't we distribute 3? 3 times 2 is 6. 3 times negative x, negative 3x. Okay, well, we have multiple x's on one side, so why don't we combine like terms? Negative 3x plus 4x. If I am $3 in debt and I'm given $4, now I have $1. Well, we have an x here and 3 x's over here, so why don't we bring all the x's to one side? Well, we like to have our constant be away from the x's, so what I'm going to choose to do is subtract x on both sides. How do I undo plus x? By subtracting x on both sides. Plus x minus x just goes away. You have 3 apples and you eat one of them. Now you have 2 apples, and then we just divide both sides by 2. Okay, so fear not. It's okay to have 3 equals x. Just because it's not x equals 3 doesn't mean anything went wrong. 3 equals x, same thing as x equals 3. And now this is a really good opportunity to tell you, you always have a choice of where you bring your x. I think a lot of people prefer having x on the left-hand side. So what you could have done here as well is subtract 3x on both sides and subtract 6 on both sides so that all the x's were to the left and your constant was to the right. You would get the exact same answer. It functions the exact same way. However, whichever one is more comfortable for you, by all means, go for it. Okay, let's do another ugly one with a lot of parentheses. Well, we got a parentheses inside a bracket, right? Brackets are just another way of writing parentheses. So why don't we distribute -2 first? -2 times x is -2x. -2 times -2 is +4. Okay, well, before we do anything else with this, with this minus on the outside, why don't we simplify our inside? 3x minus 2x, 3 apples minus 2 apples, 1 apple. Okay, well, nothing else we can do inside the brackets, so why don't we distribute our negative sign and combine like terms? 6x minus x is 5x. Okay, and now we're just back to an equation we've been solving. Alrighty, let's add 4 to both sides, and let's divide both sides by 5 to get x equals 3. Not so scary. Could always be worse, and it does get worse, but it's not so bad for right now. Well, let's do one more example. And I told you, if you have a denominator, multiply by the LCD. And here's why. Well, what you could do is 2x over 9 plus 1 over 9 minus x over 6 minus 4 over 6. That's a lot of fractions. And we saw how much work just simply adding and subtracting fractions took. So instead of trying to deal with multiple fraction, addition, and subtraction, why don't we multiply everything by the least common denominator? Okay, what is the least common multiple of 9 and 6? What's the first multiple that they share? The answer would be 18. So what we're going to do is multiply everything by 18. Okay, literally multiply everything by 18. Okay, well, what we're going to do is distribute 18 to each of these two fractions. 18 times this fraction minus 18 times that fraction. This is like 18 over 1, so fraction multiplication. But notice now, we have 18 times something divided by 9. 18 times something divided by 6. Well, we learned in one of the very first few sections that we can simplify 18 over 9, and we can simplify 18 over 6. 18 over 9 is 2. 18 over 6 is 3. And now from here, not nearly as scary as it initially looked with fractions. Let's distribute 2. Let's distribute -3. We can combine some like terms. 4x minus 3x is just x. +2 minus 12. You have $2. You spend $12. You are now $10 in debt. And last but not least, we only need to add 10 to both sides. Don't even need to divide everything by some number because x is all by itself. So that's solving linear equations. Not as scary. If it sounds like I overcomplicated it, but you can get the same answers, by all means, do it your way. It's totally fine. I'm just showing you what's really happening on the inside for a college math class as opposed to, high school taking things for granted. Okay, so, well, those aren't the only types of equations we can get. We can get other, like, weird-looking equations. So what we had are conditional linear equations. Conditional linear equations just say that there's only one solution. When x equals 3, this equation is true. But that doesn't always happen. We have an infinite number of options for what we put on both sides. So we introduce two more types of equations. First one is an identity. An identity is any equation where the solution is all real numbers. Or in other words, no matter what you plug in for x, you will always get an equation that is true. And you'll see how that looks when we do an example in just a moment. We can also say infinitely many solutions, right? If we're talking about solutions, conditional only has one solution, but all real numbers would mean we have an infinite number of solutions. Likewise, we have an inconsistent equation, and an inconsistent equation is an equation with no solution. It means that no matter what we plug in for x, we can never get an equation that is true. So let's just do some examples and see where it takes us. They don't look any different from other equations, so you can't really think like, oh, this one's going to be an identity. We don't know. You'll see kind of quickly like warning signs of how these things would happen, but in other words, just solving like any other equation. Well, we got a bunch of parentheses, so why don't we distribute this 2, and why don't we distribute this negative sign? Okay, we have some combining like terms we can do, minus 12 plus 5, and 12 minus 19. And now maybe here you already start to see something kind of weird. Okay, why don't we add 7 to both sides? And why don't we subtract 6x on both sides? We could divide both sides by 6, we get x equals x, but we still need to combine those x's. So let's bring all of our x's to one side by subtracting this 6x on both sides. However, when we subtract 6x minus itself on both sides, we get 0 equals 0. So your indicator that your equation is an identity is that you end up, after simplification, you end up with a statement that is always true. 0 equals 0 is always true. There is never a time that 0 doesn't equal 0. So what we got is something that says no matter what we plug in for x, we will always get the same value on both sides. Don't believe me? Plug in anything you want. Let's just plug in 0 to say, I don't know, 3 times 0 is 0, 0 minus 6 is negative 6, 2 times negative 6 is negative 12, negative 12 plus 5 is negative 7. Okay, so our left side is negative 7 when x equals 0. All right, well, when x equals 0, 6 times 0 is just 0. 19 minus 0 is 19. 12 minus 19 is also negative 7. Well, what if x equals 2? I don't know, let's do something else, right? When x equals 2, 3 times 2 is 6. 6 minus 6 is 0. 2 times 0 is 0. 0 plus 5 is 5. When x equals 2, 6 times 2 is 12. 19 minus 12 is 7. 12 minus 7 is also 5. So we had two different answers, x equals 0 and x equals 2, that when we plug them back in, we get the exact same thing on both sides. So no matter what we plug in for x, we always get the same value on both sides. That's to say we have an infinite number of solutions. This equation is an identity. Okay, well, let's see what the opposite would look like. All right, lots of parentheses. Let's take care of this innermost one. Let's distribute 2. Let's combine like terms 3x plus 2x. And let's distribute this negative sign to 5x and negative 2. Well, we can combine like terms and say 5x minus 5x is, oh, that goes away. And we get 2 equals 1. However, 0 equals 0 is always true. But you're probably a little confused now because we're saying 2 equals 1. But 2 doesn't equal 1. 2 never equals 1. So what we got is the opposite, so to speak, of an identity. We got an inconsistent equation. We got an equation that no matter what we plug in for x, we will never get the same value on both sides. We will always end up at an equation that is never true. So in that case, we say there is no solution. Okay, well, a little bit short of an explanation because we went through all the explanation for an identity, and inconsistent is just the opposite. If we get an equation that after simplification, after solving, is always true, it's an identity, infinitely many solutions. If we get to a simplified equation that is never true, like 2 equals 1, that's never true. That's inconsistent. It has no solution. Let's do another 2 examples to see what happens. All right, lots of parentheses. Let's distribute 2. Let's distribute 5. Minus 5x plus 2x and 1 plus 14. 2x minus 5x, lots of combining like terms. Maybe you already start to see something happening. Okay, let's subtract 15 on both sides, and let's add 3x to both sides. Right, we want to get all the x's to one side, so we need to add 3x to both sides. And we again get 0 equals 0. That is always true. No matter what we plug in, both sides will always be equal, infinitely many solutions. Don't believe me? Take any x value you want, plug it into the original equation, and you will see both sides are always equal. Okay, another one. Again, lots of parentheses. Let's distribute -6. Let's combine like terms. Let's distribute this negative sign. Let's again combine like terms. 3x plus 4x is 7x. Let's subtract 7x on both sides. And when we do that, 7x goes away on both sides, and we get 6 equals -1. And we are well aware that 6 does not equal -1. So we got to an equation that is never true, no solution. Okay, as a nice little summary, again, identity, the answer is always true, like 0 equals 0. So if you get 0 equals 0, 2 equals 2, -5 equals -5, that equation is an identity. It has an infinite number of solutions. Inconsistent, the answer is never true. It's like 2 equals 1. So if you get an equation and you solve it and it gets to something like 2 equals 1, -5 equals 3, whatever it is that doesn't make any sense, your equation is inconsistent. And conditional, there's only ever one answer, like x equals 3 or x equals -1, but we don't typically need to say conditional. Conditional is taken for granted. When we come to an identity, it's important to us that we can recognize an identity equation. It's important to us that we can recognize inconsistent. But when it comes to conditional, it's not as important to say it's conditional because we're just more interested in what is the answer, right? There isn't a concrete answer for 0 equals 0 or 2 equals 1 outside of infinitely many solutions or no solution. So in conditional equations, you don't need to say conditional. All I want is the answer. And in most cases, all your instructor would want is just what the answer is. Okay. And that brings us to formulas, or more specifically formulae, but for the purpose of what we're going to talk about, let's use formulas. Okay, so this is right here for you. But formulas in general are equations that show relationships between two or more variables. So what we've done so far is in a linear equation in one variable, but we know that almost any formula on the planet has more than one variable attached to it. So if we wanted to show a relationship between multiple variables at once, that is called a formula. So some examples: Celsius to Fahrenheit. Fahrenheit equals 9/5 Celsius plus 32. Volume, length times width times height. So just as an example, right, a relationship between two or more variables. Here, there's two variables, Fahrenheit and Celsius. So this would be a formula. Volume equals length times width times height. Well, that's 4 variables, so that is also a formula. So if we wanted to find out what 15 degrees Celsius is in Fahrenheit, what we can do is plug in 15 for Celsius, right? We want 15 degrees Celsius. We want to find it out in Fahrenheit. So let's plug in 15 for C. Okay, 15 over 5 is 3 over 1. 9 times 3 is 27. 27 plus 32 is 59. So 15 degrees Celsius is 59 degrees Fahrenheit. Okay, but we just did Celsius to Fahrenheit, and how would we go from Fahrenheit back to Celsius? Well, one option we have is to just plug in what Fahrenheit is and solve for C. However, that's not the most efficient. If I asked you, what is 20 degrees Fahrenheit in Celsius? And then I asked you, what's 40 degrees Fahrenheit in Celsius? And then 60 degrees Fahrenheit in Celsius, and then 80 degrees Fahrenheit in Celsius. Are you going to continuously plug in 20 and then solve for C, and then plug in 40 and then solve for C, and then 60 and solve for C, and so on? No, that's kind of inefficient. We would like to save ourselves some time. So a better method, a more efficient method, would be to solve for C first, and then plug in Fahrenheit. So this is called solving for variables. Let's do an example of this. So let's solve the Fahrenheit to Celsius equation for Celsius. Well, what we're going to do is, even though we have two variables here, we want to solve for C. So treat everything else as a number. Okay, so Fahrenheit, I understand that that's a variable, but let's just treat it like it's a number. Maybe not a number that we can combine, but let's just treat it like a number for right now. Well, if we wanted to get C by itself, you would start by subtracting 32 on both sides. And then to get rid of 9/5, we would multiply by the reciprocal 5/9. Well, 5/9 and 9/5, 45 over 45, that cancels out. Oh, and just like that, we've derived the formula for Fahrenheit to Celsius. So now, if I asked you what multiple degree Fahrenheits are in terms of Celsius, this is so much easier. Now you could just plug 20 into here and simplify, 40 into here, 60, 80, instead of needing to plug in 20 into here, and then 40 into here, and 60 into here, and 80 into here, and continuously having to solve for C that way. So there is a huge benefit for us to solve for variables first, and that's not just for math, that's for anything. You might see in some of your biology classes or chemistry classes or physics classes that if you have to do multiple calculations of the same thing, maybe solving for the variable first can save you some time later. Okay, so one more example of this. Let's solve for the variable h. Well, we have an h here, we have an h here. If you're unfamiliar with this formula, this is the surface area for a rectangular prism, so a surface area of a box. But let's solve for h, which means if we're solving for h, treat everything else like a number. Maybe not a number that you can simplify, but a number nonetheless. Okay, think back to when we were solving equations with just x's. We wanted all the x's on one side. So if we're solving for h, let's get all of our h's on one side and all of our non-h's to the other side. Okay, well, we have an h here, but 2 length width does not have an h in it. So let's subtract that on both sides. Let's get that out of there. Now, not super obvious how we would combine 2 length height plus 2 width height, but what we do notice is that they both have an h in common. Well, think back to P4. If they both have an h, we can factor out h. Okay, last but not least, we have h times 2 length plus 2 width. Well, think back to when we were doing this for normal equations. If we had 6 times x, we would divide both sides by 6. Here we have h times something. How do we get rid of h times something? We divide both sides by that something. So 2l plus 2w over 2l plus 2w, those factors cancel out, and we're left with just this ugly looking formula for h. So maybe not so often that you would be, given the surface area and not the height, but just good practice for solving for variables. So that's the end of P1. So P1, like I said, just linear equations in one variable. I understand that this might have sounded a little complicated. Again, however you solved for equations in one variable in the past, whatever's easy for you, shortcuts you might use, they're all still correct. If you get the same answer and your work is just a little different, there's no way you can cheese these answers, right? Maybe some of them a little easier than others, but there's no way you can get to the right answer by doing the wrong work in most situations. So, like I said, too complicated. I get it. I'm just trying to explain it in as much depth as I can for a course of this level. So that's the end of 1.1. In the next section, 1.2, we're just going to do some applications of linear equations. Not a whole lot, just kind of like an exploration of some things. So, yeah, I'll see you in 1.2. Bye. Okay, and welcome back to 1.2. I mentioned at the end of 1.1 that 1.2 is just applications of linear equations, kind of practicing some modeling, some exploration of things that linear equations can do. The things that we're able to do at this level, not a whole lot. We don't have a whole lot of tools, a lot of things. So our scope of what we can explore right now is kind of small, but just know that as we move forward, there's a lot of different things that these equations can do for us. So let's just look at a whole bunch of different examples of linear equations. So as a preface, all of these problems are very different. There isn't like a very set way of solving any one of these. It's kind of a little bit of thinking on our own. Not so much like actual linear equations where, get x by itself, subtract or add a number, divide or multiply by some number. Modeling in general is just kind of like thinking on your own. The only thing I can tell you is that if it helps you, draw a picture. But in most cases, you don't really need to do that. I shouldn't say that. In a lot of cases, you may or may not need to do that. So whatever works for you, by all means, you do it that way. But okay, let's just do a whole bunch of examples. Let's say a new refrigerator is on sale for $3,000. I have no idea if that's a normal price for a fridge, but let's pretend it is. So let's say a fridge is on sale for $3,000. If the original price of the fridge was reduced by 20%, what was the original price? We know the sale price and we know the reduction, but we don't know the original price. Okay, if the fridge was reduced by 20%, that means that we're paying 80% of the original price, right? 20% off doesn't mean we're paying 20% of the original price. It means we're paying 20% less of the original price. So if we have a 20% discount, it means we are paying 80%. Okay, well, if we say that x is the original price, we don't know what x is, but if x is the original price, then 0.8x is the 80% of that original price. So decimals and percentages, right? 80% would be 0.8. 8% would be 0.08, right? Practicing some percentages, right? That should sound familiar from a while ago. But yeah, so if x is the original price, then the sale price is 0.8x. Or again, 20% off the original price. Well, the sale price that we're given is 3,000. So if the sale price is 3,000 and 0.8x is the discounted price, then 0.8x equals 3,000. Well, we know how to solve for this. Divide both sides by 0.8. And we get 3750. So I know it might be kind of tempting to find 20% of 3,000 and then add it, but that's not correct. Because if you were to go backwards and take that new price that you came up with, 20% of that price is not the discount that we're looking for. So our original price is 3750. 20% of 3750 would be 750. So 750 off 3750 would be 3,000. So please be very careful when we're practicing modeling these things. Okay, let's say that fridge was never reduced. What is the cost of the fridge, including tax? So I don't know where you're watching this, but let's assume tax in your state is a cool 6%, I guess. So if the fridge originally cost $37.50, we need to pay 6% tax on that $37.50. Okay, so we're paying the cost of the fridge plus tax on that fridge. Okay, so that means our total price is the cost of the fridge, $37.50, plus the cost of tax on the fridge, which is 6% of $37.50. Okay, well, 6% of $37.50 would be $37.50 times 0.06, right? 6%, 0.06. Okay, now this is going to be kind of weird because you could simplify this right away, but there is a little bit of a method to the madness right here. If they both have $37.50, can we factor out $37.50? Yeah, we sure can. If we factor out $37.50 from $37.50, we're left with 1. If we factor out $37.50 times 0.06, we're left with just 0.06. Well, 1 plus 0.06 is 1.06, and $37.50 times 1.06 is $39.75. So assuming the fridge was never reduced, the total cost of the fridge with tax would be $39.75, including tax. So an extra $2.25 in just tax. So
The reason why I wanted to show it to you this way is because I think it's kind of important for people to know how to calculate tax and total cost of items, right? You go to the store and it's like, this item is $39.99, and then you get to the register and it's a lot more than $39.99. Okay, maybe not a lot more, but it's more than $39.99. So in general, if you want to find the total cost of an item, you always multiply that item by 1 plus whatever that tax rate is in your state. So again, if your tax rate in your state is 6%, if you multiplied every item by 1.06, you have a really good idea on how much you would be paying for that item. So just an interesting thing you can do going forward. Or if you're trying to find like, I don't want to spend more than this, including tax, you can use that to your advantage. So we move on. A student wants her exam average to be an 85. On her first 4 exams, she got a 72, a 90, an 80, and a 67. What score does she need on the 5th exam to bring her exam average up to an 85? Okay, well, the average of her 4 exams would be adding those 4 exams together and dividing by 4. Okay, well, we want the average of 5 exams, but we don't know what that 5th exam is. Well, that's not a big deal. All we want to find is the average of 5 exams, but if we don't know what that 5th exam is, why don't we just call it X for right now? So we would add those 5 exam scores and then divide by 5. Okay, but she wants her average to be an 85, so average will be 85. And would you look at that? This is now just another linear equation, right? X to the first power, linear. Okay, well, let's solve for X. Let's add 72 plus 90 plus 80 plus 67. That is 309. Well, we don't like fractions. Let's get the fraction out of here. So let's multiply both sides by 5. 5 times 85 is 425. 5 cancels out that 5. And now we can subtract 309 on both sides to get 116. So this student would need a 116 on her 5th exam to have an 85 exam average. And if we're assuming that every exam is only 100 points, it sounds like she will not be able to get an 85 average because you can't get a 116 on a 100-point exam. Okay. A equals P times 1 plus RT is the simple interest formula. And of these variables, P is the principal, the original amount you invest. R is the rate in decimal form, right? Like 6% would be 0.06. T is your time, which is usually in years. For this purpose, it's going to be in years. And A is your final amount. So if you start with some amount, you multiply it by 1 plus the rate times time, you get the final amount that you would have in your account afterwards. So let's say the account had 4440 in it after 4 years. Not put in 4440, it had 4440 after these 4 years at a rate of 12%. How much money was originally invested? Well, let's plug in everything that we know. A equals P times 1 plus RT. We're told that the final amount is 4440. We don't know what the principal is. We don't know how much money is initially invested. We're trying to figure that out. The rate is 12%, which would be 0.12, and the time is 4 years. Okay, well, all we need to do is solve for P. Okay, well, 0.12 times 4, 0.48. 1 plus 0.48, 1.48. And now we can just divide both sides by 1.48 because this is P times 1.48. 1.48 cancels out. 4440 divided by 1.48 is $3,000. So if you start with $3,000 in an account that pays 12% interest for 4 years, then your total amount at the end would be 4,440. Lots of fours going on here. Okay, another example, right? Kind of hodgepodge, a little all over the place. Find the length and width of a rectangle whose perimeter is 64 feet. Let me get my camera out of the way. Whose perimeter is 64 feet, and the length is thrice the width, then minus 4. Okay, well, the perimeter of a rectangle in general is always given by 2 length plus 2 width. Okay, think back to when you first learned shapes. Perimeter equals 2L plus 2W. Okay, but we're saying that the length is thrice the width, then minus 4. That means the length is 3 times the width minus 4. So 3 width minus 4. Well, if P is 64, then let's plug in everything we know into this equation. P is 64, L is 3W minus 4, and now it's a linear equation for us to solve for W. Okay, let's distribute 2. Let's combine like terms. Let's add 8 to both sides. Let's divide both sides by 8, and we get that the width is 9. Now, that's not the end of the problem. We want to know what the length and width of this rectangle is. We have that the width is 9, but the length is given by 3W minus 4. Oh, we're using that equation that we started with. Well, length is 3 width minus 4. Width is 9. So 3 times 9 is 27. 27 minus 4 is 23. So the dimensions of our rectangle are 23 by 9. If we wanted to double check for ourselves, perimeter is 2 length plus 2 width. 2 times width is 18. 2 times length is 46. 18 plus 46 is 64. Alrighty, here we go. A group of office workers found that their salary can be modeled in this way, that their salary is 60,000 plus 700x plus 1850y, where S is their salary, X is their years of interning, and Y is their years of work experience. If one worker has been working for 2 years and makes 70,000, for how long did he intern? Okay, let's just plug in all of the information that we're given. We're told that this worker makes 70,000, so their salary is 70,000. 60,000 is constant. We don't know how long they interned, but we do know that he worked for 2 years. So y is 2, right? Y is their years of work experience. They've been working for 2 years, so y equals 2. Okay, and now we're just solving for x again. Let's multiply 1850 times 2. That's 3,700. Let's combine 60,000 and 3,700 for 63,700. Let's subtract 63,700 on both sides. And let's divide both sides by 700. So after 9 years of interning, 2 years of work experience, this employee makes $70,000. I don't know if 9 years of interning for $70,000 is a good deal, but so it goes. Alrighty, last example. This is a very popular question. It pops up quite a bit. There's another way of solving it if we use a section in chapter 8, but we're not in chapter 8, we're only in chapter 1. So let's see how we can do this. A store sells almonds for $4 per pound and peanuts for $2 per pound, but they want to create a 10-pound mixture that sells for $32. So how many pounds of each nut should they use? Okay, well, let's say that X is the pounds of almonds in the mixture. We have almonds, we have peanuts. Let's say X is the amount of almonds that is in the mixture. You could also let X be the amount of nuts, but it's going to end up being the same thing. Well, if we have X pounds of almonds and the entire mixture is 10 pounds, then there must be how many pounds of peanuts? This is kind of a weird question. It's probably the hardest part to the question, aside from actually setting up the cost equation. But if there are X pounds of almonds and there is in total 10 pounds, then there must be 10 minus X pounds of peanuts. So in total, there would be X plus 10 minus X pounds, right? The pounds of almonds plus the pounds of peanuts. Well, X plus 10 minus X, X's would go away and we would get 10. So we know this makes sense. It's kind of weird that we're letting the amount of pounds be 10 minus X, but all it's saying is whatever space that we still have under 10 pounds is going to be dedicated to peanuts. If we have X pounds of almonds, then we have 10 minus the pounds of almonds for the pounds of peanuts. So it's kind of a weird way of thinking. I get it. We continue. Okay, well, if the almonds cost $4 per pound, then the cost of almonds would be 4 times X, the cost per pound times the number of pounds, or just 4X. If peanuts cost $2 per pound, then the cost of peanuts would be cost per pound times the amount of pounds of peanuts, 2 times 10 minus X. Here, we can distribute 2. 2 times 10 is 20. 2 times negative X, negative 2X. And then our cost equation would be the cost of almonds plus the cost of peanuts equals the total cost of the mixture. And what is the total cost of the mixture? Oh, it's 32 pounds. From here, now we're just solving for X. Okay, let's just drop those parentheses. They don't mean anything there. Okay, let's combine like terms. 4X minus 2X is 2X. Let's subtract 20 on both sides. Let's divide both sides by 2, and we get that X equals 6. So that means that we have 6 pounds of almonds in our mixture. Okay, well, if there's 6 pounds of almonds and the entire mixture is 10 pounds, then there are 10 minus 6, or 4 pounds of peanuts in the mixture. Okay, so you want a $32 mixture of almonds and peanuts. You need 6 pounds of almonds and 4 pounds of peanuts. So yeah, very, very weird section. There's a lot of random information in 1.2, but that's kind of the idea. So lots of information, kind of take them piece by piece. And with that said, we're going to change gears completely in 1.3 and talk about quadratic equations, which if you're already looking at the screen, maybe just a tad scary, that thing right there. Don't worry, we're going to handle this thing together. So I will see you in 1.3. Hi, welcome back for 1.3. So in 1.1, we talked about linear equations, and in 1.2, we learned to apply linear equations with all sorts of weird examples. But we're going to extend linear equations to now quadratic equations. So linear equations are equations that are just single x's, x to the first power, things that would create lines if we drew them. But quadratic equations are equations that are now in the second power of x. So what we're going to do in this section is a ton of x squared. So let's get right into it. Ax plus b equals 0 is a linear equation. But ax squared plus bx plus c, oh, this might look familiar from when we did AC method. Ax squared plus bx plus c equals 0 is a quadratic equation. Specifically, we want to make sure that a doesn't equal 0. If a equals 0, then we would have 0x squared, and 0x squared is just 0. So that would go away and we're left with bx plus c equals 0. But bx plus c equals 0 is just linear, right? It would just have a single power of x. So specifically when a does not equal 0, unsurprisingly. Okay. We call ax squared plus bx plus c equals 0 standard form. And in a lot of cases, we want our equations to be in standard form. There's going to be one type of equation or one type of method of solving quadratic equations where we don't need to have equals 0. But in general, we want equals 0. So, for example, x squared minus 2x equals 3 is not in standard form. But if we were to subtract 3 on both sides and get x squared minus 2x minus 3, that would be standard form. Okay, so first method we're going to have to solving quadratic equations. Linear equations, they're all kind of the same thing, maybe just some added steps as you go. But quadratic equations have all their own steps and all their own methods with their own steps each. So the method that you use entirely dependent on the problem. Some methods work for multiple problems, and there's going to be a certain method, a certain formula that we have later on in the section that will always work, but that doesn't mean it's the only method. So the first method we're going to talk about is factoring, right? In P4, we spent a lot of time factoring, and we're going to apply that here to equations. So our steps is put your quadratic equation into standard form. So get equals 0 on one side, get everything to one side. Once you have equals 0 on one side, factor the other side. So whatever side that you bring everything to, probably the left-hand side, factor that side. What you're then going to do is set each factor equal to 0, and you're going to solve each factor. So let's explain why. When you have something factored, right, some factor times another factor equals 0. Well, we're saying that we have two things that when you multiply them, they equal 0. Well, what's the only way that two things can multiply to 0? The only way that two things multiplied equals 0 is if at least one of those things is equal to 0, right? 2 times 4 is never going to equal 0. However, 2 times 0 will equal 0, or 4 times 0 will equal 0. So when you factor, what you're going to do is set each factor equal to 0 and solve each of those factors. And then, like I said in 1.1, check your answers. Not going to happen, not going to need to be much of a worry here in 1.3, but again, I want you guys to get into the habit of checking your answers, because come 1.5, you will need to check your answers. Okay, so let's do 2x squared plus 5x equals 3. And step 1 says, bring everything to one side, get to standard form. Well, we have equals 3. If we want to bring this 3 over, all we need to do is subtract 3 on both sides. Okay, so 2x squared plus 5x minus 3, this is factorable. And we spent an entire section factoring things that looked like this. So I'm not going to go over the factoring here. If you're looking for that video, that would be section P4. I can link that into the description, but please go practice factoring before you try and understand the factoring part here. That, or just take one of the methods that we do later on. So 2x squared plus 5x minus 3 factors as 2x minus 1 times x plus 3 equals 0. Okay, and here's what I mean. Notice that we have two factors that are being multiplied together, and when we multiply them, they equal 0. The only way that these two things can multiply to 0 is if at least one of those things is 0. So what we're going to do is set both of them equal to 0. If this equals 0, 0 times x plus 3 is 0. That would satisfy our equation. If x plus 3 is 0, then 2x minus 1 times 0 is also 0. That would also satisfy our equation. So set each factor equal to 0, and what you now see is these are just a pair of linear equations. Add that, very nice, easy linear equations. This, add 1 to both sides, divide by 2. Here, just subtract 3 on both sides. So what we get are two answers. One thing that makes quadratic equations very different from linear equations. Linear equations, in most normal cases, we got one single answer, x equals 3 or x equals -5. But for quadratic equations, what we're going to get a lot of the time is two answers. Two answers, very normal. We will look into situations of how we know what those two answers are going to be, what type of answers we get. But for right now, not going to think about that. So it's very normal and it's very okay to get two answers for quadratic equations. If you want, go back in and check each one. Just as an example, let's just check -3. Well, -3 squared would be 9. 2 times 9 is 18. 5 times -3, -15. 18 minus 15 is 3. And the same would be true for 1/2. 3x squared equals 2x. Again, we need to get one side to be equal to 0. So let's subtract 2x on both sides. Okay, well, no number this time. And if anything, this is a lot easier to factor. We can factor out just an x. And now we have x times 3x minus 2 equals 0. These are still two factors being multiplied to 0. One of those factors is just plain x. And that's okay. So we're going to set x equal to 0. And we're going to set 3x minus 2 equal to 0. Well, if anything, this actually made our job quite easy. X equals 0 is already done. 3x minus 2 equals 0. Add 2 to both sides. Divide by 3. So again, we get two solutions. So that's quadratic equations. It's nice when they boil down to linear equations almost immediately. Just a little bit of tinkering, just a little bit of factoring makes our job a lot easier to deal with. Okay. X squared plus 16 equals 8x. Well, let's subtract 8x because we need to get 0 on one side. And this factors quite nicely to x minus 4 times x minus 4 equals 0. Okay, same thing. Set each factor equal to 0. But what you notice is that we get x equals 4 twice. Well, for now, we'll talk about what that means to get the same answer twice. But that's in chapter 3. This is chapter 1. Your final answer is just x equals 4. There's only one x that satisfies this quadratic equation. So the two previous examples, we have two x's. two answers, two solutions. And now we had only one. And that is, again, totally fine. It doesn't mean there's anything wrong with the equation. There's nothing wrong with your work. It is possible that you get only one solution. And again, at the end of the section, that's when we'll discuss how we get a certain number of solutions and what type of solutions. So we like the method of factoring a lot because factoring is easy, right? In comparison to other things we're going to talk about, factoring is very familiar to us and we know how to factor, but not always is it going to be the only option, right? We're also going to talk about this thing in just a wee tad, but in general, we need a stepping stone to that. So square root property and completing the square are going to be some of your least useful methods because you're probably always going to want to go for factoring or quadratic formula, but it is a good stepping stone to what we talk about. And when it works, it's kind of nice. So let's talk about square root property first. Square root property can be used if the factored side is a perfect square. And what I mean by that is something like x plus 2 squared. That would be a perfect factored square. So the other nice thing about square root property is that the other side doesn't need to be equal to 0. In factoring, one side has to be equal to 0 because we need to be able to set each factor equal to 0 separately. But for square root property, we're not going to need that to be the case. We're going to need equals 0 for quadratic formula, but for square root property, we do not require that. Okay, so in general, if u is some algebraic expression and d is some number greater than or equal to 0, so some expression squared equals some non-negative constant, what we can do is take the square root of both sides. Just like in linear equations, when you add 5 to both sides or divide both sides by -2, you are allowed to take the square root of both sides. However, when you do that, when you take the square root of both sides, what you need to pick up is a plus and minus. You are allowed to take the square root of both sides so long as one side gets a plus and minus. So the reason for this has to do with the square root of u squared, right? We said square root and that squared cancel each other out and would be absolute value of u. But we haven't talked about enough properties of absolute value to prove that right now. However, that does reappear toward the end of the chapter. We're just going to kind of take it for granted for right now. So if u squared equals d, you can take the square root of both sides to undo the squared, right? How do you undo plus 5? By subtracting 5. How do you undo u squared? By square root of both sides. However, when you take the square root of both sides, you need to get plus and minus. I also want to stress this is only for when we are solving equations. Think back to chapter P when we were just looking at random radical or root expressions. We don't magically pick up a plus and minus when there is no equation to solve. This is only used when we are solving an equation. When you take the square root of both sides, that is when you pick up plus and minus. Okay, so x squared minus 3 equals 0. How we would do this before via factoring is a little different. How we would factor this is say, oh, this is a squared minus b squared. Well, difference of squares, a squared minus b squared, a plus ba minus b. You set each factor equal to 0, and you get x equals positive square root of 3 and x equals negative square root of 3. But this is really uncomfortable because this isn't nice. Saying that 3 is square root of 3 squared and we have to factor it that way, that's not necessarily very helpful. So here's where square root property comes in. Instead of factoring something that isn't as naturally factorable as other things we've talked about, why don't we instead add 3 to both sides? And now our expression side is a perfect square. It is literally something squared. When we have something squared, we can undo squared with the square root. Again, however, when you take the square root of both sides, you need to pick up a plus and minus. So square root of x squared, well, that undoes the x, but on the other side, you need to get plus and minus the other side. That is really, really, really important. So a little bit quicker, a little bit more, a little easier to picture. Okay, let's do another example where it's not just x squared, right? X squared minus 4 equals 0. You can kind of see like, oh, 2 and negative 2. But what if we have something like x minus 7 whole thing squared? Again, this is a great example of something squared, and that would be our giveaway to take the square root of both sides. But again, when you take the square root of both sides, you need to pick up a plus and minus. Okay, square root and the squared cancel each other out. That's the whole point. Square root of 9 is 3, so we get x minus 7 equals plus and minus 3. Now, this is a really good step, and if you can get here, you did the hard work. However, our answer should be x equals one single thing. So we now need to do x minus 7 equals positive 3 and x minus 7 equals negative 3. And again, you're starting to see the pattern for quadratics where we're always going to get 2 answers. Let's add 7 to both sides. For each problem, add 7 to 3, we get 10. Add 7 to negative 3, we get 4. So we again get 2 answers. And that's square root property. One more example. X minus 3 squared equals 5. Again, this is a perfect square. So let's take the square root of both sides. And again, when we take the square root of both sides, we get plus and minus on the other side. Square root and squared cancel each other out. So we get x minus 3 equals plus or minus square root of 5. This is not nearly as pretty. So why don't we just add 3 to both sides. Now, you might be wondering, why don't we do it separately? X minus 3 equals positive square root of 5. X minus 3 equals negative square root of 5. It worked nicely in the last question because the answers were very easy to simplify. But in the case of square root of 5, not really. You could say your answers are 3 plus square root of 5 and separately, comma, 3 minus square root of 5. But this answer is nice and simplified as well. Or not nice and simplified. It's a nice simpler way of writing that. Also, you'll note that I don't use decimals in a lot of situations because in general, decimals aren't necessarily always exact. For example, if you plugged in 3 plus square root of 5 into your calculator, you would get a really ugly irrational number that at some point you need to round. So instead of doing the extra step of plugging this into your calculator and rounding, why don't we just say the answer is 3 plus square root of 5 and 3 minus square root of 5. So for those of you that are taking my class, I love this answer right here. You give that to me. We're all for it. But from course to course, you might be told to do decimals, or you might be told to write your answer separately, whatever works. So if it can be simplified like the previous question, simplify it. If not, it's okay. Let's do one more example. 9x minus 5 squared minus 49. Well, the left-hand side, as it's written, is not a perfect square, right? 9x minus 5 is a perfect square, but minus 49 doesn't make this factor as nicely. So what's the remedy? Why don't we just add 49 to both sides? Well, now this is a perfect square. We can take the square root of both sides, make sure we add our plus and minus to the other side. Square root and squared cancel each other out. Square root of 49 is 7. So now we have 9x minus 5 equals positive 7. 9x minus 5 equals negative 7. This is just a pair of linear equations, and we get 2 answers. I haven't made it clear before, but also we like to write our answers in numerical order. So for example, negative 2/9 is before 4/3 on a number line. So writing x equals negative 2/9, comma 4/3 is a really nice way of summarizing your answer. You could, in theory, just leave your answer as x equals 4/3 and x equals negative 2/9, but we like to simplify things. Okay. If our quadratic is not a perfect square, what we can do is make it a perfect square, and that's called completing the square. This is a weird method for solving equations. I don't think many of you will use it all that frequently, but it is technically needed to broach the topic of quadratic formula, so let's do that. This can only be done if a equals 1. So ax squared plus bx plus c equals 0. We need to make sure that a equals 1, because if a doesn't equal 1, it's a little bit more difficult to try and picture, so just be careful for that. Steps to do this: move your constant term away from your variable terms. So you have an x squared term, you have an x term, and you have some constant. Move your constant to the other side. Okay, the part that makes completing the square is that we're going to add b over 2 squared to both sides. Now, it seems like kind of a silly step. However, when you add b over 2 squared to both sides, what that allows you to do on your variable side is factor to just x plus b over 2 squared. And the right side, well, we move the constant to the right side. We added another constant to the right side, so the right side is just a constant. Well, we now have a perfect square. We now have a constant. It's just square root property from there. Okay, so let's do an example of this. Step 1, let's get our constant out of the way. So plus 8, let's bring plus 8 to the other side by subtracting 8 on both sides. Okay, this is ax squared plus bx plus c. And what we want to do is add b over 2 squared to both sides. So if this is ax squared plus bx plus c, what is b? B is 10. Okay, so we're going to add b over 2 squared, 10 over 2 squared to both sides. Well, 10 over 2 squared, but we're not adding it to just one side, we're adding it to both sides. If we add it to both sides, we don't change anything. Okay, well, we can simplify this. 10 over 2 is 5, 5 squared is 25. Negative 8 plus 25 is positive 17. And also, this factors very nicely. We went from something that could not be factored as it was written to something that could be factored with just a constant on the other side instead of 0. So x squared plus 10x plus 25 is x plus 5 squared. Negative 8 plus 25 is 17. And now from here, square root property, pick up a plus and minus, and just subtract 5 on both sides. And you can leave your answer like that. That's completing the square. So it's kind of a weird method, kind of like a why are we doing this type of method? There are other ways. And honestly, you probably won't go for completing the square in most cases. And that's okay. There's a reason why we have a whole bunch of different methods to solving these things. So even if you don't use completing the square, that's fine. The other methods work just as nicely. 3x squared minus 6x minus 15 equals 0. Let's complete the square on this. However, we can only complete the square when a is 1. Well, ax squared, a is now 3. So just like that, we can't do completing the square, right? Just move on? No. What we can do is simply divide everything by 3, divide both sides by 3. Well, when we do that, 3x squared divided by 3 is just x squared, negative 6x divided by 3, negative 2x, minus 15 divided by 3, negative 5. And it's nice because 0 divided by 3 is just 0. So this equation simplifies a little bit more nicely to x squared minus 2x minus 5 equals 0. Okay, now let's complete the square. Let's get our constant term away. Let's add 5 to both sides. Now we want to add b over 2 squared to both sides. b is always the number attached to x. So b is -2. We're going to add b over 2 squared to both sides, -2 over 2 squared to both sides. -2 divided by 2 is -1. -1 squared is +1. Left side factors to x minus 1 squared. Right side simplifies to 6. And now square root property, take the square root of both sides, get plus and minus, x minus 1 equals plus or minus square root of 6, and add 1 to both sides. Okay, so completing the square, like I said, probably not something you do all that frequently, but quadratic formula is something you will definitely use at some point. So we need completing the square to derive the formula for quadratic formula. So I'm going to do it in the presentation. It's a little complicated, so if it scares you a little bit, don't worry too much. In general, you will never be asked to derive the quadratic formula, but I will still show it. If it freaks you out, skip along just a little bit. So in general, quadratic formula is the most powerful way to solve quadratic equations. I say that because it always works. It might be more work than necessary, but it always works. So if you're really struggling to try and factor, you're really struggling to try and use like square root property or completing the square, you can go right for quadratic formula, assuming that we're in the correct state for it. But yeah, it always works. It might be too much, but it's better to do too much than not enough. So to do this, the right side must be equal to 0. So factoring method, one side has to be equal to 0. Quadratic formula must be equal to 0 on one side, but completing the square root property, that is not the case. But okay, it's a little complicated to derive, like I said, but the quadratic formula is right here. For ax squared plus bx plus c equals 0, the solutions to ax squared plus bx plus c equals 0 is right here. X equals -b plus or minus the square root of b squared minus 4ac all over 2a, where a, b, and c all come from ax squared plus bx plus c. So if you know what a, b, and c are, you can go right for plugging in a, b, and c, and that's how quadratic formula works. I understand it's a very scary looking formula, but don't worry, it functions just like any other thing that you're plugging stuff into. Okay, so I am going to derive it for the presentation, for the sake of the presentation. However, if it's kind of scaring you or you're not really following along, don't worry, I'm just doing it for completeness. Skip ahead like, I don't know, 30 seconds to the first example, to skip over this part. But if you're sticking around, let's do it together. So we're going to complete the square. So let's bring positive c to the other side. So let's subtract c on both sides. And now we want to divide everything by a because we know we can only do completing the square when a is equal to 1. So we divide everything by a cancels out, b over a and c over a. Okay, well now we want to complete the square. So we're going to add b, in this case b over a divided by 2 squared to both sides. Okay, well b over a divided by 2 is b over 2a. And we're going to add that to both sides. Yeah, it's already pretty messy. Now, left side is very nice. That factors to just x plus b over 2a squared. And now here, let's rearrange terms. Let's put b squared over 4a squared minus c over a. So I distributed the 2. I squared everything. B squared, 2 squared is 4, a squared is a squared, and just rearrange terms so that the minus would be to the right. Okay, well, what we can do is now combine these two terms by getting a least common denominator. So we need to multiply c over a by 4a so that we get a times 4a squared. Okay, well, now they have the same denominator, so we can subtract them. Oh, b squared minus 4ac. That looks familiar. Well, now square root property says take the square root of both sides. When we do that, the square root cancels out. X plus b over 2a. This was a little bit of a mistake. The square root should still extend over everything. That's a small mistake. It should be square root of 4a squared at the bottom here. Okay, yeah. But now we can subtract b over 2a on both sides. Again, square root of 4a squared. It was still supposed to be square root here. Square root of 4a squared is 2a. Okay, well now they have the same denominator, so we can add or subtract them. That was a very messy derivation. I promise it looks better in person. But yeah, if you wanted to know where it came from, there you go. So with that said, let's get right into examples. 3x squared equals 5x plus 2. So again, for us to do quadratic formula, we need everything to be on one side. So let's subtract 5x and let's subtract 2 on both sides. So one thing I should note is that you should always try and factor. If you're very good at factoring, if you're very comfortable factoring, you should try and factor first because quadratic formula has a lot of space for you to make a mistake. So I believe this factors. Yes, this factors. You would get 2 very nice rational answers. So in the event that you can factor, you should. But again, quadratic formula will always work, even if your answers are a little ugly. So for us to do quadratic formula, we need a, b, and c. Well, a, x squared plus bx plus c. So a is 3, b is -5, and c is -2. I'll do that again. ax squared plus bx plus c. Ax squared, a is 3, plus bx, b is -5, plus c is -2. And now what we're going to do is take a, b, and c and plug them in for a, b, and c. So we get that. right? Wherever we see A, write 3. Wherever we see B, write -5. Wherever we see C, write -2. Nobody said it was pretty, but at least now it's just calculation. Okay, -5 is +5. -5 squared is +25. -4 times 3 times -2, +24. 2 times 3 is 6. 25 plus 24 is 49. The square root of 49 is 7. So we get 5 plus 7 over 6, 5 minus 7 over 6. Well, it's a linear calculation, but not a very scary one. So our answers are -1/3 and 2. It seems very anticlimactic that quadratic formula ends up being just a calculation, but that's really all it is. There's some progression to get up to quadratic formula. If I just showed you quadratic formula, it wouldn't be very exciting, but at least now you understand where it comes from. Okay, let's do another one. 6x squared minus x minus 2. I think this is another one that could factor, but again, let's practice doing quadratic formula. Okay, well, this is already ax squared plus bx plus c. Again, ax squared plus bx plus c. Ax squared, a is 6, plus bx, b is -1, plus c, c is -2. So there's quadratic formula. Plug in a, b, and c, and use parentheses so that you don't screw yourself up. Okay, -1 is +1, -1 squared is +1, -4 times 6 times -2 is +48, 2 times 6 is 12. 1 plus 48 is 49, square root of 49 is 7, and again, 1 plus 7 over 12, 1 minus 7 over 12, we get 2 answers. So kind of not a mistake, but a coincidence that we have square root of 49 twice. That doesn't normally happen for every example. It just happens to work out for this one. Okay, and let's do another one. 5x squared plus 12x plus 4. So if this is ax squared plus bx plus c, a would be 5, b would be 12, and c would be 4. Alrighty, again, just plugging everything in. 12 squared is 144. 4 times 5 times 4 is 80. 144 minus 80 is 64. Square root of 64 is 8. -12 plus or minus 8 becomes -12 plus 8 over 10, and -12 minus 8 over 10. And we again get 2 solutions. So you think that quadratic formula is this big, very ugly, very forgettable thing, but it's actually not that bad. If you know what a, b, and c are, if you plug them in correctly, it just becomes easy multiplication, subtraction, square roots. So don't be so scared of it. I understand it's daunting. It looks very scary, but it really is just a plug and chug. Okay, x squared minus 7x plus 7. Ax squared plus bx plus 7. A would be 1, B is -7, and C is +7. So plug it in. -7 squared is 49. 4 times 1 times 7 is 28. Well, -7 is +7, but 49 minus 28 is just 21. And square root of 21 is not a pretty number. So going back to those square root property examples where I just said, leave it the way it is, don't worry too much about it. There you go. There's a perfect example of how this would look in quadratic formula. So instead of trying to figure out what square root of 21 is, instead of getting decimals, this answer, very nice and pretty. However, some instructors, if you're watching, you might prefer to have 7 plus square root of 21 over 2, comma, 7 minus square root of 21 over 2. So this is a nice condensed form to say both solutions, but it would be a little bit more correct to write them out separately. However, less writing, the better. 2x squared plus 12x minus 18. You could do quadratic formula on this. However, what you might see is that all of these numbers are divisible by 2. So instead of dealing with a is 2, b is 12, and c is -18, why not just divide everything by 2? Well, when you divide everything by 2, you get x squared plus 6x minus 9. A, b, and c are not as big, and they will save you some time in simplifying. Again, you would get the exact same answer using 2, 12, and -18. It just might be a less simplified version. Okay, so again, plug it in. A is 1, b is 6, c is -9. 6 squared is 36. -4 times 1 times -9 is +36. 36 plus 36 is 72. But square root of 72 is 6 square root of 2. So even though you don't get a perfect square on the inside, doesn't mean it's not simplifiable. I think that's a word. So square root of 72 is 6 square root of 2. Just because square root of 21 in the previous question was not able to be simplified, that doesn't mean all plain square roots can't be simplified. Okay, last but not least from here, let's just divide both of these by 2. -6 divided by 2 is -3. 6 divided by 2 is +3. So this would be a nice, pretty final answer. If you got to this point, this is most of the work. You did most of the work right, but we're able to simplify just a little bit more. X squared minus 6x plus 9 equals 0. A is 1, B is -6, and C is 9. Okay, plug it in. -6 squared is +36. -4 times 1 times 9 is -36. Alrighty, 36 minus 36 is 0. And square root of 0 is just 0. Well, if you did 6 plus 0 divided by 2 and 6 minus 0 divided by 2, you would get 3 both times. So again, we've seen plenty of times that quadratic equations can give one solution or two solutions. Just because you get one type of solution over another doesn't necessarily mean you did anything wrong. However, just wanted to show you that we could have done this easier. You might have noticed it right away, but you could have also been very much in the quadratic formula groove. This can be factored as x minus 3, and you could get x equals 3 that way. So again, I just wanted to illustrate the fact that just because quadratic formula works every single time, it doesn't mean it is the easiest method. So just keep an eye out for when you want to use which method and try and use the best method for all of these problems. Well, what you notice a couple times is that we got things like two solutions, two rational solutions, or we got one solution like the last problem, or like that square root of 21 question where we had two solutions, but we knew square root of 21 was irrational, so we would end up being irrational anyway. So with that said, how do we know, how can we get foresight as to what type of answer we can get? Well, that's where discriminants come in. So the discriminant is the b squared minus 4ac in the quadratic formula. So we had negative b plus or minus square root of b squared minus 4ac over 2a. That b squared minus 4ac inside the square root is called the discriminant. Now, the discriminant is very useful because depending on the value of the discriminant, the quadratic formula produces different types of answers, different types of solutions. So if you know what the discriminant is, you can figure out which type of solutions you would get. Okay, if the discriminant is a perfect square, like those first two examples where the discriminant was 49, if it's a perfect square, there are two real rational solutions. Go back to those first two examples when we had square root of 49 and see that we had two very nice, very pretty fraction answers. They're real numbers and they're rational solutions. If the discriminant is positive, but not a perfect square, like 21, there are still two solutions because we still had plus and minus square root of 21, but instead of being rational solutions, they're irrational solutions. So perfect square, two real rational, positive but not a perfect square, two real irrational. If the discriminant is 0, well, that was like that very last example we did where we only got x equals 3. So if the discriminant is 0, square root of 0 is 0, plus or minus 0 just goes away. You get one real rational solution. Last but not least, it didn't happen this time, but if the discriminant is negative, then you would get square root of some negative number, and there are two complex solutions. Now, we've spoken very, very little about complex numbers. I mentioned it all the way in P1. We kind of looked at it a little bit in P6 with square roots and saying, well, square root of a negative number doesn't exist. So in that case, we say there are two complex solutions, and it's almost like the entire next section is about complex solutions. So before we get into something like that, let's just do some very quick discriminant examples. 2x squared minus 3x minus 7. A is 2, B is negative 3, C is negative 7. Again, don't worry about solving it. Let's just determine what kind of solutions we would get without going through all the work. B squared minus 4AC, plug in A, B, and C. We get 9 plus 56. Sorry, 9 minus negative 56. 9 plus 56 would be 65. 65 is positive, but not a perfect square. So we get two irrational solutions, two real irrational solutions, but we don't really know the difference between real and complex at this moment right now. Next section we will. X squared plus 6x plus 9. A is 1, B is 6, C is 9. So plug that all into the discriminant. 6 squared is 36. 4 times 1 times 9 is 36. 36 minus 36 is 0. We got 0. That is one rational solution. X squared plus 2x plus 3 equals 0. All right, A is 1, B is 2, C is 3. Plug it in. 2 squared is 4. 4 times 1 times 3 is 12. 4 minus 12 is negative 8. That's negative. Two complex solutions, and we will talk about two complex solutions in 1.4. So I will see you there. Bye. Hi, everyone. Welcome back to section 1.4. At the end of 1.3, we very, very, very briefly talked about the fact that the discriminant can be negative in quadratic formula. Well, that's kind of an issue because the discriminant usually sits inside a square root. So we're saying that we can take square roots of negative numbers, which to this point, we have not been able to do. However, what we are going to introduce in this section is the complex numbers. So before I do that, I just want to very briefly discuss what the complex numbers are. All the way in P1, we talked about the set the natural numbers, which were the counting numbers 0, 1, 2, 3. And we said the natural numbers sit inside the set the whole numbers, and the whole numbers sat inside the set the integers. The integers sat inside the rational numbers. And then we had this weird little set on the outside, the irrational numbers, and both the rational and irrational numbers made up the real numbers. So the real numbers are any numbers that, even if not pretty, even if not easily calculable, do sit on the real number line. For example, you may not necessarily know where exactly, negative 1.12479 sits, but you have an idea and you can picture where it sits. However, what we're going to introduce today is the complex numbers. So the complex numbers are this set that includes all of the real numbers, and we denote it with a capital C. And what we're going to add in this set are what are called imaginary numbers, where we are now allowed to take square roots of negative numbers. Even if we cannot necessarily visualize what the square root of a negative number is, it does have very, very, very many properties, both in this course and in all of mathematics and in the real world. So just wanted to give this brief visual, and now we're going to move back to the presentation. Okay, so now we're back in the presentation. Now you see the name of the section, the complex numbers. So let's get right into it. So like we said, the natural numbers go inside the whole numbers go inside the integers go inside the rational numbers. Along with the irrational numbers, the rational numbers go inside the real numbers. And now this real number set goes inside what we call C, the complex numbers. Now, the complex numbers introduce the unit I, where we say and where we define I to be square root of -1, but not specifically just square root of -1. We have the added property that I squared equals -1. So normally we have these rules that when we square root, we're supposed to get positive numbers and all that. But in the set of the complex numbers, this is a rule that is allowed to happen. So again, just because we have I equals square root of -1 doesn't necessarily mean that all of our numbers are going to have I or are going to be imaginary. The real numbers sit inside the complex numbers. So just like all natural numbers are whole numbers, just like all whole numbers are integers, all real numbers are complex numbers. So even if it doesn't have an I, it is still a complex number. So we use the notation Z equals A plus BI. Z is what we use to denote complex numbers in general. Instead of a C, right, we like using C for constant. So Z will denote complex numbers. So we have A plus BI. That is what a complex number would look like. A and B themselves, ignoring I for a second, A and B are just both real numbers that we have dealt with before. We say A is the real part, and we say B, the part that is attached to the imaginary unit I, is the imaginary part. So the part that is attached to square root of -1 is the imaginary part. We can visualize the real part. This could be like 2, and you know where 2 sits, but you might not necessarily know where 2 plus 3i sits. We can also call it the complex part, imaginary part. We get the idea. Now, if A equals 0, well, then we have 0 plus BI, which is just BI, and a number that only has an imaginary part we say is purely imaginary. And if B equals 0, so A plus 0i, well, 0 times anything is still 0, even in the complex numbers. And that would give us just A, which itself is a real number. So one kind of added property, but goes along with what we're talking about, that if we have some B that is positive, so square root of -B, where this isn't positive, this is a negative number. Okay, square root of -B, we separate this by saying square root of -1 times square root of B, right? Breaking up the product. And then square root of -1 is just I. So we say this is I square root of B. Okay, now I want to stress that this breaks the rule of radicals that we talked about all the way in P6. In P6, we said we can only separate roots if the insides are both 0 or positive. But in the complex number system, we are allowed to separate them. That is a rule of the complex numbers. Now, that's kind of unfamiliar to many of you if you have not seen imaginary numbers before. But essentially, there are more than just the real number system out there. The most common number system, the one that we're most familiar with, is the real numbers. All numbers that we can add, subtract, visualize, graph, stuff like that. But there do exist other number systems that have their own sets of rules. Complex numbers is the beginner of sets that break apart from the real numbers. But if you go higher up in math, you can find all sorts of very, very crazy number systems. So I just want to stress that the complex numbers are their own set, are their own system, just like the natural numbers, just like the whole numbers, and so on. Okay, so just to get an idea on what real parts and imaginary parts look like, 2 plus 5i, well, this is A plus BI. The real part is the part that sits by itself, and the imaginary part is the part that is attached to I. So the real part here would be 2, and the imaginary part would be 5. Okay, pretty straightforward. 7 minus 1/2 I. The real part is the part that doesn't have I, which is 7. The imaginary part isn't just 1/2, it would be -1/2. Okay, that makes sense, the negative sign. 3i, well, 3i is completely missing a real part, right? It only has the I part. Well, we can rewrite this as 0 plus 3i. Well, now it's a little clear that the real part is 0 and the imaginary part is 3. -9, completely missing the I part, but we can rewrite -9 as -9 plus 0i. Okay, well, the real part is -9, the imaginary part is 0. So if the imaginary part is 0, we would say it's just a real number. -9 is a real number, we know that. And for the case of 3i, where the real part is 0, we would say that's a purely imaginary number. 3 plus square root of -25, well, we have to simplify square root of -25 first. In general, always simplify square roots of negative numbers before you do anything else. Well, the square root of -25 would be the square root of 1 times the square root of 25. Square root of -1 is I, and square root of 25 is 5. Another way you can look at this is the square root of +25 is 5, so the square root of -25 is 5i. And you can extend that to all square roots of negative numbers. Square root of 64 is 8, square root of -64 would be 8i. The real part, now that we have it rewritten, is 3, and the imaginary part is 5. Okay. Now, what we're interested in doing, of course, is all sorts of operations. All these operations will eventually get us back to quadratic equations, just like we finished 1.3 with. Okay, so some operations, addition and subtraction, they are a lot like combining like terms for polynomials. So if we are adding or subtracting complex numbers, we are going to add and subtract their real parts, add and subtract their imaginary parts. So kind of thinking about this as combining like terms, you add all the constants together, you add all the x's together, all the x squareds, and so on. So 2 plus 3i plus 1 plus 4i, we are going to add 2 and 1, and then separately add 3i and 4i. Well, 2 plus 1 is 3, 3i plus 4i is 7i. If you want to substitute x in for i just so it's a little bit easier to look at, that's totally fine too. 3 plus 7i plus 2 minus 4i. We're going to add the real parts, 3 and 2, and then add 7 and negative 4i, or just subtract 7i and 4i. 3 plus 2 is 5, 7i minus 4i is 3i. 5 plus 9i minus 6 minus 8i. Let's be a little careful. We're going to subtract the real parts, so 5 minus 6, and 9i minus negative 8i. For the imaginary parts, 5 minus 6, negative 1, negative negative is a plus, 17i. If we have square roots, like I said, simplify the square roots. First, square root of negative 9 would be square root of negative 1 times square root of 9. Square root of negative 4 would be square root of negative 1 times square root of 4. Okay, well, square root of 9 is 3. Square root of negative 9 is 3i. Square root of 4 is 2. Square root of negative 4 is 2i. And now, just subtracting real and imaginary parts. Okay, so not so bad so far. And multiplication isn't that much different, except think about this. If you have been thinking about I as x, well, when we are doing, for example, foiling and we get x squared, well, x squared just stays x squared. It's its own thing. But if you're doing it with I, we have the rule that I squared equals something specific. So it's just one extra step of simplification. So we say in the complex numbers that I squared is negative 1. So when doing multiplications with square roots, with imaginary parts, write the square roots as that I squared of v form before and do that before multiplying. Okay, 3 minus 5i times 2 plus 7i. Let's treat this just like foiling. So we're going to do 3 times 2 is 6. 3 times 7i is 21i. Negative 5i times 2, negative 10i. Negative 5i times 7i, negative 35i squared. Let's simplify this inside right here. 21i minus 10i would be 11i. And now, if this was polynomials with x's, we would be done. However, in the complex numbers, when we're talking about I, we have one added step, that I squared equals negative 1. Okay, negative 35 times negative 1 is positive 35. So our extra steps just lead us to adding real parts. 6 plus 35 is 41. Now we like writing 41 plus 11i. We like writing the I term second. That's just how we decide to write them. If you wrote 11i plus 41, you're not necessarily wrong. It's just a little bit nicer to put the imaginary part second. 2 plus 5i times 1 plus 4i. Okay, 2 times 1 is 2. 2 times 4i is 8i. 5i times 1 is 5i. 5i times 4i is 20i squared. 8i plus 5i is 13i. 20i squared, well, I squared is negative 1. So 20 times negative 1 is negative 20. 2 minus 20 is negative 18. So again, we kind of like writing that minus second, 13i minus 18. It is more correct to put the imaginary part second. So it's kind of interesting because all of these terms here are positive. And in polynomials, everything positive that we're multiplying, we end up with everything positive at the end. But we see in the complex numbers, we get this weird behavior that sometimes we can still get negative numbers. Negative 2i times 5 minus 9i. This is just distribution. Negative 2i times 5, negative 10i. Negative 2i times negative 9i, positive 18i squared. I squared is negative 1. So 18 times negative 1 is negative 18. Okay. 3i times 7 plus 4i. 3i times 7 is 21i. 3i times 4i squared, 12i. 3i times 4i is 12i squared. I squared is negative 1. So we get negative 12 plus 21i. So just be careful. Treat these problems as their own separate problems. In the event that you have square roots, simplify the square roots first. So square root of negative 2 is square root of negative 1 times square root of 2, essentially pulling out that negative 1 in terms of a square root. Square root of negative 8 is square root of negative 1 times square root of 8. Square root of negative 1 is I. Square root of negative 1 is also again I. So I times I is I squared. Inside the square roots, 2 times 8 is 16. Well, I squared is negative 1. Square root of 16 is 4. So our final answer is negative 4. And again, be very careful. This is true for the complex numbers. What we would do in the real numbers, but we wouldn't actually do it in the real numbers because we're not allowed to have square roots, negatives inside square roots to begin with in the real numbers. This is only allowed in the complex numbers. But just be careful. Make sure you simplify this with I first, because if you go right for combining the insides, you would get negative 2 times negative 8 is positive 16, and square root of positive 16 would be 4. So please be very careful. The rules of complex numbers dictate that we need to take out I first when we're dealing with square roots of negative numbers. Okay, and there's actually a really interesting property surrounding I and the powers of I. So we know that I to the 1 is just I. We know that I squared is negative 1. Well, then I cubed would be I squared times I, but I squared is negative 1. And negative 1 times I would be negative I. Okay, but I to the 4th, well, I to the 4th is I squared times I squared. I squared is negative 1. I squared is also negative 1. And negative 1 times negative 1 is positive 1. Oh, that is weird. Okay. Well, I to the 5th would be I to the 4th times I, right? Just using properties of powers. I to the 4th is 1, and I is just I, so 1 times I is just I. Okay. I to the 6th, I to the 4th times I squared. I to the 4th is 1, and I squared is negative 1. Well, 1 times negative 1 is negative 1. I to the 7th is I to the 4th times I cubed. I to the 4th is 1, and I cubed is negative I. So 1 times negative I is just negative I. Oh, well, hold on. I, negative 1, negative I, 1. I, negative 1, negative I. Maybe there's already a pattern. Okay, I to the 8th would be I to the 4th times I to the 4th, but I to the 4th is just 1, and 1 times 1 is 1. Look at that. The powers of I cycle. I, negative 1, negative I, 1. I, negative 1, negative I, 1. So what do you think is going to happen for I to the 9th? Well, I to the 8th was 1, so we cycle again back to I. I to the 10th would be the next one in the cycle, negative 1, and then negative I, and then 1. I to the 13th, wow, look, the cycle is exactly the same. I, negative 1, negative I, and 1. Very, very strange. Okay, now, before we get into actually solving quadratic equations using complex numbers, we got to talk about division a little bit. And division is kind of weird. Okay, so complex division is a lot like rationalization. Go all the way back to P6 when we talked about rationalizing denominators, and that's going to be very, very, very similar to here. Okay, so what we're going to do is multiply by the conjugate. So the conjugate of A plus BI would be A minus BI, and vice versa. Think back to the conjugate of A plus B. Conjugate of A plus B is A minus B, and the conjugate of A minus B is A plus B. So phraseology is the same, conjugate, its application is still the same, where if we have A plus BI, its conjugate is A minus BI. If we have A minus BI, its conjugate is A plus BI. So now the complex conjugate product theorem, very long mouthful, the complex conjugate product theorem says when we multiply these things, when we multiply something by its conjugate, well, A times A is A squared, BI times negative BI is negative B squared I squared. Notice we don't have to do the inside, that's just foiling. But this is also just difference of squares, right? A plus something, A minus something, difference of squares. Well, I squared is negative 1. So negative B squared times negative 1 would be positive B squared. Oh, that's really weird. Okay, so if we are multiplying something by its conjugate, if we're multiplying a complex number by its conjugate, all we need to do is take the real part and square it, and then add the imaginary part squared. Forget about the i's. No more i's here. So if you don't like what I just did, that's okay. You are more than welcome to FOIL, but this is going to save us a lot of time. So let's do z by z bar. That's what this little z with the bar on top, literally z bar. Okay, so if we're multiplying 2 plus 5i by its conjugate, we're multiplying by 2 minus 5i. Well, if you want to FOIL this, you can, but the complex conjugate product theorem says 2 times 2, take the real parts, square them, plus take the imaginary parts and square them. Take 2, square it, plus take 5 and square it. 2 squared is 4, 5 squared is 25, and you get 29. So again, if you want to FOIL, you can, but you don't have to. Okay, 7 minus 1/2 I, if we want to multiply by its conjugate, the conjugate of 7 minus 1/2 I would be 7 plus 1/2 I. And here is a great example of why you wouldn't want to expand this. Well, here what we're going to do is take the real parts, square them, plus take the imaginary parts and square them. 7 squared plus 1/2 squared. 7 squared is 49, 1/2 squared is 1/4, and properties of fractions, that's chapter P. 3i, well, 3i here is a little bit of a problem. There's no real part, but fear not. 3i is just 0 plus 3i. Okay, well, 0 plus 3i, its conjugate is 0 minus 3i. So take the real parts, square them, take the imaginary parts, and square them. 0 squared plus 3 squared. And we just get 9. Okay, now we did it this way so that it's a lot easier to do division. Okay, so what we're going to do for complex division is multiply by the conjugate, exactly like we rationalized the denominator. We don't want I in the denominator here. All of the complex numbers we've talked about so far have all been in the numerator. Okay, so the conjugate of 2 plus I would be 2 minus I. And just like everything else we've done, multiply in the numerator and in the denominator. So what we get is 1 times 2i over 2 plus I times 2 minus I. Oh, look at this. Complex conjugate product theorem says take the real part, 2, square it. Take the imaginary part, there's a 1 right here, and square it, add them together. 1 times 2 minus I is just 2 minus I. Real part squared plus imaginary part squared. 2 squared is 4, 1 squared is 1, 4 plus 1 is 5. Now, I like this answer. This is pretty clear. However, it is very mathematically sound to say 2/5 minus 1/5 I, just so it's a lot clearer that this is the real part and this is the imaginary part. So again, I would accept this, but those of you watching elsewhere, be careful. This might be better for your instructors. Okay. And again, if you don't like what I did, that's totally fine. You still have to multiply by 2 minus I over 2 minus I, but when it comes to the denominator, if you feel better foiling this, that's totally okay. 2 times 2 is 4, 2 times negative 2i is negative 2i, I times 2 is positive 2i, I times negative I is negative I squared. Well, we can simplify that inside. Negative 2i plus 2i goes away. I squared itself is negative 1. So 4 minus negative 1 would be 4 plus 1, and that's 5. And just like that, we get to the exact same answer. Okay, some more examples. 1 plus I over 1 minus I. We're going to multiply by the conjugate of the denominator, always. Conjugate of 1 minus I is 1 plus I. Okay, so in the numerator, we get 1 plus I times 1 plus I. We're going to need to FOIL that. But in the denominator, 1 plus I, 1 minus I, complex conjugate product theorem. Take the real part 1, square it. Take the imaginary part 1, square it, and add them together. Up here, 1 times 1 is 1. 1 times I is I times 1 is I, so we get 2 i's. I times I is I squared. Okay, well, 1 squared is 1. 1 squared is 1, so we get 2. And I squared is negative 1. 1 minus 1 goes away. So 1 plus I over 1 minus I is just I. Ooh. There is very little rhyme or reason. You should be trying to do all these problems on their own. Don't look for patterns like this. This is just a nice example that happened to work out. Okay, 7 plus 6i over 3 minus 4i multiplied by the conjugate of the denominator. Conjugate of 3 minus 4i is 3 plus 4i. In the numerator, FOIL this out. In the denominator, take the real parts, square them, plus take the imaginary parts and square them. So I FOILed at the top. At the bottom, 3 squared plus 4 squared. Okay, 28i plus 18i, 46i. 3 squared plus 4 squared is going to be 9 plus 16. I squared is negative 1. 24 times negative 1, negative 24. Alrighty, nobody said these were going to be pretty. But now we get the idea. Okay, now that we have learned to sort of work with I, what we can now do is actually solve quadratic equations where we get two complex solutions. Okay, so when the discriminant is less than 0, our final answer is a pair of complex roots. Don't forget from the discriminants part in the last section that if the discriminant is negative, what type of solutions we get is two complex solutions. So x squared plus 2x plus 2 equals 0. Okay, well, A is 1, B is 2, C is 2. Just like we did in the last section, but now let's plug in all of that information to the quadratic formula. All right, well, 2 squared is 4. 4 times 1 times 2 is 8. 4 minus 8 is negative 4. Okay, well, the square root of positive 4 is 2, so the square root of negative 4 is 2i, and now we can divide everything by 2 to get negative 1 plus or minus I. Okay, x squared minus 4x plus 13 equals 0. A is 1, B is negative 4, C is 13, right? Just to reiterate, ax squared plus bx plus c. Alrighty, and just plug it into quadratic formula. Negative 4 squared is positive 16. Negative 4 times 13 is negative 52. 16 minus 52 is negative 36. Square root of positive 36 is 6. Square root of negative 36 is 6i. And we can divide both 4 and 6 by 2. Nice. One more. 4x squared plus 4x plus 5 equals 0. A is 4. B is 4. C is 5. Plug it all in. 4 squared is 16. 4 times 4 times 5 is 80. 16 minus 80 is negative 64. The square root of negative 64 will be 8i. We can divide all of these things by 4. And just like that, that's the end of 1.4. So most of the section, even though our goal was to solve quadratic equations that involved I, what we ended up doing is spending more time just doing complex number acrobatics. So yeah, that's the end of 1.4. And 1.5, we're going to extend what we did in 1.1 and 1.3 to solve equations that have almost any power and a whole bunch of other weird looking things. So I will see you in 1.5. Bye. Hi everyone, welcome back for 1.5. In 1.1 we solved the linear equations, and in 1.3 we solved quadratic equations, and we're just going to talk about almost every other type of equation that we could possibly solve at this level. So a lot of it's going to use things like solving linear equations, things like splitting apart multiple linear equation factors into multiple answers, but in general we're going to be talking about quite a few different types. So in a way 1.5 is kind of like a showcase. You already see all the different types of things that we're going to learn to solve here, like factoring, rationals, radicals, rational exponents, and quadratic likes. So there's a lot going on here. Take each subsection as kind of its own actual subsection, but how we solve each one is very different. But again, what we're going to use is a lot of what we have talked about in 1.1 and in 1.3. One thing I want to stress before we do any of these is that, in 1.1 and in 1.3, I said, make sure you check your answers. And in 1.1 and 1.3, linear and quadratics, you don't really have that problem. Really, whatever answer we get is going to be the right answer. But what you're going to see here in 1.5 is that it is possible for us to get what are called extraneous solutions. Solutions that we get when we apply a certain algebraic method, but when you go back to plug them in, they don't actually work. So you're going to see me check a lot of answers here and say like, oh, look, this answer doesn't work. So just in general, I've been saying it for a while here in chapter 1, but but please check your answers when you are doing these types of problems. So let's get into the first type. Let's talk about factoring. And we've kind of been doing this. We've factored quadratics before. Well, all we're going to say here is if we can factor the thing, we can solve it just like we've solved anything else. So again, if we can factor it, we can solve it. So let's say we have x cubed plus 3x squared equals 4x plus 12. And what we're going to do here to solve this, let's bring everything to one side. So let's subtract 4x on both sides. Let's subtract 12 on both sides. Okay, and now what we have are four terms whose collective greatest common factor is 1. That was usually a really good heads up for us to do factoring by grouping. So let's factor the first two. Let's factor the second two. We see here in the first two, we could take out an x squared. In the second pair, we could take out a -4. Oh, well, they have x plus 3 in common. We can factor out x plus 3. And then everything that's left over, right? P4, us factoring. Well, we also know that x squared minus 4 is also x plus 2x minus 2. And now from here, this is actually pretty nice. What we had in 1.3 was two factors that were multiplied to 0, and we set each factor equal to 0. Well, we can extend this to however many factors we have multiplied equal to 0. We can set all of them equal to 0. And now from here, these are all just linear equations. Subtract 3 on both sides, subtract 2 on both sides, and add 2 on both sides. So we get 3 answers. Now, maybe there is some sort of pattern where the fact this is x cubed, we had 3 answers, maybe x to the fourth would have 4 answers, and we're not going to really broach as to how or why that is the case until chapter 3. So, don't be looking necessarily for 3 answers if you only get 1 answer, right? There is a theorem to this, but we're not going to talk about that theorem for a while. But there we go. Really no different from quadratics. It was factor and set each factor equal to 0. And the only difference is the factoring was a little different and we had 3 answers instead of 2. So factoring, just factor the thing, right? So x to the fourth equals 9x squared. Same thing. Let's get everything to one side. So let's subtract 9x squared on both sides. All right, well, these two things have x squared in common. So let's factor out x squared. Then x squared minus 9, we can make that x plus 3x minus 3, difference of squares. And now we again have 3 things that are multiplied to 0. So let's set each one equal to 0. Well, x squared equals 0. The only location where that is 0 is 0. X plus 3, let's subtract 3 on both sides. X minus 3, let's add 3 to both sides. And we again get 3 answers. So last one was x cubed. We had 3 answers. This one is x to the fourth. We have 3 answers. So like I said, don't look for patterns right now. We'll talk about what that pattern is in quite a while. It's several videos. We have an entire chapter 2 to get through. Okay, but what I want to make sure is that you don't do this. What you are very tempted to do is that you just divide both sides by x squared. Oh, right, we can divide numbers. We can divide x squareds. So you divide x squared on both sides and x squared cancels out. X to the fourth over x squared is just x squared. And then you take the square root of both sides. You get plus and minus square root of 9, which would give us x equals plus and minus 3. But here's the problem. The answer we had on the previous slide had 3 answers. For the exact same problem, one of them was 0. But when you take the square root of both sides like we just did, you only got 2 answers. So there's a larger issue at play here, where if you divide by x squared, what you're essentially allowing is that you divide by 0, right? X equals 0 is an answer. Well, if x is 0, then you just divided by 0 squared. And at no point in this class, and no point in almost any class, will you ever really broach the topic of dividing by 0 in a meaningful way. We know that anything divided by 0 is undefined. So don't divide by variables, only divide by numbers. Okay, so again, factoring, always go for factoring. Do not try and divide by variables or x's. Okay, so factoring, there's really not a whole lot to say there, right? If you can factor it, you can do it. But let's get into all other different types of equations, things that we have worked with before, but maybe not necessarily have solved before. Okay, so let's do some rational equations. And rational equations, well, rational numbers are numbers that are fractions. Rational equations are just equations that are fractions. So we have 1 over 6 plus 1 over x plus 1 equals 1 over x. And what we're going to do, the method to solve rational equations is to multiply everything by the least common denominator. We spent a lot of time in P5 talking about least common denominators. You know how to do it with numbers, and we talked about how to do it with variable terms. So let's multiply everything by the least common denominator. In our case, let's look at all the denominators we have. 6, x plus 1, and x. Well, I know x plus 1 and x look a lot alike, but as factors, they don't have anything in common, right? If x is 2, then this is 2, and this is 3. So 2 and 3 don't have anything in common. So instead, multiply everything by the LCD. Our LCD would be 6 times x plus 1. We're going to multiply it on both sides. Now, there's kind of an issue here that is very similar to that last issue I talked about in factoring, but what we're going to get is something a little different in what we did for factoring, that very last, don't do this example. What we got in that case is you lost answers, but maybe we get something a little different here. So let's distribute this least common denominator to each and every numerator, right? This is like an imaginary 6x, x plus 1 over 1, and then it just becomes fraction multiplication. 6x, x plus 1 times 1, 6x, x plus 1 times 1, 6x times x plus 1 times 1. And now what you probably see is that some things cancel out. How nice. 6 cancels out here. X plus 1, the whole factor cancels out here. And x, that cancels out here. Oh, that's really, really nice. Cool. Alrighty. From here, we can distribute x. We can distribute 6. We can combine x and 6x. If you have 1 apple and I give you 6 more, you now have 7 apples. Let's bring 6x plus 6 to the other side. Let's get everything to one side. So let's subtract 6x and 6 on both sides. Well, 6x minus 6x, that goes away. 6 minus 6, that goes away too. That's the whole point. But here, you have 7 apples, and then I take 6 more of them away. Now you're back to 1 apple, and now we're here. And wow, look at that. We have a nice, very pretty, factorable equation. So we factor x squared plus x minus 6 to x plus 3x minus 2. Again, go back to the P4 video if you want to see practice on how to factor. And now set each one equal to 0, and we get x equals -3 and x equals 2. So 2 answers. Okay, nothing weird happened in that question, but I already told you that something weird still might happen. Let's see. All right, 1 over x minus 1 over 5x plus 10 equals 1 over 5. Well, before we try and determine what the least common denominator is, I've been preaching factoring for so long. Let's factor this middle term. We can pull out a 5. Okay, well, now we're still going to multiply by the LCD, but notice that we don't need to multiply by 5 twice, right? This 5 is here, this 5 is here. Okay, we got to multiply by a 5 to everything, multiply by an x, multiply by an x plus 2. So you could have multiplied by x times 5x plus 10 times 5. Your numbers would be just a little bit bigger, maybe a little bit weirder to deal with toward the end. So again, factoring saved us from needing to multiply by an extra 5. Okay, well, put all this into the numerators. And now I didn't really stress it in the last example, but notice something. The reason we multiply everything by the LCD is so that we get rid of the fractions. In general, fractions, scary. We don't like dealing with fractions. So what is instead quite nice is by multiplying everything by the LCD, all the fractions go away. And that's the benefit to multiplying everything by the LCD. So here, x is going to cancel out. Here, x plus 2 and 5 is going to cancel out. And in the last one, 5 is going to cancel out. So again, the method of multiply everything by the LCD is very nice because it gets rid of all the fractions. The less fractions we need to deal with, definitely the better. All right, let's distribute a 5. Let's distribute an x. 5x minus x is 4x. And let's bring everything to the right-hand side. So let's subtract 4x on both sides. Let's subtract 10 on both sides. 2x minus 4x. You have $2 and you spend $4. You are now $2 in debt. And this doesn't factor, but you know what? Why not? Let's do some more quadratic formula practice. A, if this is ax squared plus bx plus c, a is 1, b is -2, and c is -10. Quadratic formula looks like this bad guy right here. And let's plug in everything we know. B is -2, B is -2, A is 1, C is -10, and A is 1. Alrighty. -2 is +2. -2 squared is +4. -4 times 1 times -10 is +40. 4 plus 40 is 44. We can rewrite square root of 44 as square root of 4 times 11. Square root of 4 is 2. And now we can divide both of these by 2. We can, in a sense, distribute the parts of the numerator with the denominator. So 2 over 2 is 1. 2 squared 11 over 2 is 2 squared of 11 over 2. And, I wanted to do this just to make sure that you don't try and cancel out just one of these 2's. Don't forget, we can only cancel things out when everything is multiplied or divided. So, just very briefly going back to what we had here, we were able to cancel out x because it was 5 times x times the factor x plus 2. That's why we could factor out x. 5 times x plus 2. 5 times x plus 2. That's why things can cancel out. So there is a little bit of a reason why we are able to do these things. So again, don't just try and cancel out one of the 2's. You're dividing both of them by 2 because we got this plus and minus up here. Well, 2 divided by 2 is 1. 2 divided by 2 is also 1. And we're left with just square root of 11. Okay, so maybe still nothing weird. I might have misremembered when the weird things happen, but I swear they do happen. Maybe I think it happens in this one. So far, nothing really weird, right? We got answers that worked out nicely. You should be checking the answers on your own. I don't want to spend time just plugging in answers unless there's a problem to show you something new. So let's do it again here. All right, we're going to multiply everything by the LCD, but instead of trying to multiply everything by x minus 1 times x plus 3 times x squared plus 2x minus 3, well, it's really nice that we could factor and see that, oh, look at that. This has an x plus 3. This has an x plus 3. This has an x minus 1. This has an x minus 1. Multiply everything by x plus 3, x minus 1. Okay. All right. Well, here again, let's distribute all of these to numerators. So x plus 3x minus 1 times 1, x plus 3 times x minus 1 times x this time, x plus 3x minus 1 times 4. And now you see things cancel out. X minus 1 goes away. X plus 3 goes away. X plus 3 and x minus 1 goes away. And now we're back to just a regular equation. If you multiply everything by the LCD and things don't cancel out, you might have done something wrong. You might have chose the wrong least common denominator. So either 1, you don't do it right the first time, you accidentally make a mistake. Or 2, you didn't multiply by enough. And all you would need to do is just multiply by a little bit more. You can do it in 2 steps. That's fine. Just make sure that if you are multiplying and canceling things out, you're doing that part correctly. Okay, now that we're back to a regular equation, let's distribute this x. Then let's combine some like terms. X minus x. Oh, well, that just goes away. We can subtract 4 on both sides to get 0 on one side, right? We like having 0 on one side. X squared minus 1 factors to x plus 1, x minus 1, and we set each factor equal to 0. And I think we're pretty okay on that part. So we have 2 answers, right? Everything we've been doing so far, we've had 2 answers for rational equations. That is, to an extent, a coincidence for the types of rational equations we're looking at. But yeah, both are answers, right? We haven't had any problems so far. But very large BUT. Okay. Well, if you don't see it right away, let's go in and check our answers. Well, I'm going to let you check x minus 1 on your own, but let's check x equals 1 together. When we plug in x equals 1 back into our equation, we plug x equals 1 here, 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 and here. And what you see is 1 minus 1 and 1 minus 1. Well, 1 minus 1 is 0. 1 minus 1 is 0. 0 times anything is 0. So we have 2 of our 3 fractions that when we plug in x equals 1, we get something that is undefined. And that is not allowed. So going back to what I mentioned way back in the beginning of the section is that we sometimes get these things called extraneous solutions. That we've been doing this algebraic method of multiplying everything by the LCD. But when we did that, even though it worked 2 of the times, this third time that we did it, we got answers that didn't work out nicely. Or not, I wouldn't say didn't work out nicely, but they caused problems. They're not in the original equation's domain. We've kind of brushed domain so far. We're going to talk more about domain in 2.4, but look at the original denominators. You were never allowed to have 1 here. You were never allowed to have -3 here. So make sure when you check your answers that you don't run into problems like this, where 1 over 0 is literally undefined. 4 over 0 is undefined. X was never able to be equal to 1. X was never able to be equal to 1 to begin with. So x equals 1 is extraneous. It doesn't count. The only solution is x equals -1. So for the first time here in chapter 1, it is justified that I say, check your answers. You should be checking your answers for everything just to see if you get answers that make sense. Or just to make sure your answers are right, I should say. But, we run into very bigger problems sometimes, especially here in 1.5. So even though we got 2 solutions algebraically, only one of them is true when you go back to plug it in. Okay, let's do another one like that. X over x minus 1 minus 1 over x plus 1 equals 2x over x squared minus 1. All right, rhyme and reason. Let's factor, and you see the least common denominator is just the combination x plus 1, x minus 1. Everything that we would need to cancel out every denominator. All right, let's distribute x plus 1, x minus 1 to each numerator. And now what you see is a bunch of things cancel out. X minus 1 goes away, x plus 1 goes away, x plus 1 and x minus 1 goes away. Now we're back to a normal equation. Let's distribute x. Let's distribute a -1. X minus x goes away. Let's subtract 2x on both sides. And now we get something that factors to x minus 1, set each one equal to 0. Oh, and we actually only get one solution this time. And that's just a quirk of what the question was. But it's possible. It's possible you get an answer that happens twice. There's nothing wrong with that. It just means there's only one answer, just like it happened in 1.3 sometimes. But okay, and maybe you see what's going to happen next. Let's check x equals 1. And we actually run into the exact same problem that we had before. When we plug in 1, 1 minus 1 is 0, and 1 squared minus 1 is also going to be 0. Oh, look at that. X equals 1 is extraneous. That's a problem. But one thing that's weird here is that in the last question when we had an extraneous solution, we had 2 answers, and one of them was extraneous, so the other one was the answer. But here, we have x equals 1 is our only solution, and our only solution is extraneous. Well, that just means there's no solution. So if your only potential answer doesn't work, that's okay. It doesn't mean that it's the only answer. It has to work. No, it's possible that there is no solution to the equation. And that's very much okay. So don't be afraid to say that all of your solutions are wrong. I mean, if all of your solutions are wrong because you've got the wrong possible solutions, that's one thing. But it is entirely possible that there just is no solution to an equation. Okay, we carry on. So that was rational equations. And what we're going to talk about next are radical equations, or, totally radical equations. Don't laugh at that. That wasn't funny. But radical equations are, you guessed it, equations that have radical signs. That's it. Okay, here's what I want you to think about. When we are doing regular, polynomial equations, like quadratic equations, we talked about how if we have x squared equals a number, we can take the square root of both sides. Well, that means that x to the 2, the way we undo x to the 2 is to take the square root of both sides. Okay, well, if we have x cubed, the way to undo x cubed would be cube root of both sides. Well, how do you then undo square root or cube root or fourth root or fifth root? Well, you guessed it. The way we undo roots are by raising both sides to that power. That's it. All right, so all we need to do is raise both sides to the third power. Same way as square root cancels out x squared, kind of, right? There's some quirks there, but same way that same way that square root cancels out squared is the exact same way that cubing both sides cancels out cubed. All right, well, so cube root and 3 go away. We're left with just the inside. 3 to the 3 is 27. And now we're just back to a linear equation. Subtract 6, divide by -3, and we get x equals -7. Nice. That's it. All right, well, what if we have cube root of -3x plus x equals -3? Well, is it a problem that we got a negative on one side? I don't know. Let's see what happens. Well, we cube both sides again. Inside is just -3x plus 6. Right side, we now get -27. And we subtract 6 again, and we divide by -3, and we get 11. Oh, there's nothing wrong with there. Don't forget, way back in P6, in P6, we said cube roots, odd roots, can produce negative numbers, right? Cube root of negative 27 is negative 3. The problem arose when we were doing even roots. For example, square roots were never equal to negative numbers. Fourth roots were never equal to negative numbers. So it is a little different depending on the root. If your root is odd, it's okay that you have negative numbers on one side. There's nothing wrong with that. But maybe something is weird when we have even roots. Let's think about that. All right, so we have fourth root this time. Does that mean we completely changed how we solve this problem? No. So last one, we had cube root. We raised both sides to the fourth power. Guess what? We're just going to, last question was cube root. We raised both sides to the third power. This one's fourth root. We're just going to raise both sides to the fourth power. Again, fourth root and to the fourth cancel each other out. Negative 3x plus 6 equals 3 to the fourth, which is 81. Subtract 6 on both sides. Divide negative 3, and you get negative 25. Absolutely nothing wrong there. Well, let's try and do the exact same thing, but with fourth root of negative 3x plus 6 equals negative 3. And you notice that the slide doesn't have as much info on it because, this is all the way right here. But there's no solution because even roots can't produce negative numbers. You can absolutely try and solve this. What you would get is the exact same solution as before, right? If you try and did everything, but this is negative 3, well, negative 3 to the fourth is also positive 81. So you do all this work, you would get x equals negative 25. But when you plug negative 25 into here, negative 3 times negative 25 is 75, positive 75. Positive 75 plus 6 is 81. Fourth root of 81 is positive 3, but we're saying it's equal to negative 3. However, we can treat it far easier and just say that even roots can't produce negative numbers. Done. That's it. Okay, let's keep going. Fifth root, well, I think you guys get the idea, right? We can mix and match, what we put inside the root and what we put on the outside. But the idea is it doesn't, all the steps are still going to be the same. Only thing that changes is that we raise both sides to the fifth power instead. But from here, again, it is really no different. So again, I'm keeping the inside consistent. I'm keeping the outside mostly consistent. I'm just trying to show that depending on the root, that's all we're going to raise both sides to. Nothing too fancy or too weird. Okay, well, what if we let one side be just a variable? Okay, let's see what happens. Here we have x equals square root of 6x minus x cubed. Here we have square root. So how we undo square root is by squaring both sides. Well, x squared is just x squared. Square root and squared cancel each other out. All right, well, this is just a linear equation. Or not a linear, a regular equation. Let's bring everything to one side. I'm going to bring everything to the left. If you want to bring everything to the right, that is not wrong. You'll get the exact same answers. Let's subtract 6x and add x cubed on both sides. So here, we're a little jumbled. Let's just rewrite terms in order. And now, let's see what happens. Here, we can factor out an x. And, this is also nice, easy, and factorable. And now we're just back to an equation with 3 factors. Set x equal to 0, set x plus 3 equal to 0, set x minus 2 equal to 0. Well, x equals 0, no work to do there. Here we can subtract 3. Here we can add 2. And we get 3 answers. So we're done, right? 3 answers. No big deal. We haven't run into any problems with checking answers before, have we? Maybe we should check our work. You can take a second and think about which one might be the problem. But let's try negative 3. Well, we plug in negative 3 and, we get a square root. We get an even root equals a negative number. Square roots can't produce negative numbers. Even roots can't produce negative numbers. So negative 3 doesn't work, even if you wanted to. 6 times negative 3 is negative 18. Negative 3 cubed is negative 27. Negative 18 minus negative 27 would be negative 18 plus 27. And negative 18 plus 27 is 9. Square root of 9 is not negative 3. So our only answers are x equals 2 and x equals 0. So, you might not always need to plug in everything, but the second that you run into problems that very generally, have like domain issues, right? Like square roots can't produce negative numbers. Cube roots different. But for example, here, we get right away that we can't have a negative outside a square root like that, or equal to a square root, I should say. And like for the other ones for rationals, we couldn't have 0 in the denominator. So just look out for things like that. Beyond just, does my answer, when I plug it in, does it actually work, numerically? All right, well, here, let's do it again, but we have negative x equals square root of 6x minus x squared. So right away you say, negative x, square roots can't produce negative numbers. So we're done, right? Let's see. Let's square both sides, right? This is square root, so let's square both sides. Negative x squared would be positive x squared. Square root and x squared cancel out. All right, well, let's see what happens. Let's bring everything to the left-hand side. I'm going to add x squared and subtract 6x again. Well, here we get x squared plus x squared, that is 2x squared. 2x squared minus 6x equals 0. We can factor out a 2x. This is now 2 separate factors multiplied to 0. We can divide 2, add 3, and we get 2 answers. And let's see what happens. Well, if we plug in 3 again, would you look at that? We're left with a negative 3 equals square root of some answer. Also, I don't know why these are cubed. These should be squared. That's a mistake, but it doesn't change the problem at all. Square root still can produce negative numbers, so we don't run into an issue. Well, we run into an issue, but it's an issue we can easily pick up. When you plug in 3, we get no solution, but notice that 0 is totally okay. So don't be afraid of having negative variables on one side, right? Negative numbers, there's nothing you can do about that. Either it's positive or it's negative on the outside, but when it's variables, we have to treat it a little differently. So just be on the lookout for that. All right, let's do x equals cube root of 6x minus x cubed. Well, this is cube root, so let's cube both sides. X cubed equals 6x minus x cubed. Well, we can bring everything to one side. I'm going to bring it all to the left-hand side. Only difference here is that we now have 2x cubed. Well, we can still factor out a 2x, and we get x squared minus 3 on the inside. Well, let's set each one equal to 0. Here, we're just going to divide by 2, no big deal. But here, let's add 3 to both sides. Let's take the square root of both sides. But don't forget, when we take square roots of both sides, we get plus and minus square root of that answer. So we get 3 answers. Go back and check them on your own, but there are not any issues here. Okay, finally, we get one that all of them work out. So, okay, let's do another one. Why not? I don't remember how many solutions there are or how many questions there are. That's fine. Same thing. We got negative x on the outside, cube root. Let's raise both sides to the third power. But here, negative x cubed would be negative x cubed. Let's again bring everything to one side, but I'm just going to add x cubed this time. I'm not going to bring everything. Let's just add x cubed to both sides. And we did that because, oh, look at that. That's just going to go away. That's pretty nice. Oh, and we only get one answer this time. Just dividing 6 on both sides will give us x equals 0. So that's an interesting problem. Okay, kind of weird. That's fine. So lots of different examples. But what happens as soon as we have something like this? And what I mean by this is we got a square root and then an extra plus 1 on the outside. Well, one thing I want to stress is this. Every single problem we've done so far has been just that root on one side by itself. And you can immediately jump to squaring or cubing or to the fourth of both sides. But the second that the square root or whatever radical is not on its own, you need to get it on its own. You cannot square both sides when it is like this, because if you were to square this, this is a plus b squared, and that would be something you need to FOIL. And it wouldn't even get the square root out of there if you had to FOIL. So please be careful. When you are dealing with radical equations, make sure the radical is by itself. So all we're going to do here is subtract 1 on both sides. And now we can square both sides to get rid of the square root, but notice this. This isn't just a plain number. This isn't just a single variable. X minus 1 squared is x minus 1 times x minus 1. This requires FOILing. So very different from when there's only one thing on one side. Only one thing on one side, you raise it to the third power or whatever, and you're done. But that's not what happens here. This requires us to FOIL. X squared minus x minus another x minus 1 times negative 1 is plus 1. Let's combine like terms. And now we can solve it like, a regular single equation, but we had to make sure that we did that FOILing part. So please don't forget rules of algebra. Don't forget rules of multiplying polynomials that we did all the way in P3. If you forget stuff like that, you're going to be in trouble. Let's bring everything to one side. Let's subtract 2x. Let's subtract 1. All right. After we combine, 1 and negative 1 goes away. Negative 2x and negative 2x becomes negative 4x. And now from here, factor out x, set each one equal to 0. We get 2 solutions. All right. Well, what would this problem be without an extraneous solution? Which one do you want to plug in? I don't know. Let's plug in 0. Let's try what happens when we plug in 0. Well, 2 times 0 is 0. 0 plus 1 is 1. Square root of 1 is 1. And then 1 plus 1 is 2. 2 doesn't equal 0. So this is actually an even different type of problem, and a problem that you might run into more if you just get the wrong possible answers. So beyond just, we can't have square roots of negative numbers, and square roots can't produce negative numbers, and we can't have zeros in the denominator, it's possible you get one that just doesn't work out nicely for this type of reason, where when you plug it in, both sides literally just do not equal each other. And that is totally okay. There is nothing wrong with that. So x equals 4 is our only solution, because plugging in x equals 0 does not work for us. All right, well, kind of similar. Here we have square root of 5x squared minus 10x plus 9 with minus 2x plus 1 on the outside. Same thing. We need to get the root by itself. So let's add 2x to both sides. Let's subtract 1. And now we can square both sides. But this is, again, FOILing. It is not just say 2x squared minus 1 squared. No. This is 2x minus 1 times 2x minus 1. So let's FOIL that. 2x times 2x is 4x squared. 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x. Negative 1 times negative 1 is positive 1. Negative 2x minus 2x is negative 4x. All right, lots of adding and subtracting on both sides. Let's subtract 4x on both sides, add 4x, subtract 1. All right, 5x squared minus 4x, 1x squared. Negative 10x plus 4x, negative 6x. 9 minus 1 is 8. Oh, that actually worked out pretty nicely. It's almost like this is a presentation problem. Factor, set each one equal to 0, solve each one, and we get 2 answers. And I think both of them work out. Yeah, how about that? All right, one more crazy example. You're not going to see one like this all that often. But what if we have 2 roots? Oh no, the world is going to end, it seems. Don't worry. When you have multiple roots, what our goal is here is to get one root by itself first, and then we're just going to need to do the process twice. So here's what I mean. Let's add square root of x minus 1 to both sides so that square root of 2x minus 1 is by itself. Well, what we're going to do is square both sides to get rid of this root. It's not going to get rid of this root, but that's okay. All it means is we're just going to need to do this twice. So let's square both sides. And again, this square root and squared goes away, but 1 plus square root of x minus 1 is foiling. So that square root cancels out. And now let's FOIL. 1 times 1 is 1. 1 times square root of x minus 1 is square root of x minus 1. Square root of x minus 1 times 1, square root of x minus 1. Square root of x minus 1 times square root of x minus 1. Oh, square root of anything times itself is just itself. Square root of x minus 1 plus itself is going to be two of them, right? If we're multiplying them, square root of x minus 1 times square root of x minus 1, it's just itself. But when we are adding, it is two of them. Be very careful. All right, so lots of simplification we can do here. 1 minus 1 goes away. Let's bring this plus x to the left-hand side. Let's subtract it on both sides. 2x minus x is just x. And now the root is mostly all by itself. What you can do is you can divide by 2 and then square. But what you'll see is when everything is multiplied together, it's actually okay for us to square it, right? Because if this was 2 plus square root of x minus 1, well, then we would need to FOIL. But 2 times square root of x minus 1 is just 2 squared, which is 4. Square root of x minus 1 squared is just x minus 1. Here, we got a FOIL on the left-hand side. X times x is x squared. X times negative 1, negative x. Negative 1 times x, negative x. Negative 1 times negative 1, positive 1. And distribute 4. All right. Combine like terms on the left. Negative x minus x, negative 2x. Let's subtract 4x on both sides. Let's add 4 to both sides. Negative 2x minus 4x, negative 6x. 1 plus 4 is 5. Factor, set each one equal to 0. And we get 2 answers. So radical equations, not so totally radical as I had in the beginning. They can get kind of messy, but they end up kind of all being similar situations. All right, let's get out of radical equations and let's start talking about something a little different. Okay, so let's talk about rational exponents. Now, rational exponents are just fraction exponents, right? Rational equations, fraction equations. Rational exponents was the end of P6 where we had a fraction in our exponent. So let's say we had something like 3 over 2 as an exponent. Well, in 3 over 2, what that's saying is square root of something, the denominator is 2, square root, but then the numerator was 3, so that's cubing. So basically, numerator is what we're actually doing to the thing. Denominator is what kind of root are we taking. And we're going to use a lot of that today, or in this subsection. So say we have some expression, u to the a over b equals c. Well, kind of think about this. When we were doing square roots, we squared both sides. And when we're doing squared, we square root both sides. And we know square root is like 1/2. So what we're going to do is something very similar, except instead of trying to think about it in terms of roots and cubes and all that, what we're going to do is just raise both sides to the reciprocal power. However, we need to keep something in mind, that if we raise both sides to the reciprocal, what the value of a is matters. Because think about this. If this is 3 over 2, we're raising both sides to the 2 over 3. When we raise both sides to the 2 over 3, that's saying take the cube root and then square it. But if this is 2 over 3 and we raise both sides to the 3 over 2, that's like saying take the square root of both sides and then cube it. But remember what happens when we take square roots of both sides. So what this ultimately boils down to is this. All right, so if this original numerator is odd, nothing weird happens. You raise both sides to the reciprocal power, so you raise both sides to the b over a. That gets rid of it for u, just like square roots and squared, it just gets rid of that. But on the other side, you get c, whatever that constant is, to the b over a. And I've already told you that to the b over a is basically saying 8th root raised to the b. But if a is even, well, we pick up an extra plus and minus. Again, if this original numerator is even, let's say 2, that means that when we raise both sides, the 2 ends up in the denominator, but that is like taking a square root. So, again, long story short, if original numerator is odd, nothing weird happens. If original numerator is even, pick up a plus and minus. So you could take these two things as a rule. If a is odd, raise both sides to the reciprocal, and then do, denominator, new denominator, raised to new numerator, and same thing here, but when it's even, plus and minus. All right, hey, that's kind of wordy, kind of complicated. Let's do a bunch of examples. X to the 3 over 5 equals 8. So what we're going to do is raise both sides to the reciprocal power. Well, this is 3 over 5, so we're going to raise both sides to the 5 over 3. Okay, but now what we need to look at is this original numerator of our exponent. If the original numerator is even, we pick up a plus and minus. But if the original numerator is odd, nothing happens. So original numerator even, plus and minus. Otherwise, no. Okay, well, this original numerator is 3, and 3 is odd. So we do not pick up a plus and minus, but we still raise both sides to the 5 over 3. Okay, Well, that's so far the new part, but it's been a while since we talked about rational exponents, so let's look at this a little bit more. 3/5 and 5/3, well, that cancels out. That's the whole point. But what this says is 8 to the 1/3 to the 5, right? Exponent raised to an exponent. We could multiply those exponents to get back to 5/3, but this is like to the 1/3 and then to the 5. Well, to the 1/3 means cube root. Cube root of 8 is 2. 2 to the 5th is 32. So denominator root, numerator power. So this says cube root and then raise it to the 5th. Cube root of 8 is 2. 2 to the 5th is 32. Okay, well, let's do more examples of this. Another thing I want to stress is that, if your rational exponent part is not by itself, get it by itself, just like other things we've done before. In a lot of cases, these things that we want to apply, they need to be by themselves on one side for us to be able to do that. So let's add 30 to both sides. Let's divide both sides by 2. And now we can finally, do the rational exponent step. This is to the 3/2, so we're going to raise both sides to the 2/3. And again, this original numerator, this 3 up here, can I highlight just that? I did it before. Okay, the original numerator was 3. 3 is odd. Nothing weird happens when it is odd. Okay, so we're going to raise both sides to the 2/3. So the 2/3 says cube root first, and then squared. So cube root of 27 is 3, and 3 squared is 9. Oh, but don't forget, the thing that had the rational exponent wasn't just x, and that's okay. So 2x minus 1 equals 9. You know how to add 1 to both sides. You know how to divide both sides by 2, and you get x equals 5. Okay, well, let's start doing things where things actually start to happen and things that are weird. Well, here, you already see we're going to raise both sides to the 3/2. However, this original exponent's numerator is even now, right? Previous two cases, let me go back to them really quick. Here, this is 3/2. Numerator was odd. Nothing weird happened. No plus or minus happened when this was odd. But for the first time, we have an example where this numerator is even. If the original numerator is even, we pick up a plus and minus. Again, when we raise both sides to the 3/2, this is like saying, take the square root of both sides and then cube it. And we remember from 1.3 that when we are taking the square root of both sides, we pick up a plus and minus. All right, so 4 to the 3/2 says take the square root first. Square root of 4 is 2. 2 cubed is 8. And now we just get two equations. 3x minus 1 equals positive 8. 3x minus 1 equals negative 8. Add 1 to both sides. Divide both sides by 3. And we get two solutions. Okay, so a little messy, but really not all that much of an extra step. I mean, yes, it created two separate problems for us at the end, but I think by now, solving equations like this, we absolutely love. So again, it all comes down to the original exponent. So here, we got to get 2x plus 1 to the 4/3 by itself. Let's add 7 to both sides. And now we're going to raise both sides to the reciprocal of 4/3. That would be 3/4. But this original numerator is even. So if it is even, we pick up plus and minus. So 16 to the 3/4. Okay, 16 to the 3/4 says take the 4th root and then cube it. So 16 to the 1/4, 4th root of 16. 4th root of 16 is 2. 2 cubed is 8. And now we again have two equations. 2x plus 1 equals positive 8. 2x plus 1 equals negative 8. Subtract 1 and divide by 2. And we get two answers. So again, one more time. Original numerator odd, no plus and minus. Original numerator even, yes, plus and minus. All right, let's do two more examples. 5x minus 14 equals 3/800. We're going to raise both sides to the 800/3. However, original numerator is odd, no plus and minus. So we raise both sides to the 800/3. Well, very convenient. 1 raised to any power is just 1. You add 14, you divide by 5. How beautiful. But if the original numerator is even, 800, we pick up plus and minus. But still, 1 raised to any power is just 1. So just two separate equations. Add 14 to both sides. Divide both sides by 5. And you get two solutions. So that's rational exponents. Not really much else we can do with them right now. And maybe we come back to those in a little while. But one more small part, quadratic likes. The thing with quadratic likes is kind of interesting because you will see stuff like this in the future. It's just kind of annoying. You're going to see why in just a second. It requires a very well-seasoned mind to recognize some of these things. I don't think any of these are so obvious that you're going to look at it and be like, oh, yeah, I see it right away. So just getting in the habit of noticing these type of things is definitely the key to doing quadratic likes. But again, you're going to find all sorts of stuff like this. So just keep an eye out for them. So for example, let's say we have x to the 2/3 minus 5x to the 1/3 plus 6. Well, here we have an x to the 2/3, and this is like x to the 2 minus 5x to the 1 plus 6. Only weird thing is that we have these extra, 2/3 and 1/3. Well, what if we rewrote x to the 2/3 as x to the 1/3 squared? Well, now this is like something squared minus 5 times something plus 6. It's quadratic like x squared minus 5x plus 6. Only thing is that our variable isn't x, it's x to the 1/3. Well, we don't want to just magically substitute x in because that kind of screws up what we're looking at. Instead, let's say x to the 1/3 is u. We like using u to substitute things a lot of the time. If you end up taking Calc 2, you might even come back to u substitution, but that's a long time from now. All right, so wherever we see x to the 1/3, let's instead call it u. All right, well, x to the 1/3 would be u squared minus 5 times u plus 6 equals 0. Oh, well, if I gave you this, you would know to factor, you would know to set each factor equal to 0. But here's the thing. We're saying that u equals 2 and u equals 3, but we're not solving equations that are u. We're solving an equation that had x in the beginning. So we substituted u in for x. However, we're not solving a u equation. We need to resubstitute whatever we substituted in as u. Well, I have it here that u is x to the 1/3. So this isn't u equals 2. This is x to the 1/3 equals 2. This isn't u equals 3. This is really x to the 1/3 equals 3. Now, from here, you know how to solve these equations from the last step. We'll just cube both sides, and we get 8 and 27. And those are our two answers. So quadratic likes just introduce this one like kind of intermediate process of just saying, let's solve an equation that looks very similar, and then just resubstitute in the thing we initially substituted. And that's essentially what quadratic likes are. Okay, this video is probably very long. I don't want to go super crazy into doing this, but here you might also notice something squared minus 6 times something plus 8. Well, u, if we say is x plus 1 over x, well then this is like u squared minus 6u plus 8. And you know how to factor this. You know how to set each factor equal to 0. So we have u equals 2 and 4. But if u is x plus 1 over x, what we're really going to get is x plus 1 over x equals 2, x plus 1 over x equals 4. All right. Something like this is way crazy. It's more just, to show you the process. From here, to solve each specific part, you would multiply everything by the least common denominator x. X squared plus 1 equals 2x, subtract 2x, factor, set each factor equal to 0, you get 1. But for the other one, this is not nearly as pretty. You do the same thing, and now you have to do quadratic formula. So if you want to watch the whole thing, feel free to slow it down. But essentially, we had 2 separate branched equations, and then we got 3 separate total answers. So just something to keep in mind. Again, you can slow down the video to watch all those steps, but once we've set up each specific part, they become equations that we've already talked about. So that's the end of 1.5. Kind of long, kind of showcase. 1.6 and 1.7 are not nearly as long. What we've done in 1.1 to 1.5 has been equations. We're going to learn to solve inequalities in the next section, and then 1.7 is a nice way of going out. We're just going to introduce absolute values to equations and inequalities. So that's the end of 1.5, and I will see you in 1.6. Bye. Hi, everyone. Welcome back to 1.6. So chapter 1 in general is about solving equations. However, we do kind of change gears to the last 2 sections and start to solve inequalities. So the whole chapter is technically solving equations and inequalities, except the first 5 sections has been solving equations. So we can solve inequalities now. And the only thing is that we have a slightly different way of referencing our answer, but the way we solve inequalities is almost identical to how we solve equations. So here in 1.6, we're just going to start solving inequalities. And then when we get to 1.7, it's just a little bit different. We just introduce some new properties that revolve around absolute value. But for now, let's talk about inequalities. So inequalities in general are expressions that describe the relationship between any 2 numbers. But what we're going to do here is have an expression that describes the relationship between a variable and some number. So previously we had x equals a finite set of disjoint numbers, right? Like the very last example in 1.5 said our answer was 2, 1 plus square root of 3 and 1 minus square root of 3, something like that. 3 values that are all very different. And even if we didn't get weird answers like -3, 0, and 2, they're still disjoint. However, what we're going to have for inequalities is a solution set. And a set is just a set of values that make the inequality true. Now, you can say that equations also have a solution set. Only difference is now our solution set is going to be this nice, smoother set of continuous values. So it's a lot easier to satisfy an inequality than an equation. In an equation, we are forcing things to be equal to each other. But now in inequalities, we're just saying, well, one side can be bigger or one side can be greater than or equal to. So we have a little bit more leniency when it comes to that. It just means we're going to need to write our answer in such a way. So we also have 3 different types of inequalities that are all very, very similar to equations that we had in 1.1. In 1.1, we had conditional equations, inconsistent equations, and identities. And the same thing is true here for inequalities. An inconsistent inequality is just any inequality that is never true. An identity inequality is just any inequality that is always true. And conditional inequality is just any inequality that has one particular set of answers. So we use all these words for equations. We can talk about them in terms of inequalities. But again, not really worried about you naming them, more interested in you being able to actually do something with them. So solving inequalities, like I said, is a lot like solving equations, except we have one added rule, only one. That added rule, aside from, writing our answer different, the rule itself, the only difference is that when we are multiplying or dividing by negative numbers, we need to flip the sign of our inequality. So let's talk about that. If you are doing anything in your inequality, it is functioning exactly like solving equations. However, in the very specific scenario that you have to multiply or divide by a negative number, you have to flip the inequality sign. Less than would become greater than would become less than, and so on for the greater than or equal to, less than or equal to. That's the only added rule when it comes to inequalities. So let's just get into doing examples. 2x plus 5 is greater than 3. And again, we solve these exactly like we solved equations. If this was an equation, you would subtract 5 on both sides, you would divide both sides by 2, but again, we got to be very careful when we're multiplying and dividing numbers. In this specific case, we are dividing by positive 2. When we divide by positive 2, we do not change the sign. Okay, well, negative 2 divided by 2 is just negative 1. Now, again, only added step, not an added rule, the added step to solving inequalities is that we need to write this as an interval. So we have been doing that all the way since P1. So x is greater than negative 1 says negative 1 and everything bigger than it. Specifically for just greater than, we're going to use parentheses. Don't forget that if it was greater than or equal to, we would use a bracket. So, and also parentheses for infinity and negative infinity. Infinity will never have a bracket. Negative infinity will never have a bracket. So just keep an eye out for stuff like that. And again, if you need inequality help, go back and check out the P1 presentation. Okay, 8 minus 3x is greater than or equal to 2. Again, if this was an equation, you would start by subtracting 8 on both sides, and then you would divide by negative 3. Except, however, we have the added rule that if we are dividing by negative 3, we have to flip the sign from greater than or equal to less than or equal to. And then from here, okay, negative 6 divided by negative 3 is positive 2. X is less than or equal to 2 says everything to the left of 2, and 2 included because of the less than or equal to. So negative infinity up to 2. Okay, let's keep going. 7x minus 11 greater than or equal to 2 times x minus 3. If it was an equation, you would distribute 2. You would subtract 2x on both sides. You would add 11 to both sides. You would divide both sides by positive 5. And if we are dividing or multiplying by positive numbers, nothing changes. It only changes for negative numbers. So we get x is greater than or equal to 1. X is greater than or equal to 1 says everything bigger than 1 with 1 included. So from 1 to infinity. Okay. 7 minus 2x is less than negative 3. All right. Again, if it was an equation, you would start by subtracting 7. You would then divide by negative 2. But again, that's the key here. We're dividing by negative 2. So if we divide by negative 2, we have to flip the sign. Less than becomes greater than. And negative 10 divided by negative 2 is positive 5. X is greater than 5 says 5 and everything bigger than it. Okay, and parentheses for 5 since we have strictly greater than. Okay, 7 times x plus 2 minus 20 minus 4x is less than 3x minus 1. Okay, let's distribute 7 here. Let's distribute 3 here. And let's combine like terms. 7x minus 4x is going to be 3x. 14 minus 20 is going to be negative 6. And maybe if you have the foresight from 1.1, you already start to notice something is wrong. Well, let's combine our x's. So let's subtract 3x on both sides. Well, when we do that, it happens to go away and we're left with just negative 6 is less than negative 3. Okay, this is kind of weird. When we were dealing with equations, don't forget that when we were dealing with equations, if we got to a point that the statement was always true, 0 equals 0, 2 equals 2. When we got to a statement that was always true, that was the definition of an identity. And likewise, if we got to a statement that was never true, we call that an inconsistent equation. And same thing is true here for inequalities, except don't forget, we look at inequalities a little different from equations. So yes, if we had negative 6 equals negative 3 equals, like in equations in 1.1, we would say that was not true. But don't forget, this is an inequality. We need to determine if the inequality is true. Now, the question we ask, is negative 6 less than negative 3? Is negative 6 to the left of negative 3? And that is always true. So yes, maybe the values don't equal each other, but we're not looking for equals. We're looking for less than. And this inequality is true. If the inequality is always true, we say the solution set is all real numbers, negative infinity to infinity. No matter what we plug in for x, this inequality will always hold true. Okay, well, you can probably guess what the next one's going to be. So here, let's distribute 2. Let's distribute 5. Let's combine like terms, 2x plus 3x. 2 apples plus 3 apples is 5 apples. Negative 5 plus 3, you're $5 in debt, and I give you 3. You are now only $2 in debt. Well, let's subtract 5x on both sides. And that goes away on both sides, and we get 10 is less than negative 2. So again, it's not a matter of if these values are equal. We saw that in the last case, those values weren't equal, but we're looking for, satisfying an inequality, not satisfying an equation. And now I ask, is 10 less than negative 2? Is this inequality true? Well, 10 is definitely never less than negative 2. That's never true. So there is no solution. We would call this inconsistent. We would call the last one an identity, but it's more interesting for us to say what the solution set is. For inconsistent, more interesting for us to say no solution. Okay, so solving inequalities, I don't think all that crazy. Well, we're going to introduce another type of inequality called compound inequalities, where all it is we have multiple inequalities going on at the same time. Now, that's actually an interesting question because if we have multiple inequalities at one time, are we looking to satisfy both? Are we looking to satisfy one or the other? And that brings us to this really interesting logic question. So this is a question you would solve, not solve, you would study in the study of logic, logical mathematics. So it's the difference between and or. And there's a very big difference when we're talking about English and mathematics and likewise for or. So here's what I mean by that. If we're talking about English, if we're speaking, to each other, not in a mathematical sense, of course, because, most people don't do that. But so let's say, I'm going to my friend's house Friday and Saturday. What does that mean to you? That means that I'm going to my friend's house on Friday as well as Saturday. I am going both days. However, if I say I'm going to my friend's house Friday or Saturday, what we think is that I would go to my friend's house Friday or I will go Saturday, but I won't do both. And that's different from mathematics or. And yes, that's different from mathematics or. So English and says both need to be true. English or says that only one of them should be true. But mathematics and or works like this. Well, mathematics and functions the exact same way. If we're saying two things and, both of them need to be true for it to be a true statement. However, mathematics or doesn't say one or the other, one either or. Mathematics or says at least one of those things need to be true. So if we're thinking mathematical or to my original statement, I am going to my friend's house Friday or Saturday. Now, mathematical or would be satisfied if I am going Friday, if I'm going Saturday, or I'm going both. So mathematics or is also satisfied in the case that it is and. So if I go at least one of those 2 days, I could go Friday, I could go Saturday, or I could go both days. We say go both days is and, but mathematical or says one or the other, or both, and that would satisfy. So that's kind of complicated, right? This isn't the study of logic. This is the study of college algebra. So what we eventually bring this to is that or will be a union of intervals, right? If we're looking at two separate inequalities, we solve two separate inequalities. If we're throwing an or in between them, all we're doing is taking the union of those things, having one, having the other, union together, whereas and will be an intersection. So that's where it comes down to, but it's a good example to talk through. Let's get right into compound inequalities. So let's say we have 2x plus 7 is less than or equal to 1, or 3x minus 2 is less than 4 times x minus 1. So here's what I mean. What we do is we're looking for a set that if we plug in a value to both inequalities, at least one of them is true. So let's say, let's do the example first. So if we're doing or, we still solve each one separately. We're still going to distribute 4. We're still going to combine x's. We're still going to subtract numbers. And we're still going to divide by constants. So first one, we divide by 2. Second one, we divide by -1. But don't forget, when we divide by -1, we have to flip the sign. Okay, x is less than or equal to 3 says everything to the left of that should be a 3. Everything to the left of 3, and x is greater than 2 says everything to the right of 2. And now what or is telling us is that we are taking, this should be the -3. My apologies. This should be the -3 right here. Okay. What mathematical or is telling us is that we want to take the union of these two things. So we just take those two intervals and put a union sign between them. Basically, that's basic. There are cases where it's actually a little simpler than that. We can combine it into one, but everything to the left of -3 and everything to the right of 2 don't have anything in common. So here's what or is saying. It's saying that we can choose any value in this solution set, and at least one of these two things is true. Maybe not necessarily both of them, but at least one of them is true. So for example, if we plug in -5, well, 2 times -5 is -10, -10 plus 7 is -3, and now -3 is less than or equal to 1. So this is satisfied. Okay, well, if we plug in -5 here, 3 times -5 is -15, -15 minus 2 is -17, okay? -5 minus 1, -6. 4 times -6 is -24. I think we said -17 on this side is less than -24. Well, that wouldn't be true, but that doesn't matter. Only one of them needs to be true. At least one of them needs to be true. So when we plug in -5, this statement's true, but even though this statement isn't true, the or says one of them is true, we're good to go. Okay. And same thing if you were to plug in 3, this one would be satisfied, this one would not. However, let's say we plug in 0, a value that isn't in the solution set. If you plug in 0, 2 times 0 is 0, 0 plus 7 is 7, and 7 not less than or equal to 1. So this one wouldn't be satisfied. Well, for us to satisfy this entire mathematical statement, that must mean that this one is satisfied. Let's see. 3 times 0 is 0, 0 minus 2 is -2. 0 minus 1 is -1, 4 times -1 is -4. So is -2 less than -4? No, neither of them were satisfied, but we knew that because 0 wasn't in our solution set to begin with. Okay, let's do another or 1. 3x minus 5 is greater than or equal to 7. 5 minus 2x is greater than or equal to 1. All right, let's add a constant to both sides. Let's divide by 3 and -2. Don't forget that when we divide by -2, we have to flip that sign, and we get x is greater than or equal to 4. X is less than 2. Okay, well, those are the intervals. Everything bigger than 4, everything less than 2. And or says take the union of them, and just make sure you write your answers in order. For example, 4 to infinity would be to the right of negative infinity to 2. Negative infinity up to 2, and then 4 to infinity. Technically, you wouldn't necessarily be super wrong by writing just this, but for the case of what we're trying to talk about, or we want to make sure we're taking the union of these things. Well, now let's do and. And at the very end is identical, except we take the intersection of them, everything they have in common. Okay, so we're still going to solve each inequality the same. Let's distribute 2. Let's distribute 3. Let's combine some constants. Let's add or subtract constants on both sides. And now you know that we need to divide by 2 and divide by negative 3. And don't forget, we divide by negative 3. We're going to flip that sign. All right, so this says everything to the left of 5. This says everything greater than negative 2. And now what we want is the intersection of these things. What do they have in common? Okay, I'm going to go to the whiteboard just for a moment just to show you what this one looks like. I'm not going to do it for the next one, but just so you have an idea. Okay, so just to give the brief example of what an intersection would look like for intervals, since we didn't really do it in chapter P, we had negative infinity to 5, negative 2 to infinity. So if we were to draw these on a number line, first one would be everything to the left of 5. And the second one would be everything to the right of 2. So if we want to take the intersection of these two things, it would be everything they have in common. Well, let's draw some spots right here. And we see the only thing that these two both have in common is this section in the middle. Well, what's this section in the middle? Negative 2 up to 5. Everything to the left of negative 2 isn't true because everything to the left of negative 2 is not between negative 2 and 5. And same thing we could say for here, does not count here. So the answer to this intersection would be negative 2 to 5. So I'm going to go back to the presentation. Okay, so we get our answer to be negative 2 to 5. So for the next one, I'm not going to go back to the whiteboard and draw it, but it's good practice for you if you want to practice drawing intersections. So what we're saying is that this is the solution set. Negative 2 to 5 is the solution set. That means if it's in the solution set, it will satisfy both things. That's the definition of or. We need both of these to be satisfied for and. So let's say we take 0, which is in the solution set. 0 minus 3, negative 3. 2 times negative 3 is negative 6. Negative 6 plus 5 is negative 1. And negative 1 is less than 9. That part is true. If we plug in 0, 1 minus 0 is 1. 3 times 1 is 3. 3 minus 2 is 1. 1 is less than or equal to 7. So a value in our solution set satisfied both. And that's the key to and versus or. And you have to satisfy both. Or you only need to satisfy one of them. You can satisfy both, but you only need to satisfy one of them. So it's a little less restrictive. Now, if we were to plug in a value that is not within our solution set, let's say we plug in 6. Well, 6 minus 3 is 3. 2 times 3 is 6. 6 plus 5 is 11. 11 less than 9 is not true. 11 is not less than 9. So this one fails. And by definition, for and, the whole thing fails. Even though when we plug in 6, 1 minus 6 is negative 5. 3 times negative 5 is negative 15. Negative 15 minus 2 is negative 17. Well, this inequality would be true, but since it's not true in both, it doesn't count. So our solution set is the intersection of each individual part's final answer. Okay, let's do another and example. Again, you can draw it on your own. Let's do it. Here, let's distribute 2. Let's combine some constants. Let's add or subtract some constants. Let's divide by negative 2 and 2. Don't forget here, when we divide by negative 2, we got to flip the sign. This says everything bigger than negative 1 with negative 1 not included. This says everything less than 3, 3 included because of the less than or equal to. So now what are all the numbers that are in common from negative 1 to infinity, negative infinity to 3? You could practice drawing it on your own, but that would just be everything between negative 1 and 3. So for example, if you plug in 0, 3 minus 0 is 3, 2 times 3 is 6, 6 minus 3 is 3, 3 is less than 5. That one's true. 0 minus 5 is negative 5. 2 times negative 5 is negative 10. Negative 10 plus 7 is negative 3. Negative 3 is indeed less than or equal to 3. So everything in the solution set is true. Everything outside of the solution set would not be true. Try something outside of the solution set to prove to yourself that at least one of them fails. So again, for or, we're looking for a union at the end because only one of the two statements needs to be true. But for and, we're looking for an intersection because both of the things need to be true. All right, we can also have compound inequalities that look like this. Now, we're going to look at inequalities that look like this again in the next section. So it's important that we solve it here, but actually solving inequalities like this is actually really, really nice. So what it turns out is that this type of inequality is actually an and inequality in disguise. However, when it's written in this way, so much easier to solve. Okay, when we're doing equations, or when we learned to do equations, we said we needed to subtract 3 on both sides, but never in equations did we have 3 parts. It didn't make sense to have this part equal to this part equal to this part, right? If they're equal, everything's going to be equal. So for inequalities, it's a little different because notice in all the questions we've done so far, there have been bounds to where our answer starts and ends in a lot of these compound inequality cases. So long story short, when you're solving inequalities that look like this, if you do something to one part of the inequality, you need to do it to all of the parts of the inequality. So when you go to subtract 3 to get x by itself, you're not just subtracting the inside part and one of the two sides minus 3, you are subtracting everything by 3. Okay? You subtract 3 everywhere. And now when you go to divide by 2, you divide by 2 everywhere. So we get -4 less than x less than or equal to 3. Well, if you were to draw all the values between -4 and 3, that would just be the interval. -4 not included because of the less than, but 3 included because of the less than or equal to. So way easier to get a solution set. So if you plugged in something between -4 and 3, you would get this entire inequality is true. Let's plug in 0. 2 times 0 is 0. 0 plus 3 is 3. -5 less than 3. That's true. 3 less than or equal to 9. Also true. Okay, so these are actually pretty nice. Let's do another one. Maybe we see this -4x. That's going to be a problem. Let's see what happens. We want to subtract 2 to start, but make sure we subtract everything by 2. Okay, we're going to divide by -4, but make sure when you divide by -4, you divide everything by -4. But also, we know that when we're dividing by negative numbers, we need to flip the sign. Well, in this case, we're going to flip both signs. So this less than will become a greater than, this less than or equal to will become a greater than or equal to, and now we get this. This is kind of ugly, though. Q is to the left of -3. That's not what the inequality is saying, but it's written to the left of -3. Ugh, that's not good. Here's what we're going to do. To solve this problem, all we need to do is just read it backwards. And what I mean by that is literally -3, instead of reading this as greater than or equal to, if we're reading it backwards, this is then -3 is less than or equal to x, which is less than 2. That's all it means to read it backwards. Literally go piece by piece and just read it backwards. Well, now from here, saying -3 to 2, not so shabby. Again, if we were to plug in something outside of the solution set, we've seen so many times outside of the solution set works, inside the solution set works. Let's plug in something outside. Let's plug in 3. -4 times 3 is -12. -12 plus 10 is -10. -6 less than -10. Oh, well, that's not true. So part of this fails. -10 is less than 14, but it doesn't meet that first bound criteria. So something like that. So inequalities, a lot like equations. Compound inequalities, also a lot like equations. Whole thing is just kind of like its own weird rule. And there exists one more type of inequality that we can solve when it comes to like rational inequalities, right? Where just one side is a fraction. So not super common here in algebra, but something like this is actually going to be very popular when you go to solve increasing, decreasing, and for extrema and concavity, all very fancy words in Calc 1. So I'm going to do some examples here, but odds are you're not going to do a ton of them in your classes, no matter where you're watching this. But if you're watching this for Calc 1, you definitely want to listen up. If I ever decide to make Calc 1 videos, I'll do those separate. But yeah, for now, let's do test point method. So we want to use it for anything not linear. So for example, quadratic, rational, etc. The steps are as follows. Make sure one side is equal to 0. We have to make sure one side is equal to 0. We're going to simplify everything as much as possible. And we're going to set the numerator and denominator, if we have it, equal to 0. We want to find all the locations where the numerator is 0 and where the denominator is 0. We're going to put those values on a real number line, which create multiple subintervals. Okay. And we're going to test values in those subintervals by plugging them into the original equation or an equivalent simplified version that we find, right? Our final answer is all the subintervals that are true, and we're going to ignore all the ones that are not true. So last thing we need to do is make sure that the endpoints are either included or not included, parentheses versus brackets. These are a lot of steps. Let's just do some examples. So I'm going to move to the whiteboard, and I'll see you in just a moment. Okay, so here we are on the whiteboard. Let's do x squared plus 4x greater than or equal to 5x plus 6. Step 1, we need to get 0 on one side. So let's start by subtracting 5x. 4x minus 5x is negative x. Let's then subtract 6. X squared minus x minus 6 greater than or equal to 0. This side we can factor as x minus 3, x plus 2. And now let's set each one equal to 0. So I know it says greater than or equal to 0, but we just want some reference points. So let's set x minus 3, x plus 2 equal to 0. We're going to set each part equal to 0. So x is 3, x is negative 2. And now what we're going to do is take these 2 points and put them on this subinterval. I like to put 0 there as a placeholder, but it is not one of our points. Well, notice we have an interval to the left of negative 2. We have an interval between negative 2 and 3, and we have an interval to the right of 3. So our 2 points created 1, 2, 3 subintervals. And now what we're going to do is plug in a value in each of those 3 subintervals. And what we want to determine is if our inequality is true. So let's plug in negative 3 for the first one. Well, negative 3 minus 3 times negative 3 plus 2. Well, negative 3 minus 3 is going to be negative. Negative 3 plus 2 is also going to be negative. And a negative times a negative is a positive. And positives are greater than 0. So our left interval is true. And notice that I didn't even really care what the values were. I only care about the sign. And that's the benefit to us being greater than or equal to 0, or having whatever with one side equal to 0. If one side's equal to 0, all we're trying to determine is if it is positive or negative. Positive numbers are greater than 0. Negative numbers are not. So you can find the actual value if you want, but it's easier to just determine signs. Okay, so we know the left one is true. Let's do the next one. Okay, let's plug in 0 for the middle interval. 0 minus 3, 0 plus 2. Well, 0 minus 3 is negative, 0 plus 2 is positive, but a negative times a positive is a negative number, which is not greater than or equal to 0. So our middle interval is not going to be true. Okay, last but not least, let's check a number to the right of 3. Let's plug in, let's say 4. 4 minus 3 times 4 plus 2. Well, 4 minus 3 is positive. 4 plus 2 is also positive. It is 6, but it's positive. Okay, and a positive times a positive is indeed a positive, and positives are greater than 0. So that is true. So then we know our answer is going to be negative infinity up to negative 2 with 3 to infinity. And now all we need to do is determine which of each of our 4 things, 1, 2, 3, 4, have brackets or parentheses. So to start, negative infinity and infinity always get parentheses. Now negative 2, what we need to do is plug in negative 2 into our inequality to see if it is true. If it is true, it is part of the answer. We put a bracket. If it is not true, we don't put a bracket. So if we plug in negative 2, well, what we get, negative 5 times 0, negative 5 times 0 is greater than or equal to 0. So negative 2 works. And then same thing for 3. 3 also works because if you plug in 3 to x minus 3, that is 0. 0 times anything is indeed greater than or equal to 0. So our answer would be negative infinity up to negative 2 with 3 to infinity. That's an interesting looking negative infinity, but I know you guys get the idea. Okay, let's do one more example, and then we'll call it a day for this section. Okay, so let's do x squared plus 2x minus 15 over x minus 1 is less than 0. Okay, first things first, we got to simplify everything as much as we can. Numerator, x plus 5, x minus 3 over x minus 1 is less than 0. Okay, so what we need to do now is, even though we have a denominator, we still want to set each and every part equal to 0. Well, we get x equals negative 5, x equals 3, x equals 1. And you might be wondering, why are we setting 1, x minus 1 equal to 0? Why is 1 part of that? We never want the denominator to be 0. And that is true. However, notice that in what we were doing before, if the denominator was negative or positive, it could completely change what happens in the numerator. So yes, we're never going to actually plug in 1. However, we just got to be a little bit careful. So we set everything equal to 0. All right, let's put all of those values on a number line. We have negative 5, 1, and 3. And again, I like just putting 0 there as a placeholder. Not one of our intervals, but it's good to put there. We have everything to the left of negative 5, everything between negative 5 and 1, everything between 1 and 3, and everything bigger than 3. So our now 3 values created 4 subintervals, and there's nothing wrong with that. Now we're going to plug in a value into each of these 4 subintervals and determine whether or not the inequality is true or false. So I'm going to rewrite the inequality over here. X plus 5, x minus 3 over x minus 1 less than 0. Let's plug in negative 6 for here. Negative 6 plus 5, negative 6 minus 3 over negative 6 minus 1. Negative 6 plus 5 is going to be negative. Negative 6 minus 3 is going to be negative. Negative 6 minus 1 is going to be negative. So we have a negative times a negative is a positive, divided by a negative. Whole thing is negative, and negatives are indeed less than 0. So again, don't care about what the value is. We only care about the signs. Well, all negative numbers are less than 0, so this one's going to be true. Okay, let's do the same thing for x equals 0. That's the wrong thing. Let's do the same thing for x equals 0 to test the value between negative 5 and 1, and we'll see what happens. 0 plus 5, 0 minus 3, 0 minus 1. 0 plus 5 is positive. 0 minus 3 is negative. 0 minus 1 is negative. Well, negative divided by a negative is going to be positive, or actually we should probably look at it this way. Positive times a negative is a negative, divided by a negative. Negative divided by a negative is a positive, but positives are not less than 0, right? We want less than 0, so this interval not going to be true. Okay, we're almost there. 2 more values. Let's plug in a value between 1 and 3. I think 2 is a great choice. 2 plus 5 times 2 minus 3 over 2 minus 1. 2 plus 5 is positive. 2 minus 3 is negative. 2 minus 1 is positive. Well, positive times a negative is a negative. Negative divided by a positive is negative, and negatives are indeed less than 0. So that interval is going to be true too. Again, it's not a matter of what the value is in between 1 and 3. It's a matter of, if we plug it in, is the inequality true? Okay, and we are almost there. Let's test one more. Let's plug in 4. So we plugged in 2 here. All right. Oh, I erased too much. All right. Well, x plus 5, x minus 3, x minus 1 less than 0. All right. If we plug in 4, 4 plus 5, 4 minus 3, 4 minus 1. Well, 4 plus 5 is positive. 4 minus 3 is positive. 4 minus 1 is positive. Whole thing is positive, right? Positive times a positive is positive, divided by a positive is positive. But positive numbers are not less than 0. So that answer is not true. Okay, that interval is not true, I should say. So our answer is all the correct spots here and here. Well, that would be negative infinity up to negative 5. And then we skip all the way from 1 to 3. Now, you might be wondering why I was so quick to use parentheses. Well, you can go in and check each one, but actually a really good giveaway is the less than sign up here. So if we have a less than or greater than sign, there's no chance that we can ever be equal to 0. So we're always going to use parentheses if this is greater than or less than. So even for the other one, if it was greater than or less than, you could jump to that right away. But if you don't like this, check each value to determine. You would see that if you plug in -5, the numerator is 0. Well, 0 is not less than 0, so that's not true. If you plugged in 1, well, the numerator is going to be 1 squared is 1, 2 times 1 is 2, 1 plus 2 is 3, 3 minus 15 is -12. But 1 minus 1 is 0, and you'd have -12 over 0. So that wouldn't work. That would have to have a parentheses because we can't be equal to 1. 3, same argument as -5. Top would be 0, but 0 not less than 0. So with that said, that's the end of 1.6. We got one more section in 1.7. It's actually a pretty nice section. We like absolute values. They get a little twisty, but not really so hard to wrangle down. So I will see you in 1.7. Bye. Hi, everyone. Welcome to 1.7, where we wrap up Chapter 1, an entire chapter just on solving equations and inequalities. So in 1.1, we solved some linear equations. In 1.2, we learned to apply some of those things. 1.3, we solved quadratic equations, which we extended into 1.4, where we introduced complex numbers. 1.5, we talked about all sorts of other different types of equations we can solve, right? You see 5 different types right here. And then in 1.6, we changed gears a little bit to solve inequalities. But what we saw is that solving inequalities really isn't that different from solving equations. Different frame of reference, but really similar steps. And then in 1.7, what we're going to do, solve equations and inequalities in the same section. However, this time, all we're going to do is very briefly discuss what happens when we have absolute values. So just kind of some new rules, nothing really crazy. And you're going to see it's a lot of things we've already talked about, just a step or two of setup. So let's just start by talking about some basics of absolute value. So if we want to solve an equation that is the absolute value of some expression u equals c, where c is some constant, what we're going to do is solve u equals positive c and u equals negative c. So that comes from the definition of what absolute value really means. We don't need to, at this level, really spend time looking into the theory of that kind of thing. But long story short, if you see absolute value of u equals c, you are then breaking it into two equations, one of which looks identical to the original, just without the absolute value, and the other one is almost identical, except negative, whatever our constant is. So u is some expression. It's any algebraic expression, right? 5x plus 1, negative 3x plus 200, whatever it might be. And c is both a constant or an algebraic expression. So when I first mentioned it, I said, yes, this is a constant like 9 or 5, and you're going to solve an equation where it's then positive 5 and negative 5. But what ends up happening is that it works the exact same way, even if that c is another algebraic expression. Requires us to be a little careful, but otherwise it's not that different. If we have absolute value of u equals a negative constant, well, don't forget that absolute value always produces a positive number. Absolute value of 5 is positive 5. Absolute value of negative 5 is also positive 5. So there is no way absolute value of something can be negative. So there is no solution in this very specific case, right? Negative algebraic expression, that's different. A negative constant like negative 3 or negative 6, no. Like I said, absolute values can't produce negative numbers, so that's our only reason. And if we have absolute value of u equals 0, well, what you're really supposed to do is u equals 0 and u equals negative 0, but negative 0 doesn't really make any sense. Negative 0 would be the same thing as 0, so all you really need to solve is just u equals 0. So in the case where we have equals 0 on one side, we don't need to solve two separate equations. You're just going to set the inside equal to 0. So let's get right into it. And kind of like we saw in 1.5, when we go to apply some rules or when we go to apply some methods, we want to make sure that our absolute value, that our radical in 1.5, for example, is all by itself. So let's just start by adding 5 to both sides to get absolute value of 2x minus 3 by itself. Okay, there's supposed to be an absolute value here. I dropped that part by accident. So absolute value of 2x minus 3 equals 13. That splits up into two equations. 2x minus 3 equals positive 13, and 2x minus 3 equals negative 13. Again, I accidentally dropped the absolute value sign here. So this part that's highlighted right now, absolute value of this. Okay, and now what you see is, oh, that's a linear equation, and that's a linear equation. Let's add 3 in both of those two cases. Let's divide both of them by 2. And we get two solutions. Negative 5 and 8. It took one real new line of setup to break one absolute value equation into two separate ones. But aside from that, not really anything different, right? Just solving a pair of linear equations. Maybe a little meaty, right? 2x minus 3 equals positive and negative 13 isn't necessarily short, but I think you guys see the method here. So let's do the same thing. We got to get absolute value of 6x minus 3 by itself. So let's start by adding 18 to both sides. Then let's divide both sides by 3. Then we have absolute value of 6x minus 3 equals 9. This is what the last equation was supposed to look like. I accidentally dropped the absolute values, but that's okay. So what we're going to get is 6x minus 3 equals positive 9, and 6x minus 3 equals negative 9. And again, from here, it is exactly like stuff we've already talked about. Let's add 3 to both sides. Let's divide both sides by 6. And we get two answers. So absolute value equations, not really anything super insane. Some slight new steps, some slight new setup that could be very easy to forget. But I don't think there's anything here that is really blowing anybody's mind after that setup. Absolute value of x plus 3 equals 0. So what we would do is x plus 3 equals positive 0, x plus 3 equals negative 0. But at any point in your life, have you ever written negative 0? No, you haven't. So really, these two equations are one and the same. x plus 3. I don't know why there's an extra x plus 3 equals negative 0 here. That might have been a mistake. So x plus 3 equals 0 is the only equation we need to solve. Negative 0 would, in a sense, be the same as 0. All we're doing is solving x plus 3 equals 0. Subtract 3 on both sides, and we get only one answer. And that makes sense, because if we want the absolute value of something to equal 5, well, the absolute value of 5 is negative 5, and the absolute value of negative 5 is 5. However, the only thing whose absolute value is 0 is 0. So it makes sense that there's only one possibility there. Same thing, absolute value of 4x minus 7 equals 0. Well, all we need to know is when the inside is 0, we're going to add 7. We're going to divide by 4. And I think this is pretty okay. So I know I'm moving kind of fast. I don't think any of the steps here are really screwing with anybody's mind. Okay. Now, 400x minus 1. The absolute value of 400x minus 1 equals negative 1. Well, don't forget, absolute values only produce positive numbers. They can't produce negative numbers. So in this case, there would be no solution. There's absolutely nothing whose absolute value is negative 1, so there's no solution. Okay, that's a pretty easy way to jump. That's kind of like what we did for square roots and even roots when it came to negative numbers. Now, I just want you to be careful, because just because one side is negative doesn't necessarily mean the equation will fail. So for example, if we have absolute value of 400x minus 1 minus 2 equals negative 1, well, all we need to do is add 2 to both sides, and now it's positive. Same thing, if we have negative on the outside, we can divide both sides by negative 1. Oh, and look at that. Just because one side is negative, make sure that there's nothing you can do to change it to be positive, right? Simple algebra like that could change you from, doing a problem that you think has no solution to a problem that has a solution. And it can also be the other way around too, right? If this was a positive 1 and this was positive 2, you subtract 2 on both sides and then you would get negative 1. So that would be no solution, but not to get too deep. So just to solve that equation, we want to solve 400x minus 1 equals positive 1 and 400x minus 1 equals negative 1. Let's add 1 to both sides. Let's divide both sides by 400. Well, 2 over 400 would just be 1 over 200. 0 divided by 400 is just 0. So we get 2 solutions there. Okay, now was all true for when the thing on the right-hand side is a constant, like 1, like 9, whatever it might be. But I also told you that it functions the exact same way, even if we have an expression on the right-hand side. So let's do just that. All this is instead of just making it a positive constant and a negative constant, all we're going to do is say 2x minus 1 equals itself, x plus 5, and 2x minus 1 equals negative the whole thing, x plus 5. So just, it doesn't really, mean so much for numbers when we say 9 and negative, parentheses 9. We really write that parentheses 9, but it does make a very big difference when we're talking about, expressions. So be careful. It's not just negative x plus 5. It's the whole thing, negative x plus 5. So we have to distribute a negative sign. And now we have 2 equations again. Just got to be careful because they're going to be solved a little different. Over here, let's subtract x on both sides, whereas this one, we're going to add x to both sides. Well, 2x minus x is just 1x. 2x plus x is 3x. Here we're going to add 1. Here we're also going to add 1. And then one more step for the rightmost one. We're just going to divide both sides by 3. So there we go. Again, not all that different when one side is an expression. Just be a little careful. Use parentheses. They are free. Let's do one more like that. Absolute value of 3x minus 4 equals 2 times x minus 1. So what we're going to do is 3x minus 4 equals itself 2x minus 1, and 3x minus 4 equals negative 2x minus 1. You could put another set of brackets or parentheses around these two if you want. It would end up just creating another step for you, but if that helps you see the difference, by all means, go for it. Here, we're going to distribute just positive 2, but here we're going to distribute negative 2. All right, here we're going to subtract 2x, but here we're going to add 2x. 3x minus 2x is just x, but 3x plus 2x is also just x. We're going to add 4 to both sides in each separate equation. And last but not least, we just need to divide by 5 on the right. And there we go. 2 answers. So constants or expressions make one side positive, make the right side positive, then make a separate equation where the right side is negative. That's it for both constants and expressions. Okay, what about the case where we have absolute value of u equals absolute value of v? We have a double absolute value. Well, let's apply with the rules that we have created, but let's apply them twice. And what I mean by that is we would drop this absolute value sign if we made this one positive and this one negative. I don't know why why does it keep doing that? Okay, Zoom has been giving me a hard time for whatever reason on this slide. In 2 takes of recording this, it's bugged out on this slide, so I got to talk through it. Forgive me that it's not, we're not doing it in a presentation-wise, but here we go. So if we wanted to drop this absolute value sign, what we know is that we're going to just drop the absolute value of u, but keep the one side as itself, right? That was kind of like 2x minus 3 equals positive 9, just leaving it just like itself. But then we also solved another equation where the right side is the negative version of itself. Okay, well, that's not so crazy so far. And if we want to drop this absolute value of v, we will keep this side itself and then solve a separate equation where that side is negative itself. And same thing for over here. If we want to drop this absolute value sign, make one side positive and make one equation negative. All right, so we get 4 equations and you would think, oh no, double absolute value, we got to solve 4 equations. Actually, not quite. because these four equations are really two equations. So what if we divided both sides by -1 in this equation? And what if we divided both sides by -1 in this equation? So that's what I do here, and that's what I do here. Okay, well, when we do that, negative u over -1 is positive u, v divided by -1 is negative v, negative u divided by -1 is positive u, negative v divided by -1 is v. Now, we still have four equations, but notice something. U equals v, and u equals v. Oh, this second equation we got in the second case is actually redundant. And same thing here. We had u equals negative v, and we also got a redundant answer here. So guess what? Just like we've been solving every other equation, even when you have double absolute value, all you're solving is u equals positive v and u equals negative v. And as always, check your answers. Okay. So if we have absolute value of x minus 1 equals absolute value of x plus 5, again, one equation, one side is going to be x minus 1 equals positive version of the right-hand side, and the other one is going to be x minus 1 equals negative, the right-hand side. Again, use parentheses, be careful, and also notice, not really all that different from things we've already done, but also, if you wanted to apply that, make one side positive, make one side negative, where you keep x plus 5 the same, you can do that too and say, oh, x plus 5 equals x minus 1, x plus 5 equals negative x minus 1. So you could technically flip one side as long as you stay consistent. So here we're just going to distribute -1. Over here, we're going to subtract x on both sides, and over here, we're going to add x to both sides. Well, kind of strange over here. X is going to cancel out on both sides, but on this one, x plus x is going to be 2x. Well, we got an equation here that makes no sense. That's totally fine. That means we're just going to solve this one. Add 1 to both sides. Let's divide both sides by 2, and we get -2. So just because we got one equation that made no sense doesn't mean the whole thing fails. It just means our only solution is coming from the second half, and that's totally fine. Let's do it one more time before we get into inequalities. So we have double absolute value, but again, all it is, one version says just drop the absolute values, right side is positive or itself, and right side is the negative version of itself, right? It's been the same thing over and over and over again. Okay, we're going to distribute -1. Over here, we're going to subtract 6x on both sides. Over here, we're going to add 6x to both sides. Well, 3x minus 6x is -3x. 3x plus 6x is 9x. Let's add 2 to both sides. Let's divide one side, or one equation, by -3 on both sides. Let's divide the other one by 9 on both sides. And we get two answers again. And that brings us to inequalities. So solving inequalities is kind of putting everything we've talked about in this chapter together, right? Now, not necessarily going to use, properties we talked about in 1.1, but we are going to need to solve linear inequalities, which were like linear equations from 1.1. So putting together a bunch of different things we've talked about, from absolute value and equations and, all sorts of different stuff. Essentially, putting together all of these things about inequalities and absolute values, we get 4 rules, which are kind of like 2 rules. But instead of going through all the theory to end up at these results, let's just show them off. If you have absolute value of u is less than c, we convert this to another inequality that says -c less than u, less than c. That's a compound inequality. So if you have something that looks like this, immediately jump to this. That's it. Don't try and do too much. Likewise, if it's less than or equal to, guess what? Same thing, but less than or equal to signs. Now, it's a little different from when we have a greater than sign. When we have a greater than sign, this becomes an or type of inequality. So we have regular version itself and make one side negative. But, when we made things negative, when we multiplied or divided by negative numbers, we had to flip the sign. So that actually happens here as well. So equations, we don't flip equation symbols. But when we do this for inequalities, when we make one side negative, flip the sign for that negative side. And same thing for greater than or equal to. So you might notice that these two rules are very similar. These two rules are very similar. So it's kind of like 2 things to remember. But, really 4 separate rules, since those inequalities are indeed unique. Okay, so 4x minus 1, absolute value of 4x minus 1 is less than or equal to 9. What we're going to do is use this rule right here. Absolute value of 4x minus 1 is less than or equal to 9 would be, make this -9, less than or equal to 4x minus 1, less than or equal to 9. And now it's an inequality we solved in the last section. We're going to add 1 to everything, not just one part, add 1 to everything, divide everything by 4, and now everything between -2 and 5/2, including -2 and 5/2, brackets around them. That's it. Not crazy, nothing scary. Absolute value inequalities. Yes, it's a very different setup from what we had for equations, but it really isn't anything different. Let's do it for greater than when it becomes an or. Okay, well, or, when we have greater than, we split it up into just itself without the absolute values, and then we do itself, flip the sign, and make it negative. Okay, there you go. Well, now we have 2 linear inequalities. Let's add 8 to both sides. Let's divide both sides by 2. Let's write each of those as intervals. And now, since we're dealing with or, we're taking the union of those things. So absolute value inequalities, not really crazy, not much new from 1.6. If you still need help solving ands and ors, check out the 1.6 video. Alrighty, absolute value of 3x minus 2 is greater than -5. Well, absolute values always produce positive numbers. Well, if they always produce positive numbers are always greater than -5. So this statement is always true. our solution set for solving inequalities would be all real numbers, negative infinity to infinity. No matter what you plug in, this statement, this inequality will always be true. Absolute value of 5x plus 3 is less than or equal to negative 2. Well, absolute value expressions always produce positive values. So this statement is never true. If this is always positive, there's no way a positive number can be less than or equal to negative 2. In this case, no solution. That's it. So that's the end of 1.7. Like I said, 1.7 moves kind of fast. It's a nice summary of all the different tools, some of the different tools that we've talked about in chapter 1. And yeah, that leads us into chapter 2, where we really start to talk about functions and a lot of function properties. But without the ability to solve equations or inequalities, we can't talk about a lot of the different properties that we will discuss in chapter 2. So I will see you in chapter 2, and yeah, bye. Hi everyone, welcome to chapter 2. So chapter P, we build some of the very basic rules of algebra, and in chapter 1, we spend a lot of time solving equations and inequalities, and we're going to finally learn to use all of these equations and inequalities and properties here in chapter 2. So in chapter 2, we eventually want to work our way up to functions, and then all the various properties of functions, but we're going to take a couple sections to get there, but that'll be 2.4. Until then, we have 2.1, 2, and 3, all pretty nice, just kind of establishing what graphs are. So let's start with the plane. So the coordinate plane, as you've seen it in the past, or also known as the Cartesian plane, it's kind of like a second dimension number line. What we've done in chapter 1, and even before that, is we had just a single number line for all of our answers. We had, say that x equals 5 is the answer, or x is greater than negative 3 is the answer. All of those answers, all those solutions sat on just one single x line. However, what we now want to eventually get to is using a coordinate plane, where not only do we have an x part of the solution, we also have a y part of the solution. So in a way, the coordinate plane is kind of like a second dimension number line, but don't necessarily need to think of it that way. We're just working our way up to 2 dimensions. So we have a horizontal line in our coordinate plane and a vertical line. That horizontal line we call the x-axis. Well, that's pretty nice, right? We just talked about a real number line. We had answers that were x's. So that horizontal line is called the x-axis. The right half of the x-axis we define to be the positive x direction, and that kind of makes sense. And then the left half would be the negative x direction. Like I said, this kind of makes sense because when we read left to right. Well, if we're reading left to right, that's kind of how x values run. They run negative to positive. We like it when things go up. Likewise, we have a vertical line called the y-axis. So not only are we going to get things with x's, we're going to get things with x's and y's simultaneously. The upper half of the y-axis is the positive y direction, and the lower half is the negative y direction. Well, horizontal is kind of intuitive in this way because we read left to right, and things increase as we go left to right. However, even though the y-axis is kind of intuitive, up means positive, down means negative, it's a little backwards because we read negative to positive left to right, but negative to positive will be up to down. So in other words, up is positive, right is positive, left is negative, down is negative. These two axes meet at what we call the origin, which has the coordinate point 0, 0. And we're going to spend a little bit more time in just a moment actually graphing coordinate points. So here is the coordinate plane. You see the x-axis that runs left to right, y-axis that runs up and down. And you see these y values are positive, these y values are negative, these x values are positive, these x values are negative. Like I was saying, we use coordinate pairs or coordinate points or ordered pairs of the form a, comma, b. So this is the same notation that we use for open intervals, right? Kind of saying everything from a to b, a not included, b not included, but we're going to use the same notation to do something different now, where a, comma, b is some point in two-dimensional space. A is our horizontal location, the x coordinate. B is the y coordinate, or the vertical location. So if you're trying to figure out where some a, comma, b goes to, you would go to the left or right coordinate for a and up and down coordinate for b. So for example, some random ab right here, a would be the horizontal distance, b would be the vertical distance. And here you see the origin at 0, 0. Okay, well, quadrants, well, if you notice here, do you see that these two lines create 4 divided areas? We have the area above the x-axis and to the right of the y-axis, left of the y-axis and above the x-axis, and so on. Each of these 4 things are called quadrants. So going from the top right and working our way counterclockwise, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. And even if we don't spend a ton of time looking at that here in algebra, you will definitely look at it in pre-calculus. So quadrant 1 would be all the locations where x and y are both positive. Quadrant 2 would be every location where x is negative but y is positive. Quadrant 3, both x and y are negative. In quadrant 4, x is positive, y is negative. So let's do some graphing. Let's graph these 6 points here. Well, let's start with just one. Let's start with 3, 1. 3, 1 says we go 3 units in the positive x direction and 1 unit in the positive y direction. Or in other words, 3 is positive, go right 3, 1 is positive, go up 1. Well, negative 2, 4, if this is positive 3, then negative 2 would be 2 units in the opposite direction. So negative 2, 4 would be 1, 2 units to the left, but still 4 units up. 1, 2, 3, 4. Negative 3, negative 4 says we're going to go 3 units to the left, 1, 2, 3, and also 4 units down, 1, 2, 3, 4. Okay, 2, negative 3 says we're going to move 2 units in the positive x direction, 1, 2, but then we're going to move 3 units down, 1, 2, 3. Negative 3, 0 says we're going to go 3 units in the negative x direction, 1, 2, 3, and we're going to move 0 units up and down since we have negative 3, 0. 0, 5 says we're not going to move left or right at all, but then we're going to go up 1, 2, 3, 4, 5 points. Okay, so I'm trying to break this down into as formal terms as possible in terms of describing it for a college level algebra class. However you have graphed points in the past, whatever is easy for you to remember, by all means, keep doing it that way. Well, what if we want to take the distance between any of these 2 points? Maybe not so hard to say from this point to this point is 3 units, but how about going from this point to this point, or even this point to this point? Well, that's where we come up with distance. We can draw a line from the origin to any point on the graph. So let's say we have the point 3, 4, and we want to draw the line from 0, 0, the origin, to 3, 4. Okay, well, this line is the distance between 0, 0 and 3, 4. But how do we find the length of this line? It's not quite that obvious. It isn't just 3 plus 4. This isn't 7 units. Okay, well, what we can do is we can make a triangle with this line right here. We can go bottom leg right here. We can go upper leg, or however you want to word it, right? We can go this leg right here and this leg right here. And now the question is, what are the values of these 2 legs? We have a formula to tell us, the distance of this leg. We have a way to relate all 3 legs. But what is the distance of this leg? What is the distance of this leg? Well, very conveniently, you see that this leg has 1, 2, 3 units. Oh, that's the x coordinate. And you see this vertical leg has 1, 2, 3, 4 units. That's the y coordinate. So the horizontal leg has length A, or the x coordinate. Vertical leg has length B, the y coordinate. And then we say that diagonal line, the actual distance, is the hypotenuse. And we define it to have length C. Now, we relate A, B, and C using what is called Pythagorean theorem. You've probably heard it in the past. It's got some very funky applications in pre-calculus, but for here in algebra, very simply, it is A squared plus B squared equals C squared. The length of the horizontal leg squared plus the length of the vertical leg squared equals the diagonal's length squared. Okay, so if we want to find the length of that line, the hypotenuse, well, if we have the point 3, 4, then A is 3 and B is 4. So all we're going to do is plug info in to A squared plus B squared equals C squared. Well, A is 3, B is 4. We know how to square numbers. 3 squared is 9, 4 squared is 16. We know how to add. 9 plus 16 is 25. And we know from here, in chapter 1, we would take the square root of both sides, get plus and minus. Square root of 25 is just 5. But for the purpose of talking about distance, distance should always be positive. So the length of that line that we drew before from 0, 0 to 3, 4 is 5 units long. Now, this is great and dandy, but what if we want to find the distance between any 2 points and not just the origin? Well, if we combine the general distance formula, if we combine Pythagorean theorem with the one-dimensional distance formula, absolute value of A minus B or absolute value of B minus A, in total, we can jump to its definition. If you have 2 points, x1, y1, and x2, y2, the distance between them is this right here. Now, you already see some squares. You see a square root. You also see this x2 minus x1, kind of like b minus a. So there is both Pythagorean theorem and the distance formula we had in chapter P. So putting that all together, we get here. It takes a little too long for us to derive, but I think you guys see the elements here. So if we want to find the distance between any 2 points, we're going to just plug things into x2, x1, and y2, y1. So let's find the distance between negative 2, 5 and 3, negative 4. Well, x1, y1 is going to be our first point. So x1 would be negative 2, and y1 would be 5. Likewise, q would be our second point, 3, negative 4. So x2 is 3, and y2 is negative 4. And what we're going to do is just plug in all of this information for x2, x1, y2, y1. x2 is 3, x1 is negative 2, y2 is negative 4, y1 is 5. 3 minus negative 2 is positive 5, negative 4 minus 5 is negative 9. 5 squared is 25, negative 9 squared is 81, and square root of 25 plus 81 is square root of 106, which is roughly 10 units. So the length of the line that connects negative 2, 5, and 3, negative 4 is roughly 10 units long. Okay, but also I want to stress that our choice for x1 and x2 doesn't matter. Intuitively, you're probably going to just use first point is x1, y2, second point is x2, y2, but I just want to show you that it doesn't matter. It doesn't matter how we define one or the other. So if we instead let 3, negative 4 be x1, y1, x1 is 3, y1 is negative 4, and then x2, y2 would be negative 2, 5. x2 would be negative 2, and y2 would be 5. So let's again plug in all of those numbers. x2 is negative 2, x1 is 3, y2 is 5, y1 is negative 4. Negative 2 minus 3 is negative 5. 5 minus negative 4 is positive 9. Negative 5 squared is 25. 9 squared is 81. Oh, and look at that. We're right back to where we got. So you're most likely going to use the first point to be x1, y1, and second point to be x2, y2. But if you're ever feeling a little funky, you're more than welcome to change it up. Okay, let's find the distance between 3, 3, and 6, 6. Well, you're probably thinking 3 and 6 are 3 units apart, so the answer must be 3 units. Let's see why that's not true. Okay, first point, let's let that be 3, 3. In that case, x1 would be 3, and y1 would be 3. Let's let the second point be 6, 6. So x2 is 6, and y2 is 6. So we're going to plug in all that information to this formula right here. x2 is 6, x1 is 3, y2 is 6, y1 is 3. 6 minus 3 is 3. 3 squared is 9. 9 plus 9 is 18, but 18, square root of 18, square root of 18 is 3 square root of 2. So the distance between 3, 3 and 6, 6 isn't as simple as just, oh, it's 3 apart for x's and y's, so the whole answer must be 3. No, the distance between 3, 3 and 6, 6 would be roughly like 4.2 units, and square root of 2 is 1.41. So just be careful for that. Doing this with some very ugly negative numbers, let's let -2, -1 be x1, y1. x1 is -2, y1 is -1. x2, y2 would be -7, -3. So x2 is -7, y2 is -3. All right, let's plug in everything we know. Now just be very careful. -7 minus -2 would be -7 plus 2. So this is -5. -3 minus -1 would be -3 plus 1, or -2. -5 squared is positive 25. -2 squared is positive 4. 25 plus 4 is 29. Okay, see, not a negative insight in our final answer. Okay, well, let's go back to doing Pythagorean theorem on the same 2 points that we started with. We said the distance from 0, 0 to 3, 4. We got our answer to be 5 using Pythagorean theorem, but that means we should also get the same answer doing the general distance formula. Well, x1, y1 would be 0, 0. x1 would be 0. y1 would be 0. x2, y2 would be 3, 4. x2 would be 3. y2 would be 4. Well, plugging in everything we got, well, conveniently, subtracting 0 doesn't change anything. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is 5. Oh, how nice. Exactly the same thing. So Pythagorean theorem is very nice when we're doing it just from the origin, but in any other case, you're probably more likely to just use the distance formula. So in the past, I've actually done baseball research. There's a video of it out there somewhere, probably unlisted. But what if we want to extend this to the real world and actually do something with something that we're familiar with? So let's talk about baseball a little bit. So on a normal Major League Baseball stadium, but even on some Little League stadiums, or Little League fields, I should say, consecutive bases are 90 feet apart. So here we have, home plate is, let's say it's 0, 0. Well, it takes us 90 units to get to first base, 90 units to get to second base, 90 units to go to third base. But now what I want to know is how far apart are opposite bases? How far apart is home from second? How far is third from first? Well, you see 0, 0, and 90, 90, and you want to be like, well, it's 90 units, or even it's 180 units. But not quite. If you were to throw a ball from home plate to second base, throwing it 90 units would be over here. Throwing at 90 units would be over here. That would not quite match to get to second base. So let's figure out how far that is. Okay, home plate is at 0, 0. Second base is at 90, 90. So just find the distance. That's all we're looking for. Well, we would have 90 minus 0 plus 90 minus 0. 90 squared plus 90 squared would be 2 90 squares, right? X plus X is 2X. Well, this is 90 square root of 2, which is roughly 127 feet. So that throw from home plate to second base would be 127 feet, or likewise from third to first would also be 127 feet. So get out of the idea of just looking at, 0 to 90 is 90, 0 to 90 is 90. Answer must be 90. It's a little more convoluted than that. Well, let's talk about one more thing here in 2.1, and that is midpoint. So midpoint, as it sounds, is literally the point equally distanced from two others, the point in the middle of any 2 points. If we're using the same x1, y1, x2, y2, well, this would be our formula. How do we find the point in the middle of any 2 things? Well, take their average. Add the x values together, divide by 2. Add the y values together, divide by 2. So let's find the midpoint of -3, 6, and 1, 4. x1, y1, -3, 6. x1 is -3, y1 is 6. x2, y2 would be 1, 4. x2 is 1, y2 is 4. So what we're going to do is add the x values together, divide by 2. Add the y values together, and then divide by 2. So -3 plus 1 over 2, 6 plus 4 over 2. I have these out of order. I just realized that. Okay, -3 plus 1 is -2. 4 plus 6 is 10. So -2 divided by 2, -1. 10 divided by 2, 5. Okay, that's really not all that surprising at all. Very nice. Okay, 820 and 1123. Well, x1, y1. x1 would be 8. y1 would be 20. x2, y2. x2 would be 11. y2 would be 23. So we're going to add the x values, add the y values, divide each of those sums by 2. Well, we just get 19 over 2 and 43 over 2. That's it. Nothing crazy. No need to find decimals. In my classes specifically, I prefer fractions, but, somewhere around, you guys might prefer decimals. Okay. Find the midpoint of -6, -17, -12, -15. Alrighty. Well, we're going to add the x values, -6 plus -12, comma, -17 plus -15, both of them divided by 2. Well, -6 plus -12 would be -6 minus 12. -17 plus -15 is like -17 minus 15. -6 minus 12, you're $6 in debt. You spend another 12. You are now $18 in debt. -17 minus 15, you're $17 in debt. You spend another 15. You are now $32 in debt. -18 divided by 2 is -9. -32 divided by 2 is -16. Okay, so not all that crazy for midpoint. I actually think it's pretty nice. A little less careful work than distance, but of course, always be careful. And kind of like for distance formula, your choice for x1, y1, and x2, y2 doesn't matter. Okay, well, what if the pitcher's mound is the midpoint between home and second base, which at an actual baseball field, it isn't quite, but let's just say it is. So how far is the pitcher's mound from home plate? Alrighty, well, so let's say we have 0, 0, and 90, 90, and we want to find a midpoint for them that, it's between 0, 0, and 90, 90. On a real baseball diamond, it's not actually halfway between 0, 0, and 90, 90, but let's pretend it is. Well, midpoint, we're going to add the x coordinates, add the y coordinates, and we're just going to get 45, 45. So then, how far apart is the pitcher's mound from any other base? Okay, well, so like I said, it's not actually in the middle of the diamond, but we're just saying it is for this example. But now let's find the distance from the pitcher's mound to third base. We haven't used third base at all in this section, so let's use it here. Okay, let's check from third base, which is 0, 90. And again, now, if we're asking how far apart the pitcher's mound is from third base, this is the distance formula. Subtract the x coordinates, subtract the y coordinates. Negative 45 squared plus 45 squared is, negative 45 squared would be positive 45. And then we would get 2 times 45 squared, or 45 squared of 2, which is roughly 64. I believe on an actual diamond, the pitcher's mound is 60.5 feet away from home plate, but in our imaginary baseball example, that's how far pitcher's mound is from any base. Okay, and that's actually it for 2.1. Chapter 2 in general is very, very long. So we're going to go section by section. We're going to do a lot of different things. So it's a lot of different information, but take each section on its own. So with that said, I will see you in 2.2. Bye. Hi, everyone. Welcome back to 2.2. So we established the coordinate plane and some interesting things about any 2 points, right? We found some distances between points. We found some midpoints between points. And what we're going to do is now graph equations. Now, graphing equations itself isn't a crazy process, but there are some very interesting things that come out of graphing. So let's just look at some basics. Well, think about when we were solving equations in chapter 1. If we plugged in some answer from our solution set, if the equation held true, then we would have, we would say that thing is a solution. Well, here in chapter 2, when we're looking at things in 2 dimensions, we now not only have a single x equals or x is greater than something, what we now have is a point that we're plugging in. So no more just x equals and plugging in things for x. What we're now going to be doing is plugging in x's and y's. So we say the coordinate point AB is a solution if it satisfies an equation when plugged in. So for example, the equation y equals x squared plus 1 has a solution 2, 5, because if we plug in 2 for x and 5 for y, well, we get 5 equals 2 squared plus 1. We know 2 squared is 4, and 4 plus 1 is 5. This equation's true, so this is a solution. However, 3, 7 wouldn't be a solution, because when we plug in 3 in for x and 7 in for y, then 3 squared is 9, 9 plus 1 is 10, and 7 doesn't equal 10. So in the graph of y equals x squared plus 1, 2, 5 will be one of the points that's included, but 3, 7 will not be. So the graph of an equation in general is actually a collection of solutions. We rarely ever think about it that way. We kind of think about them as individual points that we connect. But in all actuality, the graph of an equation is actually all the solutions associated with that equation. So just some terminology here. If y is found by plugging in x, then we say y is the dependent variable and x is the independent variable. Or in other words, what we're doing in most cases, plug in x to get some y. All right, easiest way to graph is to make what we call a table of values. And in general, maybe like plugging in values from negative 3 to 3 might be helpful, but that isn't going to be always your only option. So we're going to begin with a set of x values and plug them in to find corresponding y values. Well, if we plug in x's and we get y's, we have a bunch of coordinate points, x, y's, or ab's. So we're going to plot those points and then connect them. So let's say we have y equals x squared minus 3. Well, this is what your table could look like, and we're going to plug in some arbitrary x's that we want to plot. Like I said, in general, negative 3 to 3 isn't a horrible option, but depending on what your equation is, depending on what values are allowed, what values are easy to calculate, you might want to choose some other set of values besides just negative 3 to 3. Again, I'm using negative 3 to 3. That doesn't need to be your only option. Well, if x is negative 3, we're going to plug in negative 3. Negative 3 squared is 9. 9 minus 3 is 6. So that means one of the solutions to this equation is negative 3, 6. And negative 3, 6 will be on the graph of y equals x squared minus 3. Let's do negative 2. Well, we're going to plug in negative 2 for x. Negative 2 squared is 4. 4 minus 3 is 1. So the point negative 2, 1 is on the graph of our equation. Let's do negative 1. Negative 1 squared is 1. 1 minus 3 is negative 2. So negative 1, negative 2 is a point. And I think you guys get the idea here. But take a second, look at all the points that we have. Okay, now you might notice there's some funky things about the y values and the x values, but don't think about those right now. Don't worry too much. We're going to come back to that by the end of the section. Okay, so let's take all 7 of these coordinate points and plot them. That's the first thing we did in 2.1. So all of those points are right here. And what we're going to do is connect them with a nice smooth curve. Now, how did we know it looks like that and maybe not a little bit more jagged? Well, it comes with practice, comes with understanding what x squared looks like. It's a parabola. We haven't really defined what parabolas are, but there we go. Look for the pattern of what your graph will look like. If you can't quite figure out a pattern, graph more points. The more points you have, the easier it is to figure out what your graph is going to look like. Let's do one more. Y equals absolute value of 2x minus 4. Okay, let's plug in negative 3 for x. 2 times negative 3 is negative 6. Negative 6 minus 4 is negative 10. Absolute value of negative 10 is positive 10. So that means we have a point at negative 3, 10. Let's plug in negative 2. 2 times -2 is -4. -4 minus 4 is -8. Absolute value of -8 is +8. Please be careful. Don't use absolute values too early. Simplify the inside before you take absolute value of anything. So we have -2, 8 as a point. -1, 2 times -1 is -2. -2 minus 4 is -6. Absolute value of -6 is +6. So we have -1, 6. All right, at 0, 2 times 0 is 0. 0 minus 4 is -4. Absolute value of -4 is 4. Okay. What else we plug in 1? In the last example, value started to repeat. Are they going to do that here? Is it going to be nice, perfectly symmetrical? Keyword symmetrical here. Well, when we plug in 1, 2 times 1 is +2. +2 minus 4 is -2. -2, absolute value of that is +2. Oh, yeah, you might be able to find patterns, but don't be too quick to jump the gun, so to speak, and look for them, right? See them as they come. And if you don't see them, that's okay. You'll get better at it. All right, if we plug in 2, 2 times 2 is 4. 4 minus 4 is 0. Absolute value of 0 is 0. 2, 0. And do one more. 2 times 3 is 6. 6 minus 4 is 2. Absolute value of 2 is 2. So 3, 2 is a point. So let's plot all those points. And we actually kind of get like a check mark type of thing right here. So maybe you don't see it right away. And if you're looking at this going, I'm not really sure what's going to happen after 3, that's okay. Just plug in more points. It's not going to hurt you. If you were to plug in 4, you would have had 2 times 4 is 8. 8 minus 4 is 4. Absolute value of 4 is 4. So it's okay to plug in more points than necessary. And like I said, maybe -3 to 3 isn't the ultimate option. Maybe you want to do -2 to 5 or -3 to 6, right? Whatever works for you to figure out what the graph looks like, by all means, do it that way. Okay, well, that brings us to something called intercepts. And you've been wondering, why do we solve equations? We haven't solved a single equation so far in this chapter, and here we go. So intercepts are points that cross the x or y axes, or they intercept the x or y axes. So the y-intercept, I just want to go back to our graph here real fast. The y-intercept would be the point that crosses the y-axis. But let me ask you something. Ignoring the graph right here, what do all of the points that would be y-intercepts have in common? This is a y-intercept, this is a y-intercept, this is a y-intercept, this is, right? What do all of these points have in common? Well, I'll tell you since we're not talking directly, but all of them have the same x value. They all have the same x value of 0. So if you want to find the y-intercept, if you want to find where it crosses this line, set x equal to 0. And likewise, x-intercepts, we'll find that in just a second. Well, if we want the x-intercepts, we would set y equal to 0. All of these points that I'm covering with my cursor right now, well, all of them share the same y value, y equals 0. Okay, so y-intercept, you set x equal to 0 and solve for y. Then you would say 0, comma, whatever that y is your y-intercept. X-intercepts, we're going to set y to 0 and solve for x, and x comma 0 are going to be the x-intercepts. Now, you might be wondering why I'm not using y-intercepts, plural, but I'm using it for x-intercepts. Essentially, it comes down to the definition of a function in 2.4, and when we get there, we're going to say that we're not allowed to have multiple y-intercepts, but for now, it's more likely than not you're just going to have a single y-intercept. Okay, so let's find the intercepts of 12x plus 14y equals 16. If I want the y-intercept, we're going to set x equal to 0. So instead of 12x plus 14y equals 16, this is going to be 12 times 0 plus 14y equals 16. Well, 12 times 0 is just 0. 14y equals 16. We're going to divide both sides by 14. And then 16 over 14 is 8 over 7. So the point 0, comma 8 over 7 is the y-intercept. X-intercept, let's set y equal to 0. So 12x plus 14 times 0 equals 16. 12x equals 16. Divide both sides by 12. 16 over 12 is 4/3. But for x-intercepts, it would be 4/3, comma 0. So there is 0, comma, what was it? 0, comma 8 over 7, 4/3, comma 0. And actually, interestingly, when it comes to lines, if you know the x and y intercepts, you can graph them. This is only true for lines, though. We haven't really described what lines are. We'll do that in 2.3. All right, let's find the intercepts of y equals x squared minus x minus 2. Let's solve for the y-intercepts first. Let's set x equal to 0. Well, 0 squared minus 0. 0 squared is 0. Minus 0 is 0. Minus 2 is -2. So 0, comma -2 is the y-intercept. Now, we're actually going to get multiple x-intercepts here, and this is where solving equations became a big deal to us, especially in 1.3. We're going to set y equal to 0, but notice this is a quadratic equation. This is something that you would use quadratic formula for, completing the square, or even easiest, factoring. Set each factor equal to 0, x minus 2 equals 0, you would get 2, x plus 1 equals 0, you would get -1. So -1, 2 are the x-intercepts, but formally written as points, -1, 0, comma 2, 0. So you wouldn't be able to graph this just with those 3 points. You could if you were very careful about what you're doing, but odds are don't try and do what we just did for lines in the last example. Okay, another one. Find the intercepts of x cubed minus 9x. Y-intercept, set x equal to 0. Well, this is pretty nice. 0 cubed is 9. 9 times 0 is, 0 cubed is 0. 9 times 0 is 0. 0 minus 0 is just 0. All right, cool, nice. 0, 0 is our y-intercept. X-intercepts, we're going to set y equal to 0. So let's factor out x to solve this. X squared minus 9 is x plus 3x minus 3. And then set each of these 3 factors equal to 0. x equals 0 at just 0, x minus 3 equals 0 at 3, x plus 3 equals 0 at negative 3. All right, well, we have 3 x-intercepts. That's okay, totally fine. Okay, and what you might also notice is that the y-intercept and x-intercepts are the same, or not entirely the same. There's 2 more x-intercepts than there are y-intercepts, but it's okay that the x and y-intercept match, that we repeat. That's totally fine. It just means it crosses the x and y-axis at the same time. Okay, find the intercepts of x squared plus 9, square root of x squared plus 9. Y-intercept, set x equal to 0. Okay, well, 0 squared is 0. 0 plus 9 is 9. Square root of 9 is 3. So 0, 3 is our y-intercept. Let's do the same for x-intercept. Let's set x equal to 0, or sorry, let's set y equal to 0. Well, let's square both sides. Let's subtract 9 on both sides. And, well, we could take the square root of both sides, but we would get x equals plus and minus 3i. And we've never graphed I before. Or even easier, there's just no solution here. And that's okay. You don't always need an intercept of some type. It's okay to get, no x-intercepts or no y-intercept. It entirely depends on the graph. One thing I'll also note is, we spent a decent amount of time in all of 1.4 talking about I and complex numbers, but at no point did we talk about graphing complex numbers. So almost everything we do here in chapter 2 will be entirely based upon real numbers. So don't worry about I so much when it comes to graphing. Okay, intercepts of y equals square root of x minus 9. Y-intercept, set x equal to 0. 0 minus 9 is negative 9. And we can't take the square root of negative 9. So same thing here. There just is no y-intercept. That's totally fine. X-intercept, however, let's set y equal to 0. Let's square both sides. Let's add 9 to both sides. So we get 9, 0 is our x-intercept. So like I said, not necessarily a rhyme or reason as to when we get x-intercepts versus y-intercepts, and that's totally okay. But now let's talk about symmetry, right? The very first example we talked about when we were making a table of values, it was symmetric over the y-axis. It was perfect on both sides of the y-axis. It matched. Well, there's a specific property of that called symmetry. So they might have symmetry about certain lines or points. And we're going to talk about symmetry again once we get to 2.4, I think, or 2.5. So graphs have symmetry over certain lines or points, like the x or y axes and the origin. Well, we can algebraically determine if something is symmetric. We don't need to graph. We don't need to try and graph something we don't really know how it looks. So to algebraically determine if something is symmetric, we're going to do one of the following things. If we are testing for symmetry over the y-axis, we are going to replace every x with negative x and simplify. Okay, now you might be wondering why symmetry over the y-axis would change x. Well, think about it this way. Here, we had a parabola before where it was symmetric over the y-axis. Now, the y values were the same on the different parts of the symmetry. The only thing that was different were the x values, right? This would have been like x is negative 3. This would have been like x is positive 3. So if we want to check for symmetry over the y-axis, we replace x with negative x. You can also think about it as like solving solving for y-intercepts. Y-intercepts, we set x to 0. Symmetry over the y-axis, replace x with negative x, and then simplify. For symmetry over the x-axis, well, you probably guessed it. We're going to replace every y with negative y. And then for symmetry over the origin, this is kind of weird. Long story short, replace both x with negative x and y with negative y and simplify. Okay, so in all of these cases, you simplify. And if the simplified equation is exactly like the original, exactly the same as the original, then it is symmetric about that axis or point. If it is not identical to where you started, it is not symmetrical over that axis or point at which you are testing. So again, just to summarize, symmetry over the y-axis, replace x with negative x and simplify. If they're equal, symmetric. And you see the cases for x-axis and origin. Okay, so is 1 over x squared plus 5 symmetric over the y-axis? Okay, symmetry over the y-axis, we're going to replace x with negative x. Okay? So we have y equals 1 over x squared plus 5, replace x with negative x, and here's what I mean by simplifying. Negative x squared is the same as positive x squared. Okay, and now no more simplification we need to do, so now the question is this new equation exactly the same as the original? Well, you see that this starting point, this ending point are identical, so that means we are symmetric about the y-axis. Cool. Well, there's the graph of 1 over x squared plus 5, not the prettiest thing in the world, but you see that it is symmetric over the y-axis. 4x minus x cubed, is this symmetric over the y-axis? Well, symmetry over the y-axis, we're going to replace x with negative x. So wherever we see x, write negative x. So instead of 4 times x, it's going to be 4 times negative x. Instead of positive x, right, negative x cubed, it's going to be negative x cubed. All right, well, 4 times negative x is negative 4x. Negative x cubed itself is negative x cubed, but negative x cubed is positive x cubed. Okay, no more simplification we can do, but now, is this equation that we started with identical to the equation that we ended with? The answer is no. So this is not symmetric about the y-axis. Okay. Well, you probably noticed there was something in common with that last example. There's something weird about that example. Why don't we test it over the origin? For symmetry over the origin, replace both x with negative x, and y with negative y. Alrighty, so wherever we see x, we're going to write negative x just like the last one, and wherever we see y, we're going to write negative y just like, or not just like, similar to what we've already been doing. Okay, well, we just simplified the right-hand side before, but we have negative y, and we want to eventually get it to look like y equals to be able to compare them. So why don't we divide everything by negative 1? Divide everything by negative 1 because negative y divided by negative 1 is now positive y. Negative 4x divided by negative 1 is positive 4x. Positive x cubed divided by negative 1 is negative x cubed. And now my question is, are these identical? And sure enough, they are. So it is symmetric about the origin. Okay, very last thing here in 2.2, we're going to talk about graphing circles. This is going to be likely the only time we talk about circles in the entire course. So buckle up. It's not that scary. So with the help of SpongeBob, we're not talking about this or this. We are talking about circles. Of course, Krusty Love from 2002, legendary episode. SpongeBob helps Mr. Krabs go on a date with Mrs. Puff. Very big deal. Okay, the formal definition of a circle is, if I ask you to define it, you're kind of like, well, I don't know. It's like this, right? It's this kind of thing. The formal definition is it's kind of clever, if you're not really thinking in that way, but it's a set of points that are all a fixed distance away from a center. So we have some center, all the points that are, say, 5 units away from that center. So kind of a weird way of thinking about it, but it is very true and it makes a lot of sense. That fixed distance away from the center we refer to as the radius, which we denote with the letter r. And the center is denoted by the point h, comma, k. So here's a good example of why we're not always trying to, reuse the same letters over and over again. A, B, a little different, but hk would be the center of the point. Now, standard form of a circle looks like this. And this is where things are a little strange. Well, this says x minus h squared plus y minus k squared equals r squared. Well, r squared, we can take that for granted. That's not so bad. But you might be wondering why we have x minus h. Well, be very careful. Okay, if our center has positive points, let's say 3, 2. Well, if h is 3, then you plug in 3 here, and you would have x minus 3. If k was 2, you would have y minus 2. So the signs of your center in the equation are going to be backwards. If the center is positive, that part of the equation is going to be negative. So be very careful about that. So let's write the equation of a circle with a center 4, 2 and a radius 7. Well, hk would be 4, 2. So h would be 4, k would be 2, and your radius is 7. Okay, that's given to us. That's not so bad. Well, let's start with this equation right here. And again, h right away is 4 and k is 2. Radius is 7. And now you might be a little uncomfortable with that, like, oh, well, our center is positive, but these are negative. Yes, that is on purpose. Please be very careful. I'm aware this is positive and these are negative. That is by design. Okay, so there's nothing to change here, but we do know that 7 squared is positive 49. Okay, so this would be the equation of a circle whose center is at positive 4, positive 2 with a radius of 7. Let's do the same thing, but for negative 6, 3. Well, hk is negative 6, 3. So h is negative 6, k is 3, the radius is 1. So again, when we go to plug these things in, just be very careful. H is negative 6, k is 3, and radius is 1. Well, here, now we see the difference between positive center values and negative center values. X minus negative 6 is positive 6. Y minus 3 doesn't change, and 1 squared is just 1. So again, there is an element of like kind of flipping signs here, sort of. So be very careful with the signs of your center in or coming from an equation. Okay, let's do one more example of writing equations. Center is negative 5, 9, and the radius is square root of 14. hk would be negative 5, negative 9. So h is negative 5, and k is negative 9. Radius is square root of 14. That's given to us. Okay, well, x minus h plus y minus k squared equals r squared. H is negative 5, k is negative 9, and r is square root of 14. But here we're going to get plus plus, here we're going to get plus plus, and square root of 14 squared is just 14. So again, I can't stress enough, be careful with centers of circles. Well, what if we want to go backwards? Alrighty, well, x minus 6 squared plus y minus 7 squared equals 100. The center is always h, k, so in this case it would be 6, 7. Don't forget, negative 6 is going to mean positive 6, negative 7 is going to mean positive 7. Now the radius, well, in the circle equation, it's x minus h squared plus y minus k squared equals r squared. So r isn't 100. R squared is 100, which means that r is 10. So, technically you take the square root of both sides, you get r equals plus and minus 10. Kind of like hypotenuse in 2.1, it doesn't make sense to talk about, negative distance. So radius is 10. X plus 7 squared plus y plus 6 squared equals 25. Well, center is going to be backwards values, right? X minus h, this is x plus 7. So our center is going to be negative 7 and negative 6. Radius, well, r squared is 25, so r is 5. Okay, again, be careful with signs. X squared plus y squared equals 1. Well, there's nothing adding or subtracting x, so center is just 0, 0. Okay, Well, radius, r squared is 1, but that also just means that r is 1. So, we could also have written our circle like this: x minus 0 squared plus y minus 0 squared equals 1. And now you kind of see a little bit more as to why the center is 0, 0. Also, this is the equation of what is called the unit circle in pre-calc, so you might see this equation again in the future. X minus 10 squared plus y plus 10 squared equals 12. Well, center, alrighty, x minus h. So h is positive. X minus h is 10. Y minus k, but k is going to be negative, right? Opposite signs. So the radius, well, r squared is 12, which means that r is square root of 12. So be careful of that as well. Let's say we wanted to graph. Well, let's do exactly what we were just doing. Extract all of the information about the circle and then go to graph it. Well, our center will be -2, +3. The radius, well, r squared is 25, so r is 5. So what we're going to do is start from the center, -2, 3, and go out 5 units. The radius, 5 units in each direction. So let's plot the center, -2, 3. Let's go 5 units up, 5 units to the right, 5 units down, and 5 units to the left, and connect those points. And that's how we get a circle. Okay, let's do it one more time. X minus 5 squared plus y plus 1 squared equals 9. Well, our center is going to be +5, -1. Well, r squared is 9, so r is 3. Okay, so start at the center and now move 3 units in every direction. There's 5, -1. Go up 3, go right 3, go down 3, go left 3, and connect those points. And that's how we graph circles. Not the scariest thing on the planet, I don't think. Okay, so that's 2.2. We are slowly working our way to functions. So we've now done what the plane is, graphs of any equation, and what we're going to do in the next section are lines. Okay, so with that said, I will see you in 2.3. Bye. Hi, everyone. Welcome back for 2.3. So in 2.1, we started talking about the coordinate plane. 2.2, we talked about any graph, how we can get any graph. And now we're going to look at the very specific study of just lines. So the entire section is just about lines. So first thing we're going to talk about is slope. So linear equations, right? We looked at linear equations in early chapter 1, and linear equations result in lines for graphs. That's not really surprising, right? Linear lines, right? So the first thing we need for a linear equation is the slope. Now, the slope of a line represents the steepness of a line. How fast does it grow, or how fast does it decline? How slowly does it decline, and so on. So one way that a lot of people remember this is rise over run, or in other words, the change in y divided by the change in x. So to find slope, we use the letter m, and m is given as y2 minus y1 over x2 minus x1. So same way as we found midpoint, same way as we found distance, same way as we have found a lot of different things with x1, y1, x2, y2, same thing here. So we're going to subtract the y values, divide by, subtract the x values. So rise, how much does the y change? How much do we go up and down over the course of some interval, divided by how much we changed in terms of x, how much we ran, so to speak. So if your slope is positive, your line trends upward. So positive slope goes up. If m is negative, though, your line trends downward. So positive slope, positive m, is kind of like something is growing, whereas negative slope is like something is decreasing. If you have m equals 0, your line is horizontal. So if that's the case, it means the line is running, but it's not rising. So for example, if it doesn't rise, if it's horizontal, right? Horizontal, the y value doesn't change. Well, 0 divided by anything is just going to be 0. So m equals 0 are horizontal lines. Vertical lines, on the other hand, similar, but they have undefined slope. Well, vertical lines, they rise, but they don't run. Well, so if it's rising but not running, y is changing and x is not. So in that case, anything divided by 0, undefined. So in the very specific case of vertical lines, they have undefined slope, whereas horizontal is 0 slope. Very different. So let's do some practice of just finding slope. So we have 1, -1, and 3, 3. Just like we've done in the past, this can be x1, y1. This can be x2, y2. So our slope is y2 minus y1 over x2 minus x1. So we're going to take the y values, subtract them, 3 minus -1 over 3 minus 1, the x values. 3 minus -1 is just 3 plus 1. Well, 3 plus 1 is 4, 3 minus 1 is 2, so our slope is 2. So for every 1 unit that we run, we go up 2 units, or for every 2 units that we run, we rise 4 units, and so on. Okay, let's do another one. -7, 5, and 6, -3. Well, we know what the slope equation is, so we don't need to keep remembering it each time. But here we go. Here's the slope equation. Same thing. Let's subtract the y's. -3 minus 5 over 6 minus -7. 6 minus -7 is addition, so 6 minus -7 is plus. $3 in debt, spend $5 more, you're $8 in debt. So 6 plus 7 is 13, or just -8/13. So both of these would be correct. Okay. -2, -3, and 5, 4, same thing. y2 minus y1 over x2 minus x1. Both cases, minus is plus. Well, 1. That means for every unit that we rise, we also run 1 unit. It goes up 1, right 1, up 1, right 1, up 1, right 1, and so on. But just like a lot of the other things we've talked about so far in this chapter, order doesn't matter. So using the exact same points, if we instead want to use, 1, -1 as x2, y2 for some reason, right? Maybe you just prefer going that way. And then this was x1, y1. Well, guess what? -1 minus 3, -4, 1 minus 3, -2. -4 divided by -2 is +2. Exact same answer we got in the last slide. Okay, same thing, -7, 5, and 6, -3. Let's call this x2, y2, and this one x1, y1. All right, well, okay, so 5 minus -3 is plus, $7 in debt, spend $6 more, -13. 8 over -13 is the same as -8/13. It's just like the last one, right? Numerator's negative or denominator's negative. We can just write that negative on the outside. Last but not least, let's do the same thing with these last 2 points and see that we get the exact same thing. You're $3 in debt, you spend $4 more, you are $7 in debt. Or if you have $2 in debt and you spend 5, you're still $7 in debt. -7 divided by -7, anything divided by itself is 1. Okay. So that's slope. And what we want to do is write equations of lines. And we have 2 ways we do that. We have 2 ways. One is called point slope form and the other is called slope intercept form. I personally really like slope intercept form, but a lot of people across the world don't mind slope intercept. So I'm going to be very centric to slope intercept, but don't think that point slope is necessarily bad. It's really just a preference in the way I teach. So here's the slope equation. And what if we multiply both sides by x2 minus x1? Just multiply both sides by the denominator. Well, here, this obviously cancels out. That's the whole point. And if we just rearrange terms and relabel some things, this is what is called point slope form. It's called point slope form because you have the slope m, and you would plug in any point on the line, x1 and y1. So for that reason, since you are plugging in a point and a slope, it's called point slope form. So we need 2 points to find the slope, but we only need to include one of those 2 points when we're doing point slope form. Now, it doesn't matter which one we're given. So, we need 2 points to find the slope. That we can't negotiate on. But of those 2 points, when we go to plug it into point slope form, we have a choice of using either point. So let's do just that. Let's say we have these 2 points, -3, 1, and 2, 11. I want to find point slope form, and then I want to solve for y. Okay, well, we start with the slope always. Let's subtract the y values divided by subtract the x values. 10 over 5, that's 2. Okay, well, point slope form is this equation right here. And what we're going to do is plug in 1 point and plug in the slope. So for this one, let's plug in -3, 1 for x1 and y1, and we're going to plug in 2 for m. So we get y minus y1, which is just 1, equals 2x minus -3. Okay, well, we can do one step of simplification. X minus -3 is x plus 3. And this is formally point slope form. So a lot of people in math don't mind this notation right here to write lines. But for me, let's say we want to solve for y. Okay, well, we can distribute 2, and then we can add 1 to both sides, and we get y equals 2x plus 7. Okay, I think it's a little cleaner this way. We have a name for that thing. Well, I already said it before, but we'll give it just another second until we get there. But I just also want to take the time to show you that it doesn't matter which point we use. I told you you can use either point and you should get the exact same answer. So let's do the exact same thing, but with 211 instead. So slope is still 2, right? It's the same 2 points, but we're going to plug in 2 for x1 and 11 for y1 this time. All right, we still distribute 2. This time we're going to add 11 to both sides to solve for y. You're $4 in debt, and somebody sends you $11, you now have $7 again. So point slope form, they are really the exact same line when you solve for y. Now, this solved version for point slope, right? Point slope is this version right here, or the one that we had on the previous slide, but this solved for version, this kind of cleaner version, is called slope intercept form, because what we have is the slope m, okay, surprise, surprise, and what so happens to be the case is that b is the y-intercept. Think about that. Y-intercept is when we set x equal to 0. So if x is 0, well, m times 0 is just 0, and then 0 plus b is just b. So m is your slope, b is your y-intercept, hence slope intercept form. Okay, so let's do some practice of finding slope intercept form. So let's do 5, 0, and 0, 8. Let's find the line between them. I have an asterisk here just because when we get to that step, I'm going to plug in 5, 0. On the next slide, I'll show you plugging in 0, 8 and how it's the exact same thing. All right, find slope first, subtract the y values, subtract the x values. Also, more so now than every other thing that we've kind of looked at, it's okay to change the order in which one is x1 and y1 and x2, y2, but just be very careful that when you do that, you stay consistent. So for example, if you're calling this x2, y2, make sure that you do this y minus this y over this x minus this x. Don't magically flop and say like this is x1, y2 and plug it in that way. That's not going to be good. So just be careful of that. Okay, so we have our slope. Here's slope intercept form. And what we're going to do, similar to point slope form, just with a different equation, we're going to plug in slope m. But instead of plugging some point into x1, y1, we're just going to plug that point into x and y. Writing equations, you've already seen that every equation has a y and has an x, but b would be new. So we need to solve for b. Okay, so y is going to be 0, m is going to be -8/5, and x is going to be 5. We'll start by plugging in the slope, and now I'll plug in that term. All right, 5 cancels out. We're going to add 8 to both sides, and we get b equals 8. Now, that's not the end of the question. We want to write the formal equation. The formal equation says y equals -8/5 x plus 8. And that is very formally slope intercept form. And now you see that because we have the slope -8/5 and we have the y-intercept 8. Oh, it actually happens to be right there. But just for the purpose of showing you, that's how we would get it. Well, let's do the exact same thing, but this time we're going to use 0, 8, just to show you that it doesn't matter what point we plug in. So now let's plug in 0 for x and 8 for y. All right, well, negative 8 fifths times 0 is just 0. Oh, look at that. b is 8. So if you do this correctly, it doesn't matter what point you plug in, you should get the exact same answer for point slope, for slope-intercept form. Okay, let's do another example of that. 11, 20, and 8, 14. Let's start by finding the slope. At this point, we're pros of doing this. Let's subtract the y values divided by subtract the x values. Subtract, and negative 6 divided by negative 3 is positive 2. Okay, so when y equals mx plus b, m is 2. And now we want to solve for b. I believe I'm going to plug in 11, 20 for x and y. Yeah, there we go. 2 times 11 is 22. Subtract 22 on both sides, we get that b is negative 2. So the answer to slope-intercept form is y equals 2x minus 2, or plus negative 2, but also, plus negative 2. It's a lot easier to just write negative 2. And again, for practice, try doing the same thing with 8, 14. In this step right here, you'll see you get the exact same answer. Alrighty, let's do another set. Negative 5, 1, and 2, 7. Subtract the y values over subtract the x values. 2 minus negative 5 is 2 plus 5, so we get 6 sevenths, sorry. Okay, well, y equals mx plus b, m is 6 sevenths, and we're going to plug in an x and a y. I don't remember which one I use. We're going to use the second point here. Alrighty, so plug in 2 for x, 7 for y. 6 sevenths times 2 is 12 sevenths. We're going to subtract 12 sevenths on both sides. I'm going to trust you can subtract fractions. So slope-intercept form is y equals 6 sevenths x plus b. b is 37 over 7. Okay, so now that we have slope-intercept form, we actually can now graph lines in a slightly easier way. So the easiest way to graph is to find the x and y intercepts of whatever your line is and connect them infinitely. That's the easiest way to graph lines. So let's graph y equals 4x plus 12. All right, well, let's find the y-intercept. To find the y-intercept, we set x equal to 0. So y equals 4 times 0 plus 12. Y is just 12, right? 4 times 0 is 0. 0 plus 12 is 12. So the y-intercept is 0, 12. X-intercepts, we're going to set y equal to 0. Well, 0 equals 4x plus 12. Let's subtract 12 on both sides. Let's divide both sides by 4. So the x-intercept is negative 3, 0. Okay, we're going to graph these 2 points, draw a line between them, and connect them infinitely. Easiest way to graph. So there's a little theory in there as to the fact that linear equations are degree 1, and and that we needed 2 points to graph it. That we'll come back to in chapter 3. But for now, it's good practice. Alrighty, 12x plus 6y equals 12. Well, first things first, let's get this into slope-intercept form. In general, it's a lot easier to deal with slope-intercept form, and it's a lot cleaner looking. This is technically called standard form, but to each their own. Okay, so to solve for y, right, slope-intercept form has y all by itself. Let's divide everything by 6. Just kidding. Okay, let's start by dividing everything by 6. So 12x divided by 6 is 2x, 6y divided by 6 is y, 12 divided by 6 is 2, and then let's just subtract 2x on both sides. Alrighty, well, y-intercept, we're going to set x equal to 0. Well, pretty clear to see that y is just 2. Negative 2 times 0 is 0, so 0 plus 2 is 2. Y-intercept is 0, 2. X-intercepts, we're going to set y equal to 0. So we're going to subtract 2 on both sides. We'll divide both sides by negative 2, excuse me. So our x-intercept is just 1, 0. So we're going to graph those 2 points and connect them infinitely. Not bad, but we actually didn't need to do that. It was nice to get it into slope-intercept form, but nothing about this said we needed to put it in slope-intercept form. All we care is graphing the thing. Well, if we only just want to graph it and we don't care about what the actual line is, why don't we just go for finding the intercepts right away? Y-intercept, set x equal to 0. So 12 times 0 is 0, divide by 6. Oh, we get 0, 2 again. And same thing for x-intercept, set y to 0. 6 times 0 is 0, divide both sides by 12. We get x equals 1 again. So, kind of keep an eye out for what the question's asking. If somebody's not asking to get the equation of a line, maybe you don't need to. So just something to keep in mind. All right, one more example of this. 3x minus 4y equals 12. Y-intercept, let's set x equal to 0. So 3 times 0 minus 4y is 12. Well, 3 times 0 is 0. Negative 4y equals 12. Divide both sides by negative 4. So our y-intercept is 0, negative 3. X-intercept, let's set y equal to 0. All right, well, 4 times 0 is 0. Divide both sides by 3. We get 4, 0. And there we go. Okay. So that's slope-intercept form. That's how we formally graph lines. I think it's a nice, easy way of thinking about it. But let's just look at some other weird lines, because why not? Alrighty. Horizontal lines. They all have a constant y value. So their form, how you would write a horizontal line, is just y equals k. If you want to think about this in terms of slope-intercept form, think about the fact that slope-intercept form, y equals mx plus b. But we said in the very beginning that horizontal lines have 0 slope. So it'd be y equals 0x plus b. But 0x would just be 0. So you just get y equals b. In that case, instead of using b, we just use k. Vertical lines have a constant x value. So similarly, this would be x equals h. Or h and k in both cases are just real numbers. So for example, we have y equals 2 and x equals 4. Very, very, very exciting. So, but more interestingly, parallel and perpendicular lines. So parallel lines run side by side each other. Imagine you and your friend are running in the park and you are both running side by side each other. You are parallel to each other. So they never meet and they have the same slope, right? Maybe you and your friend aren't necessarily running at the same pace, but you are in the same direction. Just the goal is to make sure you guys never meet or crash into each other. So parallel lines don't meet, but they have the same slope. So for a line with slope m, a line parallel to it, this m parallel notation right here, well, the parallel slope to any line would be just m. Okay, now you're kind of wondering what does that mean? M parallel equals m. It just means that the parallel slope is the same as the original. Now, a line perpendicular to another line creates a right angle when it meets. So for example, if you're running in this direction, a perpendicular line runs in this direction. You kind of create like an X or a cross, and you would create a right angle where they meet. So it's a little harder to see. It'll make a lot more sense when you see it graphed, but in that case, m perpendicular, that slope is -1 over m. A good way of remembering that is flip the slope, make it negative. Not that that's easier to remember, but I think it's a little bit easier to remember this right here. Perpendicular slope, flip it, make it negative. Okay, so let's find the equations of a line parallel and perpendicular to y equals 2/3 x plus 2, each of which will pass through 2/8. Okay, well, here we have y equals mx plus b. The parallel line slope, okay, well here, slope is 2/3. Now, the line parallel to a slope with 2/3 is also 2/3. So m is 2/3 in our question. Any parallel line will also have 2/3 slope. Perpendicular slope is going to be -1 over m, or in other words, take your slope, flip it, and make it negative. So instead of 2/3, flip it to 3/2 and make it negative. Well, now this question is just like any other question that we've dealt with in the past. Here we have a slope, we have a point. All we're going to do, y equals mx plus b. We have m is 2/3, x and y come from 2 and 8. All right, 2/3 times 2 is 4/3. Subtract 4/3 on both sides. We get, fraction, subtraction. So b is 20/3. So y equals mx plus b. M is 2/3. B is 20/3. So the line that is parallel to y equals 2/3 x plus 2 that passes through 2/8 is this line right here. Okay, and there you go. They literally run parallel to each other and they will never meet. That's the whole point of being parallel. Okay, well, likewise, doing this with perpendicular lines. This is the slope we want to work with. So plug in m, x, and y. Well, a little bit nicer here. 2 divided by 2 is just 1. Add 3 to both sides, we get 11. So y equals m, x plus b. And there we go. This is what a perpendicular line would look like. They cross, they make a right angle right here. A little bit easier to visualize. Okay, let's do another example of this, but let's find the equations of any parallel line and any perpendicular line when the original line is 5x plus 1. Okay, well, m is 5 here, right? Y equals mx plus b. So that means the parallel slope is just itself, and the perpendicular slope would be -1 over that slope, -1/5. Alrighty, so we have our parallel slope. We don't have a point this time. I'm just saying do any points. Well, the original equation's y-intercept is 0, 1. Well, why don't we just use 0, -4? I don't know, totally arbitrary. Well, y equals mx plus b. Plug in m, x, and y. So b is just -4, y equals 5x minus 4. That's it. You have a slope. We found some other random y-intercepts, and there we go. Not so bad. Alrighty, one more example of this. The perpendicular slope is -1/5. Original y-intercept is 0, 1. Let's use 0, -1. Why not? Let's be weird. Alrighty, y equals mx plus b, m, -1/5. X is 0, y is -1. Oh, actually, that wasn't a bad choice because that's just going to go away. So y equals mx plus b, y equals -1/5, x minus 1. There we go. Very, very exciting. And that's the end of 2.3. So 2.1, 2, and 3 kind of set up this very nice, like what graphs are type of deal. But what we're going to do for the entire rest of the section is, rest of the chapter is introduce functions. So functions are kind of like the study of algebra, right? We need functions to describe a lot of the things that we're going to be doing. And that's going to carry us all through the rest of the chapter and all through chapter 3. So I will see you in 2.4. Bye. Hi, everyone. Welcome back to 2.4, where we really start talking about like the big study to college algebra, and that's functions. So like I said, at the end of 2.3, functions are going to carry us through most of the rest of the way. So yeah, we're gonna get right into that here. So functions in general are rules that assign elements from one set to exactly elements in another set. So technically you can have a mapping where any number of x's go to any numbers of y, and you can have whatever you want. But for functions, we very specifically want rules or mappings where elements in some starting set x get mapped to exactly one element in some ending set y. Well, this starting set x we would refer to as the domain, and y, this ending set, we would refer to as the range. Domain is where we start, range is where we end. And maybe you're already starting to think about x's and y's. What do we usually plug in? Do we normally start with x's and find y, or do we normally start with y's and find x's? It's almost like I use the right letters when I'm defining these sets. So the rules for functions, again, is that every element in set x, every element in the beginning set x, has to be assigned to something in y. However, not everything in y has to be used. Everything in x has to be used, not everything in y. Likewise, Every element in X can only go to one element in Y. However, multiple X's can go to one Y. It's just that X can only be used once. Y's can be used more than once, but X's may only be used once. So correspondence diagrams, we're not going to spend a whole lot of time with this, but I'm going to move to the whiteboard just to show you some examples of what would be a function and what would not be a function. Okay, so now we're on the whiteboard. Just in general, what a correspondence diagram would be is something like this, X and Y. Let's say we have 1, 2, 3, 4, 5, 6, and just any mapping, just to show you what a general mapping could look like. 1 could go to 4, and 2 can go, and 2 can go to 5, and 1 can go to 5, and 3 can go to 4, and 3 can go to 6, and why not? 3 can also go to 5. Just this mapping of X's to Y's. Now, I'm not going to comment on this one. This is not a function by any stretch of the imagination, but let's go into some of the properties specifically of functions. I just wanted to show you a very quick correspondence diagram. So let's say we have some set X, some set Y, and we're mapping from X to Y. Okay, so let's again go 1, 2, 3, 4, 5, 6, 7, 8. So the rules of functions are as follows. First rule is that every X must be used, and 2, every X can only be used once. Okay, so for example, 1 can go to 8, 2 can go to 6, 3 can go to 5, and 4 can go to 7. This checks both rules. Every X was assigned to something in Y, and every X was assigned only once. So that's okay. There's nothing wrong with that. Now, another example of something that would be okay would be something like 1 goes to 5, and 2 goes to 5, and 3 goes to 5, and 4 goes to 5. Just to review the rules again, well, every X was used, and every X was used once. We don't have any rules that run against multiple Ys, or Ys being used multiple times. So as long as it checks these two rules, we are totally okay. All right, let's do an example of something that would not work. So for example, let's say 2 goes to 6, 3 goes to 8, and 4 goes to 7. Okay, let's go through our two rules. Every X must be used. Well, 1 wasn't used. Well, that's kind of a problem. That fails the first rule. So this, as written, is not a function because X equals 1 was never used. Okay. So that would be an example of something that isn't a function. Well, let's do another example of something that is not a function, but maybe it violates the other rule. Okay, so let's say 1 goes to 5, and 2 goes to 6, and 3 goes to 7, but 3 also wants to go to 5, and 4 goes to 8. Well, let's look. Was every X used? Yeah, 1, 2, 3, 4, 5. 1, 2, 3, 4 were all used. However, not every X was only used once. Look at 3. 3 went to 2 things. It went to 5, and it went to 7. That violates the second rule because every X was used. Sorry, at least one X was used more than once. So even if one X does this bad thing, that's all that matters to make it fail. So that's how we visually define functions. Of course, we're going to do this more with algebraic methods and terms, but I still wanted to show you this nonetheless. So I'll see you back at the presentation. And now we're back at that presentation. Okay, so let's now introduce function notation. And what we use is this f of x in parentheses. This is not f times x, right? In the past, we have used parentheses to denote multiplication. This is not that. This is f of x. Or in another way, saying the value of f, the value of your function, at some x value. Okay, well, we also use y to denote the exact same thing, right? We can say that y is the value at x. So in a lot of ways, y and f of x are interchangeable. And maybe at some point in the section, we will do something where we literally interchange f of x and y. So like I said, f of x is saying value of the function at x. Y is also saying the value of your equation at x. So they're very, very similar. If you can write something as f of x equals or y equals something specific, where you get only one y value for every x, right? It correspondence diagrams. If we had something where every x only goes to one y, we are good to go. Okay? It would then be a function. So let's do that algebraically. What we want to do is get exactly like I have written here, y equals one specific thing. So if we can write this as y equals where every x only goes to one y, we are good to go. Okay, so we're going to solve for y, right? That's what y equals would be. So let's subtract 6x squared on both sides, and let's divide everything by -3. Now, this, let's see, does every x go to 1y? When I plug in x, how many y's do I get back? Well, if I plug in x equals 0, totally arbitrary, let's plug in x equals 0. Well, 0 squared is 0. 2 times 0 is 0. 0 minus 4 is -4. But that doesn't really mean anything. What we're most concerned about is that when we plugged in 1x, we only got 1y back. That's the key here. So every x only goes to 1y. No matter what we plug in for x, we can only get 1y back. So this is a function. Now you're probably wondering, how could this possibly fail? Well, let's do one like this. Let's solve for y. Let's add x to the fourth to both sides. Let's take the square root of both sides. But don't forget that when you take the square root of both sides, you get plus and minus. Okay, maybe we already start to see the problem. All right, let's plug in anything for x and see how many y's we get back. Let's again plug in x equals 0, because why not? Well, 0 to the fourth is just 0. 0 plus 4 is 4. Square root of 4 is 2. But then we tack on plus and minus to that 2. So when we plugged in one single x, x equals 0. We got two answers back. We got positive 2 and we got negative 2. One x went to two y's. So this is not a function. Okay. X plus y cubed equals 12. Let's subtract x on both sides, and let's take the cube root this time of both sides. But think back to 1.5. In 1.5, when we take a cube root or an odd root of both sides, we do not get plus and minus. So we can take the cube root, it's not an even root, and we are good to go. Well, you already see we don't have plus and minus this time. So let's plug in x equals 0. Why not? Well, negative 0 is 0. 0 plus 12 is 12. Cube root of 12, no idea what it is. The point is we only got one answer back. So 1x goes to 1y. This is a function. All right, just moving up the ladder. Let's say y to the 4th. You probably already know what's going to happen, but let's subtract x to the 8th, 15x to the 8th on both sides. Let's divide everything by negative 1. And now let's take the 4th root of both sides. But don't forget, when you take the 4th root of both sides, you again get plus and minus. Okay, and now you see no matter what we plug in, we're going to get two y values back because of the plus and minus. So not a function. All right. Another thing we're very interested in when it comes to things that are actually functions, not guessing and checking whether or not something is a function. Okay, we're given something, we know it's a function. We want to evaluate at specific x values. Well, to evaluate a function, simply plug in whatever value you want for x. So let's say f of x equals x squared minus 6x plus 8. Well, we moved from y equals x squared minus 6x plus 8 to just f of x equals x squared minus 6x plus 8. Let's say I want f of 3. F of x equals 3. Well, here, f of x, f of 3, the only thing that changes is wherever we see x, we're going to write 3. So plug in 3 in parentheses, and now it is just simplifying. 3 squared is 9. 6 times 3 is 18. 9 minus 18 is negative 9. Negative 9 plus 8 is negative 1. The value at 3 is negative 1. That's basically the point. 3 comma negative 1. No different from how we have done it in the past. F of negative 2 says wherever we see x, plug in negative 2. Again, use parentheses. Be very careful. We've talked about this problem so many times. Negative 2 squared is positive 4. Negative 6 times negative 2 is positive 12. So we get 24. Okay. F of 1/2. Yeah, I know how much you guys love working with fractions, but same thing. All it says is wherever we see x, plug in 1/2. 1/2 squared is 1/4. 6 times 1/2 is 3. And I'm going to trust that you guys can add and subtract fractions. Okay, so you see the pattern here. Wherever we see x, just plug in that value. That's it. Nothing else. What if we want f of potato? Nothing says we can't do that. Well, f of potato says potato squared minus 6 times potato plus 8. Whatever we want to plug in for x, all it says is replace x with that value. Of course, potato is a little silly. I totally get it. But the idea here is it does not matter what is in here. All it says is to plug in that thing for x. So kind of moving in that same direction, what if we don't want to plug in just a single value? We want to plug in another expression. And we're going to do that quite a bit here and in the future. So f of a plus 2 just says wherever we see x, write a plus 2. So a plus 2 squared minus 6 times a plus 2 plus 8. That's it. This is foiling. This is distribution. And now just combine like terms. It doesn't always have to be something we can combine. It's okay. Alrighty, 4a minus 6a is negative 2a. 4 minus 12 is negative 8. Negative 8 plus 8 is 0. A squared minus 2a. It's not as comfortable. I get it. We want to plug in numbers and we get numbers back. But that doesn't always have to be the case. And you're going to see in the future how we would get something useful doing something like this. Okay, for example, we can also do f of x plus h. Now, let's be very, very, very clear about something. I understand there is an x here and there is an x here. These x's are not the same thing. This is saying some single x value in space. This is saying the expression x plus h. So same thing. I know it already has an x there and we have an x in our original function. That doesn't matter. Wherever we see x, we're going to write x plus h. And again, this is going to be foiling. You are going to foil, you're going to distribute, and you get to something that it can't even be combined, but that is totally fine. There's actually very good use for something like this. I don't remember what section it's in. It might be in 2.5, but I can tell you for sure, those of you that have to take calculus in the future, you will see f of x plus h again. So again, wherever you see x, just plug in that thing in parentheses. All right, let's do negative 2x squared plus 5x. F of 0, wherever we see x, plug in 0. 0 squared is 0. Negative 2 times 0 is 0. 5 times 0 is 0. All right, whole thing 0. That's very exciting. F of negative 1, wherever we see x, plug in negative 1. Negative 1 squared is positive 1. Negative 2 times positive 1 is just negative 2. 5 times negative 1 is negative 5. Negative 2 minus 5, negative 7. F of x plus h, wherever we see x, we're going to write x plus h. I get it. I know it is uncomfortable because there's already an x there and you just want to plop on a plus h. Can't do that. Imagine this was an a. If this was a plus h, well, you'd already be good. You'd have nothing to worry about. But it isn't a plus h. It's x plus h, and it functions exactly the same way as if it was a plus h. All right, this is foiling. This is distribution. All righty, foil the insides, then distribute -2, and that's all you get. We have to leave it like that for right now, and that's okay. Okay, well, that's the basics of function. That's probably one of our longest basics we've had in a long time, but yeah, so it goes. All right, domain and range. Well, domain and range, we talked about on that very beginning slide. Domain is the set of all places we start, and range is all the places that we end. So domain, in general, for algebraic functions, not like what we were doing before, is the set of all real numbers for which our algebraic function is defined. And we always write these things as intervals. Okay, another good way of thinking about it is the set of all x values that are included. Okay, what I mean by that is take the set of x values that when you plug it in, you get something normal back. You don't get like 2/0 or square root of -3. So by default, a function's domain is -infinity to infinity, or all real numbers. However, we have some red flags that we need to bring up when they happen. First one is for rational functions. Rational functions are just functions with a denominator. And in that case, well, think about what causes problems when we're in a denominator. We can't divide by 0. So in rational functions, the denominator cannot be equal to 0. Okay. Square root functions. Well, we know we can't take a square root of a negative number, so we need to make sure the inside is not negative. If you have a square root in the denominator, well, kind of like a combination of the previous two examples. These two are kind of red flags on their own, these first two bullets. This third bullet, though, is a nice combination of them. Well, we just said square roots. The inside of a square root can't be negative. So that means it can be 0 and it can be positive, but if it's in the denominator, it also can't be equal to 0. So long story short, inside must be positive, not just negative, must be positive. So it can't be 0, it can't be negative, it has to be positive. If you have a rational and a square root, so for example, you have a square root in the numerator and there's still a denominator that causes problems, find the domains of each part and then take their intersection. This happens not frequently enough for us to spend a whole lot of time doing it. So let's find some domains. Find the domain of 400x squared plus 236x plus 19,003. Well, look at the red flags that we have. We have rational functions, we have square root functions, and all even root functions, right? We can't take negatives inside an even root. But rationals, fractions, square roots, those are our red flags. And we don't have either of those here. How nice. There is no rational, there's no denominator, and there's no square root, so we have nothing to worry about. No denominator, no square root. By default, our domain is all real numbers, -infinity to infinity. What this says is that you can plug in anything you want for x, and you will always get a defined number back. It might not always be a pretty number. It might be very big, or in this case, can anything be negative? I don't even think so. So, it might be very, very big and very, very ugly, but the point is it's defined, and that's the key to domain. Find a domain of 1 over 2x minus 6. Well, this is a rational function. It has a fraction. It has a denominator. And we want to make sure that the denominator never equals 0, right? The only place that this could be undefined is when the denominator is 0. Well, rational denominator cannot equal 0, so we set the denominator not equal to 0. You can similarly set it equal to 0 and take those values out. It kind of has the same ending effect. Well, just like equations, let's add 6. Let's divide by 2, and we get x cannot equal 3. And now I want to write that as an interval. So just for one quick example, I'm going to show you how this would work on a number line. I'm not going to do it on every single one. Normally when we're in person, I like using people to kind of come up to the front of the room. But let me draw this one out for you guys. Okay, so we have our function f of x equals 1 over 2x minus 6, and we say the domain is x cannot equal 3. However, we write domain as intervals, right? We've been talking about intervals for the last couple chapters. So how do we write that? Well, on a number line, right, these are all going to be x's. This is -infinity to infinity, and we're saying we can be everything except 3. We don't want to be 3. Absolutely not 3. If you plug in 3, 2 times 3 is 6. 6 minus 6 is 0. So 3 is our only problem child, so to speak. However, just because 3 is a problem doesn't mean everything else is. We can be everything to the left of 3. We can also be everything to the right of 3. So here's how we write that. Everything to the left of 3 would be -infinity up to 3. Right? This says all the x values to the left of 3, with 3 not included because we're using parentheses. Okay? Well, we can also be everything to the right of 3, right? This was everything to the left of 3. This is everything to the right of 3, and that would be 3 to infinity. Again, 3 not included. So this right here would be the domain written in interval form. A good way of looking at this just says everything except 3. And that's all it is, right? It includes everything except 3, which is not included on either side of 3. So that's how domain's going to work. I'm going to come back and do like one example when we get to other cases, but in general, this is the thinking here. Okay, let's go back to the presentation. Okay, and we're back, and just to go over that again, we're saying everything to the left of 3, everything to the right of 3. All right, 1 over 1 minus x squared. Well, we want to make sure that the denominator does not equal 0, right? That's our red flag here. Okay, 1 minus x squared cannot equal 0. Well, we can factor 1 minus x squared. We can set each factor equal to 0, so we can be everything except -1 and 1. Okay, well, think about this. We can be everything except -1 and 1. We can be everything to the left of -1. We can be everything in between -1 and 1. And we can be everything to the right of 1. So I'm not doing this one on the whiteboard, but I think you guys see, oh, we excluded -1 and we excluded +1. Everything to the left of 1, everything between -1 and 1, and everything to the right of 1. So, be very careful and kind of think about this. Look for this pattern that when we had one x value, that was a problem. We had 2 separated intervals. When we had 2 problem values, we had 3 separated intervals. So if you had 3 problem x values, what would the last one be? All right, how many intervals would that be? Alrighty, let's talk about square roots. Well, for square roots, we want to make sure that the inside is always 0 or bigger than 0. Case in point, we can be everything except negative numbers. Okay, so x plus 1 greater than or equal to 0. This ensures that everything we get on the inside is greater than or equal to 0. Well, subtract 1 on both sides, and wow, haven't we been writing intervals like this since like chapter P? This says everything to the right of 1 with -1 included. That's it. So stuff we were doing in chapter P, it's coming back. And that's sort of how this works for domain for square roots. Now, doing a whole bunch of examples. Here we go. Find the domain of the 7th root of 400x squared minus 600x plus 800. Okay. But the rule we have for roots is for even roots. For even roots, for square roots, for 4th roots, for 6th roots. And 7th root is definitely not an 8th root. Sorry, 7th root is definitely not an even root. Think about when we were trying to evaluate odd roots versus even roots. We knew we can have negatives inside odd roots. You can take the 3rd root of -27, but you can't take the square root of -27. So because this is an odd root, the domain is all real numbers. Simple as that. Actually kind of nice. But now let's find the domain of the 6th root of x minus 12. Well, this is an even root, so we need to make sure everything on the inside is greater than or equal to 0. All right, x minus 12 greater than or equal to 0. Add 12. This says everything bigger than 12, so 12 to infinity. Alrighty, let's keep going. X minus 5 over square root of 3x minus 12. And here we have a square root, but it's in the denominator. So this was kind of like our 3rd red flag case. It's a combination of both those first 2 red flag cases with rationals and square roots. Normally, we're okay with our square root being 0 or positive. However, the second that square root or that even root is in the denominator, we're not allowed to let it be equal to 0 anymore. So instead of saying it can be 0 or bigger than 0, all we say is has to be bigger than 0, just greater than. Okay, well, we add 12, we divide by 3, all the x values bigger than 4, 4 to infinity, right? And specifically, we exclude 4 because if we had 4, 3 times 4 is 12, 12 minus 12 is 0, square root of 0 is 0. Oh, 0 in the denominator. So the only thing separating square roots in general versus square roots in the denominator is just whether or not we use a greater than or equal to sign. Okay, 15x squared plus 1 over square root of 2 minus x. Same thing. There's just a square in the denominator. We just want to make sure the inside is greater than 0. We don't want it to be equal to 0. It has to be strictly greater than 0. Alrighty, well, we can add x to... Okay, well, we can subtract 2 on both sides. We can divide both sides by -1. Let's think back to 1.6. When we divide both sides by -1, we flip the sign. Don't forget that. It's been a while, I understand, but divide both sides by -1, the sign flips to less than. This says all the x values less than 2, so everything to the left of 2. It's kind of weird to say that we can be, negative values for this, but think about what our square root is looking at, right? If x was -10, well, 2 minus -10 is 2 plus 10, and 2 plus 10 is 12. That's good for the denominator. But if you plugged in something like 3, 2 minus 3 is -1. Square root of -1 is complex. It's not a real number, so that wouldn't work. All right, one more case. In the event that you have a square root in the numerator and a denominator that separately causes a problem, what we're going to do is find the domains of each part separately and intersect them. So domain of the square root, square in the numerator, 0 is totally fine. So we have to make sure it's greater than or equal to 0. Subtract 2 and -2 to infinity. All right, we've done that before. But of the denominator, we want to make sure that the denominator does not equal 0. So x cannot equal 1. And that would be everything to the left of 1 with everything to the right of 1. And now what we're going to do is just intersect them. What does this interval and this interval have in common? Everything from -2 to 1 with 1 to infinity. So it has to be within these ranges. I know this extends all the way to -infinity, but let's plug in, say, -5. Well, -5 is okay for the denominator. -5 minus 1 is -6. That's good. But -5 plus 2 is -3. And we can't take square root of -3. So for square roots and denominators separately, take the domain of each part and intersect them. But this doesn't happen a ton. It does happen, but not a ton. Find the domain of 1 over 1 plus x squared. Oh, it's a fraction. Denominator cannot equal 0. 1 plus x squared can't equal 0. Let's subtract 1 on both sides. And you might think that you take the square root of both sides, square root of -1. Oh, it's not a real number. So there's no problem values. Every x squared is going to be not equal to -1. You can't square any number and have it be negative. So this is always true. Another way of thinking about this, there's always 3 types of numbers. There's negative numbers, positive numbers, and 0. Well, if we take a positive number and square it, it's positive. And then you add 1 and it's still positive. Well, we're looking for 0. Positive numbers are never 0. So this is good. Negative numbers, kind of similar, but you take a negative number and you square it, then it's positive. And then you just add 1 and you are still positive. So positive numbers aren't the problem. Negative numbers aren't the problem in this case. So it must be 0, right? Well, 0 squared is 0. 1 plus 0 is 1. And 1 doesn't equal 0 either. So all 3 types of numbers, positive, negative, and 0, don't actually cause any issues. Now, that's not a perfect way of thinking. It doesn't work nicely for all the other questions. But, if you get to a point where you're kind of like, what the heck is going on? There's pretty good rationalization for that. No pun intended with the rational. Okay, well, domain is the set of all x values that are included. So likewise, the range is the set of all y values that are included, or all the values that we can get by evaluating the function. Now, graphically, this is the set of all y values that appear in our graph. But it's kind of weird to solve for when it comes algebraically. Like graphically, makes a lot of sense, no problems at all. But algebraically, it's very hard to determine range. Range is the set of all values that we get by evaluating the function. So are you going to evaluate the function at every x value in the domain just to see what y's you get? Absolutely not. So determining range algebraically, we're going to put on the back burner a little bit. We'll come back to that in 2.8 or 2.9. So some graphs, we've been doing a ton of graphing, and guess what? Graphing functions, no different than how we did it before. Plug in x and get a y or f of x value. So throw it back to 2.2 when we did like y equals x squared minus 3. You plug in x's, you get y's, table of values. It's no different, except now we're just using f of x's. So, but one thing that is interesting is that we can test to see if a graph represents a function. Well, that's called the vertical line test. Vertical line test says if your pencil or if your vertical finger, whatever it is, if it covers any 2 points at once on the graph of your equation, then the graph does not represent a function. Let's think back to that very first definition we came up with for functions. We said functions must use every x, but every x can only be used once. So if you have a vertical line and it covers a point here and a point here, it says that that same x value is going to 2 separate y values, and that violates the second rule of functions. So vertical line test says if your finger covers 2 points at once vertically, right, your vertical finger covers 2 points at once, it is not a function. Okay, finger, pencil, whatever works for you, right? And we can get some information about a function by looking at its graph. For example, if AB is a coordinate point on the graph, then A is in the domain, B is in the range, and B is the value at A. But these are things that we already knew. Domain would be the set of all x values that you see, all the x values that are included. And like I said, range, not so bad to find graphically. It's the set of all y values that are included. So let's take this graph right here, and we want to find domain, range, and determine whether or not it's a function. Well, domain, set of all x values that are included. And how we read domain is left to right. Look at some of those domain examples. It was always furthest left we could go to furthest right we can go. So to find domain, we're going to follow this graph left to right and see what x values and y values are included. Y's will be, vertical. But let's all see all the x values we get. Well, this arrow tells us that we go forever down and forever to the left. So even though we don't see it on this specific picture, it does say by this arrow that it's defined for every value to the left of where this is pointing, right? Arrow says forever down, forever left. So we know this is defined for everything from -infinity. So we're at -infinity. We follow the graph, and we just want to see how far right we can go. Well, we can go up and down and left and right. And this goes forever up and forever to the right. So our domain is -infinity to infinity. Even though we don't actually see every single value on here, this says that it is extending forever to the left and forever to the right. Range, similar, except when we read domain, we read left to right because x's run left to right, negative to positive. But y doesn't work the exact same way. Y, running negative to positive, is going down to up. Ooh, that's kind of weird. So range, instead of reading left to right or up and down, what we're going to do is read down to up. How far down can we go to how far up can we go? All right, how far down does this graph go? Oh, well, it's a little clear that this goes all the way down to -infinity. But how far up does it go? It goes up, and it comes back down, and it goes back up, and it goes up forever. So that's also -infinity to infinity. Last but not least, is this a function? Vertical line test says if our pencil, if our finger covers any 2 points at once, it is not a function. So I know that this, my little cursor here is not a nice long vertical line, but you should do it, follow along with your pencil and see that at no point does your pencil cover more than 1 point at a time. Since it never covers more than one point at a time, it is a function. It's a problem when you do cover 2 points at once. Okay, similarly, let's do this for a circle. We already have an answer to the function part, but let's still take some information. Domain, set of all x values that are defined. So we're going to go left to right, see how far left and right we can go. Well, we see that the first x value that is defined, that has a value, is -3. Now let's follow the graph left to right. Everything between -3 and 3 are defined. Notice -4 isn't defined. There's no value here. 4 isn't defined either. The only values for which this graph has value, only x values for which this graph is defined is from -3 to 3, -3 and 3 included. Similarly, for range for the y values, the furthest down we can go is -3, furthest up we can go is +3, so that's not so bad. However, bigger question, is this a function? And the answer is no. Take your pencil, cover this line right here. Do you notice that your pencil covers this point right here and this point right here? Oh, well, your pencil covers 2 points at once. That's the definition of not a function. It fails the vertical line test. We could say this one passes the vertical line test. This would be fails the vertical line test. Okay, so with that said, that's the end of 2.4. 2.4 really sets the stage for functions, but 2.5, we're going to get back to looking at some of the properties of functions. So I will see you in 2.5. Hi everyone, welcome back to 2.5. In 2.4, we introduced functions for the very first time, and now we're just going to look at some odds and ends properties of functions, so to speak. So the first two, very interconnected. Third one, similar to something we've done before. Last subsection, those other properties, kind of weird looking things. One really nice, one not so nice. But let's get right into it. So increasing and decreasing. Your function is said to be increasing if your y values increase over some interval x1, x2. So if your ending y value is greater than your beginning y value, then your function is increasing on the interval x1, x2. Likewise, we say your function is decreasing if the y values go down on an interval x1 to x2. We say a function is constant if the y values remain the same. But one thing I want to stress here is that we are talking about intervals. Our answers for increasing, decreasing, and constant are intervals of x's. What we're trying to do is say on these x values, we're describing what is happening for y's. On this set of x values, the y values are decreasing. On this set of x values, the y values are increasing. We're not saying how much they increase. We're not saying how much they decrease. We're just saying from x equals 1 to x equals 2, we are increasing. You can kind of think about it like this too. Let's say you are driving in your car. At time 30 seconds, you are increasing your speed. So from time equals 30 seconds to time equals 40 seconds, you are increasing your speed. We didn't say how much your speed increased by. We just said on that 10-second interval of time, your speed went up. Now let's say you hit the brakes at time 90 seconds, and then at time 100 seconds, your speed is lower. So from the interval 90 to 100 seconds, your speed went down, your speed decreased. Or you can also say your speed remained constant from time equals 2 minutes to time equals 3 minutes. Let's say if you're in like cruise control or something. So we're not talking about the y values. We're talking about the x values. Our answers are going to be in terms of x, but those x values are going to describe what the y's are doing. Okay, here we go. So let's say we have a graph like this. It extends forever in both directions. I just didn't put the arrows, but that's okay. So notice that things are a little different around these points. What I mean by that is let's follow the graph. Okay, on this graph, well, if we follow it, we are literally going up. So we are increasing up to the point -1, 2. So what this says is this: from x equals -infinity to x equals -1, the y values are increasing. So we say from -infinity to -1, again, these are x values, not y values. I don't care what the y values are. I only care on what interval of x's your function is increasing. So on this first interval, again, I don't care how high it increased. I don't care what it got up to. I just care that on this subset of x's, the y values went up. Okay, but at -1, something changes. We stop increasing and we start decreasing. We start going down. So we know we're increasing from -infinity to -1, but on the x values, -1 to 1, the function is decreasing. Again, no y values included. We're saying from x equals -1 to x equals 1, the function is decreasing. The y values are decreasing. Don't care what the y values are, only care to describe what they are doing. Last but not least, -1 to 1, we decrease, but at x equals 1, we change to increasing one more time. So notice this is an interval of x values. This is an interval of x values. This is an interval of x values. At no point do we use the y values. We are only describing what the y values are doing with some set of x's. That's really, really important. Now, in total, we like to write our answers as increasing all the increasing intervals together. So -infinity to -1, union 1 to infinity. Likewise, decreasing, well, we only had one decreasing interval, So there we go. We like to write our answers as all the increasing ones, all the decreasing ones. However, it's easier for me if I just, show them to you one by one. But this is how we would formally write our answer. But on each individual interval, here's our answers. Again, sets of x's to describe what the y's are doing. Also, I want to stress that for increasing, decreasing, we're always going to use parentheses. It isn't quite clear. For example, at x equals 1, are we technically decreasing or are we increasing at x equals 1 specifically? Well, it's kind of a hard question to answer because the decreasing ends and the increasing starts. So instead of trying to say like, oh, well, it's decreasing on this part or it's increasing on this part, we're just always going to use parentheses for when it comes to increasing, decreasing. So this is not a coordinate point. It is an open interval. I know this is like the one time that we're really using similar notation for different things. Bear with me. All right, let's do another one. Here, let's start from the left of our graph and just follow along and see what happens. Okay, well, we start up here, and you'll notice that we are going down. So from negative infinity to x equals -1, our y values are decreasing. From negative infinity to x equals -1, the y values go down, so we are decreasing. But then at -1, we change. So from -1 to 0, we increase. From 0 to 1, we decrease. And last but not least, from 1 to infinity, we increase. So again, we do not care what the y values are. We only care what x values, for what set of x values do the y values increasing, decrease. Notice we have this to say, oh, on this set of x's, the y values went down. On this set of x's, the y values went up. That's our goal here. Not including y values, only including x values each and every time. Okay, so in total, we like to write our answer all the decreasing and increasing intervals together. So we are increasing from -1 to 0, union 1 to infinity, and decreasing from negative infinity to -1, and 0, 1, union 0, 1. Okay. So that's increasing, decreasing. I think you guys get the idea. It's just gotta be really careful because again, you're gonna be so tempted to use the y values, but that's not what we're doing. We're using sets of x values. Just read left to right. From this x to this x, did we go up or down? From this x to this x, did we go up or down? That's what increasing, decreasing is. Now, extrema is a really fancy word for maximums and minimums. So technically, maximums isn't grammatically correct. It's technically maxima. However, I am very conditioned to say maximums and minimums instead of extrema or maxima and minima. Also, my name may or may not be Max. So in a lot of cases, I say maxes and mins. I don't even say maximums and minimums. So fancy phrasing. All it is this. Maximums occur when your function changes from increasing to decreasing. Think about what happens when your function changes. Let's say you're increasing, and then at some point, you start to come back down. Well, that location at where it stopped increasing and started decreasing, that location at the top represents kind of a maximum value. Around, that point, nothing is bigger than it. It might get bigger than it, down the road. That's where we get into different phraseology of what types of maximums. But where we change from increasing to decreasing, we call that a maximum. Likewise, we use minimums to say decreasing to increasing. At the location that we change from decreasing to increasing, that is a minimum. So, big so here. The big difference from increasing, decreasing, and maxima and minima is that increasing, decreasing are intervals that describe what happens to the y's. But extrema, maximums and minimums, are specific locations in time or in space. Notice, we'll go back to this example. We're going to come back to this example in just a moment. But the increasing, decreasing were intervals, these long, smooth intervals of time where we were decreasing and then increasing and then decreasing and then increasing. But at the locations where it changes, those are maximums and minimums. So increasing, decreasing are intervals. Extrema are points. So if your function does not change, well, nothing happens. I want to stress that maximums and minimums only occur when we change between increasing to decreasing or decreasing to increasing. So if your function doesn't change at some specific value, there is no maximum or minimum. What sometimes happens is you'll be increasing and then you kind of plateau, but then you increase again. In the event that you change from increasing to constant to increasing again, well, we didn't change specifically from increasing to decreasing. Maximums only occur when you change from increasing to decreasing, not increasing to constant, not decreasing to constant, only increasing to decreasing or decreasing to increasing. If it doesn't change in those only two scenarios, we don't call it anything. You might actually call something like this plateau a shelf, but that's not really important right now. How we phrase this is the extremum occurs at the x value, with the maximum or minimum being the value itself, being the y value itself. So let's go back to this example. We said we increased, and then at -1, we started decreasing. Well, we call x equals -1 a maximum. It changes from increasing to decreasing. Notice, at the points right around it, there's nothing bigger than it. So this is a maximum. So there is a maximum at x equals -1 with a value of 2. Finally, we're using the y values. There's a maximum at x equals -1 with a value of 2. Okay, similarly, we are decreasing, and then at x equals 1, we change to increasing. Well, decreasing to increasing is the definition of a minimum. Okay, so there is a minimum at x equals 1 with a value of -2. And that's how we would formally write this. As you go along, it's totally fine to write maximum, with the coordinate point -1, 2. But as we're learning this for the first time formally, I want to make sure it's very clear what these things mean. Okay, let's go back to the second example again. We are decreasing from -infinity to -1, and then at -1, we change to increasing. Decreasing to increasing is a minimum. So there is a minimum at x equals -1 with a value of 1. Then we start increasing, and then at x equals 0, we decrease. So there is a maximum, right? Increasing to decreasing is a maximum. There is a maximum at x equals 0 with a value of 2. And last but not least, I don't think I need to go back, but there is a minimum at x equals 1 with a value of 1. So only maximums and minimums, they only occur when you change from increasing to decreasing or decreasing to increasing, respectively. Constant doesn't happen anywhere in that definition. Staying constant, like increasing to increasing, also does not change there. So please don't use maximums and minimums for any other situation than those two changes. Okay, so a lot going on in those two, but let's talk about even and odd. And this is something we've actually kind of talked about before. We describe a function to be even if f of -x equals f of x. Plugging in -x wherever we see x, that sounds something really familiar. It sounds like symmetry. So even functions, if you replace -x with x, are symmetric about the y-axis. So for example, f of x equals x squared is even, not necessarily because it has an even exponent, but if you plug in -x wherever you see x, well, you would have -x squared, and -x squared is then positive x squared after simplification. So because f of x is the same as f of -x, right? They both equal -2. They both equal x squared. In that case, this is an even function. Okay, so a function is odd if when you plug in -x, you get the negative version of your function. Ooh, that's kind of weird. So odd functions are symmetric about the origin. And for example, x cubed is odd because when you plug in -x, well, -x cubed is -x cubed. Okay, well, if we regroup this to say -x cubed, well, x cubed is the original function. So this would be negative f of x. F of -x equals -f of x. This is symmetric about the origin, but we also call it odd. If you plug in -x and you don't get either situation, that's totally fine. It just means your function is neither. That happens plenty of times. I also want to stress that we have symmetry about the y-axis and symmetry about the origin, but no symmetry over the x-axis. Well, let's say we have a graph that looks like this. Well, here's the x-axis, so this would be symmetric over the x-axis, but 2.4 is screaming. This doesn't pass the vertical line test. Maybe over here. Yeah, there we go. Sorry, I didn't expect to really be using my hands for this, but vertical line test. It crosses 2 points at once. Functions that are symmetric over the x-axis aren't functions to begin with. So we don't even need to talk about symmetry over the x-axis. Okay, is this function even, odd, or neither? Let's see. Well, when we were looking for symmetry over the x-axis, y-axis, or origin, we had a specific method as to how we did it. Y-axis replace x with -x. X-axis replace y with -y. But doing even and odd is actually pretty nice. For all of these examples, go right for plugging in -x, right? Notice f of -x, f of -x. Just go right for plugging in -x for x. That's how we'll start doing even and odd. Okay, -x cubed is -x cubed. -4 times -x is positive 4x. Now, this is really similar to what we started with. Well, x cubed became -x cubed, and -4x became positive 4x. Well, if we want to get the original coefficients, why don't we factor out a -1? Well, if we factor out a -1 from both, ooh, look at this. This, x cubed minus 4x, x cubed minus 4x, this part inside the parentheses is exactly f of x. However, it's not perfectly f of x because we have a negative sign on the outside. Well, if f of -x equals -f of x, this is the definition of an odd function. So the conclusion here, f of -x led us to -f of x. That is the definition of an odd function right there. Okay, let's do another one. F of x equals x to the 10th plus x to the 6th plus 5. Wherever we see x, let's plug in -x. Well, negative numbers raised to even powers are positive. Negative numbers raised to even powers are positive. Oh, well, actually, this is pretty quick. This is exactly like the other one. So f of -x gave us exactly f of x. F of -x equaled, after simplification, f of x. That's the definition of an even function. Okay, Well, you might be thinking, well, this example had all odd coefficients, sorry, all odd degrees. So it was odd. And this one had all even degrees. So this must be even. But what if we have both? Well, maybe you have an idea on that answer, but wait till you see the next example. All right, same thing. Let's go in for plugging in negative x. Negative x cubed is negative x cubed. So this will be negative 2x cubed. Negative x squared is then positive x squared. And notice that we can't treat this like the odd example. Here we have 2x cubed, and this is negative 2x cubed. So it'd be nice if we pulled out a negative 1, but here we have positive x squared, and the same thing again. If we pull out a negative 1 to change negative 2 back to 2, well, then we would be changing x squared to negative x squared, and that's not what we want. That would be going backwards. There's nothing we can do to manipulate this to look exactly like the original function. In that case, if there's nothing we can do, it's neither. Okay, well, so even exponents, it's even. Odd exponents, it's odd. Both exponents, both even and odd, it's neither. Well, how about this one? Here we have two even exponents in the numerator and two odd exponents in the denominator. It must be neither, right? Let's see what happens. Let's plug in negative x. So 3 times negative x to the fourth minus 5 times negative x squared. 4 times negative x to the fifth minus 2 times negative x cubed. Well, negative raised to even is positive. Negative raised to even is positive. Down here, negative raised to odd is negative. Negative raised to odd is negative. Well, negative is positive. Okay, well, the numerators are identical. 3x to the fourth minus 5x squared, exactly what we started with. But the denominators are off by a factor of -1. Positive 4x to the fifth, negative 4x to the fifth, minus 2x cubed, positive 2x cubed. So what if we factor out a -1 from the denominator? Well, we saw a couple times that if the denominator is negative, this technically means the whole thing is negative, right? If you were to redistribute this negative, you wouldn't distribute it to the numerator and the denominator. You would only distribute it to the to one or the other. Well, this, what is now inside the parentheses, is exactly the original function. Well, f of negative x equals negative f of x is the definition of an odd function. So, you can be easily fooled by degrees and exponents, so be very careful with that. It's just something that happens. That brings us to our last two properties of 2.5, things that are very different from the couple things that we've talked about so far. Increasing, decreasing, extrema, and to an extent, even an odd are very graph heavy, but these next two, not quite. So average rate of change, you guessed it, literally the average rate of change your function changes over some time period. So if you were to graph this, I know it said not as graphic, but you're going to spend way more time doing this algebraically. Graphically, if you were to draw the slope of the line in between 2 points, that slope would be the average rate of change, right? You have some function over some very specific time interval. So from some very defined x to some very defined y, if you have those 2 points and you draw a line between them, the slope of that line is the average rate of change. So for some interval, x equals a to x equals b, the average rate of change is f of b, the value at b, minus f of a, the value at a, over b minus a. This looks a lot like y2 minus y1 over x2 minus x1, but now we have a very specific name. But also, when we talked about slope the first time, it was specifically for drawing lines. We're saying, what is the average rate at which your function changed over some time period, right? Your function can go up and down like crazy, but what's the average rate at which it changed? And that's what average rate of change gives us. Also, I might say AROC a couple times. It's a nice way of simplifying it. All right, so find the average rate of change from f of x equals 2 minus 3x squared from x equals 1 to x equals 3. In my opinion, it is probably in your best interest to solve for f of a and f of b first. A and b are always the beginning and endpoints of your interval. This is from 1 to 3, so a equals 1, b equals 3. There's nothing really surprising going on there. But instead of, trying to plug everything into the average rate of change formula at once, do it in pieces, right? It ain't going to hurt you. Do f of a, where you solve the function with a plugged in, or more specifically 1 in this case. So 2 minus 3 times 1 squared. 1 squared is 1. 3 times 1 is 3, -1. And take the time to do it for b as well. 3 squared is 9. 3 times 9 is 27. 2 minus 27 is -25. So take the time to do that. Don't try and plug it all into the AROC formula right away. Okay, well, average rate of change, f of b minus f of a over b minus a. Well, we just found f of b, and we just found f of a, and b is 3, and a is 1. So that's actually pretty nice. We already have everything. -25 minus -1, that's plus -12. So the average rate at which our function changes from 1 to 3 is -12. If you were to draw a line from 1, -1 to 3, -25, its slope would be -12. Let's do that again. X cubed plus 1 from x equals -2 to x equals 4. Well, we start from a, end at b. So a is -2, b is 4. Let's find f of a, f of -2, by plugging in -2 to the function. -2 cubed is -8. -8 plus 1 is -7. F of b says plug in b, plug in the final endpoint. Well, 4 cubed is 64. 64 plus 1 is 65. F of b minus f of a over b minus a. Well, we got f of b right here. We got f of a right here. And we have a and b right here as well. Bunch of minus, plus 72 divided by 6 is 12. Average rate of change. Not anything super crazy. But that brings us to our very last property for 2.5, and that is the difference quotient. So its meaning is kind of crazy because we haven't spent a whole lot of time talking about this, but difference quotient is a method to find the formula for the slope of a tangent line at any point on the graph. So imagine you have some curve and you want to find a tangent line to any point on that curve. So let's say tangent lines in general, let's say you have a graph that goes like this and it comes down. But what if instead of coming down, we wanted to draw a line at the point where it is still going up? We draw a line tangent to the graph. Kind of difficult to explain. Actually, you know what? I'm going to take a second and show you what this looks like. What would a presentation be without a single thing on the whiteboard? So let's say you had some graph that looks like this. If you wanted to draw a tangent line, so a tangent line would be a line that kind of like touches at one specific x value and goes in the direction that it was heading. So at this point, the tangent line runs like this, but down here, tangent line would run like this. So imagine like you're throwing a baseball. When you throw a baseball, when you let go, the ball travels in the position that you were letting go, or with in the direction of where you would have let go. If you let go of the ball too late, you throw it to the ground. If you let go of the ball too early, it goes up in the air. But if you try and throw it straight, you have to throw it at a very specific time. So that's what tangent lines are. I realize in a digital setting, not as easy to describe, but that's what tangent lines are. So what the difference quotient is doing is getting us a formula for the slope of that tangent line at any point on the graph. So difference quotient is given by this. Oh, didn't I say this thing was going to come back from 2.4? Sure is. Difference quotient needs f of x plus h. All this is the function with x plus h plugged in, the original function, and h is going to be just some constant that we don't know. So let's find the difference quotient for 2x squared minus 3x plus 5. We need f of x, we need f of x plus h, and we need h. Well, h is just h, and f of x is sitting right there for us. So all we need is f of x plus h. This says wherever we see x, plug in x plus h. All right. Here, we're going to have to FOIL. Here, we're going to have to distribute. Here, we're going to have to distribute 2. So I know I skipped through a lot of that, but we've been doing this stuff since like chapter P. It's just a matter of, this is the new step of plugging in x plus h wherever we see x. So this is all of f of x plus h. And we want to plug this into f of x plus h. And we want to plug this in for f of x. So taking f of x plus h, taking f of x, and plugging them both in, we get this ugly monstrosity. So here, let's distribute our negative sign, right? Plugging in f of x, use parentheses. Let's distribute the negative sign. And now, you think it doesn't get any better, but it actually does. 2x squared minus 2x squared. Oh, that goes away. Minus 3x and plus 3x. Oh, that goes away too. And positive 5 and negative 5. Well, out of 9 terms that we have here, 6 of them just canceled out. 2x squared minus 3x plus 5. Well, minus 2x squared plus 3x minus 5 canceled out all of those terms. And we're left with these 3. Now, we're almost there, but notice this. Every term in the numerator has an h. So let's factor out h. And if we have h times something divided by h, we can cancel those h's out. And we're left with just 4x plus 2h minus 3. Now, we are not even close to Calculus 1 just yet. That is coming in, 2 courses if I ever make those videos. But this is one step away from being the first derivative. So that's actually a very interesting piece of information that we get. So that's the difference quotient. Like I said, it's a Calculus 1 thing, but notice that there was nothing here that we weren't capable of doing already. So that's difference quotient. Weird, very strenuous algebraic activity. This was kind of a decent amount of work for not a very exciting final answer, but we can get them to look really, really ugly. Let's do one more. That's just a polynomial, but we'll call it after that. So difference quotient, we need f of x, we need f of x plus h, we need h. H is just h, f of x is just itself, but we need f of x plus h. Wherever we see x, plug in x plus h. We're going to FOIL x plus h squared. We're going to distribute this outer negative sign. And now all of this information, f of x plus h and f of x, are going to go into the difference quotient. Alrighty, how beautiful. Let's distribute a negative sign to each term in here. And we see negative x squared cancels out with positive x squared. Positive x cancels out with negative x. And negative 3 cancels out with positive 3. All of these terms in the numerator have an h. Let's factor out h. H then cancels out. If you did this right, you should have something like this that happens, and you're left with negative 2x minus h plus 1. And that's the end of 2.5. So some very interesting properties, right? Increasing, decreasing, and maximums and minimums, kind of along with difference quotient, is something you'll study very in depth in Calc 1. But even odd, it's kind of just an extension of symmetry we talked about in 2.2. So that's the end of 2.5. We're going to change gears a little bit in 2.6 and talk more about graphs of functions, very specific graphs of functions, but not really a ton of new information there. Just looking at some of the weird types of functions that we actually have. So with that said, I will see you in 2.6. Hi everyone, welcome back to 2.6. Here in 2.6, we're just going to kind of look at some graphs of functions. Literally, it's called a library of functions. All the things that we've talked about so far, just looking at what their graphs would look like, because knowing what their graphs would look like are going to help us into the next section when it comes to transformations. But for now, let's just build our way up to what do graphs of different functions look like. Let's build a library of very basic functions. So we'll start with linear functions. Well, lines are graphs of the form y equals mx plus b. So linear functions, believe it or not, are functions of the form f of x equals mx plus b. No different, except now that we have introduced function notation, we are allowed to use f of x in terms of, instead of y, I should say. So f of x equals mx plus b is a line with some slope. That's not really surprising to us. F of x equals b, where there is no slope, or the slope is 0, I should say. We call that the constant function, because no matter what you plug in for x, you're always going to get that value b, the y-intercept. F of x equals x, we refer to as the identity function, because no matter what you plug in for x, that's what you will get back for f of x. So for example, if you plug in x equals 1, well then f of 1 equals 1. You plug in negative 5, well f of negative 5 equals negative 5. So it's the identity function. The domain of all linear functions, right, going back to 2.4 a little bit, the domain of all linear functions is all real numbers. There's nothing you can plug in that will make a line undefined, but the only thing that could be different is the range. Range is normally when there's a slope, negative infinity to infinity, but when it comes to constant functions, it's just whatever that y-intercept is. That's the only y value you can get. So here's some slopes lines. Not really surprising. We spent an entire section talking about lines. There's the identity function. There's the constant function. Not so scary. But only difference now is that instead of giving you 2 coordinate points, I can instead give you function notation for values, and you write a line based on that. Given that f of 1 equals 4 and f of negative 3 equals negative 2, write the function of a line. And guess what? This isn't really that scary. So if f of 1 equals 4, this is saying at x equals 1, the y value is 4. At x equals negative 3, the y value is negative 2. Well, that's the definition of 1, 4 and negative 3, negative 2, right? If x is 1, the value is 4. If x is 1, y is 4. Yeah, wow, that's just the point. Well, from here, this is exactly like we built lines for graphs, except it's going to be one extra step. First step, we got to find the slope, plug in everything we know. Negative 6 over negative 4 is 3 over 2. Y equals mx plus b. All right, well, we know the slope is 3/2. Let's plug in either one of our 2 points. It doesn't matter. I'm going to plug in 1, 4. So x is 1, f of x is 4, right? F of x and y are interchangeable, so that's not super scary. Well, from here, subtract 3/2 on both sides. We can do fraction subtraction. B is 5 over 2. So if we were writing the equation of a line, we would write y equals 3/2 x plus 5/2. But if we are writing the function notation for this line, it would be f of x equals 3/2 x plus 5/2. But the line itself, no different from stuff we've talked about before. One more example. If we have f of negative 2 equals 2 and f of 1 equals 8, well, this says at x equals negative 2, y equals 2. At x equals 1, y is 8. Oh, how nice. Alrighty, plug in everything we know to find the slope. We get 2. Yeah, this isn't scary at all. I think it's very familiar to us. So y equals mx plus b, and we just found to be 2. Plug in either point. I'm going to plug in 1, 8. Again, it doesn't matter which point you plug in. You will get the exact same answer. We saw that when it came to lines. All right, well, 2 times 1 is 2. Subtract 2 on both sides, we get 6. So y equals 2x plus 6, but in function notation, f of x equals 2x plus 6. Okay, linear functions, not really any new information, except we have one step in the beginning that makes us write what the points are, and we have one step at the end, just instead of saying y equals, we have f of x equals. Also, you could have just started with f of x in the beginning, but, you know. All right, root functions. So we've looked at roots before, but we don't really know what their graphs look like. They're actually kind of funky looking. But to do root functions, what we're going to do is just a table of values. So let's plug in 0 to square root of x. Well, square root of 0 is just 0, so that point is 0, 0. 1, well, square root of 1 is 1, so that point is 1, 1. And now you could go up to 2, but square root of 2 isn't a nice number. That's not an easy number to graph. Instead, why don't we jump up to 4? Okay, well, square root of 4 is just 2, so we get 4, 2. Well, the next value would be 5, but 5 doesn't work nice. So how about 9? Okay, square root of 9 is 3, so that point is 9, 3. Let's do 16. Square root of 16 is 4. So we get 16, 4. So I mentioned it way back when we started graphing in 2.2 that you could use a disjoint set of x values to plug in. At the end, you're going to connect all of them anyway. So, using 0, 1, 4, 9, 16 is to our advantage because not so scary to plug those values into square roots. The second you try and use 2 or 5 or anything like that, you might be in trouble. So here's what happens when we graph those points and connect them. We get something that looks like this. And that makes sense because we can't take square roots of negative numbers, so there's nothing to the side. Square roots can't produce negative numbers, so there's nothing below the x-axis. So, yeah, this is what square root functions are going to look like, and this is what all even root functions are going to look like. So this is square root of x, but fourth root of x would be just this graph, but a little bit growing. It would grow a little bit slower. Sixth root grow even slower than that. So the shape will not change, just a matter of the rate at which it grows a lot slower. Okay, well, let's do cube root. And cube root, we have a lot more values available to us. So let's plug in negative 27, because we can take the cube root of negative 27. That's negative 3, right? Even roots, square roots, we can't plug in negative numbers, but odd roots, we can. Okay, well, yeah, there we go. Negative 8, cube root of negative 8 is negative 2. So negative 8, comma negative 2. Negative 1, cube root of negative 1 is negative 1. Negative 1, comma negative 1. Cube root of 0 is just 0, so there's 0, 0. And I think the last couple points are self-explanatory. So again, we want to choose points that are to our advantage. So for example, plugging in -27 and then jumping up to -8, that helps because we don't know any of the cube root values in between them without getting some really ugly numbers. So again, it's okay to be picky and choosy the values you plug in. And notice that the cube root function has a similar shape to the square root function, right? This right here kind of looks like the square root part, but now we get a part to the left of the y-axis because we're allowed to plug in negative numbers. So square roots and all even root functions, their domains are 0 to infinity with 0 included. The range also 0 to infinity, right? Square roots, even roots, we can't plug in negative numbers. We can't get negative numbers out. But cube roots and all other odd root functions, also going back to that cube root picture, 5th root, 7th root, 9th root, as you go up higher in the root, the graph just grows less drastically in both directions. So domain for those, all real numbers, and range, all real numbers, because we can get anything we want out of both. So not really anything surprising so far, but we have to introduce one new type of function, piecewise functions. So kind of fancy looking here. So piecewise functions are functions made up of smaller functions over smaller intervals. So this is very scary looking notation, but all this says is that for some interval of x, let's say x1 to x2, you're going to use one function f1 of x. But on a different interval of x, you will use a different function. On a third interval of x, you will use a third function, and so on, as many as you want. Now, the higher up in number you go, the uglier it gets, right? It becomes kind of unnecessary as time goes on. But we're going to look at some examples with 2 parts and 3 parts. So, but you could really go 4 or 5, but at that point, it's just getting messy for no reason. So the x values in which we change, right? Notice this interval is from some x1 to x2, but at x2, this changes here. At x3, this interval ends and this interval starts. So the location at which these functions change and you jump between which one you use, we call those transition points. And transition points are unique because what we're going to need to do is graph our function at every transition point twice. So here's what happens. Well, actually, before we do that, let's just practice how we evaluate these things. So let's find f of 0 and f of 2. So if you want to evaluate, say, f of 0 for a piecewise function, your first step is to look at the intervals. Piecewise functions say if x falls into this interval, you're going to plug it into this corresponding part of the piecewise function. So for example, 0 is less than 1. So we would plug 0 into this first part. Okay, so it would go into x squared, which would just be 0. Notice that 0 is not greater than or equal to 1. So we wouldn't plug 0 into the bottom one. We would only plug 0 into the top one because 0 is less than 1. Likewise, 2 is not less than 1, but 2 is greater than or equal to 1. So when we go to plug in 2, we would plug it into the second one. Okay, and simplifying that, not really anything crazy. But again, figure out where that x value belongs before you start to plug it in. Okay, so going back to the transition point thing, see here that at x equals 1, we stop using this top function and we start using this bottom function. However, if we're doing a table of values like -3 to 3, you're going to be compelled to stop plugging this in at 0. But don't forget, all the values less than 1 is not just 0. Another value less than 1 is 0.5. 0.75, 0.9, 0.99, 0.999. We can plug all these values that are extremely close to 1, but values that you would miss out if you stopped plugging in at 0. So here's what we're going to do. Well, let's do -3 to 3, and let's just go down the order until we get to 1. All right. Well, -3 is less than 1, so we'll plug -3 into the first part. -3 squared is 9, so our point is -3,9. -2, well, -2 is still less than -1, so we're still going to plug it into the top. -1, still less than 1, we're going to plug it into the top. 0 is less than 1, so we're still going to plug it into the top. But then at 1, well, if we wanted to plug in x equals 1, x equals 1 fits into this bottom interval, not the top interval anymore. However, if you stop graphing this part of the function, if you stop graphing the x squared part of the piecewise function at x equals 0, you miss out on all of those intermediate values between 0 and 1. You miss out on graphing 0.5. You miss out on graphing 0.99. So to calm that fear, what we're going to do instead is we're going to plug the transition point x equals 1 into the top. It doesn't belong there. I totally get it. But what we're going to do instead is when we plug 1 into the first part of the function where it doesn't belong, what we're going to use instead is an open circle. So we're going to use some asterisks here to denote this is going to be an open circle, right? 1 should not be getting plugged in to this top one. However, what we're going to do is graph that point 1, 1. So we connect all 5 of these x squared points together. But instead of saying there is a value at 1, we're just going to put an open circle there. And you're going to see how this works when we actually go to graph. Okay, well, at x equals 1 really belongs in here. So when we go to actually plug x equals 1 in, we're going to plug it into the bottom function. All right. And then you want to plug in 2. That's going to go in the top function, the bottom function as well. You want to plug in x equals 3. You're going to plug it into the bottom function as well. So to graph piecewise functions, you're going to graph each of these sets of points together. And what I mean by sets is the set of points that all use the same function. So for example, these first 5 points all use x squared. So we're going to graph all of those x squared points and connect those x squared points. And separately, we're going to graph the 2x plus 1 points and connect the 2x plus 1 points separately. So graphing the x squared points and graphing the 2x plus 1 points. And now here's why it was important for us to graph our transition point twice. Notice that at x equals 1, well, this was, x equals 1 belonged in the top, but how do we not graft this part into the first part of the piecewise function? If we didn't graph 1, 1 with an open circle here, we would have just gotten the little branch right here. We would have completely missed out on this tiny little area between 0 and 1, right? We had to do that because if you want 0.5, 0.5 belongs in the x squared part, right? 0.5 was less than 1. So if you don't graph transition points like this, you're going to miss out on all of those points that are in between, kind of in flux around your transition point. So, if you had graphed just this part and just this part, you would see that you would have literally a gap in your graph. So just be sure to graph transition points twice and try and figure out which part of the piecewise function does it go into. Okay. Let's do the same thing. Let's do a slightly different function here. Let's do x squared, but x is less than or equal to -1, 2x, x is greater than -1. And notice this time, transition point is going to be -1. Okay, well, let's do -3. -3 is less than or equal to -1, so goes into the top. -2, -2 is still less than or equal to -1, so it still belongs in the top. And now let's think about our transition point again. Here's the weird part. In the last question, x equals 1 didn't belong in the top because the interval in the first question was x is just less than 1. But this time we have x is less than or equal to -1. Well, -1 actually belongs in this part of the piecewise function. So we don't always graph an open circle the first time we see a transition point. We need to graph an open circle at the place it doesn't belong. Well, -1 belongs in x is less than or equal to -1, and -1 does not belong in x is greater than -1. So the open circle part comes the second time around because of the greater than. So -1 does belong in the top, and we get that point, but -1 doesn't belong in the bottom. So we're going to plug -1 into the bottom, but this part is going to have an open circle. Okay, well, from here, we kind of see that as soon as we start using the next part of the function, it just stays that way. So, right, 0 is greater than -1, so it's 2 times 0. 1 is greater than -1, so that'll be in the bottom part as well. And 2 and 3. So again, what we're going to do is graph all the points that use the same part of the piecewise. These 3 points use the x squared, so we're going to graph those together and combine those. And these all use the 2x part, and we're going to graph those and combine those. There's the x squared part, there's the 2x part. And notice, right, -1 was our transition. If we only started graphing the 2x part at 0, because 0 is greater than -1, we would have missed out on this little branch right here. So please be very careful. Let's do, I think, one more example. Here, 2 is our transition point, but notice the first time we see 2, it will not belong there. So we're going to graph an open circle at the first time we see the transition point, right? Last one, we had x is less than or equal to -1. This time we have x is less than 2. So, right, open circle here, closed circle here. Well, I think plugging in the points, not so scary anymore. -2 is less than 2, goes at the top. -1, still less than 2, goes in the top. 0, less than 2, still goes in the top. 1, less than 2, still goes in the top. But 2, right, 2 technically doesn't belong in here. So we need to graph an open circle into this part of the function. But then when we actually go to graph 2, it'll belong in the bottom. So 3 times 2 plus 1 is 7. 3 times 2 is 6. 6 plus 1 is 7. And now from here, we're just going to use second part of the piecewise over and over and over again. Okay, graph these parts because these all use -2x plus 1, and then graph these parts because they use 3x plus 1 and connect them separately. So again, had you stopped graphing the top part of the function at x equals 1, you would have missed out on this tiny little branch right here. That's very important. Okay, very last part of 2.6, just looking at graphs of functions, just so we have a baseline as to what they look like. Squaring function, x squared, parabolas. We'll spend a little bit more time at this in the next chapter, but not such a scary looking picture. X cubed, cube root, kind of weird looking, but yeah, there we go. Absolute value function, absolute value of x. Reciprocal function, 1 over x, is funky looking behavior. Maybe we look at something like this in the next chapter too. 1 over x squared, similar, except if we're squaring every value, no value will be negative. Rational powers, if the denominator is even, we get just one side. If the denominator is odd, we get both sides. Notice that, right, 2 in the denominator was kind of like square root, and 3 in the denominator was like cube root, so it makes sense. And that's the end of 2.6. So really the biggest information here in 2.6 is regarding piecewise functions. So I know they're kind of scary. We won't be graphing a ton of them, but it is important enough that you know how to graph them, but especially that quirk that transition points need to be graphed twice. So with that said, I will see you in 2.7. Bye, everyone. Welcome back to 2.7. What we do here in 2.7 is a transformation of functions. So it's a little different from things that we've done in the past. It's kind of like puzzling to an extent, puzzling in steps. But what we did at the very end of 2.6 was looked at, a nice library of graphs of different types of functions that we can see here in algebra. But what we're going to do now is learn to transform those graphs into other very complicated looking ones. So just as some basics, right? You could always use the table method for graphing, but this becomes really tedious or difficult the harder we get. So for example, if you wanted to graph absolute value of x minus 3, this isn't so bad. But the second you want to graph something like 2 times negative x minus 6 in absolute value plus 6, that's a lot harder. So transformations is a step-by-step method that helps us graph things based on a parent function. Basically, if we start with some function that we do know, we can do some sort of transformation to get to a function that we don't know. So here are some of the things that we looked at in 2.6, right? Quadratic, squaring function x squared, cubic x cubed, absolute value of x, and root functions. So knowing what the graphs of x squared, x cubed, absolute value of x, and the nth root of x look like, we can take those that we do know and kind of mesh them to look into other ones, to look like other ones. All right, so the first type of shift we're going to talk about are rigid transformations. Rigid transformations are transformations that change the position of the graph, but not the shape. Okay, so vertical and horizontal shifts, most basic type of transformation. And you see here on this first slide, vertical shifts are going to be the most basic transformation. So vertical shifts for some function f of x, well, its transformed version, if you are vertically shifting it, would be f of x plus or minus k, right? So using g of x now instead of f of x, not to double dip. So f of x plus or minus k would be a vertically shifted function. So now the big thing here is that this plus or minus k is on the outside of the function. We're going to see some stuff where stuff happens on the inside, but for now, this plus or minus k is on the outside. If you have f of x plus k, so f of x plus k means you are taking your graph of f of x and shifting it up k units. And if we're shifting up k units, what we're doing is changing all the y values. So you would add k to all the y values to go from previous function to new function. For example, or not for example, as the opposite, if we have f of x minus k, well, f of x minus k is a shift down k units. Well, if you're shifting down, you're changing all the y values, you would subtract k units from all the y values. So this makes a lot of sense, I think, right? Plus k up, minus k down. Unfortunately, that nice intuition is not going to stick over the course of the section, but I think as a very basic type of transformation, it makes a lot of sense. Two very quick examples. X squared plus 2 would be the graph of x squared shifted up 2 units, or 2 units up, right? Either way. Absolute value of x minus 3 would be the graph of absolute value of x shifted down 3 units. Okay, so here's absolute value of x. Absolute value of x plus 2 would be take all the y values and shift them up 2 units, right? Shifting up. So 2, 2 would become 2, 4. 0, 0 would become 0, 2, right? Adding 2 to all the y values. Well, going to absolute value of x minus 3 instead, we're going to take all the y values and subtract 3 this time. So 2, 2 would become 2, negative 1. 0, 0 would become 0, negative 3. And now you see all three graphs. The original, vertically shifted up, vertically shifted down on one slide. Makes a lot of sense. Well, horizontal shifts are similar, but a little weird looking. So instead of plus or minus k on the outside, what we're going to have is minus plus on the inside. Now, that use of minus plus versus plus minus is very important, and you're about to see why. For f of x minus h on the inside, right? Again, big difference. Vertical shift plus or minus k was on the outside. This time minus plus is on the inside. If you have f of x minus h, where minus h is on the inside, this is a shift to the right h units. Okay, I am well aware that is backwards. That is uncomfortable. Vertical shifts are intuitive. They are as you'd expect. Plus k means up, minus k means down. However, horizontal shifts are counterintuitive. Minus h, you would really like to be to the left h units. That's not the case. It's backwards. So f of x shifted to the right h units, but if we're shifting to the right, that means we're taking all the x values and adding some value. So please be very careful the difference between vertical shifts and horizontal shifts. Vertical shifts, intuitive. Horizontal shifts, counterintuitive. Well, now that you know what f of x minus h is, f of x plus h would be a shift to the left h units, right? We like plus to mean right, but it doesn't here in horizontal shifts. In this case, we would subtract h from all the x values. Okay, two more quick examples. If we have x minus 4 squared, this is x minus 4 on the inside, but don't forget minus 4 on the inside is a shift to the right 4 units. Okay, absolute value of x plus 6. We would really like plus 6 to mean to the right, but plus 6 means to the left 6 units. Okay. So here's x squared. If we want x minus 2 squared, well, minus 2 is a shift to the right 2 units. And if we're shifting to the right 2 units, we're taking all the x values and adding 2. So adding 2 versus subtracting 2, we see the difference, I think. All right. Well, if we add 2 to 2, 4, it becomes 4, 4. If we add 2 to 0, 0, it becomes 2, 0. And now you see how that graph is shifted to the right as opposed to the left. X plus 3 squared, this is a shift to the left 3 units. So 2, 4 would become negative 1, 4. 0, 0 would become negative 3, 0. So vertical, intuitive, horizontal, counterintuitive. Unfortunately, that's not the only time this is going to happen. Okay, reflections. So reflections are another type of rigid transformation because you're not changing the shape of the graph, you're still only changing its location. For reflections over the x-axis, its transformed version is negative f of x, specifically with that negative sign on the outside. Okay, so we say f of x is reflected over the x-axis, but what we're going to do is negate each y value. Okay, so what it means to negate something is to multiply all those values by -1. I want to be careful with my wording here. I can't say make that value negative, because if I say make that value negative, you're going to think in terms of like absolute value. Absolute value says make it positive. That's not what the case is. Negation says if it's positive, if some value is positive, its negated value is negative. If an original value is negative, its negated value is now positive, right? So very careful of that. In other words, just multiply all the y values by -1. That keeps you staying careful. So that's reflections over the x-axis. Reflections over the y-axis, well, instead of negative on the outside of our function, that negative would be on the inside of the function. So we say f of x reflected over the y-axis. But instead of negating the y values, we're instead going to negate the x values. So we're going to multiply all the x values by -1. So reflections don't really take us that long. Here's f of x equals x squared. But if I want negative x squared, negative on the outside, we're going to take all the y values and multiply them by -1. Well, 0, 0 won't change, but 2, 4 will become 2, -4. Okay, square root of x. Well, what if I want square root of negative x, specifically with this negative on the inside? Well, if that negative is on the inside, we're negating the x values, right? Negative on the outside here, negate the y values. Negative on the inside, negate the x values. So what we're going to do is make all the x values negative. Well, 0, 0 stays 0, 0, but 4, 2 becomes -4, 2. This is actually kind of interesting because normally square roots need to be all positive, but if we're taking square root of a negative x, well, square root of -4 is square root of +4, which is 2. So that's reflections. Not really scary. Now the weird one, right? The least, not least intuitive, I don't want to say, but the most involved type of transformation are stretches and compressions. We refer to these as non-rigid transformations because they can change the shape of the graph, right? Vertical shifts, horizontal shifts, reflections are just taking this graph in space and just kind of moving it around, but it doesn't change the shape. It just changes where it is. But stretches or compressions will change the composition of your graph. So let's start with vertical stretches or compressions. So g of x equals c times f of x. And I think you're already seeing the pattern of this c is on the outside. So kind of like x-axis reflections, if c is greater than 0, we're going to multiply all the y values by c. If c is negative, well, think about this. If this is -2 times f of x, this is like 2 times f of x, and then reflected because that negative is on the outside. So if your c is positive, it's one step. Multiply all your y values by c. But if c is negative, you're going to multiply all the y values by absolute value of c, and technically then do a reflection where you multiply all the y values by -1. If you're strictly going for the graph, you can multiply all the y values, in this case by -2 in one step, and that's okay. It'll have the same desired effect. However, what we're going to be interested in doing, at least in my classes watching, is understanding the order in which we do things. Well, the order in which we do things would be stretch or compression, multiplying all the y values by that constant, and then doing the reflection by -1. Now, different from class to class, that's how I prefer to teach it in my class. If the absolute value of c is bigger than 1, then what you do is stretch away from the x-axis. Your graph gets sharper, it grows quicker, so that's what it means to stretch away from the x-axis. Now, the phraseology is going to get kind of complicated because right now we're doing vertical stretches or compressions, and then we're very shortly going to do horizontal stretches or compressions, but that's the idea here, that if your c is bigger than 1, even if it's negative, right? If this is 3, you take all the y values and multiply them by 3, it gets sharper. Even if you multiply by -3, yeah, you would reflect, but your graph would still be sharper than the original. Likewise, if your constant is some fraction between between 0 and 1, like 1/2, well, then you're multiplying all the y values by 1/2. And if you're multiplying by 1/2, you're kind of dividing by 2. Well, in that case, you would get a lot closer to the x-axis. So if c is bigger than 1, you are stretching away from the x-axis, but vertical compression, you are going toward the x-axis. It gets closer. It doesn't grow as quick. It gets wider. That will be a compression. So here's absolute value of x. Let me move my picture. My picture still might be in the way. I really don't know how to get rid of having my picture appear twice. That's okay, though. So if we wanted 2 absolute value of x, well, what we're going to do is take all the y values and multiply them by 2. So if we multiply all the y values by 2, this 1, 1 would become 1, 2, this 2, 2 would become 2, 4, and you see it got a little bit sharper. However, if I want 1/2 of x, well, this 2, 2 would become 2, 1, right? Take this y value multiplied by 1/2. 2, 2 becomes 2, 1. 4, 4 becomes 4, 2. So that would be a vertical compression because we are vertically compressing toward the x-axis. Here, we got away from the x-axis. Here, we went toward the x-axis. So away from the x-axis would be a stretch. Toward the x-axis would be a compression. Personally, if you're watching this and you're in my class, I'm not picky with how you word it. I'm more interested in the actual change itself. Okay, well, we have vertical stretches or compressions, and we have horizontal stretches or compressions, where we instead look at everything in a frame of reference from the y-axis. So instead of that c on the outside, we have a b on the inside. Okay, well, you're probably already starting to get the idea of how weird these things can be. Remember, for horizontal shifts, that -h meant add h or to the right h plus h on the inside, and then to the left h. So for this b on the inside, if your b is positive, you are going to divide all the x values by b, right? On the inside, we're affecting x now, but instead of multiplying, we are dividing constantly backwards when it comes to the inside. If your b is negative, well, this is like negative 2x on the inside. Well, negative 2x on the inside would be dividing by absolute value of b and then reflecting over the y-axis by multiplying the x values by -1. Very similar to what we were just dealing with in the last part, except now x values and division instead of multiplication. If your b is bigger than 1, then you compress toward the y-axis. And this is kind of hard to picture. Its meaning isn't perfect here in algebra. We need trigonometry to really see the difference here. But for now, yes, if your b is bigger than 1, you are compressing toward the y-axis. You're getting thinner. But if your b is a fraction between 0 and 1, then you would stretch away from the x-axis and you would get a wider version of the original graph. So kind of hard to tell, but here's x squared. And if I wanted 1/2 x squared, well, this b on the inside is between 0 and 1. So our graph is going to get wider. Well, so we divide all the x values by 1/2, which is really like multiplying all the x values by 1/2 to get the same, multiplying all the x values by 2 to get the same effect. So for example, this is x equals -1, but if we're dividing by 1/2, we're multiplying by 2. To get that same y equals 1, we now need -2. And you know what? Kind of notice this too, that this is 1/2 x squared. We could have also written this as 1/4 x squared without the parentheses, and then it would have been a vertical stretch or compression. So horizontal stretches or compressions, not super meaningful here in algebraic functions because it's a little harder to tell, but again, the effects are still the same. If we had 2x squared, we are taking all the x values and dividing them by 2. So instead of x equals -1 here, it would be x equals -1/2, right? Dividing by 2 to get that same y equals 1. But also notice this could have just been like y equals 4x squared, where it's a vertical stretch or compression. So horizontal stretches or compressions, kind of weird. You're probably not going to do a lot of them here in your algebra course, but definitely those things come in handy when it comes to pre-calculus. Okay, well, the order in which we do these things is as you see it on the screen. So the original graph, you start there. Horizontal stretches or compressions, you do that first, then reflection over the y-axis if your b is negative, then your horizontal shift, then vertical stretch or compression, then x-axis reflection if applicable, and vertical shift. And one thing I want you to know is, even though this is kind of daunting looking, right? There's a lot of information on this slide. Don't worry. The order in which we do these things is the order in which you would plug something in for x. So for example, let's take this really full version right here. If you were to plug some value in for x, well, maybe if you plugged in some value for x, as written here, you would subtract h, but then again, we could distribute this b, you would multiply by b, and then subtract h. Well, multiply by b, that's the first thing we did. And then subtracting h, oh, that's the next thing we did. Okay, well, then the next thing you would do, right? Okay, so you plug in some x, you multiply by b, you subtract h, which I know this isn't how this is written here, just showing you. But then what you would do after that is apply the function, right? Square root of squared, then multiply it by c. Well, that was the next step right here, and then plus k. So order in which we do things is the order in which you apply things to x. The order in which we do these things in a nice simplified fashion is as follows. So our order, specifically for my class, right? You might in your classes be doing horizontal stretches or compressions, but like I said, they're kind of like vertical stretches or compressions in a lot of cases. Okay, so what we're going to do is start with our original graph and then do horizontal shifts. So in my case, I kind of cut out the horizontal shift. You can change, you'd be able to change horizontal stretches or compressions into vertical stretches or compressions, but odds are you're probably not going to get that deep. Horizontal shift, first thing we do. If we have f of x minus h, add h to all the x values, right? Horizontal shifts are backwards. If you have f of x plus h, we're going to subtract h from all the x values. Vertical stretch or compression, if we have c times f of x, multiply all the y values by absolute value of c. But if your c is negative, then do an x-axis reflection and multiply all the y values by -1. Vertical shift, very last thing we do. If we have f of x plus k, we're going to add k to all the y values. F of x minus k, subtract k from all the y values, right? Again, here now that they're side by side, notice the difference between horizontal shifts and vertical shifts. Okay, so just going back, here's all those parent functions that we had, but without further ado, let's do an example. Okay, so let's graph square root of x minus 2 plus 3. We want to start with square root of x. We know what square root of x looks like. We want to work our way to this. Okay, if you don't remember the order in which we do those transformations, that's okay. The order in which we do transformations is the order in which you would do something to x when you plug it in. So for example, we plug in some x, and what's the first thing that happens to it? Well, it's not plus 3. You wouldn't take the square root of it yet. The first thing you would do is subtract 2. That's the first thing you would do to x. Now, what does x minus 2 on the inside mean? X minus 2 on the inside is a horizontal shift. And if we have minus 2, that's a horizontal shift to the right 2 units. Okay, so you plug in some x, you subtract 2, you take the square root of it, and the last thing you would do is plus 3. Plus 3 on the outside is a vertical shift up 3 units. Now, depending on your class, depending on who's teaching it, again, this one is very centric to my classes. I think I teach this kind of weird, but I hope this is still helping you. But this is one way you can write it. This is the very formal mathematical way of writing transformations. But also, if you just want to describe what's happening, you can also use it in words. So shift right 2, add 2 to the x values. Shift up 3, add 3 to all the y values. Exactly the same as what's happening in the coordinate parts, but for the description parts, you're literally describing what's happening, just not giving the function part. So in my class, if you're watching, I don't care about either. It's one way or the other. So here's square root of x. First thing we said was to shift right 2 units and then up 3. So there is our transformed version of the graph, and we didn't need to do any tables, table of values, I should say. No table of values. All we had to do was take something we already knew, shift it to the right 2, shift it up 3, and that's how transformations work. Okay, let's do another one. We have negative absolute value of x minus 2 plus 3. Parent function here, where are we going to start? Absolute value of x. Okay, now the order in which we do things is the order in which we apply things to x. So x minus 2 on the inside, where you plug in some x, and you would subtract 2 first. Well, we just saw on the previous page that subtracting 2 is a horizontal shift to the right 2 units. All right, so you have some x, you subtract 2, you take the absolute value of it, then do you do negative or plus 3? Well, you do the multiply by a negative sign. Well, negative on the outside is a reflection over the x-axis, but if we're reflecting over the x-axis, we are multiplying all the y values by -1. We are negating all the y values. Well, last but not least, all right, you plug in an x, you subtract 2, you take the absolute value, you multiply by -1, and then you add 3 last, okay? And then if we're adding 3 on the outside, this is a vertical shift up 3 units. And again, this is the nice mathy way of writing it, but if you wanted to give a description of what's happening, here you go. All right, here's absolute value of x. We had a horizontal shift to the right 2 units. We had an x-axis reflection, and then we went up 3. So there's our nice finally transformed version. No table of values at all. Okay, let's do another one. 3 square root of x plus 1 minus 2. What we're going to do is start with square root of x, because that's our parent function, right? We see the square root here. First thing we would do is the plus 1, but plus 1 on the inside means shift to the left 1 unit. Then would we multiply by 3 or subtract 2? We would multiply by 3 first. And if we're multiplying by 3 on the outside, what we're doing is taking all the y values, multiplying by 3. And last but not least, minus 2, that's the only thing we were missing. Minus 2 on the outside means down 2 units. There it is in words. Okay, first thing was to the left 1 unit, multiply by 3, and down 2 units. And there's our nice transformed version. So these are transformations. I think we got 1 or 2 more examples. -2, x minus 1 squared plus 3. Okay, well, first thing you would do when you plug in an x would be the -1. Start with x squared, and then we do x minus 1 squared. -1 on the inside is a horizontal shift to the right 1 unit. Then we would have -2 on the outside, but technically the order in which you would do this would be the 2 first. So we would multiply all the y values by 2, and then you would make it negative in terms of 2 separate steps. Here is the vertical stretch or compression. Here is the reflection if we're describing what's happening. So you could, if you're not looking to describe what's happening, you could do these 2 into 1 step. But again, you'll see on the next slide in terms of words how their descriptions are very different. So if you were to combine this into 1 step using like the mathy steps, it would just be x comma -2 times y. Last but not least, we got the plus 3 on the outside. That's a shift up 3 units. In words, here now maybe you see why we need to do it in 2 steps. Vertical stretch by a factor of 2, reflect over the x-axis. It's hard to combine those 2 into 1 step when we're using, words to describe it. All right, first thing was to the right 1, then stretch by 2, reflect over the x-axis, and then up 3. And there's our nice final version of this transformed graph. So that's transformations. Transformations kind of weird, kind of quirky if you're not careful, but if you stick to doing it as a step-by-step method, it's not as bad as it seems. So with that said, thank you so much for watching, and I will see you in 2.8. Yeah, bye. Hey everyone, welcome back to 2.8. So in 2.6 and 7, we had changed gears a little bit to talk about graphs of functions, but what we're going to do is get back to doing very algebraic-based stuff, more calculation-based stuff in 2.8 and 2.9. So sections are relatively short. It's not really a ton of new information here, just some new methods, some new things we can talk about, but I wouldn't think that anything here is super scary compared to stuff we talked about, especially in 2.7. So 2.8, 2 types of things we're going to do. We're going to combine function, and we're going to compose functions. So let's start with combining functions. Well, different ways to combine functions, and they are as follows. F plus g of x. Take a wild guess what this is. And if you said it's just taking 2 separate functions and adding together, you would be correct. F minus g of x. Take a wild guess. Taking 2 functions and subtracting each other. Okay. F times g of x. Well, take 2 functions, multiply them together. F over g of x. Take 2 functions and divide them. Also, you could do g minus f, where you just do g of x minus f of x. G divided by f of x, where you take g of x divided by f of x. Nothing really crazy here, but literally the 4 ways to combine functions are to add, subtract, multiply, or divide. And then we just introduce some new notation for all 4 of those. The domain of a combination function is the domain of f intersected with the domain of g. So it's not going to change a whole lot, really. We're not going to spend a whole lot of time doing domains of combination functions. It's not really that exciting. But yes, if you wanted to find the domain of a combination function, you would just take each separate domain and intersect them. The only added restriction we have for this is when we are doing division, we also want to make sure we take out all the values where g of x is 0. If g of x equals 0, then we get something undefined. Not good. So to find domain of any combination function, intersect each part. But if you're doing division, make sure the denominator does not equal 0. Also, if an x value does not appear in the domain of f or g, it cannot reappear in the domain of the combination. So here's what I mean by that. Let's say in f, you can't plug in 1. For whatever reason, you can't plug in 1. But after you do your combination, if you can all of a sudden plug in 1 and you would get something defined, well, you actually can't. Because since 1 wasn't in the original domain of f, it is not able to be in the domain of the combination, whichever combination you're doing. Of course, we're not going to do a ton of domains of combinations here, right? The more interesting part here is actually doing the combinations, at least in my opinion. So not super crazy, but nonetheless, if you wanted to find the domain of something, just make sure that values don't reappear in your domain. So you would plug in x values the same way as you would plug in values for single functions, or you could also plug values into original functions and then do the combination. So for example, if you wanted to do f minus g of 4, this says find f minus g of x and then plug in 4. But also what you can just do is do f of 4 and then subtract g of 4. You would have the exact same effect. All right, so let's do combination functions. All right, let's say f of x, x squared minus 6x plus 8, and g of x is x minus 2. Find all 4 combinations, plus, minus, multiplication, division, and then plug in x equals 6. Well, let's just start with f plus g of x. F plus g of x says take f of x and add g of x. Well, f of x is right here. G of x is right here. So add those together. Well, negative 6x plus x is negative 5x. 8 minus 2 is 6. And we can simplify that to x minus 2 times x minus 3. And now what I want is f plus g of 6. So wherever we see x, we're going to plug in 6. 6 minus 2 is 4. 6 minus 3 is 3. 4 times 3 is 12. But also, if you're looking for a specific value of your combination, you didn't have to do it this way. So for example, do we get 12 if we plug 6 into here, and then add them? Well, 6 squared is 36. 6 times 6 is 36. 36 minus 36 is 0. 0 plus 8 is 8. Okay, well, 6 over here, 6 minus 2 is 4. So 8 plus 4, by virtue of, f plus g of x, 8 plus 4 would be 12. So you could also plug values into the originals first, and then do the addition, subtraction, multiplication, division. But I think it is very good algebraic practice to actually do the combination first and then plug the value in. Okay, f plus g of 6. Oh, okay. I didn't realize I had a slide here where I actually do that. So take a second and write the slide down if you want. But yeah, you could also do it this way. All right, f minus g of x says take f of x, subtract g of x. All right, well, only difference here is that now we're going to subtract x, negative 6x minus x, negative 7x. 8 minus negative 2, 8 plus 2, which is 10. Which we can factor to x minus 2, x minus 5. Now plug in 6. 6 minus 2 is 4. 6 minus 5 is 1. 4 times 1 is 4. And again, you can do this by plugging 6 into here, and then plugging 6 into here, and in this case, subtracting them. Here we said we got 8. Here we got 4. 8 minus 4 is 4. Multiplication, all right. F of x times g of x would be f of x times g of x. And, well, if we want to get a nice simplified answer, I wouldn't expand this. I would just factor this one part. And, oh, actually, one thing we can do is say x minus 2 times x minus 2, x minus 2 squared. And then if I want f times g of 6, plug in 6 into here. 6 minus 4 is 2. 6 minus 2 is 4. 4 squared is 16. 2 times 16 is 32. Or you could, again, plug 6 into here, plug 6 into here, and then multiply them. 8 times 4 is indeed 32. Let's do division. Alrighty, f of x over g of x. There's f of x, there's g of x. X squared minus 6x plus 8 factors to x minus 2 times x minus 4, and we can cancel out x minus 2. Okay, well, plug in 6. 6 minus 4 is 2. And again, just doing the example of if we plugged it into here originally, plugging 6 into here gave us 8, 6 into here gave us 4, 8 divided by 4 is 2. So multiple ways to do the same thing. All right, let's do the same thing, different functions this time, and now we're going to plug in negative 2. F plus g of x, f of x plus g of x. Here's f of x, here's g of x. Let's combine like terms, and now let's plug in negative 2. Negative 2 squared is 4. 3 times negative 2 is negative 6. And we get negative 1. So not very crazy, I don't think. Subtraction, same thing, except now we're going to subtract. Well, we just get minus 3x. But 2 minus negative 1 is 2 plus 1. And then plug in negative 2. And this is almost getting a little repetitive because we have been plugging in values for a very long time in this class. Okay, f times g of x. F of x times g of x. Take these things, multiply them together. You know what? Don't even bother. This is actually nice and factored for us already. So let's just go right for plugging in negative 2. Negative 2 squared is 4. 3 times negative 2 is negative 6. 4 plus 2 is 6. Negative 6 minus 1 is negative 7. Negative 42. Okay, I don't think this is crazy to many of you watching. If you have gotten to the point of combination functions, you're probably very comfortable, adding, subtracting, multiplying, dividing, as well as plugging numbers in. One more, let's do g over f, because why not? Let's change it up, right? Point is, it doesn't matter what I say. G over f is just g over f instead of f over g. Well, g is now at the top, f is now at the bottom, and now let's plug in 200. 3 times 200 is 600. 200 squared is 40,000. Yeah, why not? I don't know. Just plugging in numbers. Okay, let's do some combination examples, some domain examples of combinations, I should say. So if we want to find the domain of each of the 4 combinations, don't forget 3 of them are exactly the same. To find the domain of f plus g, f minus g, and f times g, what we're going to do is intersect those domains. Okay, so domain of f of x, x plus 2, the inside has to be greater than or equal to 0. So x is greater than or equal to negative 2, or negative 2 to infinity. Domain of g of x would be 5 minus x is greater than or equal to 0. X is less than or equal to 5, however you get there. So everything less than 5. Now, the domain of f plus g, f minus g, f times g is just intersect these. So the intersection of negative 2 to infinity, negative infinity to 5 would be negative 2 to 5. What do those 2 domains have in common? Everything between negative 2 and 5. Now, for f over g, the only added restriction is that we need to make sure that the denominator does not equal 0. Well, g of x can't equal 0. Absolute value of 5 minus x can't equal 0. X just can't equal 5. Before we had negative 2 to 5. Well, if we now take out 5, it's just negative 2 to 5, with 5 no longer included. So domain of combinations, kind of weird, right? It's more important that we know how to find domains of functions in general. But yeah, now you can do it with combinations. Well, that's combinations. Let's now do composite functions. They are similar in thinking, but different way we reference them. So composite functions are literally putting one function inside another and simplifying. In combination functions, you are taking 2 functions and just adding them or subtracting them or multiplying, dividing them. But here in composite, we are plugging functions into other functions. So we have to introduce some new notation. We introduce f of g of x. F of g. And f of g of x says f of x with g of x plugged in. So this outer function with this inner function plugged in. Then we also have g of f. Same thing. We have this outer function with the inner function f of x plugged in. F of f, okay, I joke in my classes saying it's a little cannibalistic, but that's kind of what it is. You're taking f of x and you're plugging f of x into itself. And same thing for g of g, you are taking g of x and plugging it in to g of x. So f of x says take f of x, plug it into itself. G of x says plug in g of x into itself. But at least for f of g and g of f, this is taking one function and plugging it into another function. A little less weird. Okay, another way people mention these functions is fog and goff. So we use this little circle symbol to represent of. So some people like to say this is fog and goff, which if that helps you, by all means do it. It doesn't really help you remember like f of g of x, but I also think it sounds kind of weird when you go to say like foff and gog. I don't know. Those are weird sounding phrases, I guess. I don't know. So however, it helps you remember these, but it's literally just taking this inner function, plugging into this outer function. If you want to find the domain of a composite function, you would take the domain of the inner function. So here, domain of g, here, domain of f, here, domain of f, here, domain of g, right? Whichever one is the inner function. You take the domain of the inner function and you intersect it with the domain of the final composition. All right, let's just do some composition examples. Okay, let's start with f of g of x. F of g of x says f of g of x. So this says wherever we see f, we're going to write g of x. Think back to when we originally started talking about functions. I said that f of potato says wherever we see x, plug in potato. So f of potato would be potato cubed. But now we're not plugging in just some single term. We're not plugging in like x plus h. What we're doing is plugging in g of x. So in f of x, wherever we see x, we're going to write g of x. So f of g of x would be g of x cubed. Again, wherever we see x, write g of x. But then the question is, what is g of x? Well, g of x we have a definition for. G of x is x plus 1. So we get x plus 1 cubed. Notice x plus 1 inside x cubed. But we just got to be very careful with how we talk about that. Some people some of my students in the past have been able to jump right from here to here. So if this middle step is confusing to you, that's totally fine. It's kind of hard for me to understand why that is. But yeah, if you are not seeing this middle step, but you see this ending step and all the ending steps we're about to do, that's totally fine. Do as you need. Okay, so if we want to plug in x equals 2, f of g of 2 would be 2 plus 1 cubed, 3 cubed, 27. Now, there is actually another way of doing compositions like this. And what it is plug in 2 to g and then plug that value into f. So doing that same kind of idea, 2 plus 1 is 3. 3 into x cubed is 27. So that's really what's happening. Not really anything crazy in terms of simplification going on here, but that is another way you are able to evaluate. Okay. G of f of x says take g of x, plug in f of x. Well, if this was g of potato, wherever we see x, we would write potato, but now we have g of f of x. So wherever we see x, we're going to write f of x. Okay, well, f of x plus 1, but we have a definition for f of x. F of x is x cubed. Okay, well, x cubed plus 1, now we plug in 2, and we get 8 plus 1, which is 9. Okay. F of x, this is where it starts to get a little funky. That's okay. F of x says wherever we see x, write f of x. Well, if this was f of potato, you would say potato cubed. But if f of x says f of x cubed, wherever you see x, plug in f of x. But what is f of x? F of x is x cubed. So we have x cubed cubed, which is x to the 9th. Well, if we want f of 2, just plug in 2, and 2 to the 9th is 512. 2, 4, 8, 16, 32, 64, 128, 256, 512. There we go. G of x. Okay, g of g says g with g of x plugged in. All right, well, here's g of x. G of potato would be potato plus 1. So g of x is g of x plus 1. But again, we have a definition for g of x, and that is x plus 1. So in total, x plus 2. G of 2 would be 2 plus 2, 4. Very exciting. Okay, so let's find the 4 compositions. We don't need to keep plugging in values. I think we get the idea. But let's find the 4 compositions. F of g of x says f of x with g of x plugged in. F of x is 2x plus 1, but we instead have 2 g of x plus 1. And then g of x is x squared minus 3. Let's distribute 2, and negative 6 plus 1 is negative 5. G of f says g of x with f of x plugged in. Well, g of x is x squared minus 3, so g of f of x is f of x squared minus 3. But f of x is 2x plus 1. 2x plus 1 squared, that's foiling, right? Be very careful. 4x squared plus 4x plus 1, and then subtract 2 and factor out 2 just to be fancy. Looking for compositions, we can simplify, but if we're plugging in values, at some point you don't need to simplify. We're just looking for that actual value. F of x says take f of x, plug it into itself. So instead of 2x plus 1, this is 2 f of x plus 1. But f of x is 2x plus 1. Distribute 2 and add. G of g, all right. G of g says take g of x, plug it into itself. G of x is normally x squared minus 3. So the g of x plugged in, we get g of x squared minus 3. But g of x is x squared minus 3 itself. So here we're going to FOIL again and subtract 3. And that's composite functions. Okay, let's do another example. F of g of x says take f of x, plug in g of x, for x squared plus 1. Now for g of x squared plus 1, because we're plugging in g of x. But g of x is 3 minus x. All right, FOIL 3 minus x squared, multiply by 4, and add. And we can put it back in order. G of f says take g of x, plug in f of x. So instead of 3 minus x, we get 3 minus f of x. F of x, 4x squared plus 1. 3 minus 1 is 2, and negative 4x squared. F of f says take f of x, plug it into itself, for f of x squared plus 1. F of x, though, is 4x squared plus 1. FOIL, multiply by 4, and add. And then g of g says take g of x, plug it into itself. Instead of 3 minus x, we get 3 minus g of x. G of x is 3 minus x. All right, 3 minus 3 is 0. Negative x is positive x. All righty, let's do some domain stuff. All righty, f of x is 1 over x. G of x is 3x minus 12. If we want to find the domain of f of g of x, this is domain of the inner function g intersected with the final domain. All right, so the domain of the inner function g is all real numbers, right? This is just a polynomial. There's nothing that we can plug in that gets this in trouble. So f of g of x would be 1 over g of x, 1 over 3x minus 12. So what's the domain of 1 over 3x minus 12? 3x minus 12 can't equal 0, x can't equal 4, everything except 4. So domain of the entire composite function would be negative infinity to infinity intersected with negative infinity to 4 with 4 to infinity. In that case, it's just negative infinity to 4 and 4 to infinity. Okay, so one very brief composite domain example, not super exciting, but we get the idea. So that's the end of 2.8. We got one more section here in chapter 2 for inverse functions. Inverse functions are actually kind of interesting. It's the same method over and over and over again, so we're going to like that a lot. So I will see you in 2.9. Bye. Hi, everyone. Welcome back to the final section of chapter 2. This chapter is very long. It's got a lot of really important information about functions that you need or you can't do a lot of other stuff in mathematics. So long, tedious, but it is finally coming to an end here with inverse functions. So the first thing we're going to talk about are one-to-one functions. Now, one-to-one functions are similar to functions. We're going to think about them kind of similar, except we're going to get one extra rule. So if you think back to 2.4, when we talked about functions initially, the rule we had is that every x has to go to 1y. Every x has to be used, and every x can only be used once. We had no restrictions on the y's. However, what we now introduce in 2.9 are one-to-one functions, and one-to-one functions mean that every x goes to one unique y. So in regular functions, we allow all the x's to go to the same y if we wanted to. If 1 goes to 1, and 2 goes to 1, and 3 goes to 1, and 4 goes to 1, and 5 goes to 1, that's fine. As long as every x is only used once, we're good. But now in one-to-one functions, we're restricting that every y can only be used once as well. So this is going to be the last time in this chapter that we're going to go to the whiteboard. So let's do that one more time. Okay, so for the last time here in chapter 2, don't forget that when we did functions initially, we allowed ourselves to do 1, 2, and say something like that every x was used and every x was only used once. The second we did something like this, where 1 was used twice, that wasn't a function to begin with. The second that, say, 3 doesn't go to anything, that also isn't a function to begin with. Don't forget that for just functions, every x has to be used and every x can only be used once. Now, when we're talking about one-to-one functions, the extra restriction we have is that every x can only go to one unique y. So now we're only allowing y's to be used only once. So in this example that you see on the screen right now, this isn't one-to-one because 4 is used twice. This isn't one-to-one, this is 2-to-1, right? 2 x's go to 1 y, 2-to-1. So instead, what we can do is if we have something like this would be 1-to-1. So it's as simple as that. It doesn't even need to be in that order, right? For example, 2 can go to 6 and 3 can go to 5. As long as every x is only used and every y is only used, this is a one-to-one function. So just wanted to show this off. Now we're going to get back to the presentation for the rest of the lecture. Okay, so now we're back. Just wanted to show the correspondence diagrams. That's what those little circle things are. But now let's continue. So for example, f of x equals x is 1-to-1 since every x goes to 1y. There's no way that you can make two different x's equal the same y value. However, x squared is not 1-to-1 because -2 squared is 4 and +2 squared is 4. Two x's go to one single y value. Okay, well, two ways to determine if a function is 1-to-1. We have an algebraic way and a graphical way. Algebraically, what we're going to do, we want f of a equals f of b to lead to a equals b. If this is true, then it is 1-to-1. Graphically, how we do this is the horizontal line test. So vertical line test says if our vertical pencil covers any 2 points at once, it's not a function. And likewise, horizontal line test would say if your horizontal pencil covers 2 points at once, it's not 1-to-1. Now, the big thing here to note is that a function can be a function, and it might just not be 1-to-1. That's totally okay. We'll come to what that means to not be 1-to-1 in just a moment. But just because something isn't 1-to-1 doesn't mean it's not a function. It just means it's not a 1-to-1 function. So just something to keep in mind. So let's just do some examples of determining if something is 1-to-1. So let's say we have the function 4x minus 4. What we want to do is start with f of a equals f of b and get it down to a equals b. In other words, we want to solve for a. If we get a equals b, then your function is 1-to-1. Otherwise, if you get anything else besides a equals b, it is not 1-to-1. So f of a says plug in a, f of b says plug in b. And what we can do from here to solve for a, we can add 4 to both sides. Well, that gets rid of both of the 4s. We can divide both sides by 4 and we get a equals b. So we got a equals b. In the event that f of a equals f of b leads to a equals b, your function is 1-to-1. This is the result we want. Now, you might be wondering, how on earth could we possibly get anything besides a equals b in this way? Well, let's do another one. Let's do x squared minus 2. Well, again, we start with f of a equals f of b. So we're going to plug in a and plug in b. We're going to add 2 to both sides. And then if we want to solve for a, we need to take the square root of both sides. But don't forget from the entire chapter solving equations that when we take the square root of both sides, we pick up plus and minus. Okay, so the square roots cancel out the squares, but we now get a equals plus and minus b. This is not our desired result. Our desired result is a equals b, and we got something that isn't exactly a equals b. In that case, we would just say our function's not 1-to-1. X squared minus 2 is still a function. It's just not a 1-to-1 function, and that's okay. So the reason this is true is because f of 2 would be 2 squared minus 2, 4 minus 2, which is 2, and f of -2, well, -2 squared is also positive 4, and we get 2 that way. So even though that -2 and 2 both went to positive 2, the two values weren't equal to begin with, so that's not allowed for 1-to-1 functions. So that's all that is. F of x equals x cubed plus 1. Well, you might think that every exponent now is going to fail. Well, let's see. Plug in a, plug in b. Let's subtract 1 on both sides, and let's now take the cube root of both sides. But don't forget that when we take square roots and even roots, we pick up a plus and minus. But when we do cube roots, fifth roots, odd roots, we do not pick up a plus and minus. Well, in this case, The cube root and the cube cancel each other out on both sides, and we get our desired result, a equals b. So you probably already start to see that anything that is even power might not be 1-to-1, whereas odd powers will. We'll look at those graphs in just a moment. Let's say we have f of x equals 7 over x plus 2. Well, here's what we're going to do. Same thing, f of a equals f of b. And what we're going to do is cross multiply, right? We haven't really done a whole lot of cross multiplying in this class, but let's do 7 times b plus 2 equals a plus 2 times 7. Let's divide both sides by 7, and let's subtract 2 on both sides, and we get b equals a. Okay, I know this isn't exactly a equals b, but it is basically the same thing, right? A equals plus and minus b is fundamentally different from a equals b, but b equals a and a equals b are saying the exact same thing. So this function would be 1-to-1. So just to show you graphically how these would work, again, horizontal line test says if your finger, your pencil, covers 2 points at once, it's not 1-to-1 when it's held horizontally. So here's 4x minus 4, just a line. Notice that there is no horizontal line that covers this graph at more than 1 point. X cubes plus 1, odd roots. Oh, yeah, okay, that's not so bad. But the second we got x squared minus 2, well, now we have plenty of horizontal lines that cover more than 1 point at once. So there you go. This would fail the horizontal line test. Again, x squared minus 2 is a function. It passes the vertical line test, but just because it is a function, it doesn't mean it's necessarily a 1-to-1 function. And there's 7 over x plus 2, rational functions. We will spend a little bit more time with in chapter 3, but point is not quite anything of interest. So, all right. Well, so now we know what 1-to-1 functions are, but the entire purpose of the section is for inverse functions. So let's say we have the function x cubed plus 1, and when we plug in 2, we get 2 cubed plus 1, which is 9. Okay, nothing really surprising there. So 2 goes to 9. But how do we go from 9 back to 2? Well, that would be the process of taking inverses. Now, the whole reason we found 1-to-1 functions is because if a function is 1-to-1, it has an inverse. So only 1-to-1 functions are what we call invertible. So if it's not 1-to-1, it doesn't have an inverse. Likewise, if it has an inverse, the function is 1-to-1. So the whole reason we spend all this time finding 1-to-1 functions is to determine whether or not a function has an inverse. Okay, we write the inverse of f of x as f inverse of x. This is not reciprocal. This is not raised to the -1. This is saying f inverse of x. And that's very different from anything else. That -1 has no algebraic property besides denoting an inverse function. Okay, so how do we find inverse functions? Well, it sounds like it could be a complicated process, but it actually isn't that bad. So to find the inverse, we have 4 steps. One of those steps is going to have multiple steps, but in general, 4 steps. Step 1, you're given f of x. Change f of x to y. You'll see why we do that in just a moment, no pun intended. You'll see why we do that in just a moment because working with f of x can be kind of complicated for no reason. However, we know that f of x and y are the same thing, so it doesn't hurt us at all to replace f of x with y. Step 2, we're going to exchange the locations of x and y. And what I mean by that is literally wherever we see x, start writing y. Wherever we see y, start writing x. So we are literally taking all the locations and flipping them between x and y. And this is the new step to this section. So next step is to solve for y. You started with y equals something. So then after you change x and y, you get x equals something. Well, we want to get our answer back to be y equals something. Okay, so our step 1 was to get y equals. We solve for y. We have a new y equals, but those y's aren't the same. This y came from f of x. This y will be f inverse of x. Okay, so let's get right into it. F of x equals 4x minus 4. Step 1, replace f of x with y. That's the important part. That's the important start. Step 2, wherever we see y, write x. Wherever we see x, write y. So instead of y equals 4x minus 4, we are instead going to have x equals 4y minus 4. Literally switched x and y. Step 3 is going to be your longest step every time. Step 3 says solve for y. We want to get this y by itself. How we do that? We can add 4 to both sides. We can divide both sides by 4. And look at that. We got y equals. However, we have one more step. Notice that this is y equals 4x minus 4, and this is y equals x plus 4 over 4. We have y equals 2 completely separate things that are not equal to each other. In that case, this y was originally f of x. This y is f inverse of x. And that's always going to be your last step, changing y to f inverse after you have completed the process of inverting the function. Okay, let's do the same thing for x cubed plus 1. First step, change f of x to y. Step 2, wherever we see y, write x. Wherever we see x, write y. So instead of y equals x cubed plus 1, we are instead going to have x equals y cubed plus 1. From here, we're going to solve for y. We want to get this y by itself. So let's subtract 1 on both sides. Let's take the cube root of both sides. Don't forget taking cube roots, taking fifth roots, and taking odd roots. Do not add plus and minus, so nothing's wrong here. Okay, and yeah, we have y equals cube root of x minus 1, but this y is different from this y. This y was f of x. This y is f inverse of x. Okay, well, we said this function here, x squared minus 2, wasn't 1-to-1, so it doesn't have an inverse, but let's see why. Okay, so step 1, if this was to be inverted, let's say f of x equals y, step 1. Step 2, switch x and y. Step 3, let's solve for y. So let's add 2 to both sides. And let's take the square root of both sides. But don't forget that when we take the square root of both sides, we get plus and minus. Okay, and here's where something is very wrong. This isn't a function to begin with. If it's going to be a function, if this thing right here is a function, that means when we plug in 1x, we only get 1y back, right? Vertical line test, definition of a function, we can only get 1y value for every x. So if we plugged in x equals 2, 2 plus 2 is 4, square root of 4 is 2, and we get plus and minus 2. 1x went to 2 y's. That's completely illegal in terms of functions. So the inverse isn't even a function to begin with. So if the inverse is not a function, that function just doesn't have an inverse. Or, we already knew that because of the one-to-one thing we checked earlier. So if you try to invert a function and if it gets you to a point that it doesn't, it's not a function, that's fine. It just means it wasn't invertible to begin with. And that's very much okay. Alrighty. Well, what if we started with square root of x plus 2? Well, if we start with square root of x plus 2, we can find its inverse. Don't forget, x squared minus 2 isn't 1-to-1 to begin with. But square root of x plus 2, if you were to graph it, that is 1-to-1. So let's see what happens. Switch f of x to y, switch x and y. Let's square both sides, and let's subtract 2. Okay, well, you're probably wondering why, not literally why, x squared minus 2 is now the inverse. Well, what it comes down to is the domains of these functions. So, for example, the domain of square root of x plus 2 is -2 to infinity. There's only one branch to this square root of x plus 2. Well, if the domain is -2 to infinity, that means that this is restricted to something similar. If you start with something whose domain is all real numbers, you can have a problem at the end. But if you start with something that has a more restrictive domain, then you will get to a point that is okay. So kind of hard to explain here without showing a picture. Long story short, don't worry. In most cases, it's usually noted like, okay, when x is greater than -2 or something to that effect. So it works this way algebraically, but there are some quirks at hand that most likely you don't have to worry about. So instead of y equals, we have f inverse. But again, it just comes down to the definition of the function we started with versus the function we ended with, right? Starting from square root of x plus 2 is different than starting from x squared minus 2. Okay, let's do a weird one. F of x equals 7 plus the cube root of x minus 6. Step 1, switch f of x to y. Step 2, switch x and y. Step 3, solve for y. Okay, let's get the root by itself. So let's subtract 7 on both sides. We can get rid of this root by cubing both sides, right? Cubing, not a problem at all. And then we can add 6 to both sides. All right, well, this is pretty okay. Well, instead of y equals all of this y is different from this y, so we're going to change this y to f inverse. That's it. Nothing scary at all. Let's do the rational function, right? We did that earlier. We found it to be 1-to-1, so let's find its inverse. Okay, step 1, switch f of x and y. Step 2, switch x and y. Step 3 is to solve for y, and we really got to get back into our toolbox of solving for variables like we did in chapter 1. Well, first things first, we got to get y out of the denominator here. This is kind of a problem. So why don't we multiply both sides by y plus 2? Okay, well, this y is stuck inside the parentheses, so why don't we distribute x? X times y is xy, x times 2 is 2x. Well, we want to get y by itself, so why don't we subtract 2x on both sides, and then divide by x. If this was 5 times y, you would divide by 5. So just because this is an x, we can still divide by x. Okay, not so shabby. This y is different from this y. We have f inverse. Just be very careful. This isn't technically the only way you could do this. You could actually divide by x here and then subtract 2. Your answer would be equivalent, but just something to keep an eye out for. Okay, let's do it where we have x's in both cases. Oi, all right, kind of scary looking. That's fine. Step 1, switch f of x to y. Step 2, switch x and y. But this time, we're going to switch it twice, right? X appears twice, y is going to now appear twice. All right, well, kind of an issue. We got multiple y's to deal with. Let's start by multiplying both sides by y minus 5. And let's again do what we did in the last slide and distribute this x. And now notice this. We have xy here and a y right here. We want all the y's to be together. So what I'm going to do is I'm going to subtract this y on both sides, and I'm going to add 5x to both sides because we don't want the x's on the same side as y. All right, now that all of our y's are on one side together, what we can do is factor out y. Okay, not so shabby. And now, if this was y times 5, you would divide both sides by 5. However, no different. Even though this is y times x minus 1, we can just divide both sides by x minus 1. And now, this new y is f inverse. Okay, not super scary. But this might be, funny memes. Yeah, woo. All right. Well, just some results of inverse functions. Not going to spend a whole lot of time doing this, but just to show you some things. If f of x is 1-to-1 and f inverse is the inverse of f of x, then here's something about domain and range. This is interesting. The domain of f of x is the range of f inverse. And that's actually kind of interesting. Likewise, the range of f of x is the domain of f inverse. Oh, that's kind of neat. Well, kind of think about this because when we were doing step 2 literally said switch x and y. Well, x is like domain, y is like range. So when you switch x and y in that step, you're changing the domain and range of f of x with itself, right? The domain became the range, x became y, and the range became the domain, y became x. So that's kind of interesting. Likewise, since we're switching x and y, this is technically a reflection over the line y equals x, which is pretty neat. So if xy is a point on f of x, and yx would be a point on f inverse. So for example, if 3, 4 is a point on the original function, then 4, 3 is a point on the inverse. Also, inverses undo their original functions. So the inverse function property says that f inverse composed with f gives you just x for every x in the domain of f of x, and f composed with f inverse also equals x for every x in the domain of f inverse. So that's why we needed to talk about compositions in the last section before we got here. Okay, just some very silly looking examples. If f of 3 equals 5, then f inverse of 5 is 3. Yeah. If f inverse of -1 is 7, then f of 7 is -1. F inverse of f of 500, assuming 500 is in the domain of f, well, that's just 500. And assuming 2000 is in the domain of f inverse, f of f inverse is 2000. Very exciting. Okay, well, if we wanted to graph the inverses, you could find the inverse and graph it, or even easier, if you already have the graph of the original function, all we need to do is reflect over the line y equals x. So how we do that is take all the x's, make them y's, make all the y's the x's, or in other words, just flop the coordinates. 2, 4 will become 4, 2. 0, -4 will become -4, 0, and there is the graph with its inverse. X cubed plus 1, switch all the coordinates. -1, 0 becomes 0, -1. 1, 2 becomes 2, 1. Okay, well, we said x squared minus 2 is not invertible. We've now found it twice. It wasn't 1 to 1. Its inverse wasn't a function. Well, if we tried to do the same thing here, switching all the x's and y's with each other, we would get this. Well, this doesn't pass the vertical line test. So yeah, that's a different issue. So again, some more proof that if something isn't 1 to 1, its inverse, whatever it might be, is not a function. Okay, 7 over x plus 2. This is what the original graph looked like. When you invert it, when you switch all the x's and y's, it's actually pretty similar. Just another weird example for some obscure graph that we have here. Again, just switch all the x's and y's. -5, -5 will just stay -5, -5. But 0, -3 will become -3, 0. 3, 1 will become 1, 3. And 6, 5 will become 5, 6. Okay, and last but not least, going back to domain and range, if we think all the way back to 2.4 when we practiced finding domain, I said finding domain, very easy, but finding range is a lot more difficult. Well, here's finally the time that we can find range. Now, the only sad part is that we can only find range of 1 to 1 functions. This doesn't work for just any function. Function has to be 1 to 1 for us to find the range. Well, we saw a couple slides ago that the range of a function is the domain of the inverse. So if you want to find the range of a 1 to 1 function, you take its inverse, you take the domain of the inverse. So let's find the range of 3 over x minus 6. Well, y equals 3 over x minus 6, x equals 3 over y minus 6, multiply both sides by y minus 6, distribute x, add 6x, divide by x. So the inverse is 6x plus 3 over x. And what we're going to do is find the domain of the inverse. Again, domain of the inverse is range of the original. Okay, domain of f inverse, where is this defined? Everywhere the denominator does not equal 0, everywhere that x is not equal to 0. So the range of the original function 7 over x plus 2 is, or not 7 over x plus 2, 3 over x minus 6 is -infinity to 0 and 0 to infinity. So that's how you can find range of 1 to 1 functions. And that's finally the end of chapter 2. So a lot of information here in chapter 2, lots of small things, right? For the most part, this section wasn't too crazy. It was introducing this switch x and y step, and there was really just a lot of algebra to finish up. So with that said, next up is one section in chapter 8 for our course that kind of goes along with solving equations and graphing a little bit, and then we'll jump to chapter 3 after that. And chapter 3 will be the last section, last chapter of the algebra course that these lectures are for. So until then, bye. Hi, everyone. Welcome to this lecture for this random section in chapter 8, chapter 8.1. Chronologically, if you're watching these in the order in which they're intended, we're doing chapter 8.1 after doing chapter 2. So you're kind of like, how do we jump all the way there? We eventually jump back to chapter 3, but 8.1 is a section that you really could do a lot earlier. You could do it as early as after section 1.1. However, since some of the meaning of the section is rooted in graphs, you should more likely do it after 2.3, but instead of breaking up a chapter in the middle of it, I think it's better to just throw it in at the end. So after chapter 8.1, just this one section, we'll jump back to chapter 3 and talk more about specific types of functions and the fundamental theorem of algebra. But until then, this section is actually pretty nice. This is a pretty popular section. A lot of the things you can do here are very nice to do in a world where we enjoy things that are kind of ASMR and cleaning videos and all that. This is a section that it's nice to eliminate some things. So here we go without further ado. So not multiple sections, just multiple things. We're only going to do these first two parts. This last section, I just got really bored one night and decided to do all the same problems, but swap the method in which we do them. So we're not going to go over that. But if you want to see it, by all means, I can give you this presentation. All right, so some basics. We started solving equations in one variable with answers like x equals, right? 1.1, 1.3, we had answers x equals this. Then toward the end of chapter 1, we solved inequalities that had solution sets like x is greater than some number, or x is less than or equal to some number. Then we looked at graphs, which were technically collections of solutions, right? We said 2, 5 fell on one specific graph because it was a solution to the equation y equals whatever it was. And then what we're going to do now is solve systems of equations where the solution is also a single point x comma y. So graphs are collections of solutions, but what we're going to do now is look for a single point that satisfies two separate equations. So our focus in this section is two linear equations and two variables. However, you can get really, really funky with this type of stuff. You could do 3 linear equations and 2 variables. You could do 3 and 3. You could do 2 and 3. You don't necessarily have to do linear equations, but for the purpose of what we're talking about in algebra, the scope of this course, it's fine for us to do 2 linear equations in 2 variables. So how we verify a solution is similar to how we verified solutions in the past, except now we're going to plug in x and y to whatever our system is. So systems will look like this, not always necessarily with a bracket, but I like putting the bracket there to show this is the system. So now we want to know, is 3, 1 a solution to the system? Well, we can tell if it's a solution by plugging in 3 for x and 1 for y, but not just into one of these equations. We want to plug it into both equations. So let's substitute 3 and 1 for x and y respectively into both equations. 2 times 3 is 6, 2 times 1 is 2, 6 minus 1 is 5, 3 plus 2 is 5. Well, normally we're only satisfying one equation. So if it satisfies one equation, then we're good. But here in systems of equations, we are just trying to satisfy every equation. So for example, if this was 5 equals 5 and 5 equals 4, 3, 1 would not have been a solution because it doesn't satisfy both equations in the system. 4, 3, for example, if we plugged in 4, 3, well, in the top, we get 5 equals 5, and in the bottom, we get 10 equals 5. So for example, this would not be a solution because it doesn't satisfy both equations in the system. So one way you can solve is actually via graphing. Notice that I said that these are linear equations. Well, if they're linear equations, that means they are just lines. So the solution to a system would be where those two lines meet. So if we were to graph 2x minus y equals 4 and 2x plus 3y equals 12, well, let's get them both down to y equals something. And when we graph those two lines, this is what we get. And then the point at which they meet is the solution. Well, that point is 3, 2. So if you were to go back and plug in 3, 2 to each of these equations, your system would be satisfied. Okay, so we have some types of solutions we can also get. Most solutions are going to be x comma y's, but you could get to a point where a single statement in your system is never true. In that case, the system is what we call inconsistent. Oh, that sounds familiar to how we've solved equations and inequalities in the past. This is similar to no solution. And when graphed, these lines are parallel. So if you get an inconsistent system, it means that the lines are parallel and they never meet. Well, if they never meet, you can't have a solution. So there's that. If you get to a point where you have a statement that is always true, right? For example, 5 equals 5, then your system is dependent. Well, this is similar to all real solutions. It means that every solution on the line is a solution. And when graphed, these lines are actually the same thing. They overlap everywhere. Now, there's actually some deeper meaning here to dependent solutions, and there's such a way you're supposed to write dependent solutions. However, for the scope of the specific course that I have taught, we don't go into that. But if you ever take a class like linear algebra, or you spend a little bit more time in this type of chapter or this section, you will do some weird things with dependent solutions. But again, not the scope of our course, but it is something that is of note. Okay, so most importantly, we want to talk about the methods. So there are 2 algebraic methods. One method is to graph, right? We just did that. But there are 2 methods that require no graphing at all, and they are substitution and elimination. Substitution says we are going to solve one of our 2 equations in the system for x or y. Well, so now we have x equals or y equals. Once we have x equals or y equals, we're going to take that and plug it into the other equation, right? There's 2 equations in our system. So what we're going to do is take one equation, plug it into the other. Well, once you do that, what you end up getting is a single equation in just one variable. You might have all x's now or all y's now. In that case, you solve that equation for x or y, and then you would take that x or y that you get a value for and plug it into either original equation of the system. Well, that's substitution. My personal favorite, however, is elimination. And elimination, what we're doing is eliminating one of the variables. So what we want to do is add or subtract the equations to eliminate that variable. So one thing that you should note is that you might need to manipulate your equations to be able to do this. For example, if you add or subtract the equations right away, it's totally possible that you will get x's and y's in your added or subtracted equation. So what you might want to do instead is manipulate the equations, multiply by some type of constant, so that when you go to eliminate, one of the variables actually eliminates. Well, once you eliminate x or y, now you can solve for the other variable that you did not eliminate. And now it's back to the original question, or and now it goes back to the last method that you have solved an equation for one of the variables, and now you just plug that variable into either original equation. So let's just do these algebraic methods, handful of examples. This first one, I want to solve via substitution. X minus y equals 5, 2x plus y equals 7. You could do this with elimination, but again, I'm showing it with substitution just so we see the different things. If your method works and you like sticking to one method, if you get the right answer, you get the right answer. So here's what we're going to do. We're going to solve the first equation for x. Again, not the only option. You have two options for method you use, and then after you choose your method, you have two options for what variable you either solve for or eliminate. So not necessarily any one correct way, but so it goes. All right, so let's solve the first equation for x by adding y to both sides. Okay, and what we're going to do now is we have x equals y plus 5. So what we're going to do is plug in y plus 5 for x. We got x equals y plus 5. So plug in y plus 5 for x into the second equation specifically. Oh, well, why don't you look at this equation down here now? This equation is just a simple linear equation that we have solved all the way back in 1.1. So let's distribute 2. Let's combine 2y and y. $2 plus $1 is $3. Let's subtract 10 on both sides, and let's divide both sides by 3. Okay, so we have the value to one of our two variables. We have that y equals -1. Okay, well, if we know that y is -1, plug -1 into the first equation. Well, y is -1, -1 plus 5 is 4. So the solution to the system is 4, -1. However, you could have plugged y equals -1 into the either original equation in the very beginning. So, the way we're writing this here is that, the second equation kind of goes away, just becomes this y equals -1. But you could plug y equals -1 into the original second equation, and you would get the exact same answer. So not perfectly a rhyme or reason any one way or the other, just something to keep in mind. Okay, and like I said, is this the only way to do the problem? Did we have to substitute y plus 5 in for x? Did we have to use substitution at all? Stuff like that. Again, I bring up that multiple paths can get you to the same answer. Okay, and if you were to graph those two lines, there you go, 4, -1. All right, let's solve this one via elimination. 3x plus 2y equals 3, 9x minus 4y equals 4. So if you're looking for an idea as to whether or not you want to use substitution or elimination, this example is great to not want to do substitution. If you were to do substitution, notice that you would need to solve for x, and at some point, you would need to divide by 3. So you would subtract 2y on both sides, and you would divide by 3, and you would get -2/3 y. Fractions, not good. Well, what if we solve for y instead? Well, you would subtract 3x on both sides, and you would divide by 2, and then you would get -3/2 x. So maybe not the best option for substitution. However, we're going to do elimination. Specifically, we are going to eliminate y this time. You don't have to eliminate y. You can instead eliminate x, but I'm going to eliminate y. So our goal in elimination is to add or subtract these equations. But notice that if we add or subtract these equations right away, 3x plus 9x is 12x, 2y plus -4y is -2y equals 7. So we get 12x minus 2y equals 7, and then we still have an equation in one variable. That didn't do anything. So what we need to do is manipulate one of these two equations to get to a point where we can add or subtract and something will actually go away. So I flashed it on screen a little too quick, but why don't we multiply the top equation by 2? Maybe not obvious right away, but you'll see it in just a second. If we multiply the top equation by 2, 2 times 3x is 6x, 2 times 2y is 4y, 2 times 3 is 6. So make sure you multiply everything by 2. And now it's a little clearer why we chose to do it this way, because now if we add or subtract the equations, notice we have plus 4y and -4y. When we add them together, plus 4y minus 4y is just going to go away. 6x plus 9x is 15x. 6 plus 4 is 10. Divide both sides by 15, and 10 over 15 is 2/3. There we go. Really nice. This is elimination. Add or subtract the equations to eliminate one of the variables, and if you need to do the added step of manipulating one of the equations, that's totally fine too. All right, well, we have x equals 2/3, but we need our y, so we're going to plug 2/3 back into either original equation. I'm going to plug it into the first. You can plug it into the second. Does not matter. All righty, well, plugging in 2/3 for x. Well, 3 times 2/3, 3 cancels out. Subtract 2 on both sides, divide by 2. Then your answer is 2/3, 1/2. So solving systems of linear equations is quite nice. Either substitute or eliminate the variables. Okay. Like I said, you could have also plugged in 2/3 into any equivalent form, but I chose to just plug it into the first original equation. Okay. Well, there's a 2/3 and 1/2, the solution to our system. Okay. Let's solve this one via substitution again. Substitution, what we're going to do is solve the second equation for y. So we're going to add 2x to both sides. Well, from here, we have y equals 2x plus 9. So we're going to take this 2x plus 9 and plug it in for y in the first equation. Okay. And now, once we're here, we substituted our y variable with the purpose of not having any more y's. Now we have just an equation in one variable. Let's distribute -5. Let's combine 2x and -10x. Let's add 45 to both sides, and let's divide both sides by -8. All of these steps in the top. So we have x equals -6, and now we're just going to plug in -6 into the second equation. 2 times -6 is -12. -12 plus 9 is -3. So the solution to our system is -6, -3. Okay, like I said, you could have plugged in x equals -6 to either original equation. I'm just happening to plug things into these. But if you plug -6 into either original, you would also get -3. There's your solution. All right, let's do it one more, or not one more. Let's do a couple more. Let's do this next one. 2x plus 3y equals 21, 3x minus 4y equals 23, and I want to solve this one via elimination. This time, I'm going to eliminate x. Last time, I think we eliminated y. This time, we're going to eliminate x. Well, notice 2x and 3x, there's nothing we can multiply 2x by to get rid of 3x, and there's nothing we can multiply 3x to get rid of 2x. So what we need to do is not just manipulate one of the equations, we need to manipulate both of them. So what number do we multiply 2x by, and what number do we multiply 3x by to get to a pair of factors, not a pair of factors, a pair of terms that can be canceled out? Well, what if we multiply 2x by 3 and 3x by 2? Well, maybe 3 times 2 is 6, 2 times 3 is 6. Maybe there's something fancy about 6 when it comes to 2 and 3. So multiply everything by 3 in the top, multiply everything by 2 in the bottom. And what we're now going to do, we have 6x and 6x. If we add 6x and 6x, we will get 12x. So instead this time, let's subtract equations. What you could also do, you could multiply one of these by -3 or -2. Well, if you multiply by negative, then the negative sign is already there, ready for you. But again, I'm just trying to show all the different ways you can solve these. So let's subtract these equations. 6x minus 6x is 0. It goes away. We eliminated x. 9y minus -8y. 9y minus -8y would be plus 8y. So 17y, 63 minus 46 is 17. Divide both sides by 17, and we get y equals 1. And now, I think you guys get the idea. We can plug y equals 1 into either original equation or any equivalent form. So let's plug it into the second original equation, because why not? Well, plug in y equals 1, and now we're just going to solve for x. 4 times 1 is 4. Let's add 4 to both sides. Let's divide both sides by 3. Our answer is then 9, 1, x, y. Okay. There's our answer. Let's do another one. Let's solve this one via substitution. We're going to solve the first equation for y. Well, if we solve the first equation for y, then we're just going to subtract x on both sides. And now we're going to take 3 minus x and plug it in for y. So 3 minus x into second equation for y. And now we just have a linear equation for the second one. So let's solve that second equation for x. Let's distribute 2. Let's combine 2x minus 2x. 2x minus 2x goes away. So we're left with the equation that 6 equals 9. But 6 doesn't equal 9. So what did we do wrong? Well, actually nothing. So what we got is an inconsistent system. We got to a statement that was never true. So if we get one statement that is never true, that means the entire system is impossible to solve. So there is no solution to this system. However, another way you can look at it is like this. If we multiplied that second equation by 1/2, or divide everything by 2, however that works, right? Divide everything by 2 in the second equation. 1/2 times 2x is just x. 1/2 times 2y is just y. And look at that. We get 2 of the exact same equations, except we're saying the same 2 variables being added together need to add to 3, and the same 2 variables also need to add to 9/2. There's no way that the same 2 numbers can add to 3 and also add to 9/2. If we're going from a graphical standpoint, well, let's subtract x on both sides. And look at this. These are 2 lines with the same slope, but different y-intercepts. That's the definition of a parallel line. So there is no solution for that reason. So there are those 2 lines. Notice that they'll never meet. There can't be a solution. Okay, well, maybe you already have an idea on what's going to happen this time. So this time, why don't we multiply the second equation by 2 so that we can eliminate x. So if we have 4x and -2x, if we multiply this by 2, we get -4x, and 4x minus 4x is going to go away. Nice. All right. 2 times -2x, -4x. 2 times -y, -2y. 2 times -6, -12. And now let's add these equations. So 4 plus -4x, or just 4 minus 4x, is 0. 2 plus -2y, 2y minus 2y is 0. And 12 plus -12 is also 0. Oh, did we do something wrong this time? Well, of course not. What we got this time is we found a statement that is always true in our system. Well, if we get to a point where the statement is always true, this is a dependent system and has all real solutions. Again, looking at it in a different way, well, what if we manipulate both of these equations to maybe look like each other? Well, let's multiply the first equation by 1/2, and let's multiply the second equation by -1. Well, 1/2 times 4x is 2x, 1/2 times 2y is y, 1/2 times 12 is 6, -1, change all these signs, and notice that we have 2 of the exact same equation. Well, they're the same equation, they're the same line, so that system is dependent. So literally, I graphed both lines here, but you only see one of them because they overlap everywhere. Okay, so just some closing thoughts. We have 2 equations that give us a 2-part coordinate, but what would 3 equations give us if we had 3 variables? A faster way, there's always a way that's faster. And this thing here, the system of linear equations, is actually the entire study of a class called linear algebra. This is a very, very small, very easy example. That's like, it's like day 1 linear algebra, and you expand very quickly to solve systems of equations that might have 5 equations and 5 variables. And it's actually very neat. Linear algebra is a very fun class. So with that said, I'm not going to go over all the opposite methods. These methods were enough. But with that said, thank you so much for watching. And next time I see you, we will be back in chapter 3 for the final chapter of this algebra course. So with that said, bye. Hi, everyone. Welcome to the beginning of chapter 3 with section 3.1. This is going to be the last chapter for this college algebra class that I'm doing these lectures for. If we were to ever do pre-calculus, we would do chapter 4 in this book, but alas, we will stop here for now. So chapter 3, 6 sections. 2 of those sections we're going to combine into one lecture. It just makes a little bit more sense. It eliminates a little bit of the weird sequencing. So we'll get to there when we get there. But for now, sections 1, 2, and 3 in chapter 3 are all on their own. So what we're going to do is start with quadratic functions, and then we're going to move to polynomial functions. So quadratic functions degree 2, and then we'll work our way up to polynomials, which could be any degree. Do something a little different in 3.3, but then we start to wrap up the entire course when it comes to 3.4. So let's do quadratic functions. In chapter P, we had ax squared plus bx plus c, the expression. In chapter 1, we had ax squared plus bx plus c equals 0, the equation. In chapter 2, we had f of x equals ax squared plus bx plus c, specifically the function. But what we have here in chapter 3 is also a function, right? The name of the section is quadratic functions, but it's going to look a little different now. Okay, so this is what we call general form for quadratic functions, and we get this via completing the square. So we'll do a couple examples of this. We haven't talked about completing the square since, I think, 1.3. It's been a really long time, but we'll get there when we get there. But this is going to be what we focus on here in chapter 3.1, but also we'll see a couple times where we can use the original form. So standard form is that original form we used to work with, ax squared plus bx plus c, but here in 3.1 we want to focus on general form, a times x minus h squared plus k. H is the horizontal shift, a is the stretch or compression and x-axis reflection, and k is the vertical shift. So all of these things would have been relevant when we did 2.7, when we did transformations, but we actually have specific meanings for some of these things now. Specifically, h comma k is going to be our vertex of the parabola. So we have a general idea as to what quadratics look like, right? They look like parabolas. They open up or they might open down, but the place where it changes from decreasing to increasing or increasing to decreasing is called the vertex. Now, the place where that vertex occurs in the function would be h comma k. Now, just want to stress, this is minus h. If you have x minus h, h would then be positive. It's backwards, but for plus k, it is intuitive. So, right, go back to that, like the 2.7 stuff where we said intuitive for horizontal, not intuitive. Sorry, intuitive for vertical, not intuitive for horizontal. Okay, h, if we don't have it in this form, h in this form occurs at negative b over 2a. So let's say you're given standard form and you don't know what the vertex is. Here, the vertex is as simple as just reading it. But in standard form, the vertex would occur at negative b over 2 times a. Now k, well, k would just be the value at h. So you can find the x coordinate of the vertex, right, the h coordinate, by doing negative b over 2a, and then you find its respective y value by just plugging in that h value into your function, right? X, y, that makes a lot of sense. X equals h we refer to as the axis of symmetry. I personally don't spend a whole lot of time with this, but it's actually a way that you can shortcut graphing quadratic functions. And I'll talk about it when we go to graph them, but in most cases, it's a little bit easier to talk about everything else. K is either the minimum or maximum value based on the value of a. So we saw in 2.7 that if a were to be positive, our graph would be a regular parabola. In that case, the value right at the bottom, the vertex would be a minimum, right? Here's your parabola. Well, we have a minimum value right here. And likewise, if a is negative, it reflects over the x-axis. And in that case, k would be the maximum value. So let's do some examples of converting to general form and converting to standard form. So general form is that a times x minus h squared plus k notation. So here's what we're going to do. We need to complete the square. We said in 1.3, completing the square, you don't ever have to do. It's one of those things that you could do if you wanted to use the square root property to solve equations, but odds are if you're in that situation, you're probably just going to go for quadratic formula anyway, since it works way more frequently and works way more consistently. So completing the square says this: if for ax squared plus bx plus c, we are going to add and subtract b over 2 squared, because what that's going to do is help us get a perfect square term. So don't believe me right now, that's okay. So in this case, ax squared plus bx plus c, b is 6. So what we're going to add and subtract is b divided by 2, the whole thing squared. In this case, b is 6, so we are going to add and subtract 6 divided by 2 squared. And again, we have to add and subtract it. Well, if we add this thing and subtract this thing, well, they would just cancel out. So it's like we added 0. And we know that if we add 0 to anything, it doesn't change the value. Okay, well, we know that 6 divided by 2 is 3. 3 squared is 9. And now let's group these 3 terms together, because you might notice something about these 3 terms. You might notice that if we wanted to factor this, this is a nice perfect square factor. Okay, x squared plus 6x plus 9 is x plus 3 squared. And then everything on the outside, minus 9 plus 7, is minus 2. Okay, so we went from standard form to general form. And what we can do now is we can pull the vertex from this a lot quicker. You could do h equals negative b over 2a and then plug that value in, but that can be a lot of work. So now, since we've already converted, let's take the vertex from here. The vertex is always x minus h and then plus k on the outside. Well, normally it's x minus h, but here we have x plus 3. That means the x value of the vertex will be negative 3. Backwards for the x value. Kind of, again, think about the intuition part of 2.7. However, the y coordinate is, as you would expect, it is intuitive. So we would get negative 3 for x and negative 2 for y. Again, sign is backwards for x, sign is as it makes sense for y. X minus h is minus 3 since this is plus 3, and k is negative 2. Okay, so let's do another example of converting to general form. The one rule that we had when it came to completing the square is that if we were to complete the square, a needs to be 1. Well, a here is 5. So that means we don't have to complete the square, right? It's all over, we're done. No, what we can do is just take out 5 from the first two terms, right? Think about when we were completing the square in the last example, the only thing we were interested in was that middle term b. We don't even need to touch that plus 8. Okay, well, let's complete the square on the inside. b, the coefficient attached to x, is negative 4. So what we're going to add and subtract is negative 4 divided by 2 squared. We're going to add and subtract it on the inside of these parentheses. Okay, negative 4 divided by 2 is negative 2. Negative 2 squared is positive 4. So we're adding and subtracting 4. But what we're now going to do is we see this is our perfect square, but we have this extra minus 4 out here. We don't want that extra minus 4. What we can do is pull out this minus 4, but notice that this minus 4 is stuck inside this 5. So if we're pulling out negative 4, what we're really pulling out is 5 times negative 4. So be very careful about that. Okay, well, this is a perfect square. Here, 5 times 4 is negative 20. Perfect square, and combine everything on the outside. We get x minus 2 squared and negative 12. Pretty nice. And now we can get the vertex from this. Again, x minus h means that h is positive. So since we have x minus 2, h is positive 2. And k, well, k is negative 12. So we get 2 comma negative 12. Again, keep in mind the quirks of the vertex stuff when it comes to hk. Okay. Let's do an example where we write a quadratic function in general form if we were given some information. So we're given the vertex here, and we want to find the version of this quadratic function that has this vertex that passes through this point specifically. Well, what's really nice is this is kind of like writing linear equations. We're given 2 points, and we just plug some information in. However, we're going to have to treat this a little different. Well, let's start with the vertex. Vertex is hk, so h is negative 3, k is 4. And the point that we're given is negative 4, 7. So x is negative 4, and f of x, or y, right? F of x and y are interchangeable. F of x is 7. Well, general form for a quadratic equation is as follows. And notice, well, we have f of x, we have x, we have h, and we have k. The only thing that we're missing is this a. So think back to when we were writing equations of lines, and we said, okay, we found a slope, we have a point, we need to plug everything in to find b. Okay, same kind of idea, except we're not looking for b anymore. Now we're going to look for a. So let's plug in all of this information that we know. F of x is 7. A, we don't know. We're going to solve for a. X is negative 4. H is negative 3. And k is positive 4. Okay, and now we just solve for a. Negative 4 minus negative 3 is negative 4 plus 3. Negative 4 plus 3 is negative 1. Well, negative 1 squared is positive 1, so a times 1 is just a. And then we subtract 4 on both sides to get a equals 3. All right, well, in general, this is what quadratic functions are. And when we were going to write the equation of a quadratic function, we need a, we need h, and we need k. All right, well, we just found a, h is negative 3, and k is 4. Last but not least, x minus negative 3, x plus 3. And now you see, here's where the vertex is, and that's where our stretch or compression factor is. So given some information, we can also write equations of quadratics. One more example, this was finding it in general form. If we want to find it in standard form, all we need to do is expand, right? Going from standard to general form is this weird completing the square nonsense. Well, not nonsense, but, kind of a pain in the butt, right? But when we are converting to standard form, when we just want to get ax squared plus bx plus c, this is just expanding. Well, x plus 3 squared is x plus 3 times x plus 3. This is a chapter P question for us to expand this. That is x squared plus 6x plus 9. We distribute 3, and then 27 plus 4 is 31. So if you want it in general form, there it is. If you want it in standard form, I think standard form is a little bit prettier, even though it's a little less useful in some cases. That is standard form. Let's do another one of these examples. This time, vertex 1, negative 5, and the point is 3, negative 21. Well, in this case, h is 1, k is negative 5. The point x is 3, f of x or y is negative 21. So again, let's plug in all of this information into the general form for quadratic functions. Okay, well, 3 minus 1 is 2. 2 squared is 4. What we can now do is add 5 to both sides and divide both sides by 4 to get a is negative 4. All right, a times x minus h squared. Well, we had the vertex on the previous slide. We have a right here, so we get negative 4 x minus 1 squared. minus 5. Not so shabby. If we want to convert this to standard form, again, this is just expansion. So let's expand x minus 1 times x minus 1. Let's distribute -4. And last but not least, -4 minus 5 is -9. Not super scary. So those are some basics to quadratic functions. But what we're going to be interested in doing is graphing. All right. So for us to graph, kind of staying consistent with how we've done things in the past, let's find the vertex, y-intercept, and x-intercepts, and then graph it that way. However, there are some shorter ways that you can graph quadratic functions. I'll point them out, but I'm not going to do any of them here. So just know that there is a shorter way, but I like going this way because it covers all the information that you might be interested in a quadratic function, the vertex, y-intercept, and x-intercepts. Okay, so we have f of x equals -3, x plus 2 squared plus 12. Let's start with the vertex. Well, the vertex here, x minus h, so h is -2, and k is positive 12. Okay, point 1 down. Y-intercept, well, to find the y-intercept, don't forget that we set x equal to 0. All right, well, f of 0 says wherever we see x, write 0. 0 plus 2 squared, 2 squared, 2 squared is 4. -3 times 4 is -12. -12 plus 12 is 0. So when x is 0, y is 0. So our y-intercept is 0, 0. Well, x-intercepts, almost identical, except for setting y to 0 or f of x equal to 0. All right, a little bit more involved. Let's subtract 12 on both sides. Let's divide both sides by -3. Let's take the square root of both sides, but don't forget we get plus and minus. Okay, so we get plus and minus 2. All right, when this is positive 2, 2 equals x plus 2, x equals 0. When this is -2, -2 equals x plus 2 is -4. Right, solving equations. Don't want to spend a whole lot of time talking about that today, but here we go. So we have two x-intercepts, -4, 0, and 0, 0. So we have a vertex, we have a y-intercept that happens to also be an x-intercept, and we have another x-intercept. So in general, we're going to talk a little bit more about this in the next section with polynomials. But in general, if you want to graph any polynomial function, you need n plus 1 points. Now, what is n? N is the degree of your polynomial. Again, we got to talk about that a little bit more in the next section. But what I'm getting at here is that if you are graphing a quadratic function of degree 2, you need at least 2 plus 1 points, which is 3. So if you want to graph any quadratic, you need a minimum of 3 points to be able to graph it. Now, you might need more than 3. Your vertex has to be one of those 3 points. But point is, if you know 3 points, most likely you're able to graph, especially if one of those is the vertex. But if you wanted to graph something that is cubic, you would need 4 points. Something to the 4th power, you need 5 points, and so on. Okay, so let's graph all 3 of those points. And here we go. So, and now we know this is a parabola. So there you go. That's how you would graph this quadratic. Now I mentioned that there's a shorter way to graph, and here it is. Well, I just told you that we need 3 points to graph quadratics. One of them has to be the vertex. Okay, so think about to this last example. We found the vertex, and then we found the y-intercept. So just for a moment, ignore that we found -4, 0. If we have -2, 12, and 0, 0, what we also know is that the line, the vertical line on which the vertex lies, is the line of symmetry, axis of symmetry for quadratics. What that means is that if you know one point to the left or to the right of your vertex, you can reflect it over that axis to get a third point. So what we could have also done is start with -2, 12, and 0, 0, and said, okay, 0, 0 is 2 points horizontally from the axis of symmetry. So that means it has an equivalent point 2 units to the other direction of your axis of symmetry. So 0, 0 takes 2 units to get to -2, 12. If you go another 2 units, it'll have a reflected point. So with that said, you technically could have graphed knowing 2 points, but you could have found a third point just using symmetry. Now, of course, this is only helpful if you know the vertex. If you don't know the vertex, you have no idea where this graph changes from increasing to decreasing, or in other cases, decreasing to increasing, but that is another option available to you. In my opinion, I personally think that it's very important to know how to find x and y intercepts for your functions. So that's why I prefer to graph this way. But again, that is a quicker way you are able to graph quadratics. Okay, well, let's do another example with 2 times x minus 1 squared minus 4. Let's start with the vertex. Vertex, x minus h. Okay, h is positive 1. Plus k, k is -4. Okay, vertex, the easy part. Y-intercept says set x equal to 0. All right, well, wherever we see x, just write 0. 0 minus 1 is -1. -1 squared is 1. 2 times 1 is 2. 2 minus 4 is -2. So when x is 0, y is -2. Okay, so we have 2 points. And again, you know the vertex, you know the y-intercept. You can technically graph from here. But again, I think it's very important to also be able to find x-intercepts. X-intercepts say to set y or f of x equal to 0. All right, let's add 4 to both sides. Let's divide both sides by 2. Let's take the square root of both sides and just add 1 to both sides. So you would need quadratic formula technically to find these x-intercepts. So we have 2 x-intercepts that way. All right, graphing all 4 points that we know now, we can connect them just like that. So notice that we could have done this with just the 2 points. We could have done this with just these bottom 2 points, reflected 0, -2, over to 2, -2, and graph that way. But also always good use to find our x-intercepts. Okay, well, the last 2 examples we did were in general form, and now we're given one in standard form. Well, we need to convert to general form to be able to answer the same question, right? So let's start by converting to general form. Well, for us to complete the square, we need this a to be 2. So let's factor out 2 just from the first 2 terms. Here, let's complete the square. We're going to add and subtract 4 over 2 squared, right? B divided by 2 squared. 4 over 2 is 2. 2 squared is 4. Okay, we want to pull out this negative 4 because here we have the perfect square. Let's pull out this negative 4. But since this negative 4 is stuck inside this 2, we have to pull out 2 times negative 4. All right, 2 times 4 is 8. And now this is x plus 2 squared, and this is negative 18. Okay, and now we can answer all of the exact same questions. The vertex x minus h, so h is negative 2, plus k, k is negative 18. Y-intercept set x equal to 0, so f of 0. 0 plus 2 is 2. 2 squared is 4. 2 times 4 is 8. 8 minus 18 is negative 10. So our y-intercept is at 0, comma, negative 10. X-intercepts, we're going to set f of x equal to 0. All right, let's add 18. Let's divide by 2. Let's take the square root of both sides. And now when this is positive 3, 3 equals x plus 2, x is 1. When this is negative 3 equals x plus 2, x is negative 5. So our two x-intercepts right there. Plotting all 3 points that we found. Also, I forgot to plot the y-intercept. Y-intercept, I think, was 0, negative 2. Or no, was it 0, 0, negative 10? Right, my bad. All right, so plotting the 4 points that we knew, connect them, there you go. Or you could have also, found the two x-intercepts and graphed that way, but then it is good practice to know the y-intercept anyway. So there we go. However, I said we had to convert to general form first. But is that true? The answer is no. Okay, so what we're going to do is this. Instead of converting this to general form, we also know that the vertex occurs at h equals negative b over 2a. ax squared plus bx plus c. Without needing to convert it all, we can find h via calculation. Okay, well, b is 8, a is 2, so 8 over 2 times 2, 2 times 2 is 4, 8 divided by 4 is 2, so the vertex occurs at x equals negative 2, or h equals negative 2. But we knew that from the last example. Well, how do we find k, right? We know h, how do we find k and h comma k? Well, that's just plugging in h. So when we plug in negative 2, 2 times negative 2 squared plus 8 times negative 2. All right, negative 2 squared is positive 4. Okay, positive 4, and then 2 times 4 is 8. 8 times negative 2 is negative 16. So this is negative 18. So our vertex is at negative 2, negative 18. Y-intercepts, we set x equal to 0. So plug in 0 into this standard form. Well, this one's even easier. This term is 0. This term is 0. Whole thing, just negative 10. So actually, in some ways, standard form could be easier as opposed to general form. X-intercepts, all right, set f of x equal to 0. And, all right, well, this requires a little bit more work to solve because it's not in a nice factored version that we could just take the square root of both sides for. However, let's divide both sides by 2, right? All of these have are a multiple of 2. This we can factor, and then we get negative 5 and 1, just like we got before. All right, and look at that. We had all the exact same points that we had from doing it in general form. Okay, here's negative 3x squared minus 3x minus 6. So instead of doing this one via general form, let's just go right for keeping it in standard form. Vertex occurs at h equals negative b over 2a. So b, ax squared plus bx plus c. B is negative 3. A is also negative 3. 2 times negative 3 is negative 6. Well, negative 3 over negative 6 is 1/2, but the extra negative on the outside makes the vertex occur at negative 1/2. Well, we don't love fractions. We would have gotten fractions doing it the other way too, so this isn't going to be super pretty, but we can find k by doing f of negative 1/2. And yeah, I'll trust you guys to do your fraction multiplication and addition. So the vertex is at negative 1/2, negative 21 over 4. Y-intercept says set x equal to 0. Okay, well, this is really nice because that's 0, that's 0. So it's just negative 6. 0, comma, negative 6. X-intercepts, set the whole thing equal to 0. Let's divide everything by negative 3. And actually, this doesn't have any x-intercepts. So try doing it with quadratic formula, and when you get that, you end up getting 2 complex zeros. So in that case, there are just no x-intercepts. Okay, well, we're given only 2 points, but like I said, now that we only know 2 points, we can take this point, reflect it over the axis of symmetry, 1/2 of a unit to get to here, another 1/2. We would get, oh, just kidding, this was the vertex. So take this point, reflect it over this axis of symmetry, and you would get this point right here to also be negative 6. So that's graphing. Some more basics. We're just going to wrap up the section here. The domain of all quadratic functions, there's no point that you can plug in an x and get something undefined. So the domain is all real numbers. The range is dependent on the value of a. So if a is positive, that means your parabola opens up. That means all of your y values are your k to infinity. But if your parabola opens down, then your range is negative infinity up to k. Your parabola looks like a cup if a is positive and a hill if it is negative. We saw that in the examples, but it's a good way of checking your work if you know what a is. If your a is bigger than 1, the absolute value of a is bigger than 1, that means your graph gets a little bit sharper, a little bit narrower. But if it's a fraction between 0 and 1, it gets a little wider. And then, just throwing this out there, there's a ton of physics applications when it comes to quadratic functions, right? Physics is very, very broad. However, usually the first chapter of physics when you take a basic physics class is kinematics. Even before kinematics, you might just do, you throw a ball off a cliff, and when does it hit the water? how fast is it hitting water, stuff like that. And you'll deal with quadratics a ton when you are doing information like that. So just throwing that out there. So that's the end of 3.1. 3.2, we're going to get into in the next section, but that's the end of 3.1. We're just going to go from degree 2 to any degree and talk about all of the information associated with polynomial functions. Okay, so with that said, I will see you in 3.2. Hi everyone, welcome back to 3.2. So in 3.1, we talked about quadratic functions, and what we're going to do here in 3.2 is talk about polynomial functions, right? Quadratic functions are degree 2, but what we're going to do here in polynomial functions are for any degree and talk about properties that it can apply to any polynomial. So let's get into some basics. So linear functions are f of x equals mx plus b. Quadratic functions are a times x minus h squared plus k, or ax squared plus bx plus c. So then the general polynomial function for any degree is this messy looking thing right here. However, we've actually seen this before. We looked at this in chapter P when we talked about general polynomials, just the expression polynomials. So not super scary, not kind of familiar, but we'll just go through some of the bullet points about them. So each of these things sitting out in front, for example, a sub n minus 1, a sub n minus 2, we call those all coefficients. Specifically, we want them to be real numbers when we talk about polynomials. Then each of the exponents are referred to as exponents, but we specifically want them to be whole numbers. So the coefficients themselves can be any number we want. However, the exponents have to be whole numbers. If you think all the way back to chapter P, in the case that we had something like x to the 2/3, we didn't even call it a polynomial. We just said it's not a polynomial. So just be careful of that. Each specific thing being added or subtracted together is called a term. And specifically, the one that sits in front is the leading term. Well, that would make the coefficient the leading coefficient, and we say n, that exponent is the degree. Now, specifically, the leading term in any polynomial is the term with the highest degree, and normally we like to write terms in descending power order. We call it standard form, but in the event that your terms are not in descending power order, your leading term is the term with the highest degree. So very quickly, some more basics before we get into the interesting stuff of the section. The domain is all real numbers for all polynomials. There's no number that we can plug in that would make a polynomial undefined. And the range of all odd degree polynomials, well, odd degree polynomials, they go in different directions. So in that case, that would be all real numbers, but the range of all even degree polynomials would be dependent on the leading coefficient and whether or not we have maximums or minimums, kind of like for quadratics. So first thing we're going to talk about in polynomials is end behavior. And this is new information, but you're going to see it's not really all that scary. So the leading term tells us about the end behavior, or specifically how a function behaves as it goes forever to the right or forever to the left. Okay, so start by looking at the degree of the leading coefficient. Okay, if n is even, so squared to the 4th to the 6th, your end behavior is the same as you approach both directions. So kind of think about a parabola, right? X squared, both sides go up, negative x squared, both sides go down. Well, how do we know the difference between both sides go up and both sides go down? That comes down to the leading coefficient. If the leading coefficient is positive, then both sides will go up. If the leading coefficient is negative, then both sides will go down. However, when the degree is even, the end behavior is the same. So when the degree is odd, the end behavior is different as you go in each direction. So kind of think about x cubed in this case. If the leading coefficient is positive, the left end goes down, right end goes up. And if the leading coefficient is negative, then the left end goes up and the right end goes down. So the opposite to what we just talked about. So putting all this information, we actually get this nice little graphic right here that says when our degree is even or odd and the leading coefficient is positive or negative, we get these 4 situations. So notice this kind of looks like negative x squared, x cubed, and what would be negative x cubed. So just some more specific graphical examples. We have x to the 4th minus 2x squared, even degree and positive leading coefficient, even degree and now negative leading coefficient. One thing I want to stress about here too is these little zigzags. Well, these little zigzags say we don't really care what's happening in the middle. Of course, this graphic is only telling us what's happening on the ends, the end behavior. There's x cubed, degree is odd and leading coefficient is positive, and if we make the leading coefficient negative. So let's do some examples where we determine end behavior. Well, we have 2x cubed plus 5x minus 2. So the first thing we want is the leading term. Well, the leading term in this case, the term with the highest degree, happens to come in the front, which is 2x cubed. Now, what we're interested in terms of degree and leading coefficient is whether or not the degree is even or odd, if the leading coefficient is positive or negative. We don't care about the actual values themselves. We only care about that very general case of even, odd for degree, positive, negative for leading coefficient. So here, the degree is 3, which is odd, and the leading coefficient is 2, which is positive. So now go back to that graphic and look where degree is odd, leading coefficient is positive. It looks like this. Okay, so here's the graph of that. And next up, let's do negative x squared plus x plus 4. The leading term is the term with the highest degree, which again is negative x squared. Okay, the degree, we only care about even, odd. Well, the degree is 2, which is even. For leading coefficient, we only care about positive versus negative. Well, negative x squared is negative. So even and negative, look at that graphic and see what it corresponds to. Even and negative is going to look a lot like this one right here. There's the graph of that function for a little bit more proof. Let's do another one. 1 minus x cubed minus x squared. So the leading term, it's supposed to come to the front However, notice that our term with the highest power is not in front. That's okay. We can pull it right from here. If it is more comfortable for you to rewrite it with negative x cubed in front, you're very welcome to do that, but you don't necessarily have to. So leading term is negative x cubed. Again, easy way of remembering it is the term with the highest power. Okay, well, the degree, again, just even versus odd. 3 is odd, and the leading coefficient is obviously negative. Odd and negative corresponds to this right here. And the graph of that, a little bit something like that. Okay, 4 plus x to the fourth. Okay, well, leading term is going to be term with the highest power. Again, not actually sitting in the front, but that's okay. It's x to the fourth. The degree is even, and the leading coefficient is positive. Even and positive just looks like x squared. However, what if in the case that we have a function who's not fully expanded and instead all factored? How do we do this? Well, think about this again. When we're looking for the leading term, we don't care what the values are. We only care about even versus odd, or positive versus negative in the case of leading coefficient. So here's what we're going to do. In the case that this is all factored, we're just going to look at the x terms in each factor. So in this case, if we have 4x raised to the fifth power, we would do 4x minus 5 times 4x minus 5 times 4x minus 5 times 4x minus 5 times 4x minus 5, but that's a lot of work. So instead, just take this 4x and raise it to the fifth power. Well, 4x to the fifth, you would get an x to the fifth term at some point in there. And same thing here, you would do 2x plus 1 times 2x plus 1, but at some point you would be doing 2x squared, which would give you 2x's. So a nice easy way of looking at this is we have 5x's here, 2x's here. In total, we have 7x's. Well, we know what the degree is now. It's x to the seventh, but what is the leading coefficient? Well, let's do the exact same thing, but now look at the coefficients of each of these x's. Well, this coefficient is positive. Raise it to the fifth power, still positive. This leading coefficient is positive. Raise it to the second power, it's still positive. This positive leading coefficient times this positive leading coefficient will be positive. So the degree is 7, which is odd. The leading coefficient is, we just said, is positive. Odd and positive looks like this. Next up, 3x minus 6 cubed times 2 minus x to the fifth. All right, well, same thing. To get the leading term, let's take a look at our x terms and see what happens. Well, we have an x here. We raise it to the third. We have 3 x's. Here we have an x and 5 of them. So in total, we have 3 x's plus 5 x's. We have 8 x's. So we know what the degree is. The degree is 8. But what's the leading coefficient? Okay, well, here we have 3, raise it to the third power, that's positive. Here we have negative x, though. Ooh, be very careful. The sign of our x is negative. So a negative x raised to the fifth power will still be negative at the end. So in total, positive times a negative would be a negative leading coefficient. So negative and even would be this one right here. Okay, let's do that again, but just slightly change it so that it's x to the fourth here. Well, notice that we can just add the exponents to figure out how many x's we have, right? X cubed, x to the fourth, we have 7 x's. But now we need to determine what that leading coefficient is. Well, 3 cubed is still positive, but now we have negative x to the fourth. Well, negative x to the fourth is then positive. So we have a positive times a positive in this case. So we have a positive leading coefficient. Okay, the degree is odd. Leading coefficient is positive, again, because negative x to the fourth will be positive, not negative anymore. Odd and positive right there. Okay, we can make it one step funkier to do x squared here. Only thing that changes is when we are going to count how many x's we have. Well, this is x squared to the fifth power. So here we actually have 10 x's. You would do x squared times x squared times x squared times x squared times x squared, but each of those x's was 2 of them. Sorry, I'm doing like a John Cena thing here. So we would have 10 x's in total. So we have x to the 10 times x squared. So in total we have 12 x's. 4 is positive, 2 is positive, positive. Okay, even degree, positive leading coefficient, we get this bad guy right here. So that's end behavior. Well, next thing we're going to talk about are zeros. Now, zeros are actually really, really nice because we've been doing stuff like this forever. We're just going to start to give these things names in this subsection and in the next subsection. So zeros of a function are the values, the x value specifically, where your function equals, you guessed it, 0 for talking about zeros, right? But the locations where f of x is 0, we had a definition for that. That is the x-intercepts. Oh, we've been finding intercepts almost entirely in chapter 2. So here in chapter 3, we're doing the same thing, except now we're going to give these things some new names. So suppose that c is our 0. Suppose c satisfies f of x equals 0, then all of these following statements are true. C is a 0 of f of x. Okay. C is a solution to f of x equals 0. Also okay. C is an x-intercept of f of x. Okay, that also makes sense. And then last is x minus c is a factor of f of x. Now, we know what factors are, but we're going to talk a little bit more about how this is possible in the next section, sort of see how important this is in 2 sections in 3.4 and 3.5. So we're going to put this one on the back burner for right now, but essentially, in terms of nomenclature, 0, solution, and x-intercept all mean the exact same thing. So another interesting thing that we want to keep some foresight out for is a degree n polynomial has, at most, n real zeros. Okay, we're going to think about that. But again, it'll be a little bit more important in 3.4 and 5. All right, find the zeros of 5, x minus 4, x minus 3, x plus 1. Well, to find the zeros, we got to set this thing equal to 0. So let's take each factor and set them all equal to 0, right? Exactly like how we solved equations in the past. If we have 4 things being multiplied to 0, well, at least one of them has to be 0. There's no way that all 4 of these could be non-zero and allow them to multiply to 0. Okay, well, 5 doesn't equal 0. X minus 4 equals 0 at x equals 4. Just add 4 to both sides, then add 3 to both sides, then subtract 1 on both sides. So we have 3 zeros. -1, 3, and 4. Okay, let's do it again. This one we're going to have to do a little bit of work because this isn't perfectly factored for us. So we want to find its zeros. Let's start by taking out an x, and then the inside of that parentheses can factor to x plus 2 times x plus 1. Okay, well, now if we want to find the zeros, set it equal to 0, and just like the last example, set each specific thing equal to 0. Well, x equals 0 is just x equals 0. Then we get -2 and -1 when we subtract 2 and subtract 1 respectively. So we get 3 zeros, -2, -1, and 0. Okay. Well, here's something interesting. We said before a degree 3 polynomial would have at most 3 real zeros, right? A degree n polynomial has at most n real zeros. So this degree polynomial has 3 zeros. Okay, let's do it again. X to the 4th minus 2x cubed minus 3x squared. Let's find the zeros. We got to start by taking out an x squared, then we can factor, then we can set it equal to 0. Let's set each factor equal to 0. X squared equals 0. That's just x equals 0. Then x equals 3. Then x equals -1. So our zeros are -1, 0, and 3, but this degree 4 polynomial has only 3 zeros. Well, that's kind of weird. Well, I mean, that fits the statement we made earlier that a degree n polynomial has at most n real zeros, but you would think that it would have 4. I wonder why. Okay, x cubed minus 2x squared plus x minus 2. We can factor by grouping. All right, we get x minus 2 times x squared plus 1, and we'll set that equal to 0. Set each of those two things equal to 0. For the first one, we get x equals 2, but for the second one, well, x squared plus 1 equals 0 is never true, right? You could subtract 1 on both sides, and then you get x squared equals -1. Then you take the square root of both sides, you get square root of -1, which we know isn't real. Well, that's one way you can think about it. You can also think about it that x squared equals -1. Well, take any number and square it, it's positive, so that can't be true. But also, take a positive number, square it, it's positive. Plus 1, still positive, not 0. Take a negative number and square it. Well, negative squared is positive. Positive plus 1 is still positive. Okay. Well, 0 squared is 0, but 0 plus 1 is also not equal to 0. So this one never equal to 0. That means x equals 2 is our only 0, and that's okay. However, a degree 3 polynomial has only 1 0. Weird. X to the 4th minus 16. Alrighty, we can factor this using difference of squares twice and set it equal to 0. Let's set each factor equal to 0. Well, first one we just saw wouldn't work. If x squared plus 1 never equals 0, x squared plus 4 definitely is never going to equal 0 either. Subtract 2, add 2, so we get 2 zeros. But again, this was a degree 4 polynomial, and it only has 2 zeros. That's pretty weird. Okay, well, that brings us to multiplicity, which is going to help us start to explain why we had some mismatches in our degrees and our zeros. Well, let's do the same question, but let's do x minus 1 cubed. Well, x minus 1 cubed is x minus 1 times x minus 1 times x minus 1 equals 0. So what we're going to do is set each factor equal to 0, but we get 1, and we get 1, and we get 1. So x equals 1 is the only 0, and this degree 3 polynomial has only 1 0, but that 1 0 happened 3 times. Maybe there's something about that. Well, it happens to be called multiplicity. So the multiplicity of a 0 is simply the number of times a 0 appears in your function. So in the very last example, normally if we're just solving the equation x minus 1 cubed equals 0, well, you would just take the cube root of both sides, add 1, and you're done. But now what we're going to start to say is that x minus 1 cubed equals 0 says that x equals 1 has a multiplicity of 3. So you can say has multiplicity 3 with multiplicity 3. I believe I use with everywhere that we talk about multiplicity, but has with, same thing. So it's not just x equals 1, it's x equals 1 with multiplicity 3 in the context of finding zeros. So x plus 2 to the 5th equals 0. Before we would just say that x equals -2, but what we can now say is that x equals -2 with multiplicity 5. Multiplicity being just the exponent. All right, well, the interesting thing about multiplicity is that graphically, it helps us determine whether or not your function crosses the x-axis or touches the x-axis at that 0. So let's say you have some function and it works its way down to a 0. Well, the multiplicity of a 0 determines whether or not that function just touches it, it comes back up, or crosses through that 0. If a 0 has odd multiplicity, then the graph of your function crosses the x-axis at that 0. But if a 0 has even multiplicity, then the graph of f of x just touches and does not cross the x-axis at that 0. Okay, and then just one thing to note is that when I've taught this in the past, I've been told bounces is a good way of thinking about it. So yes, it touches and doesn't cross, but you can also think about it as it hits the x-axis and then bounces back up or bounces back down. That's another good way of thinking about it. We'll come back to this in a little bit. So let's just practice finding zeros and their multiplicities. Well, redoing some of the examples we just had, well, here, this was the answer that we got for this function, but what's the multiplicity of each zero? Well, x equals -1 appeared only one time, x equals 3 only appeared one time, and x equals 4 only appeared one time. So all three zeros multiplicity is 1. Here we go, same thing. This is what we got before. -2 appeared only once, -1 appeared only once, and 0 appeared only once. Okay, one more time. Here we have -1, -1 appeared only once, but for the first time, notice that where we got x equals 0 from happened twice. So x equals 0 would have multiplicity 2. If this was x cubed, it would be x equals 0 multiplicity 3, x to the 200, x equals 0 multiplicity 200, and so on. X equals 3, well, this one, there's an imaginary 1 exponent up here, so multiplicity 1. So usually exponent's really helpful for us to figure that out. So this time, there's only 3 zeros. That part hasn't changed, right? The problem we had before was that we had 3 zeros, degree 4, but the multiplicities all add to 4. That helps us explain where the missing 0 went. Well, it was really just hidden behind a multiplicity. All right, well, here, this function, degree 3, we got only 1 0, and that 1 0 still only has multiplicity 1. So we're still degree 3, and we still only have 1 0. Maybe there's another explanation to that. That'll come in a couple sections. X to the 4th minus 16, well, x equals -2 and 2. X equals -2 appeared only once. X equals +2 appeared only once. But then same thing, this is degree 4, and we still only have 2 zeros. We're going to have to come back to that. Okay, let's do some brand new examples. X minus 1, x plus 2, x minus 3. Just go through and set each factor equal to 0. Well, first one, we get x equals +1 when you set this equal to 0. And this 0 appears only one time. The next one we would get is x equals -2 with multiplicity 1. And then we get x equals +3 with multiplicity 1. Okay, 2x plus 1 to the 4th times x minus 36 squared. All right, I'm going to trust you guys to set each factor equal to 0. So set this equal to 0 and solve it. You would subtract 1 on both sides and divide both sides by 2, which would give us -1/2. And this multiplicity is 4. Okay, for the next one, a little bit easier. We're going to add 36 to both sides. So we get x equals +36, multiplicity 2. Okay, let's do this one. X plus 6 to the 7th times 2x minus 3 times x minus 4 cubed. All right, first one, we get x equals -6, multiplicity 7. 2x minus 3, set this equal to 0. Add 3 to both sides, divide both sides by 2. We get 3/2, multiplicity, whatever this exponent is, 1. X minus 4 would give us x equals +4, multiplicity 3. All right, let's do a horrible example. X to the 32,123, 4x minus 100 to the 200, 10x plus 1,000 to the 633. Well, first factor, x to the 32,123, x equals 0 with multiplicity, whatever that exponent is. 4x minus 100 here, add 100 to both sides, divide by 4, you get 25, multiplicity 200. And last but not least, 10x plus 1,000, subtract 1,000 on both sides, divide both sides by 10, we get -100, multiplicity 633. I do not recommend graphing this function, but there we go. Okay, well, let's take this jumbled mess and find its zeros and multiplicities. So in order, we would get -1, 6, 2, -1, -1, 4. Okay, 2x plus 4, subtract 4 on both sides, divide by 2, we get -2. Add 4 to both sides, divide by 2, we get +2. So in total, x equals -1 appeared 3 times, x equals 6 appeared 1 time, x equals 2 appeared twice, x equals 4 appeared once, and last but not least, x equals -2 appeared once. Okay, one more weird example, x squared minus 9 to the 4th. Okay, x squared minus 9 is x plus 3, x minus 3. Since x plus 3 times x minus 3, they're multiplied together, we can distribute 4. So we get x equals -3, multiplicity 4, and x equals +3, multiplicity 4. So multiplicity, really just taking into account degrees. Well, before we actually use zeros and multiplicities, I just want to talk about one very, very quick theorem, and then we'll come back to that for one example in graphing. So that's intermediate value theorem. Now, intermediate value theorem is this very wordy definition right here, but let me use temperature to explain what's happening. So think about it this way. Let's say you wake up at 8 a.m. and it is 40 degrees outside. Then at noon, you check the temperature and it is 60 degrees outside. So in 4 hours, the temperature went from 40 degrees to 60 degrees. And then I ask you, was it 50 degrees at any point between 8 a.m. and 12 p.m.? Well, yeah, it might not have been for long, but temperature doesn't work in such a way that it's like, it's 40 degrees now, and all of a sudden it's 60 degrees 5 minutes later. I mean, it can do that, right? It can heat up very quickly, or it can cool down very quickly, maybe not 5 minutes quickly, but it can do that. But the point is that it doesn't just immediately jump from 40 to 60. What temperature has to do is go from 40 to 41 to 42 to 43, and even smaller than that, right? 43.1, 43.2, 43.3, 43.31, 43.32, and so on. It has to hit all of the temperatures up to 60 degrees. Now, it might not be for a very long time that it hits that temperature, right? It could be 43 degrees for maybe, 15 seconds. But the point is, it does hit every temperature. So my question to you asking, was it 50 degrees at any point? Yes. If it was 40 before and it's 60 now, even if it was for an instant, it had to be 50 degrees at least once. However, what if I asked, was it 20 degrees at any point? Well, that's not guaranteed. If it started at 40 and ended at 60, it is totally possible the temperature dipped and then all of a sudden shot back up. But that's not a guarantee. That's a very specific scenario where it does that. So we can't say confidently that it did happen because, that's very unlikely. But we also can't say that it didn't happen because even though it's unlikely, it's still possible. So with that said, intermediate value theorem just says, depending on what your endpoints are, every value in between those values of the endpoints is guaranteed to have happened. So how we contextualize this to what we've been talking about is that essentially, let's say you have some function on some interval from A to B. If one of your endpoints values is positive when you plug it in, and one of the endpoints when you plug it in is negative, well, if one is positive, one is negative, at some point you had to cross 0. And that's going to be the important part to this section. So all we need to do is show that one value is positive, one value is negative. There's no way we can go from negative to positive without crossing 0 at some point. And that's what we're interested in. So what we're going to do is, for these examples, plug in the endpoints and see what we get. If the signs differ, then we do guarantee that there was a 0. If they don't, we can't necessarily guarantee that. Okay, so f of x equals negative 2x cubed plus 4x plus 5 from 1 to 2. Well, let's just plug in the endpoints. So when we plug in 1 cubed is 1, negative 2 times 1 is negative 2, 4 times 1 is 4, negative 2 plus 4 plus 5 is 7. Okay, likewise, let's do the same thing for the other endpoint. All right, for the other endpoint, 2 cubed is 8, negative 2 times 8 is negative 16, 4 times 2 is 8. Well, negative 16 plus 8 is negative 8, negative 8 plus 5 is negative 3. So we started at 7 and we ended at negative 3. Did we cross 0 at some point? Yes, we had to. There's no way we can go from 7 magically down to negative 3 without crossing 0. So now we don't necessarily care where it happened. All intermediate value theorem says is that we guarantee it to happen. So that's kind of interesting. It's kind of a funny glimpse into mathematics that in some cases we don't even necessarily care what the value is. Like, we're saying that there is a spot that it crosses the x-axis, but we don't really care what it is. You can solve it, but we don't care. We just care that it does exist at some point. And that does actually kind of happen. The higher up in math you go, that at some point we stop caring what the answer is and just say there is an answer. That's good enough. Okay, let's do the same thing for x cubed minus 5x squared plus 6x minus 6 from 1 to 2. All right, so let's plug in each of our endpoints. 1 cubed is 1, 1 squared is 1, 5 times 1 is 5, 6 times 1 is 6, 1 minus 5 is negative 4, negative 4 plus 6 is 2, but minus 6 again, we're back to negative 4. Plug in 2. All right, 2 cubed is 8, 2 squared is 4, 5 times 4 is 20, 6 times 2 is 12, 8 minus 20 is negative 12, negative 12 plus 12 is 0, 0 minus 6 is negative 6. So we started negative and we ended negative. Is there necessarily a 0 between 1 and 2? Well, we can't guarantee that. It is entirely possible that if we started at negative 4, ended at negative 6, that we go up very quickly and down very quickly. So we can't guarantee that's what happened. It might have happened, but we can't guarantee it. So that's the important part. Okay, let's do the same thing, but with 3 and 4 instead. Plugging in 3, 3 cubed is 27, 3 squared is 9, 5 times 9 is 45, 6 times 3 is 18, 27 minus 45, negative 18 plus 18, 0, 0 minus 6, negative 6. Okay, same thing for the other endpoint. 4 cubed is 64, 4 squared is 16, 5 times 16 is 80, 6 times 4 is 24. 64 minus 80 is negative 16, negative 16 plus 24 is 8, 8 minus 6 is 2. Is there a 0 between negative 6 and 2? There sure is. Has to be. So that's intermediate value theorem. Now, to end off polynomial functions, this very large section, right? It's very interesting because even at this very low level of mathematics, we're able to sketch graphs. They might not be very good sketches, and there's one really key part that we're missing that I'll point out when we do an example. But yeah, with everything that we talked about in this section and everything we've talked about in the past, we can actually graph. We can at least sketch graphs. So the steps to do that are as follows. Determine the end behavior using the leading term. That's what we did for the first 2 examples of this section. Next up, find the y-intercept by setting x to 0. Find the zeros and their multiplicities by setting the whole function equal to 0. And here's the weird new step. Once we find the zeros, we're going to take those zeros and partition the domain. Very fancy phraseology. All it's saying is put your zeros on a number line. When you put those zeros on a number line, what you create is separated intervals. What we're going to do is check in each of those intervals to determine whether or not our function is above the x-axis or below the x-axis. After we know that, we can sketch the graph. And in general, I kind of mentioned it in the last section too, but if we are dealing with degree n, you should use n plus 1 points. So if you were trying to graph something that is x cubed, you should have 4 points officially graphed. So I'm going to do one example of this. It's a very long section. I don't want to stretch it out any further. Let's do one example of this, and then we'll call it a day. So I'll see you on the whiteboard. Okay, I know how much we love the whiteboard, so here's our function, x times x plus 2 cubed times x minus 1 squared. Okay, so step 1 says find the end behavior. So we need the leading term for that. Okay, leading term says how many x's do we have? We have 1, 3, right, because of the 3, and here we have 2. So in total we have 1 plus 3 is 4, 4 plus 2 is 6, and now we care about the leading coefficient. The leading coefficient of this x is positive, this x is positive, this x is positive. Multiply a bunch of positive numbers together, you get positive. So when we have positive and even, this corresponds to something that looks like that on our original little graphic of all 4 cases. So there we go. Well, now we can find the y-intercept by setting x equal to 0. So f of 0 is 0, 0 plus 2 cubed, 0 minus 1 squared, but this 0 out in front, the whole thing is just 0. So our y-intercept is 0, 0. Next up, zeros and their multiplicity. So we're going to do whole function equal to 0. Well, we get x equals 0, x plus 2 cubed equals 0, x minus 1 squared equals 0. So we get x equals 0, multiplicity 1, x equals negative 2, multiplicity 3, and x equals 1, multiplicity 2. Okay, so here's the weird new step. What we're going to do is take these zeros and put them on a number line. So we have negative 2, 0, and 1. And what we're going to do is check to see whether or not our function is above or below the x-axis on each of these 1, 2, 3, 4 intervals. Now, what we could do is what we're supposed to do is take a value in each interval. So say negative 3, negative 1, 1/2, and 2, plug those into the original function and see if we're positive or negative. That's actually a little bit more work than we really need to do because we found the end behavior and we found the multiplicities. Well, our original end behavior told us that both sides are going to go up, both ends are going to go up. So we know right away, left side goes to positive infinity, right side goes to positive infinity. Well, in that case, it has to go up. It has to be above the x-axis. Okay, so now what we're going to do is determine what happens at each of the zeros. Don't forget, multiplicities told us whether or not our function crosses the x-axis at that 0 or touches the x-axis at that 0. So odd multiplicities cross, but even touches, or some people also like to say bounces. So we start above the x-axis at negative 2, and then at negative 2, we have odd multiplicity. So odd multiplicity means that we will cross into negative territory. So we went from plus to minus, right? We crossed at negative 2. Okay, so at some point, we come back up and we get up to 0. And at 0, we again have odd multiplicity. So we're negative and we cross at 0 into plus. At some point, we come back down and then we come back down to 1. But 1 has even multiplicity. Even multiplicity means it'll just touch, but not cross, and it goes back up. So it kind of bounces. That's where this like bounces idea comes from. Okay, so we know when our function is above and below the x-axis, but now let's graph this. Let's put our zeros where we just found them. We said the function is above the x-axis. At negative 2, it crosses into negative. At 0, it crosses back into positive. And at and at 1, it bounces back up to positive. Also, one thing I'll note is that even though we knew this end behavior is plus, we could still have checked it with this bounce. So you didn't necessarily need to check this last spot because we already knew it via the end behavior, but you know what? Still good practice to see why. So this nice rough sketch of our graph. So the big thing here is that, one, we could be more precise by actually plugging in values, right? Say we plugged in negative 1. What's the value here? Say we plugged in 1/2. What's the value here? The other problem, too, is notice this is a minimum and this is a maximum. The question is, where exactly does it start to come back down? Where exactly does it start to go back up? Right? I said at some point we start to go back up. And the question is, well, what's that some point? Well, here's the thing. We can't answer that right now. We technically need calculus 1 to be able to answer that question. So can't do it right now. That's not a big deal. But for very little algebra we have under our belt, it is cool that we're able to graph functions as clearly as this. So that's the end of 3.2. In 3.3, we're going to completely change gears. There's a little surprise. In 3.3, you'll see it right away, but then we'll come back to the normal format in 3.4. So I will see you in 3.3. Bye. Hi everyone, welcome to section 3.3 where we do polynomial long division. To this point, we've talked about zeros, we've talked about factors plenty of times. So what we're going to do in this section is if we have the opportunity to divide by a factor that would help us divide and then factor some more, we would like to take that opportunity, right? So what we're going to do is take some really big polynomials, try and divide them by certain factors, and if we divide them by factors, they might be factorable. So for example, we could potentially go from something that's like x to the 4th that we can't factor, but if we divide by a certain factor and it works, then maybe we have something with x cubed, and then we can then factor from there. So it is a popular tool, it's a very famous tool. There's 2 ways we're going to do it, so yeah, let's get right into it. So how we're going to do this is a lot like how we did this for numbers. So think about when you were in elementary school and you did something like 830 divided by 5. Well, you would set this up as 830 over 5,
and then you would say 5 into 8 one time. You would do 1 times 5, which is 5. 8 minus 5 is 3. Then you would bring down the next number. 5 into 33 6 times. 6 times 5 is 30. Bring down the 3. And then we get 5 into 30 6 times, and that's 0. So we say this is 166, but another way we could say this is that 830 is 5 times 166. So that kind of ideology is going to carry us for these first few examples. So let's do just that with polynomials. Okay, so the first example we're going to do is x cubed plus 2x squared minus 5x minus 6 all over x plus 1. Okay, so how we set this up is a lot like how we set this up for numbers. We would say x cubed plus 2x squared minus 5x minus 6 divided by x plus 1. Okay, but how we do this is a little different. When we do it for numbers, we're used to saying 5 into 8 one time, but it's not that easy because we have an addition here or even a subtraction. So what we're going to do is this. We're going to ask how many times does this first term go into each consecutive, or successive, I should say, term. And what I mean by that is how many times does x go into x cubed? What I'm really asking is what is x cubed divided by x? X into x cubed is saying x cubed divided by x, which is x squared. So what we're going to do with x squared is line it up with the other x squared terms, right? We want to make sure we're lined up, just like we're lined up for tens, hundreds, thousands when it comes to dividing numbers. And what we're now going to do is the same step as we did for numbers. When we said 5 into 8 one time, we would then say 1 times 5 is 5. And we're going to do the same thing here. X squared times x plus 1, okay? X squared times x cubed. X squared times 1, x squared, okay? And now we subtract. So it's a little different because we're not subtracting just single numbers. This time we're subtracting expressions, and that's a-okay. If we did this correctly, these two things should be the same. This says x cubed minus x cubed. Oh, well, that goes away. That's pretty nice. But then this says 2x squared minus positive x squared. Well, 2x squared minus positive x squared is just x squared, right? 2 apples, you subtract one of those apples, you now have 2 apples, okay? And then, just like we did for numbers, bring down the next term, okay? And now we rinse and repeat. So now we ask, how many times does x go into x squared? Or in other words, what is x squared divided by x? And that's just x. So now we put x up here, and we again do x times both of these. X times x is x squared, x times 1 is x. But now we gotta be a little more careful. Again, if we did this correctly, x squared minus x squared, that's just 0. But here we have negative 5x minus positive 1. You're $5 in debt and you spend $1 more. You now have negative $6 of debt. Okay, bring down the next term. And now one more time, x into negative 6x. Negative 6x divided by x is negative 6. All right, and one more time. Negative 6 times x, negative 6x, negative 6 times 1, negative 6. And in this specific case, this is pretty nice. Negative 6x minus itself goes away. Negative 6 minus itself goes away. We're left with 0. So now, our original question asking, what is x cubed plus 2x squared minus 5x minus 6 divided by x plus 1? Well, this equals x squared plus x minus 6. Okay? X cubed plus 2x squared minus 5x minus 6 over x plus 1. Well, what we can do like we did with numbers, where we said 830 divided by 5 is 166, we can multiply x plus 1 on both sides. And even better yet, this factors to x plus 3, x minus 2. So what polynomial division did is that if we find a factor that is indeed a factor of our original polynomial, just like 5 is a factor of 830, if we find one of these that works, well, it lowers our degree of our polynomial to a point that we could potentially factor it. So this, before, you would never have been able to factor using regular means, but just like that, with one run of polynomial division, now it is factorable. And that's the idea. Okay, let's keep going. Let's do some more examples. Okay, so next up, we're going to do x to the 4th minus 26x squared plus 25 divided by x minus 5. So what we're going to do here, same thing, let's set it up. X to the 4th minus 26x squared plus 25 over x minus 5. And now what we're going to do is say x into x to the 4th. X to the 4th over x is x cubed. And, well, that's kind of weird because we don't have a spot for x cubed. Well, whatever, let's throw it up here for right now. Now we do x cubed times all this. So x cubed times x is x to the 4th. X cubed times negative 5 is negative 5x cubed. And just like that, all of our terms are out of whack. Notice this is x squared, this is x cubed. We can't subtract like that. So what we're instead going to do is put placeholders in for all of these powers of x that we're missing. So this is a bad setup. And again, if you are missing powers of x, what you instead need to do is this. Okay, x to the 4th, next term is negative 26x squared, but since we're missing an x cubed term, let's put 0x cubed there. Minus 26x squared, we're missing an x term, so let's put 0x there, plus 25. Okay, so same thing, x into x to the fourth, x cubed times x to the fourth, x cubed times negative 5x cubed, and now we have less of an issue because we have x cubed terms that line up. However, be very careful here, because what we're doing is x to the fourth minus x to the fourth. That's the whole point, it goes away. But here, 0x cubed minus negative 5x cubed. Well, this is plus. So this is positive 5x cubed. So please be very careful when you are subtracting. Don't forget parentheses. If you forget parentheses, you're going to just subtract here, and this will be negative, and then you're going to be all sorts of thrown off. Okay, so please be very careful of that. We continue, minus 26x squared, x into 5x cubed is 5x squared, 5x squared times x, 5x cubed, 5x squared times negative 5, negative 25x squared. Okay, those are the same. But over here, careful, negative 26x squared minus negative 25x squared. Well, negative 26x squared minus negative 25x squared is plus. You're $26 in debt, and you're given $25, you are now just a single dollar in debt. Let me bring down the next term. Okay, x into negative x squared is negative x, right? Don't forget each of these steps. 5x cubed divided by x, that's how we get the 5x squared. Right here, negative x squared divided by x is how we get negative x. All right, negative x times x, negative x squared. Negative x times negative 5, ooh, positive 5x. All right, those are the same. 0 minus positive 5 this time. Okay, you have nothing in your bank account and you spend $5. Now, negative 5x again. One more time. X into negative 5x. Negative 5x divided by x is negative 5. Negative 5 times x, negative 5x. Negative 5 times negative 5 is positive 25, and both of these are the same. And we found a factor. So this original polynomial is equal to x minus 5 times all of that. And if you wanted to, this can be factored by grouping, and you can continue to factor this polynomial. So that's a really nice, powerful tool. This could have actually been factored in the beginning if you have a little bit of foresight, but let's assume we don't know how to do that and instead use division. Okay, let's move to something a little different now. So both of these examples worked, but we know in division that that's not always going to be the case. So what happens when something doesn't work? Okay, so in terms of numbers, what if we did 830 divided by 7? Okay, 830 divided by 7 would be 830, 7. 7 goes into 8 one time. 1 times 7 is 7. 8 minus 7 is 1. Bring down 3. 7 into 13 one time. 1 times 7 is 7. Bring down 6, and we get 0. 7 into 60 8 times. 8 times 7 is 56. 4. Well, 7 doesn't go into 4, so what you are used to doing in elementary school is to say 118 remainder 4. Well, here's what 118 remainder 4 actually means. What this means is if you were to divide 830 divided by 7, you would have 118 sevens plus 4 of the way to 7. You go around 118 times, and then you get 4 more steps to your next 7. Well, this is how you would write this. This, plug this into your calculator, is the same thing as this. So what we're going to do in the next couple examples is look at the possibility when what we're dividing by isn't a perfect factor. In this case, it's a little weird, but we're going to write our answer something like this. Quotient plus remainder divided by divisor. I'll put that up here. Quotient plus remainder divided by divisor. Okay, so let's do another example, but this time, let's do an example that doesn't work. Okay, let's do x cubed minus 3x squared minus 6x plus 8 all over x minus 3. Okay, so we're going to set this up as x minus 3, x cubed minus 3x squared minus 6x plus 8. And now we rinse and repeat. X into x cubed, x squared. X squared times x squared times x is x cubed, x squared times negative 3, negative 3x squared. Okay? And by chance, these both happen to cancel out. That doesn't mean anything's wrong. It just means that's what happened. So we get 0, and we bring down minus 6x. And let's also bring down 8 for when we go to subtract later on. Okay, x into negative 6x. Negative 6x over x is negative 6. Just negative 6, right? Not negative 6x. So that's okay. It just means that we skip over an x term. There's nothing wrong with that. Now, negative 6 times x. Negative 6 times x is negative 6x. Negative 6 times negative 3, positive 18. Okay, these two are the same. Here we get 8 minus 18. That's negative 10. And of course, x minus 3 can't go into negative 10. So here's what our answer actually says. Our answer then says this division is the quotient plus the remainder divided by the divisor. Or if you want to be more particular, minus 10 over x minus 3. This is the same as that 118 plus 4 over 7. Quotient plus remainder divided by the divisor, 830 over 7. So just because something doesn't work out doesn't mean anything's wrong. It just means it means something else. In the case of polynomials, this has use, but in terms of factoring like we were trying to do before, it doesn't quite work out that way. However, this is still of interest to us. Okay, so let's then do another example that maybe also doesn't work, but that's okay. Okay, now let's do something funky like x to the 4th minus 16 over x minus 1. Okay, actually we're going to do x plus 1 instead because why not? Okay, so when we go to set this up, we have x to the 4th, but we're missing an x cubed term, we're missing an x squared term, we're missing an x term, but we finally have our constant term. Okay, so again, if you're missing terms like here, you're missing x cubed, you're missing x squared, you're missing x, make sure you put placeholders in. Okay, so here's what we're going to do next. X into x to the 4th is x cubed times x to the 4th, x cubed times 1, positive x cubed. X to the 4th minus itself, 0 x cubed minus 1x cubed, negative 1 x cubed, and bring down the next term. Okay, x into negative 1 x cubed is negative 1 x squared. And then, again, if you haven't seen it by now, it's just rinse and repeat. Negative x squared times x, negative x cubed, negative x squared times 1, negative x squared. Okay, so negative 1x cubed minus negative 1x cubed goes away. 0 x squared minus negative x squared, negative is a plus, just x squared, and we keep going. Alrighty, x into x squared, just x. X into x plus 1, x squared, x times x is x squared, x times 1 is just x. X squared minus x squared goes away. 0 minus positive 1, negative x, and bring down our last term. Okay, x into negative x divided by x is negative 1. Negative 1 times x, negative x. Negative 1 times negative 1 is negative 1. Negative x minus itself goes away. Negative 16 minus negative 1, you're $16 in debt and somebody gives you $1. You are now only $15 in debt. Okay, so that means our original question is x cubed minus x squared plus x minus 1 quotient plus the remainder divided by the divisor. And again, you could be a little bit more specific by saying just minus 15 over x plus 1, but I think at this point, if you're watching a video about polynomial long division, I think that part is fairly okay. All right, so this is called long division, and in a lot of ways, this can be very tedious, and it's very easy to make mistakes. So there does exist another type of division when it comes to polynomials that's actually pretty nice. So we're going to do that next. However, I just want to talk about one small thing. Let's say you're trying to divide by something that is more than just like x plus 1 or x minus 5. Let's say you have some polynomial, and you're trying to divide it by x squared plus 2x plus 1. So when you go to set this up, x squared plus 2x plus 1 divided by whatever your polynomial is, well, before we had just those two terms, and you said x into whatever that first thing was, or whatever that next thing was. In the event that you have x squared, nothing changes. Now it's 3 terms, now it's going to be a little more work. However, you're still just doing this first term into whatever's next. So let's say we're starting with an x to the 5th here. Well, then you would have, so whatever, plus, I don't know, 2x to the 4th minus 6x cubed and so on. Okay, x squared into x to the 5th. X to the 5th over x squared is x cubed. Okay, and now the only added difference is when you are multiplying x cubed is that you have to multiply it by all 3. X cubed times x squared, x to the 5th, x cubed times 2x, 2x to the 4th, that is completely by chance, x cubed plus 1 plus x cubed, and now x to the 5th minus itself, 2x to the 4th minus itself, negative 6x cubed minus 1x cubed, negative 7x cubed, and whatever you bring the next thing down, and you would continuously use x squared. So all I'm trying to show is that in the event you're dividing by something that is higher than just x, that's fine. This x squared or x cubed or whatever it is will just be your new leading term to divide by. Okay, also, just like we put placeholders in for the numerators, right? X to the 4th minus 16, we had to do x to the 4th plus 0x cubed plus 0x squared plus 0x minus 16. In the event you're dividing by something like x squared minus 5, well, you have the x squared term, but you're missing an x term in your divisor, so you still put a placeholder just there. So the examples work very similarly when they're just x compared to x squared, but the same rules of take this leading term, put it into each and everything, putting placeholders, all those rules are still the same. Okay, so since we have now talked about that, let's move to this other type of division. It is, I will say, not a very mathy way of doing long division, and if I'm being honest, I didn't really get it the first time that I learned it a long, long time ago, but as I've been teaching, it makes a lot more sense. However, not very mathematical, not very algebraic, but if you're looking for a very quick way to do long division, it's really, really nice. So this is called synthetic division, and synthetic division is only for when you're doing division with linear factors. So for example, we've done dividing by x plus 1, x minus 5, x minus 3. You can do synthetic division on those factors, but these last two examples that we just did with an x squared, synthetic division can't work. Synthetic division is only for dividing by linear factors. Okay, so let's go back to this example, x cubed plus 2x squared minus 5x minus 6 over x plus 1. I don't remember what our answer is, but it's okay. We'll match it up with whatever we get. Synthetic division works like this. We're going to set up this little bar here. I don't even know what to call it. So what we're going to do is have a row of numbers up here, and we're going to continuously do calculations below them. Okay, let's start with this. The numbers that go on the inside of our bar will be the coefficients to each of these x's. So x cubed, coefficient is 1. 2x squared, coefficient is 2. Negative 5x, coefficient is negative 5. Negative 6, it is just itself. Okay, that's pretty straightforward, I think. Okay, and then what we're going to put out here is the 0 to our linear factor. So we're not going to put x plus 1 here. We're going to put negative 1 out here. Okay, that is really, really important here. This is not the number itself. It's the 0 associated with this number. At some point, you probably talked about zeros already in your classes when you talked about polynomials, and that's what we're talking about when it comes to zeros. It is not x plus 1. It is the 0 associated with x plus 1, in this case, negative 1. Okay, so how synthetic division works is like this. First step, bring down the first number. Okay, not super scary. What we're going to do is continuously work up, down, up, down, up, down. Okay, to get to here, we are going to take our 0 and multiply it by this number. Negative 1 times 1 is negative 1. Okay, so it's multiplication to get back up. But then when we go down, so now 2 and negative 1, when we go down, we add. So diagonals are multiplication, but the columns are addition. 2 plus negative 1 is positive 1. And now negative 1 times 1 is negative 1. Again, negative 1 times 1, negative 1. Okay, negative 5 plus negative 1, negative 5 plus negative 1. Okay, $5 in debt, and you spend another $1, you are now $6 in debt. Negative 1 times negative 6 is positive 6. Negative 6 plus 6 is 0. So multiplication, 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 addition, addition, addition. So here's what we get. We now have a row of numbers and we have no idea what they mean. So what this says is that if this was x cubed, and we divided all of these terms by a single x cubed divided by x would become x squared. X squared divided by x would become x. Negative 5x divided by x would be a constant. And that would leave this last number to be our remainder. And we remember from when we did this example earlier, this had a remainder of 0. So what we get is that our answer is x squared, 1x squared, plus 1x minus 6, and you would put the remainder 0, but we don't need to, right? 0 divided by anything, just 0. So, and now we are back to where we were before. You can multiply x plus 1 on both sides, you can factor as you go, all the steps still the same from there. However, this version, once you get very comfortable doing it, can be very, very fast. So that's really nice because you can do these problems fast. Like, what if you wanted to do division by a bunch of things? What if you don't know what divisor is going to work and you have to check a bunch of divisors? Well, that would be very helpful to us as well. Okay, let's do another one. Okay, let's do x to the 4th minus 26x squared plus 25 divided by x minus 5 again. Okay, so to set this up, this will be the coefficients to all of our x's. 1x to the 4th, we don't have an x cubed, 0x cubed, negative 26x squared plus 0x minus 25. Again, x to the 4th, x cubed, x squared, x, and our constant. Now, the number that's going to come out here isn't negative 5, it is the 0 associated with negative 5. So the number that goes out there is positive 5. Okay, so again, down is addition, diagonal is multiplication. First number comes down, 5 times 1 is 5, 0 plus 5 is 5, right? Multiply on diagonals, but add in the columns. Okay, 5 times 5 is 25. $26 in debt, somebody gives you 25, you are now just a single dollar in debt. 5 times negative 1, negative 5. 0 plus negative 5 is negative 5. 5 times negative 5, oh, did I make a mistake somewhere? Okay, we got to backtrack a little bit. This coefficient was positive 25 to begin with. Okay, doesn't change a whole lot, but still really important. 5 times negative 5 is negative 25, but now 25 minus 25 is 0. So if this was x to the fourth, this is x cubed, x squared, x, constant, and remainder. So our answer is 1x cubed plus 5x squared minus x minus 5 plus a 0 remainder. So again, even though we're doing synthetic division, the step of putting placeholders is still there. Okay, well, let's see what this looks like when it doesn't work out. We got 2 more examples and then one more quick explanation, and then we'll call it a day. Okay, we had this one before. We said this one didn't work out, so let's do it again. Okay, add going down, multiply on the diagonal. Up here comes the coefficients, 1x cubed, negative 3x squared, negative 6x, and 8, the constant. Now the number that comes out here is the 0 associated with our divisor, which in this case is 3. Bring down the first number. 3 times 1 is 3, negative 3 plus 3 is 0, 3 times 0 is 0, negative 6 plus 0 is negative 6, 3 times negative 6, negative 18, 8 plus negative 18, negative 10. This was x cubed, this has to be x squared, x, constant, and our remainder. Okay, so our answer is x squared plus 0x minus 6 minus 10 over x minus 3. Okay, not so bad. One good thing too is that if you're doing what I mentioned before, that you're checking a whole bunch of factors to see what works, you only need to get up to this point. Notice that in the last 2 where it worked, the remainder was 0. So if you get to the point where this is 0, you found a factor of that polynomial. That's really nice. But in the event you get anything else that's besides 0, then not a factor. And it's a little bit quicker to get to that than doing long division. That part I will admit. Okay, okay, we don't need to do another full example, but I do want to show you one more thing. Let's say we want to do 2x cubed plus 4x squared plus 8x plus 16 divided by 2x plus 1. Okay, I have no idea what the number is or what the answer is. I did this completely out of the blue. Alrighty, so numbers that go in here are the coefficients. 2, 4, 8, 16. And what we're going to put out here is, again, not this 1, it is the number. It's the 0 associated with this divisor. So that 0 that is associated with it is negative 1/2. We're going to change this a little bit. Okay, maybe this fixes it. Okay, this is why we don't do things on the fly. Okay, so we changed it a little bit, but now let's go through all the steps. Bring down the 2. Negative 1/2 times 2 is negative 1. 3 minus 1 is 2. Negative 1/2 times 2 is negative 1. 13 minus 1 is 12. Negative 1/2 times 12 is 6. Oh, negative 6. Oh, and this actually works. I had no idea this was going to happen. Negative 1/2 times 12 is negative 6. 6 minus 6 is 0. Okay, so that means our answer is, this was x cubed, this must be x squared, 2x squared plus 2x plus 12. I legitimately had no idea that was going to work out. So I'm going to change the number so we didn't get some like super ugly fractions. But yeah, that wasn't supposed to happen. But now you see that in the event your divisor is linear, but not necessarily x plus something or x minus something, you have to do something like that. Okay, so with that said, that is polynomial long division. And I know this was kind of long. You see me in the flesh for the first time. This is weird. But yeah, that's that. So next up is 3.4 and 5. We're going to combine that into one section. So I will see you there. Bye.
Hi everyone, welcome back to 3.4 and 3.5. So, a little break there where I was in the flesh for 3.3, but now we're back digitally. At least I can beat, I'm not an AI allegation. So with that said, we're going to get into 3.4. However, 3.4 and 3.5 separately discuss the real and complex zeros of a polynomial function. Personally, I think it helps a little bit better with the flow if we treat it all as one big section. But, just so you know that if you're using this textbook, there are 2 separate sections. I think it's just easier to talk about everything all at once. So we're going to work our way up to the fundamental theorem of algebra. So if you're watching this, you might be in an algebra course, you might be in a pre-calculus course. So it's very interesting because fundamental theorem of algebra is the fundamental theorem of algebra, right? It's going to hold together a lot of the things that you talk about in your class. So with that importance in mind, let's keep it going. So let's start with the rational zeros theorem. Now the rational zeros theorem is just this quirky little thing that's actually pretty nice from what we just did in 3.3 with polynomial long division. But what it says is this. If a polynomial has integer coefficients, which in a lot of cases it will, and p over q is a rational number, that is a 0 of p of x, then p is a factor of the constant term, and q is a factor of the leading coefficient. Now, that's very wordy. Long story short, you take factors of the constant term and divide them by factors of the leading coefficient. What you get is a set of all possible rational zeros. Not a comprehensive list of all zeros, since some zeros can be irrational, like zeros you can get from the quadratic formula, but it is a list of all rational zeros that will appear in your function. So for example, if your function has a rational zero, it will appear in this list, but it just won't be a list of all of them. And you're also going to get plenty of other ones that are not zeros either. So what we're going to do is take each potential zero in our list, use synthetic division to very quickly check to see if it is a zero, and then help us factor from there. So we're not going to do that part. We're going to skip over that, right? We saw that we had to do an entire board presentation just for that, but we can take the steps for granted here. So let's start by finding all the rational zeros of 2x cubed plus 5x squared minus 4x minus 3. Okay, so how we do this is we look at the constant term and we look at the leading coefficient. The constant term is -3, and the factors of -3 would be 1 and 3, and plus and minus 1 and plus and minus 3. So here are the factors of -3, and then the leading coefficient is 2, and likewise its factors are plus and minus 1, plus and minus 2, right? These are not so scary, but think about something like 6, that might be 1, 2, 3, and 6. Okay, so the set of all possible real rational zeros is given by plus or minus 1, plus or minus 3, factors of the constant divided by factors of the leading coefficient. Now, just for the sake of redundancy, we can drop the plus and minuses in the bottom, and this right here, even though not the most mathematically perfect way of writing it, this would generate all of the possible real rational zeros for our function. So if you wanted to write that actual set, it's as follows: positive 1 divided by 1, negative 1 divided by 1, positive 3 divided by 1, negative 3 divided by 1, positive 1 divided by 2, negative 1 divided by 2, positive 3 divided by 2, and negative 3 divided by 2. Had we left the plus and minuses in the bottom, what you would get is just plenty of zeros that repeat. So save yourself a little bit of work and don't put any pluses and minuses in the denominator. Okay, so now we have a set of all possible rational zeros. Not all of them are going to be zeros, obviously, right? This is too many. Here's 8 possible zeros, but we're only degree 3. There's no way that all of them could work. So what you would then do is check each one using synthetic division. However, once you check each one using synthetic division, once you find a zero, you can factor that result based on that zero. So here's what I mean. If we know that x equals 1 is a zero, well, do synthetic division using x equals 1, and you would get x minus 1 times 2x squared plus 7x plus 3. Please go back and check the 3.3 presentation to see how exactly we would get that. But essentially, x equals 1 works, so our function can factor like this. Now, the really nice thing about this, too, is that this is also factorable. Okay, well, think about it this way. I mentioned in 3.3 that polynomial division can help us go from something that can't be factored using regular methods to something that can be factored using after using long division. For example, try factoring this using anything we've talked about in the past, and you can't. But polynomial long division brought us to a point where it is factorable, right? These factors are very nice and pretty, but we needed long division to do that. So it is a tool to factor. Okay, just to summarize 3.3. But now, if we want to find all the rational zeros, well, now just set all of these equal to 0, and we would get x equals 1, x equals -3, and x equals -1/2. Degree 3, 3 zeros, nothing missing. And here's one more interesting part about rational zeros theorem. All 3 of these zeros did appear in that list that we just had. So we got 5 other zeros that were not true, but all the zeros that are here, all these rational zeros, did appear in that list. We just happened to use x equals 1 as our starting point to do long division. But you could have done the exact same thing with x plus 3. You could have done the same thing with 2x plus 1. So rational zeros theorem says we have a way of getting all the possible rational zeros. Well, you might find this is a little inefficient for an example like this one. Your constant term is 8. So the factors of 8 are 1, 2, 4, and 8. And then your leading coefficient is 3, whose factors are 1 and 3. So the set of all possible real rational zeros would be plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8 over 1, 3. Again, take the constant factors, divide them by the leading coefficient factors. And now the set of all these zeros is a lot longer. So this is not fun. So the point here is that the rational zeros theorem only gives us a set of possible zeros, not a very necessarily useful set. So you would have to go through and check all of these. So part of the reason why rational zeros theorem isn't super useful is that you could be spending a lot of time to find a rational zero that might not actually even be a zero, right? This is a set of possible rational zeros. What if your function doesn't have any rational zeros to begin with? So we'll take for granted that we will check each using synthetic division. And again, once we find a zero, factor that result. So let's just say that we knew that 2/3 was a zero. Well, knowing that 2/3 is a zero, then we would get something like this. We could factor this by taking out a 3, and then to find the remaining zeros, well, we would need to do quadratic formula on that. So in total, all of our zeros of our function would be 2/3, and after doing quadratic formula, 1 plus and minus square root of 5. So, it would have taken you a long time just to get to 2/3. But again, the point here is that we went from something that you could not find the zeros for to something that we could find the zeros for, even if not that pretty. So that's just a lead in to the point that we actually want to look at, and that's the fundamental theorem of algebra. Okay, if your polynomial is degree n, it has at most n real zeros. We looked at that in 3.2. In 3.2, we said, we would have a degree 3 polynomial, but we would only have like 2 zeros. So like what happened? Multiplicity describes some of that, but what we're going to do here in 3.4 and 5 is perfectly describe that. Okay, but also don't forget that all real numbers are also complex numbers. Oh, it's been a long time since we've talked about complex numbers, just numbers that may contain I. So what happens if you have a degree 10 polynomial that has only 4 real zeros? Where are the other 6? Well, we saw in the last, in 3.2, that you could have multiplicity describe some of it, but not always all the time perfectly describe it. So that brings us to the fundamental theorem of algebra. Every polynomial function like this of degree n greater than or equal to 1 has at least one complex zero. So don't forget, real numbers are also complex numbers. So just because it has at least one complex zero doesn't necessarily mean it has an imaginary zero, right? Real numbers, 2, 5, -3/2, those are all real numbers. Fundamental theorem of algebra says we have at least one complex zero. But the main result of fundamental theorem of algebra isn't necessarily that part. It is factorization theorem. Factorization theorem says that all polynomials of degree at least 1 can be factored as this. P of x equals a sub n, x minus c1 times x minus c2 all the way to times x minus cn. A sub n is the leading coefficient, and ci are just non-distinct complex zero factors of p of x. Okay, that's really, really interesting. Every polynomial can be factored. Maybe the factors necessarily aren't super pretty, but it can be factored. So going back to this, we say those zeros are non-distinct because, for example, you can have a degree 7 polynomial that looks like this. And we actually described this in 3.2, where we had the possibility that like only 3 zeros for a degree 4 polynomial, but the multiplicities of those 3 add to 4. So that's kind of what's happening here. Point is, those zeros, those factors don't need to be distinct. Okay. Then if every polynomial has at most n real zeros and at least one complex zero, then every polynomial of degree n has exactly n complex zeros. Well, that is, if you include multiplicity, if you include irrational zeros like you could get from quadratic formula, if you include imaginary zeros, every polynomial has exactly n complex zeros. So before, we had a degree 10 polynomial and we said it only had 4 real zeros. Where are the other 6? Well, they're imaginary. Okay, degree 5 polynomial with only 3 real zeros has 2 more complex zeros. A degree 12 polynomial with only 8 real zeros has 4 more complex zeros. And, I'm not going to gush like crazy. Normally when I'm talking about this in person, I get very animated. That's just what the in-person lectures look like. But I get really animated to the point that I'm like, this is really, really important. It holds the study of algebra together. How do you have the fundamental theorem of algebra or how do you not have the fundamental theorem of algebra and be able to do anything that we've done in this course together? So whether or not you're watching my videos because you're in one of my 16-week classes, whether or not you're watching my video because you're in my 3-week classes, whether or not you're watching my video because you're in some other class, everything you've learned in algebra and almost all of mathematics can't be held together without the fundamental theorem of algebra. So that's my little bit of online gushing. So that brings us to 2 more theorems that we need before we actually start to apply these things. Conjugate pairs theorem says this. If you have a polynomial that has x equals a plus b squared of c, that's an irrational zero of the polynomial, then x equals a minus b squared root of c is also a zero. That is, all irrational zeros come in conjugate pairs. A plus b squared root of c is a zero, then a minus b squared root of c is a zero. Well, if x equals square root of 5 is a zero, then x equals negative square root of 5 is a zero. If x equals 11 plus square root of 20 is a zero, then x equals 11 minus square root of 20 is a zero. If x equals negative 8 minus square root of 13, then x equals negative 8 plus square root of 13 is a zero. If x equals 2 plus 2 square root of 2 is a zero with multiplicity 5, then x equals 2 minus 2 square root of 2 is a zero, also with multiplicity 5. And this is a perfect example as to why quadratic formula always gives 2 zeros when your discriminant doesn't equal 0. For example, in that second example we did for rational zeros theorem, the 2 other zeros to the function were 1 plus square root of 5 and 1 minus square root of 5 via quadratic formula. So this is why quadratic formula always gives a pair of zeros, not only when it's irrational, but also when it's rational and real. Okay, well, we also have another conjugate pairs theorem that's very similar. If you have an imaginary zero, a plus bi, then x equals a minus bi is also, this should say complex. That's a mistake. If a plus bi is a complex zero, then a minus bi is also a complex zero. That's my bad. So if x equals positive I is a zero, then x equals negative I is a zero. If x equals 11 plus 20i is a zero, then x equals 11 minus 20i is a zero. If x equals negative 8 minus 13i is a zero, then x equals negative 8 plus 13i is a zero. If x equals 2 plus 2i is a zero with multiplicity 5, then x equals 2 minus 2i is also a zero with multiplicity 5. So when quadratic formula has 2 imaginary answers, it's always why there's two imaginary answers when the discriminant is less than 0. So all of this kind of coming back to 1.3 when we initially learned quadratic formula. Okay, so let's just practice finding some missing zeros, but what we eventually want to do is construct polynomials, which is a lot more interesting. Okay, so let's say our polynomial is degree 5, and its zeros are 6, negative 4 plus 3i, and 2 minus square root of 7. I gave you 3 zeros, but we're degree 5. We are missing 2 zeros. Well, negative 4 plus 3i is a 0, so negative 4 minus 3i is also a 0. 2 minus square root of 7 is a 0, so 2 plus square root of 7 is also a 0. So in total, I gave you 3. We found 2 more, all 5 zeros right there for us. Okay, let's say we have a degree 10 polynomial, and it has zeros negative 10, 0, negative 1 minus 2i, 2 minus 3i, square root of 15, and 1 plus 5, square root of 2. I gave you 1, 2, 3, 4, 5, and 6. Well, degree 10, I give you 6 zeros. We're missing 4 zeros. Because negative 1 minus 2i is a 0, negative 1 plus 2i is a 0. Because 2 minus 3i is a 0, 2 plus 3i is a 0. Because positive square root of 15 is a 0, negative square root of 15 is a 0. Because 1 plus 5 square root of 2 is a 0, 1 minus 5 square root of 2 is also a 0. And then we had 6 zeros to start. We found 4 more, all 10 zeros right there. Okay. Well, let's do, I think, one more example of this. Degree 17. The zeros are 2 multiplicity 3, 4 plus 5i multiplicity 2, 3 minus square root of 10 multiplicity 5, and let's find the remaining zeros. Well, I gave you 3 plus 2 is 5, 5 plus 5 is 10, so including multiplicities, 10 zeros, but we're degree 17, so we're missing 7. 4 plus 5i is a 0 with multiplicity 2, so 4 minus 5i is a 0 with multiplicity also 2. 3 minus square root of 10 is a 0 with multiplicity 5, so then x equals 3 plus square root of 10 is also a 0 with multiplicity 5. So then we had 10 zeros to start, and we found 2 and 5 more, including multiplicities. How lovely, how nice. Okay, well, that brings us to constructing polynomials, and this definitely the wrap up to the course. Unfortunately, it doesn't end on such a beautiful storybook note. We have one more section at the end, but this is really, really the key to algebra, to any algebra class. So find a polynomial of degree 3 that has leading coefficient 1 and these zeros. Well, this comes back to factorization theorem. What we're normally used to doing is starting with a polynomial and then finding the zeros. But what we can now do is construct polynomials given zeros. So the information that we're given is that our polynomial is degree 3, our leading coefficient, and we have 3 zeros. So what we're going to use is factorization theorem. Now, specifically, since we're degree 3, we're only going to go up to x minus c1, x minus c2, x minus c3. And now let's just plug in the information that we have. The leading coefficient is 1, our first 0 is negative 2, our second 0 is 3, and our third 0 is 7. So leading coefficient 1, first 0 is negative 2, second 0 is 3, third 0 is 7, and we can simplify x minus negative 2 to x plus 2. We also don't need this 1 out in front. So this would be the perfectly factored version of a polynomial that fits this criteria. However, we know how to FOIL. We've practiced foiling in the past. And we would get this, right? So chapter P stuff to FOIL, I don't want to go over that here. If you need help, by all means, go back to that or just use an online calculator. I didn't say that out loud. Okay, anyway, so we have the polynomial that fits this criteria. Okay, degree 2, leading coefficient negative 1 and zeros negative 4 and 0. Okay, so factorization theorem says this, but since we're degree 2, we're only going to go up to x minus c2. Well, our leading coefficient is negative 1, our first 0 is negative 4, and our second 0 is 0. All right, well, x minus negative 4, x plus 4, x minus 0 is just x, and if we ever have just plain x's, we like to write them in front. So we get negative x, x plus 4, and you can distribute negative x to get the polynomial that does this. So all it is, plugging and chugging, and then in some cases a lot of foiling, but we don't need to do the foiling here. Okay, degree 4, leading coefficient 1 with zeros 0, 2, 5, and 10. Okay, well, if we're degree 4, we're going up to x minus c4. Our leading coefficient is 1. Our first 0 is 0, second 0 is 2, third 0 is 5, fourth 0 is 10. All right, well, x minus 0 is just x, and this nice factored version, but we can practice our foiling. So these are the best examples to fundamental theorem of algebra, just using the results of the factorization theorem. Okay, leading coefficient 3, degree 4, with zeros negative 5, negative 1, 2, and 6. All right, well, degree 4, go up to c4. Leading coefficient is 3. Our first 0 is negative 5. Second 0 is negative 1. Third 0 is 2. Fourth 0 is 6. We can simplify x minus negative 5 and x minus negative 1. And, now that we've done a couple examples, I just want to throw out there that this is usually a pretty nice form. If you can get to this point, you really learned the course. And as you see the next couple examples, it's only going to get worse when it comes to foiling, right? Foiling out 4 things is no fun by any stretch of the imagination. So, again, the stuff to take away here is really getting up to this point where we have a polynomial that equals this thing. But the point is that even if you don't know how it factors, it does factor one way or another. Okay, let's start to introduce some imaginary zeros, right? We said some weird stuff about irrational zeros, about imaginary zeros, so let's put that into here. Okay, well, polynomial is degree 4. Our leading coefficient is 2. Our first zero is -1, then 3, then I, then -I. Okay, let's simplify our negative negatives, and we get a perfectly factored polynomial. So this is what it is when you expand it, right? Practice your foiling. This would be a 1.4 practice. P3, foiling regular polynomials. But in 1.4, we practice doing that with I. So go back to 1.4 if you need help with that. But point is that this can be factored if we allow our zeros to be i's. And zeros are i's, even though we never wrote stuff like this in the past. It doesn't change the fact that this is, say, a factor of our polynomial. So something to keep in mind. All right, degree 3, leading coefficient 1, 2, 1 plus 3i, 1 minus 3i. Degree 3, leading coefficient is 1. First zero is 2. Second zero is 1 plus 3i. Third zero is 1 minus 3i. So a little uglier now, but here make sure you distribute a negative sign to both, and make sure you distribute a negative sign to both. This nice factored version, and you already start to see how crazy this could get. So yeah, be careful about that. But again, it's all really just plugging and chugging. But what we can now introduce is that you don't necessarily need to be given all the zeros to solve these types of questions. So degree 3, but I'm telling you only 2 of the zeros. Specifically, I am telling you only 2 of the zeros. So degree 3, leading coefficient is 1. First zero is -1. Second zero is 2 plus 2i. But notice that we have a factor that we haven't filled in yet. Well, don't forget that if 2 plus 2i is a 0, then 2 minus 2i is also a 0. So I can omit information, and you could still find that information the exact same way. Okay? So minus minus, distributing negative signs we get here. And maybe this answer doesn't look so bad, but when you go to FOIL something out like this that's got 3 parts each, it's not pretty. So definitely practice doing that. Okay. Degree 4, leading coefficient 1 with zeros 0, 4, and 1 minus I. Again, degree 4, but I only give you 3 zeros. Okay, well, here's degree 4. Leading coefficient is 1. First zero is 0. Second zero is 4. Third zero is 1 minus I. But don't forget that if 1 minus I is a 0, then 1 plus I is a 0. So the first few examples, I gave you both parts in the pair, but I don't always have to do that. Here, I can just give you 1 minus I, and you find the other one. However, I could also just give you both in the pair. So I can go both ways. Let's distribute negative signs here. X minus 0 is x. 1 times x is just x. This is a nice, pretty answer. And there it is after you FOIL. Okay. Degree 3, leading coefficient 4 with zeros 1 and 2i. So degree 3, leading coefficient is 4. First zero is 1. Second zero is 2i. And then our missing zero is -2i. Okay. And there we go. Degree 3, leading coefficient -2. Zero is -1. -3i. Well, degree 3, leading coefficient is -2. First zero is -1. Second zero is -3i. But if -3i is a 0, then +3i is also a 0. Distribute some negative signs and then FOIL. Lots of foiling. I know I'm skipping through all that, but I think by now, if we're talking about factorization theorem and fundamental theorem of algebra, that the foiling part is very much deep-rooted into our minds. Okay, degree 3. Well, let's start to introduce some irrational zeros like square root of 7. All right, well, they function almost exactly like i's. If anything, they're a little bit nicer to evaluate when you are foiling. Okay, degree 3, leading coefficient is 1. First zero is 3. Second zero is square root of 7. Third zero is negative square root of 7. Distribute that negative, and now we get here. Okay. Well, we can very quickly change this to me only giving you one of the irrational zeros. So degree 3, leading coefficient 1, 0 is 2, and square root of 3. I only gave you 2 of them. You can find the third one. Degree 3, leading coefficient is 1. First zero is 2. Second zero is square root of 3. But if positive square root of 3 is a 0, then negative square root of 3 is a 0. And then we are rinsing and repeating. Okay. Polynomial of degree 5 with leading coefficient 1 with zeros 2 and -5, each with respective multiplicities of 3 and 2. So here's how we could set this up. If we're degree 5, we got to have 5 factors. Our leading coefficient is 1. Our first zero is 2, but we have 2 3 times. Then our next zero is -5, but -5 multiplicity 2. Well, we can simplify this right away to be x minus 2 cubed and x plus 5 squared. So when you're going to set this up, if you were to show me work, right, if we're doing like physical assignments, you wouldn't need to show me doing this step if you can jump right to here, right? Given just this information, you probably could have jumped to what the answer was going backwards. But my point is if you are comfortable jumping right to, an exponent version of the factored form, that's totally fine too. I wouldn't have a freak out about that. But then, maybe now things will start to look a little ugly in our functions. But again, multiplicity, not changing a whole lot, just adding some exponents. Okay, degree 10, leading coefficient 1, x with zeros, x equals 0, multiplicity 2, x equals 1, multiplicity 5, x equals negative 6. No multiplicity said, so we assume it's multiplicity 1, and x equals 2, multiplicity 2. So here's a great example as to why we wouldn't write out all 10 zeros. For x equals 0, multiplicity 2, we'll do x minus 0 squared. For x equals 1, multiplicity 5, x minus 1 to the 5th. For x equals negative 6, just x minus negative 6. And x equals 2, multiplicity 2, x minus 2 squared. You would be very welcome to write out all 10 zeros if that helps you, but I think you'll find it's very tedious to be writing out something that long when you could just be using exponents. Here's a nice simplified version, and either practice foiling or enlist the help of an online resource. Okay, degree 7, leading coefficient -5 with the following zeros: -2, 1, multiplicity 2, and 1 plus I, multiplicity 2. All right, so we are degree 7. Our leading coefficient is -5. Our first zero is -2. Our second zero is 1, multiplicity 2. Our next zero is 1 plus I, multiplicity 2. But don't forget that if 1 plus I is a 0, then 1 minus I is a 0 with the same multiplicity, right? I gave you 1, 2, 3, 4, 5 zeros to start, but we were degree 7, so we knew that we were missing 2 zeros. And that came in the form of just one more factor with a squared. All right, distribute some negatives, simplify that. And these are getting even better by the slide. All right, degree 7, leading coefficient 17 with zeros: -5, multiplicity 2, 0, multiplicity 3, 5, multiplicity 2, and 23i. All right, degree 7, we have leading coefficient is 7. We have x equals -5, multiplicity 2, so we'll throw a square there. X equals 0, multiplicity 3, so x minus 0 cubed. X equals 5, multiplicity 2. Then we get x minus 23i, but don't forget that if positive 23i is a 0, then negative 23i is also a 0. Simplify a little bit, and you all definitely knew 5,620,625, right? No problem at all. Okay, degree 10, leading coefficient 1, x equals 1 plus I, multiplicity 2, and square root of 3, multiplicity 3. I gave you 2 zeros plus 3 zeros for a total of 5, so if we're degree 10, we're missing 5 zeros. Okay, well, we have 1 plus I, multiplicity 2, so this is x minus 1 plus I squared. But if 1 plus I is a 0, then 1 minus I is a 0 with the same multiplicity. Well, we have x minus square root of 3, multiplicity 3, so cubed. If x equals square root of 3 is a 0, then x equals negative square root of 3 is also a 0. Okay, simplifying some negative signs, and we get this monstrosity that I would never expect somebody to actually do in person. But there we go. All righty, we're nearing the end, but we continue. All right, leading coefficient -57 with zeros: 3 plus 7i, multiplicity 3, -4 plus 6i, multiplicity 3. So we would have -57 leading coefficient. Our first zero is 3 plus 7i 3 times. Well, if 3 plus 7i is a 0, then 3 minus 7i is a 0 3 times. If -4 plus 6i is a 0 3 times, then -4 minus 6i is a 0 3 times. Okay, this is fun. This polynomial, I think I tried plugging this into an online resource, and it just wouldn't give me an answer back. It said it was too big. So, as we get a little crazier, I would never expect you to fully expand it, but especially getting up to this point is definitely the key new part to this section. And that brings us to the end of 3.4, 3.5. So normally that would be a really nice storybook to end with, like, this is the fundamental theorem of algebra, but we have one more section that is still in a, not necessarily in the progression of quadratics to polynomials to real and complex zeros, but rational functions still important enough for us to talk about. So we'll do that in 3.6 for the final section of this algebra course and these algebra videos that you have been watching. So until then, I will see you in 3.6. Bye. Hi, everyone. Welcome back to the final section of this algebra course, the final section of this chapter. We're going to wrap up the course by talking about rational functions. So normally you would think that talking about like real and complex zeros of a function is like the perfect way to end an algebra course. But we got to tack on one more section since it's the end of chapter 3. So we'll get right into it. Some similar stuff, some new stuff, but nothing here that's really going to blow anybody's mind, I don't think. So rational numbers are numbers of the form p over q, where q doesn't equal 0. So rational functions are functions of the form p of x over q of x, where q of x does not equal 0. P of x and q of x are themselves polynomials. So as a reminder, no radicals, no absolute values, no rational exponents, right? Just straight x's to whole number powers. The domain of rational functions are all the places where the denominator does not equal 0. But you know what? We talked about that in 2.4. plenty of times. But just as a reminder, 1 over x minus 3, we want to make sure the denominator does not equal 0. So in this case, add 3 to both sides. So x can be anything to the left of 3, everything to the right of 3, just not 3 itself. The domain of x plus 1 over 4x minus 8, so denominator can't equal 0. Add 8 to both sides, divide by 4, and x can be everything to the left of 2 with everything to the right of 2. Okay, then here we go. X minus 1, denominator still can't equal 0, so add 1 to both sides. X can be anything to the left of 1 with everything to the right of 1. You want to spend a little bit more time finding domains? I recommend checking out the video on 2.4. Okay, here, x minus 2, not allowed to be 0. X can't be 2, so x can be anything to the left of 2 with everything to the right of 2. All right, here we have two things. So x can't be negative 2 and it can't be 3. Set each one not equal to 0. So we can be everything to the left of negative 2, everything between negative 2 and 3, and everything to the right of 3. Okay, x squared minus 6x plus 8 can't be 0, right? Just keep taking the denominator not equal to 0. Factor, set each factor not equal to 0. We can be everything to the left of 2, everything between 2 and 4, everything from 4 to infinity. Okay, well, same thing here. Set the denominator not equal to 0. Factor, set each factor equal to 0. We can be everything to the left of one of them, everything between them, everything to the right of them. And that's, it's going to be what happens for most of the time when it comes to two factors. If you have three factors, it works the same way. You would have left of the leftmost one, between them, and everything to the right of them. Oh, speaking of, let's do that right here. So we don't care about multiplicities here. We just care about what the zeros are. So x can't be 6, negative 54, positive 1/2 right here. Add 1 to both sides, divide by 2. So in order, we can be everything to the left of negative 54, everything between negative 54 and 1/2, everything between 1/2 and 6, and everything from 6 to infinity. So just be careful to write domain in order of how you would read x values from left to right. Okay, so basics domain, we've talked about that. But domain actually has an influence on this new thing called a vertical asymptote. So asymptotes in general are vertical or horizontal lines that your graph never crosses. So for example, in this rational function, we have two lines that are creating this weird behavior where we get really, really close to it, but we'll never hit it, get really, really close to it, but never hit it. And same thing for the part up here. Now the question is, when do they occur and how do we know what the behavior is to each one? So some of the functions we were looking at before, x plus 1 over 4x minus 8, well, we weren't allowed to be equal to 2, so 2 was a vertical asymptote. X squared plus 2 over x plus 2x minus 3, x wasn't allowed to be equal to negative 2 or 3, so we get 2 asymptotes. Now, we might notice that there's slightly different behavior here, but that's just going to be the nature of rational functions, and we'll talk about that. So if you're finding the domain of a rational function, no matter what, always set the original denominator equal to 0. Domain of a function will never change. No matter how you can simplify, no matter what you can do to a function, there was one of the functions that we were just doing domains for that you could have simplified first. However, domain is always the original denominator, no matter what, period. However, to find vertical asymptotes, to find these vertical locations where things are weird, start by simplifying the function. After you do that, then you set the new denominator equal to 0. So you have some original function, no matter what it looks like. Don't try and cancel anything out. To find its domain, simply set the denominator equal to 0. But when we're going to look for vertical asymptotes, start by simplifying. So you already found the domain. Now you simplify. Okay, so after you simplify, set the new denominator equal to 0. And now those locations that you get for x will result in vertical asymptotes, specifically vertical lines of the form x equals h. Now, what you might be wondering is, what about all the places that did cancel out? Well, right, setting the new denominator equal to 0 means that whatever corresponding values we get came from factors that didn't cancel out. Well, if a factor does cancel out, it results in what we call a whole. Now, here's the key part. Even though that factor canceled out, it still doesn't change that original domain that we found with the original denominator. We can't ignore where our simplified function came from. So we can simplify it. It could be easier to graph after we simplify, but we can't magically start plugging in values that we don't have. However, to graph a whole, all we need to do is plug in that x value that we canceled out. But we'll talk about that. So to graph rational functions, graph a simplified version of that graph. So for wholes, what we're going to do is draw an open circle or a break in the graph. But then the question becomes is how do we know which infinity each side of an asymptote it goes to? So we see that we're going to graph a simplified version. We see that we're going to graph wholes when they're applicable, but that doesn't tell us anything about the asymptotes, right? The asymptotes themselves, it's just going to be a vertical line that we can put like a dotted line for. But when it goes to actually graphing it, how do we take into account that weird behavior to each side? So for asymptotes, we determine which infinity each side goes to by plugging in numbers really, really close to each side. So let's do the example 1 over x minus 3. Well, this is fully simplified, nothing else we need to do. And when we set this new denominator equal to 0, we get a vertical asymptote at x equals 3. So to take care of a vertical asymptote at x equals 3, we need to figure out what's the behavior as we get closer to 3 from the left. Are we going up as we approach 3 or down as we approach 3? And likewise, when we approach 3 from the right, are we going up or are we going down? So what we're going to do is plug in numbers really, really, really close to 3. So for example, you would plug in something like 2.999 for the left and 3.001 for the right. Now, here's something to keep in mind. We don't actually care what the value is when we plug these numbers in. We already know that the behavior is either going to infinity or negative infinity from each side. So all we care to figure out is the sign of infinity. So for example, when we plug in 2.999, well, 1 over 2.999 minus 3 is 1 over negative 0.001. And this is a positive number divided by a negative number. Positive divided by a negative is a negative number. So in this case, to the left of x equals 3, we are approaching negative infinity. Again, did not care at all what the value was. All we care about is the sign of infinity. For 3.001, okay, well, 3.001 minus 3 is positive 0.001, and this is a positive number, so 1 divided by a positive number will be positive infinity. So from the left of 3, we're going to go down to negative infinity, but from the right of 3, we're going to go up to positive infinity. So there we go. As we approach 3 from the left, as we approach 3 from the right, negative and positive respectively, just like we found. Now, this weird behavior that's happening down here, we'll come back to that. Okay, let's do the same thing, but for 1 over x minus 1. Well, we have a vertical asymptote at where this denominator is equal to 0 and x equals 1. So we're going to plug in numbers very, very close to 1 from the left and from the right. So let's plug in 0.999 for the left and 1.001 for the right. When we plug in 0.999, we get 1 over negative 0.001, which is negative. So 1 divided by a negative number is a negative. 1.001, well, 1.001 minus 1 is 0.001, which is positive. 1 divided by a positive number is a positive infinity. So we're going to graph a vertical asymptote at x equals 1. Left side is going to go down. Right side is going to go up. Okay. Let's do this again, but now we have two things, right? X squared minus 9 is x plus 3x minus 3. So we're going to do a vertical asymptote at negative 3 and at 3. We have two vertical asymptotes, and that's totally okay. So, however, because we have two vertical asymptotes, we need to check the behavior from each side for both of them. So let's start with x equals negative 3. For the left, we're going to plug in negative 3.001, and for the right, we're going to plug in negative 2.999. So just be very careful, right? Negative, normally we would associate the 0.999 from the left when it comes to positive, but when we're negative, negative 3.001 is to the left of negative 3. Okay. So let's plug it into this factored version. Negative 3.001 plus 3, negative 3.001 minus 3. And I again want to remind you, we don't care about the value. We only care about the signs. So forget about trying to calculate this thing. Here, negative 3.001 plus 3 is just negative, and negative 3.001 minus 3 is also negative. So 1 divided by a negative times a negative, well, negative times a negative is a positive. So in total, positive infinity. Okay. Let's do the same thing for negative 2.999 plus, or negative 2.999 from the right. So this will be positive. This will be negative. Positive times a negative is a negative. So in total, we get negative infinity. So for this specific vertical asymptote, x equals negative 3, we're going to go up from the left and down from the right. Okay, well, we got to repeat the same process for the second vertical asymptote. So let's do 2.999 for the left and 3.001 for the right. 2.999. All right. This one, positive. This one, negative. Positive times a negative is a negative. Whole thing, negative infinity. 3.001. Okay. This is positive. This is positive. Positive times a positive is a positive. So in total, we get positive infinity. So for this vertical asymptote, we're going down and then up from each side. So in total, we went to positive infinity, negative infinity, negative infinity, positive infinity. So positive, negative, negative, and positive. Who chose the specific window so that's so hard to tell? I don't know. It might be somebody on the screen's fault, but I think we get the idea. Okay, well, let's graph with some holes now. So holes occur at the locations where factors cancel out. So let's start by simplifying. So simplify first. If a factor does not cancel out, it's a vertical asymptote. But if a factor does cancel out, it is a hole. All right, so x squared minus 9 is x plus 3x minus 3, and we can cancel out x minus 3. Okay, so what we're going to do is graph simplified version of the graph. This is the simplified version, but we're going to draw a hole where this factor canceled out. So this corresponding x value is x equals 3. And since there's no more denominator, it's actually pretty nice. So there's no more vertical asymptotes. So in total, we're just going to graph x plus 3 and put a hole at x equals 3. And that's the extent of drawing some rational functions, right? We're still very low, but nonetheless, this is how this works. Okay, let's do the same thing, but flipped and see how this would work. Well, we're going to simplify first. And same thing, if a factor doesn't cancel out, vertical asymptote. If a factor does cancel out, whole. Okay, well, x plus 3, x minus 3, and x minus 3 cancels out. So we're going to graph this simplified version, but x equals 3, once again, canceled out, right? I know x minus 3, the factor canceled out, but the corresponding x value to x minus 3 is x equals positive 3. So there's a vertical asymptote at this location that did not cancel out, and x equals negative 3. From the left of negative 3, the graph goes down. From the right of negative 3, the graph goes up. You could check this doing that 2.999 and 3.001 stuff we did before, but here we go. Negative and positive, and there is our whole for this function. Okay, let's do another one. X plus 2 over x squared minus 2x minus 8. So let's simplify first. If a factor cancels out, if a factor doesn't cancel out, it's a vertical asymptote. If a factor does cancel out, it's a whole. So x squared minus 2x minus 8, x minus 4 times x plus 2. X plus 2 cancels out. So we're going to graph 1 over x minus. This should be 1 over x minus 4. I don't know how that happens. So we're going to graph 1 over x minus 4, like it's right here, but we're going to graph a whole at x equals negative 2. So there's a vertical asymptote at x equals positive 4, right? Again, this should be minus. So when you go to x equals 4 from the left, you go to negative infinity. When you go to x equals 4 from the right, you go to positive infinity. And there we go. All right, some more graphs with holes. Here we go, 3 minus x over x squared minus 6x plus 9. All right, let's simplify first. Okay, denominator factors to x minus 3 squared, and this is pretty close. So what if we factored out a negative 1 from the top? Okay, well, x minus 3, well, one of them cancels out. So we're going to graph this simplified version. However, there's a vertical asymptote at the location that did not cancel out. So there's a vertical asymptote at x equals 3. So from the left of 3, we go to positive infinity. A little backwards from before since we have this negative sign up here. And from the right of 3, we're going to go to negative infinity. Now you might be wondering, why isn't x equals 3 a whole, right? X minus 3 canceled out. Well, it didn't perfectly cancel out. It didn't cancel it out everywhere. It's still remaining in the denominator. So its status as a vertical asymptote has to supersede that of a whole, right? You can't have a vertical asymptote in a whole. That doesn't make any sense. So in this case, its graph would look identical to negative 1 over, was it x plus 3? No, negative 1 over x minus 3. Okay. Well, that's vertical asymptotes. That's holes a little bit. So now let's talk about horizontal asymptotes. Now you're probably thinking, oh my God, we keep getting closer and closer to the end, and the stuff keeps getting harder and harder. Don't worry. It's actually not that bad. If anything, it's even better. So vertical asymptotes are vertical lines that your graph never crosses. But horizontal asymptotes are kind of funny. Horizontal asymptotes are horizontal lines that your graph sometimes can cross. So we can't necessarily explain it right now. Horizontal asymptotes essentially are tied to the end behavior of rational functions. We talked about end behavior for polynomials, but we can't really talk about end behavior for rational functions. It's a little quirkier than that. And if anything, it actually requires Calculus 1 to come up with, including all of these below rules to help us find horizontal asymptotes. So what we're going to do is compare the degrees of the numerator and denominator, right? Rational function, numerator and denominator, compare the degree of the numerator with the degree of the denominator. In this case, when the degree of the numerator is less than the degree of the denominator. So for example, something like x squared divided by x cubed, well, you would have a horizontal asymptote at y equals 0, or also just the x-axis. If the degrees are equal, then there's a horizontal asymptote at the quotient of the leading terms. Okay, that one's kind of weird. We'll come back to that one. However, if the degree of the numerator is bigger, there is no horizontal asymptote. So it's either going to be y equals 0 at the quotient of leading terms, or no horizontal asymptote. Okay, so let's just do 2 slides entirely finding horizontal asymptotes. Okay, in this case, the numerator is 1, denominator is x minus 3. The degree of the denominator is 1 for x to the 1. Well, since there's no x in the numerator, this is degree 0. So numerator is 0, denominator is degree 1. So the degree of the numerator is less than the degree of the denominator. And now just pull the rule from the last slide. When the numerator is less than the denominator in terms of degrees, there is a horizontal asymptote at y equals 0. Okay. Here we have 3x squared minus 1 over x plus 2. The degree of the numerator is 2. Degree of the denominator is 1, right? X to the 1. Well, in this case, the degree of the numerator is bigger than the degree of the denominator, 2 over 1. Okay, when the degree of the numerator is bigger, there is no horizontal asymptote. Okay, find the horizontal asymptote of x plus 1 over 4x minus 8. Okay, well here, x is degree 1, 4x is also degree 1, so the numerator and denominator are both degree 1. They're both equal. So here's what we're going to do. We're going to take those leading terms and divide them. So there will be a horizontal asymptote at y equals x over 4x. Well, cancel out an x, and we get 1/4. So there's a horizontal asymptote at y equals 1/4. All right, horizontal asymptote of 2x over x squared plus 1. Degree of the numerator is 1 for 2x to the 1. Degree of the denominator is x squared, degree 2. So the numerator is 1, denominator is 2. the degree of the numerator is less than the degree of the denominator. So we have a horizontal asymptote at y equals 0, right? We're just pulling rules from the last slide. Here, 3x cubed plus 2x squared plus x over 2x plus 5. The degree of the numerator is 3. Degree of the denominator is 1. Numerator is bigger. The rule for bigger numerator is no horizontal asymptote. Okay, so let's do another slide of these. Horizontal asymptote of 5x plus 2 over negative 3x plus 1. Degree of the numerator is 1. Degree of the denominator is also 1. So we're going to take those leading terms and divide them. Cancel out the x, and we get negative 5/3. Okay, horizontal asymptote of x cubed plus 1 over 4x to the 4th plus 1. The degree of the numerator is 3. Degree of the denominator is 4. So degree of the numerator is less than the degree of the denominator. So in the case where it is less than, there's a horizontal asymptote at y equals 0. All right, x squared plus 2 over x plus 2x minus 3. Well, let's FOIL out the denominator. And now you see degree 2 in the numerator, degree 2 in the denominator. So take those leading terms and divide them. X squared divided by x squared is just 1. 4x to the 4th plus 1 over x cubed plus 1. Degree of the numerator is 4. Degree of the denominator is 3. So numerator is bigger. There is no horizontal asymptote. All right, one more example. Here, the degree of the numerator is 2. Degree of the denominator also 2. So take those degree 2 terms and divide them, and we get negative 3/4. So horizontal asymptotes, even easier to find. Okay, and now let's put all of this together to graph rational functions. This is how we're going to sunset algebra in chapter 3. So here we go. So to graph a rational function, start by finding the domain. You don't necessarily need it to graph. However, it is a very important part of the function, and it helps remind us that we can't magically start plugging in values. It reminds us that we need vertical asymptotes and we need holes. So set the original denominator equal to 0. Then simplify the function. If a factor cancels out, it's a hole. But if a factor doesn't cancel out, it's a vertical asymptote. And then check numbers to the left and right of that vertical asymptote to determine which side, to determine which infinity each side goes to. And we like to sketch vertical asymptotes as dotted lines. To find horizontal asymptote, we're going to sketch that as a dotted line, but just use the 3 rules that we just talked about. Okay, find zeros and x-intercepts, set the numerator equal to 0, and last but not least, find the y-intercept by setting x equal to 0, right? Come full circle to x and y-intercepts that we've been doing since very early in chapter 2. And we sketch based on all this information. Okay, let's graph 1 over x plus 5. So domain, we want to make sure that the denominator doesn't equal 0. Subtract 5 on both sides, so we can be everything except negative 5, which is everything to the left of negative 5 with everything to the right of negative 5. Okay, simplify the function. Well, in this case, there's nothing to simplify. So that means we have a vertical asymptote at the factor that didn't cancel out, which is x equals negative 5. So to the left of negative 5, we're going to go to negative infinity. To the right of negative 5, we're going to go to positive infinity. And there's no holes since we didn't have any factors to cancel out. Horizontal asymptote, let's compare the degree of the numerator and degree of the denominator. Degree of the numerator is x to the 0, so just 0. Degree of the denominator is 1, x to the 1. So the numerator is less than the denominator in terms of degree. When the numerator is less than, there's a horizontal asymptote at y equals 0. X-intercepts, we set the numerator equal to 0. However, obviously 1 is never going to equal 0, so there's no x-intercepts. That's totally fine. Y-intercept, we're going to set x equal to 0. So 1 over 0 plus 5, 1/5. Okay, all that said together, all that put together, all that said and done, right? We've come a long way. There we go. Alrighty. Another one, 6 over x squared minus 1. Let's start with the domain. You need to make sure the denominator doesn't equal 0. Well, x squared minus 1 is x plus 1, x minus 1. Set each one equal to 0. And we get everything to the left of negative 1 with everything to the right of negative 1. Sorry. And we get everything to the left of negative 1, everything between negative 1 and 1, and everything to the right of 1. Simplify the function. Well, nothing we need to do here. So that means we have vertical asymptotes at both values that did not cancel out. To the left of negative 1, we're going to go to positive infinity. To the right of negative 1, we're going to go to negative infinity. To the left of positive 1, we're going to go to negative infinity. And to the right of 1, we're going to go to positive infinity. So again, I did the practice of checking both left and right hand side when we initially talked about vertical asymptotes. So if you need help with that, scroll back a little bit in the presentation. And there's no holes because nothing cancels out. Horizontal asymptote, all right. Numerator is degree 0, denominator is degree 2, so the numerator is less than the denominator, and we have a horizontal asymptote at y equals 0. X-intercepts, set the numerator equal to 0, but 6 doesn't equal 0, so we're good there. Y-intercept, set x equal to 0, so 6 over 0 squared minus 1, 0 squared is 0, 0 minus 1 is negative 1, or negative 6, or 0, negative 6 is our y-intercept. And there we go. Okay, 1 over x minus 2 squared. Domain, set the original denominator equal to 0, or not equal to 0. Square root both sides, add 2 to both sides, and we get everything to the left of 2 with everything to the right of 2. All right, let's simplify. And we don't have any simplification to do here either. Vertical asymptote is going to be at x equals 2. And now, interesting quirk here. Notice that no matter what you plug into this function, so you take any number you want, you subtract 2, whatever it is, the second that you square it, it's going to be positive. So no matter what, we will always get a positive value for each of these, including both sides the function approaches for the vertical asymptote. And again, nothing canceled out, so no holes. The degree of the numerator is 0, degree of the denominator is 2, so numerator is less than, we have a horizontal asymptote at y equals 0. X-intercepts, none, since the numerator still doesn't equal 0. I promise we'll look at least one example where this is different. And then y-intercept, set x equal to 0. 0 minus 2 is negative 2. Negative 2 squared is positive 4. So 0, 1/4. And there we go. Okay, some more exciting stuff is going to happen in this one. All right, domain first, set the denominator equal to 0. Subtract 2, divide by 2, and we get everything to the left of -1 with everything to the right of -1. Let's simplify. Well, in this case, also nothing to simplify. So we have a vertical asymptote at that x equals -1 that didn't cancel out. And here, just be very careful, right? In a lot of the other cases that we've had to deal with, when we plug in numbers to the left and to the right of the vertical asymptote, we normally only had to plug things into the denominator, but be careful because now you need to plug in that value into every x that you see, not just the denominator. So doing so, to the left of -1, you'll get positive infinity, and to the right of -1, you will get negative infinity. Still nothing canceled out, so still no holes. Okay, degree of the numerator is x to the 1. Denominator is 2x to the 1. So for the first time, the degrees are equal. So there's a horizontal asymptote at y equals x over 2x. Take those leading terms and divide them. Cancel out an x, we get 1/2. So we have horizontal asymptote at y equals 1/2. X-intercepts. X-intercepts say to set the numerator equal to 0. Oh, finally we can do that. Add 3 to both sides, and we get 3, 0. Y-intercept, set x equal to 0. So we get -3 at the top, 2 at the bottom. So 0, -3 over 2. All right. And 2 more examples, and then we sunset college algebra. All right, so I give you this very beautiful looking function here. I'll just give you the factored version here, don't worry. So step 1, find the domain, set the denominator equal to 0. So we get -3/4 and 5/3. So that is everything to the left of -3/4, everything between -3/4 and 5/3, and everything to the right of 5/3. Simplifying the function, well, notice 4x plus 3 goes away, 3x minus 5 goes away. So we get 4x minus 9. And this is going to be a lot easier to deal with than some of the other stuff we've had to work with. Vertical asymptote, there's none. There's no more denominator. Nice. But we do have holes at those 2 x values that we canceled out. So we got to keep going. Horizontal asymptote, the degree of the numerator is bigger than the degree of the denominator since there's no more denominator. So there's no horizontal asymptote. And we knew that this is a line, so lines don't have horizontal asymptotes. X-intercepts, set the whole thing equal to 0. Add 9, divide by 4. We get 9/4, 0. And y-intercept, set x equal to 0. Well, we just get 0, -9. So kind of an interesting looking function when we do that. Okay. One more example. Let's just flip the numerator and denominator, and then we'll call it a day. Domain, set the denominator equal to 0. Oh, well, this time we actually get 3 values that this happens. So in order, we can be everything to the left of -3/4, everything between -3/4 and 5/3, everything between 5/3 and 9/4, and everything to the right of 9/4. Now let's simplify. You'll see the same 2 factors cancel out, except now we have 4x minus 9 in the denominator. So some of the rules that we just had, or some of the things we just talked about, are going to be a little opposite. So there's a vertical asymptote at this remaining term, right? 4x minus 9 didn't cancel out. So we have a vertical asymptote at 9/4. To the left of 9/4, it's going to be negative infinity. To the right of 9/4, it's going to be positive infinity. And we have holes at those 2 values that canceled out. Well, this time, the degree of the numerator is 0. The degree of the denominator is 1. So numerator is less than again, horizontal asymptote at y equals 0. X-intercepts, set the numerator equal to 0. That never happens. So we have y-intercept when x is equal to 0. So we get -1/9. Very nice. And there is our graph. And that is the end of my college algebra lectures. So that's it. I like, 3.4 and 5 being the end, but sometimes we don't always have it our way. So with that said, thank you so much for watching 3.6. And if you watch other videos, thank you so much for watching all the lectures here in college algebra. And I hope these videos have helped. So, hi.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Lesławska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.